steps you need to do in order to achieve the same thing that you get in a high-level language like C or even languages higher than that. Taking a lot of things for granted, especially things like loading registers. So every CPU's got a series of registers that can store values, and then the CPU has logic that knows that you can basically say, okay, if the value in register A is greater than or equal to some value, then branch to this sequence of the assembly code. And you often will have to do things like and or operations on byte level, just on bytes. Like right here, we can see we're anding the value 3 on whatever's in register A. Like I said, don't intend to get too much into what assembly is, but for those curious as to how games were implemented in the 80s and even the early 90s, it was all in assembly language. Because assembly language is, you're literally programming the CPU of whatever machine you're trying to program. And that's how you get as much efficiency as possible if you know your computing environment, you know what your CPU is capable of. The thing about compiling a language like C or C++ or Java, which is even higher of an abstraction than those, is you're allowing sort of algorithms to do the work for you. You're allowing algorithms to take your source code and turn it into this, basically. A layer lower than this, effectively. This is an intermediary level that it does generate, but suffice to say, in the 80s and 90s, C compilers were not as good as humans were in creating games, especially to do a lot of the tricky things that they needed to do in order to get them working efficiently on processors that were, at the time, 1 to 3 megahertz in speed, which now we have like 3 gigahertz processors, and it's no big deal. But that is effectively, that's sort of a window into what it was like developing games in the 80s and 90s. And then in the 90s, with like things like the N64, PlayStation 1, going on to PlayStation 2, and so forth, it was typically done in a language like C or C++, sometimes with some variants. Certain consoles, like the PS3, has a notoriously difficult graphics processor to program, so a lot of PS3 teams needed to program in assembly, even at the time, which was 2007, 2009. But that's, in a nutshell, what it's like programming the 6502. So if you want, those links up above. It's a pretty enlightening experience actually digging into that sort of thing and trying to make sense of what the assembly does. It's quite difficult and it's quite burdensome because of how long these programs are and just how minute each individual instruction is. Like just loading a value into a register, just to do a loop, often will just be iteratively loading a value into a register and then like performing some operation or calculation off of that, and then branching to some other loop of code. A lot of that can be condensed into like just a couple lines of C, or even fewer lines of Lua. So a lot more of a burden, but there is insight, definitely some insight into digging a little deeper and sort of looking there. So once again, those are the links on the NESDev wiki, wiki.nesdev.com, if you're interested in looking at that. In assignment 5, you will, like you did in assignment 4, you can create a game object that's consumable, and feel free to use code from assignment 4 to do this. When you define your onConsume function, if you're going to adopt the same model as the last assignment, then any ideas as to what we need to do? Probably just add, the opposite of damage the entity, right? We want to add hearts. We want to add HP to it. And you'll see in the distro that health is modeled as an even number because every one digit is half a heart. Yeah.
Can you give a negative number to damage?
You can. And that'll effectively be the same thing too. So the second part is including pots. So there are pots in the sprite sheet. So these should be solid. So when the player interacts with them, he should be bumped out of where he was. Allow the player to lift them. So there's an animation in the sprite sheet that'll actually that shows the player lifting up the pot. So you probably need a new state, player lift pot state, walk with pot state, whatever you want to define it as. But you'll need basically to have those two in order to get this to work. What's one thing that we'll need to do in order for the player to lift the pot? Any ideas? Besides the rendering aspect of it, when the player walks around, for example, what needs to happen if he's holding the pot? You could make him slower, yeah, that's possible. It's not required for the assignment. More fundamental than that. The pot needs to track the player's location, right? It needs to be relative to the player's location. So keep the pot probably above the player by some amount. I won't be too picky as to how you implement that, but the pot needs to track the player, which is this next point actually. And their walking animations, like I said, should change while they're carrying it. Allow the player, lastly, to throw the pot. So when you throw the pot, basically turn the pot into a projectile. If it hits one of the walls, break it. You can either just despawn it instantly or have some animation. It's up to you. But just if it hits a wall, despawn it. Maybe just trigger it to some value as false, render as false, whatever you want to do. If it hits an enemy, it should damage the enemy by 1, just like we've seen already. And if it travels farther than 4 tiles, in addition to also hitting one of the walls, then destroy it too. So those are the main components for assignment 5. And the ways that which you achieve most of it's fairly flexible. But yeah, that's assignment 5, or lecture 5, Legend of Zelda. So thanks for coming. I'll see you next time. All right, good evening, everybody. Welcome back to GD50. This is lecture 6, and today we're going to be venturing out of the 8-bit world and back into sort of a more modern era of gaming. We're talking about Angry Birds today. I have pretty fond memories of Angry Birds, actually. It was the first sort of mobile game that I remember playing where I sort of realized that mobile was actually a viable platform for gaming. I played it, I think back in 2009 was when it was first released, and I really enjoyed it. It has a very simple formula. The goal, if you're unfamiliar, is you have birds that you sort of control via a slingshot on the left side of the screen, and then these pigs that have stolen your eggs. You're trying to sort of destroy them or kill them by knocking down their fortresses made out of various materials, wood, glass, metal. And you get a few different bird types, but the gist of it is basically just slingshot a bird into some structure, knock it down, and the whole entire sort of underlying mechanism for how things work is via a physics engine, which we'll talk about today in lecture, called Box 2D, probably the most ubiquitous 2D physics engine. But that's sort of like the overall sort of structure of the game. It's literally just throwing things into structures, knocking them down, and then that sort of tactile and fun gameplay makes for really great mobile gaming, and I enjoyed it a lot back in the day. This is a screenshot of the first level in the first Angry Birds, which most people I think have probably seen. This is a sort of a sample from one of their newer games. As you can see, it's kind of taken a whole new layer here. There's stone and a bunch of varying, intricately varying structures and new creatures and stuff like that. The game has changed a lot, but the formula has stayed the same. And today we'll sort of explore the foundation of what makes this game work. And the topics today, a smaller list than usual, but Box 2D we can sort of consider as being a pretty large topic. We'll be talking about Box 2D, which is the physics engine we'll be using today in lecture, and via LÖVE 2D, which has its own wrapper for Box 2D. And we'll also talk about a little bit about mouse input, which you haven't really done a lot, but it's very apt, especially in the context of mobile gaming, because mouse input and touch input are synonymous. But first, let's get a lecture demo. If we have, can you have a volunteer come up on stage to showcase what I've put together here? So let me make sure I'm in the right directory here. All right, so whenever you're ready, go ahead and press enter. And so this is a little demo I put together that sort of demonstrates the concepts we'll talk about today in class. This is just the start screen, but it already shows Box 2D sort of representing a bunch of these square-shaped aliens, which will actually be what we're trying to target in the game. But notice that they all sort of fell and had their own collision and their own physics that sort of took place, and I didn't have to manually code like rotation and stuff like this. This is all stuff that Box 2D takes care of for us, and we'll see it used to great effect soon. So if you go ahead and just click on anywhere on the screen, we'll go to the main sort of part of the game. So this is a very simple representation of what Angry Birds is. You start on the left side of the screen, you have a bird, in this case an alien. We used a free art pack that uses aliens instead of birds, but it's the same concept. you have an alien that you can click and drag. So if you click it and then drag around, you can see the sort of trajectory that you'll have when you let go of the mouse. So we're simulating where it's going to go via these purple circles. And then the goal in Angry Birds is to sort of throw the bird into, or the alien, into the fortress guarding the pigs, or in this case, square-shaped aliens. So if you go ahead and just launch the bird by letting go of the mouse, you'll see, oh, there we go, and we knocked down the, okay. So what happened was we shot the alien into the structure. It destroyed one of the wooden pieces of, one of the wooden blocks guarding the other alien. And then as soon as that happened, the top box, because these are all being simulated via Box 2D's physics engine, that other box was detected as being unsupported, so it fell down. It hit the other alien, and we've coded it so that when a collision occurs between an obstacle and our alien of sufficient speed, it should kill the alien, which is sort of how it works in Angry Birds. So if we try it again, and this time we hit both of those at the same time, so it triggered both of those being deleted, but this guy is still alive, so after it stops moving, which is similar to how it behaves in the original game, it's going to let us try again to shoot. So if we try one more time, and then we launch and hit it, we kill it, and then we get a victory. And so that's the overall sort of underlying foundation for what Angry Birds is. Obviously, we're using a very simple representation. It doesn't have a lot of the frill that Angry Birds does, but we could easily build upon this and create a fully fleshed out game very similar to Angry Birds. So thanks, Stephen. I appreciate the demonstration. All right. So that's our goal today. We'll be talking about how to construct a sort of very basic but functional simulation of what Angry Birds is at its core, which is just flinging things into obstacles, destroying them, and ultimately destroying the things that they're protecting, the aliens, the pigs that are in the base game. So here's a shot of what the different sprite sheets we're going to be using are. There's a really great sprite sheet that I got off of Open Game Art. Kenny is the artist. He makes a lot of great art. If you notice, it's very similar looking to the art that we used in the Mario lecture, actually. It's the same artist. So if you're ever looking for assets, he's got a ton of awesome assets on Open Game Art. So we have a set of aliens, square and round shaped. I decided just arbitrarily we made the round shaped aliens the birds. So we shoot those into the structures that are protecting the square-shaped aliens. The square-shaped aliens will be the sort of the bad guys in this case. And then we have another sprite sheet down here below on the left side, which I used the tile here just to make a ground element. The rest of these you could easily include in the game if you wanted to, but we are only using the ground here. And then notice here we have this large sprite sheet which has a bunch of different shapes and sizes of materials. The whole sprite sheet comes with metal and explosive and glass sheets as well, but just for simplicity we only use the wood here. But notice that we have like entirely whole pieces, and then we have pieces that are partially destroyed, and then pieces that are hollow. You could easily model all of these in your game and use them, but we only decided to use just a couple of these, which was just the horizontal and the vertical ones that are completely whole. These unfortunately don't have quite the same sort of systematic layout as the sprites that we used before. They're not laid out in a grid evenly spaced. So in this case, in util.lua, I ended up hard coding the different x, y, width, and height quads for each of these, which is kind of what you have to do in the situation where you're interacting not with tiles per se, but with more organic shaped objects. So it can take a little more time to end up constructing all of the quads for your objects when you have a sprite sheet like this, but fortunately you only have to do it once. So here's a few useful links before we get started in talking about what Box2D is and how to use it, and basically how it's called love.physics effectively in Love2D. The first two links are documentation for Love2D, sort of what the functions and objects are that we'll be talking about, and a simple tutorial that talks about how to make a ball bounce in Love2D using Box2D. The third is a great resource that I used actually to learn most of what I know about Box2D, especially in the context of this lecture. So it talks about a lot of different concepts, talks about all the things that we'll be talking about, and then it goes into a lot more detail about how you can go about constructing a lot of really cool, crazy things like tanks and pulleys and a whole bunch of different things that are worth looking into if you're looking into potentially making a physics-based game. Obviously, we won't be going into things of that complexity here, but you could easily do it with Box2D. It makes it very, very possible. So the very first thing that we should talk about when we want to construct a game or a simulation or whatever we want to do with Box2D is we need some sort of system that will actually perform the simulation for us. And the fundamental core of what a Box2D app or game is, the core is the world object. So there is a world that you can think of as sort of being your world, but what it effectively is a machine that simulates all of the pieces that you've told it interact with each other in Box2D. So Box2D has a set of objects called fixtures and bodies. Those perform the physical interactions, and it's up to the world to update all of those and apply the relevant forces and physics calculations that resolve collisions and do all sorts of things. All of the things that Box2D does for us, the world takes care of this for us. So we don't have to manually go through and update every single object with its velocity that we've done before and check for collisions. The world does this for us and resolves them based on how we tell it to resolve them. And the world also possesses, like an actual world would, gravity on the x and y axis. In this case, we have gravity applied on the y-axis going down, so it's a positive value. We set it to 300 in this distro, but you could set it to whatever you want. Setting a lower gravity would have the effect of making it feel like we're on the moon or something, making it feel like we're on a different planet. So that's what the world is. The world simulates everything. And we'll go through just a few terms here before we look at some source code, but there's a few terms that we need to sort of understand before we can really understand what Box2D is doing. And this is the function that we use to create a new world in LÖVE2D. Very simple. love.physics.newWorld. And this love.physics is just a namespace that encapsulates everything it encapsulates all of the Box2D functions and objects that LÖVE2D has access to. So anything that you see in love.physics is effectively a wrapper for Box2D. And to clarify about Box2D, Box2D is just a library that's written in C++ that you can plug in pretty much anywhere you want to. Unity uses it, and most 2D game engines that I've ever seen, including libgdx, for example, which is a very large Java 2D game framework, uses Box2D. You can use it anywhere. In this case, we are using LÖVE2D's own wrapper for it. So the people that created LÖVE2D, they took Box2D and then they just put a bunch of Lua functions around all the objects and functions to make it possible to use it in the same style that we use the rest of the framework. So this is how you create a new world. This is the first step in getting your Box2D simulation sort of working. So any questions so far as to how we can get that going? Okay. So beyond the world object, which is the foundation, sort of sets up our stage, you can think of it as our stage, we need bodies to actually interact with each other. So a body is just an abstract container. It basically holds a position and a velocity, and you attach things to it via what are called fixtures that allow you to give the body a shape and therefore a collision box, and therefore allow it to interact with other things. But a body is essentially all the disparate things in your scene that interact with each other and move around. And so to create a new body, we just do love.physics.newBody. We pass in the world. So therefore, when we do this, the world has a reference to this body now. And every time we call update on our world, which we'll see in the source code, it will know, OK, I have a reference to this body, perform all of the relevant checks on the collision for that body and all of the fixtures that it contains, update its position, update its velocity, and so forth. And it, not only a world, but it also gets an x and a y, which will place it in the world on instantiation. The last parameter here, type, there are three fundamental types of bodies, which we'll see in LÖVE2D: static, dynamic, and kinematic. And that basically influences how it'll interact with the other objects, the other bodies in our scene. So we have the world, which encapsulates everything, all the bodies, all the fixtures. And then we have the bodies, which are the entities in our game world that have position and velocity, effectively. The last sort of key ingredient here that will allow us to create interactions between the bodies that we have are fixtures. And fixtures, all a fixture is sort of this abstract object that will allow you to attach a shape to a body. So bodies are shapeless by default. They don't have a shape. They are just a container that has position velocity effectively. But they don't interact with anything else, and they don't know how to interact with anything else until you give them a fixture. And the fixture you will give the body and a shape. So for example, if you want the bird that we were looking at earlier, the alien, the round alien, we create a body for it in our world, which doesn't mean anything yet, but we say, I'm going to attach a fixture to that alien, I'm going to give it a circle shape, and it'll then know whenever it performs any calculations that that alien should interact with things as if it were round, and therefore trigger collisions based on a circular hitbox, as opposed to a rectangular or polygonal hitbox, as we'll see. Fixtures, in addition to attaching shapes to bodies, which will, as said here, influence how they collide with other bodies, they have density, which we'll see, so that things with higher density obviously will fall faster, or not fall faster, but they will influence things as if they have more weight. They will push things farther when they collide with them. They also have friction, and they have restitution. Restitution is bounciness. So something, if we had our alien, no restitution, when it hits the ground, it'll just kind of fall flat. But if we give it a higher restitution, it'll actually bounce when it hits the ground, and therefore interact with the world a little bit differently. So when we want to take a fixture and apply a shape to a body, we have a few different shapes that we can apply to it that are given to us by default in LÖVE 2D. So circle shape, rectangle shape, edge shape. These are just effectively how we define how our bodies interact with other bodies. How, for example, if something is circular, it should roll when it's moving along the ground, or when it hits something, the corner obviously of it won't hit something because it's rounded, as opposed to something that has a square hitbox. It'll affect things in a slightly different way. And we can define arbitrarily shaped hitboxes thanks to the polygon shape. If we want something to be shaped like a pentagon, for example, and have it roll around and behave like such, we can just define a polygon via a set of vertices and then affix that to a body, and it'll behave as if it were pentagon shaped. And this is how you would instantiate, just as we've seen with love.physics.new world and love.physics.new body. Love.physics.new fixture takes in a body and a shape and will apply that shape to the body, and the world after that will know exactly how to collide with things. And so the last slide we'll look at here before we start looking at source code is what the different body types are. So I alluded to having 3 different body types before: static, dynamic, and kinematic. So a static body will exist in our world but not actually be affected by gravity or the collision of anything else. Things can hit it and bounce off of it and do their own thing, but the static body will never be influenced by something else. It exists as some sort of permanent structure, almost like the ground. You don't really affect the ground by moving into it and bouncing into it unless you do it with enough force. But in our box 2D world, a static body cannot be influenced by anything else. A dynamic body is the opposite. It has the full sort of simulation of box 2D. It has gravity affects it, things collide into it, it will bounce off of them. It'll do what you would expect a normal body to do. If I throw a ball in this room and it hits the wall, it's a dynamic body. The walls are the static bodies in this case. And then a kinematic body is sort of a hybrid between the two. It's something that can move and can sort of rotate and do things, but it's not influenced by other objects colliding with it. So for example, if I have a platform that's just spinning indefinitely, but it's not being affected by gravity and it doesn't move when I hit it, that's a kinematic body. It's still moving and it's semi-static and it influences other things, but it's not purely static. It does have a little bit of behavior that we can grant it. So let's go ahead and look at a few examples now and see how this actually looks in code. So I'm going to go into an example. If you're looking in the distro, there's an example called static. So we'll take a look here and see what a static body looks like in our scene. And for all of these examples leading up to Angry Birds, we're just going to render everything with shapes for simplicity. But this, as anticlimactic as it is a full box 2D world with just a single static body, and it's just this square here, colored white. The static body doesn't move, it doesn't do anything, nothing can influence how it moves or behaves, but it exists in our world as a permanent fixture, and if we had dynamic bodies, and we threw a dynamic body at it, for example, the dynamic body would bounce off, the static body would stay there permanently. So let's go ahead and take a look at what the source code looks like for that. So I'm here in main.lua of our static file. And just as we've seen before, we need to define a world. So I have a world here on line 45. LÖVE.physics.newWorld, no x gravity, but we are going to have 300 units of positive gravity on the y-axis, which is going from top to bottom. We need a body for our square that's in our game world, our static square. So we're going to go ahead and define a new body here. LÖVE.physics.newBody takes in the world, recall, because that's how our world's going to have a reference to that body. It doesn't know about it unless we pass it into here, our new body constructor. And then I'm just going to put it right in the middle of the screen. So virtual width divided by 2, virtual height divided by 2. The difference between box 2D bodies and things that we've drawn before or seen before is that everything is defined by its center point as opposed to its top left. So I'm able to say virtual width divided by 2 and virtual height divided by 2 here, but I don't actually need to say virtual width divided by 2 minus whatever the half of that square is. By default, the center point is the xy of that object. And this last string here in the constructor for our new body, static, tells the constructor that this is going to be a static body specifically, not a dynamic body and not a kinematic body. So we have a body, and it's static, but it doesn't have a shape. It doesn't really know how to interact with anything else in our world. So we're going to create a new shape first. So LÖVE gives us a few functions in the form of new X shape. We have new rectangle shape, new circle shape, new edge shape, a few other ones. We're just going to create a new rectangle of size of width and height of 10. So that's what the 10 and 10 are here. Then we're going to create a new fixture. We're going to affix the box shape to our body with this function. And then once we do that, all we have to do is then render a polygon with fill. And then we get the coordinates for the vertices for our polygon by saying body get world points. So that's a function off of any LÖVE or any box 2D body that will basically get where it is in the world and all of its vertices. And then you just pass in the shape that you want to get the points for. And that will end up just exploding here into a set of vertices that fill up this LÖVE.graphics.polygon. And the end result of that is we get a square. And we specifically use polygon instead of LÖVE.graphics.newRectangle because that's what the get world points function explodes out to. It doesn't explode out to the number of arguments that would satisfy LÖVE.graphics.rectangle. So not a very exciting example, but this is basically the foundation of a full box 2D application. So any questions as to how sort of this works at all?
Yeah, I'm kind of wondering, how does it determine the center of a abnormal shape, like a square, rectangle, or circle?
The center of an abnormal shape. I'm not entirely sure. The circle is just
This is the center.
Yeah, I'm not entirely sure about a polygon though. I haven't looked into that into too much detail. I can explore that and see. And that's something that I think Box 2D is that the actual library implements that and calculates that, probably based upon calculating the area of. To repeat for the camera, if I didn't repeat already, it's how does Box 2D calculate the center point of something non-symmetrical like a polygon, and best I can understand is that it would do an area calculation off of it and sort of figure out where all the vertices sort of tend towards, I guess. But yeah, that's something that's implemented in the library. I'm not entirely sure.
Okay.
I can look into it and see, and then I'll post in the Slack.
So it seems like if they did have that, it would be kind of difficult to place it in a very precise spot.
Yeah, if it were. Yeah, we did have an odd shape to get it placed in an exact spot, yeah. I'm not entirely sure. I'd have to explore that a little bit. Interesting idea, though. But yeah, that's essentially how we get a Box 2D world up and running. We have a static body. It's not terribly interesting, but with one change. So I have a separate example called dynamic in the source code distro. But all we need to do to really see the difference between a static and dynamic body is on line 48, just change static to dynamic, save it, and then rerun it. And then we'll immediately see that it's affected by gravity and it moves downwards as we've told the world that our gravity is set to positive 300. And so that behaves sort of how we would expect it to. Now there's nothing else in the scene, so it's not particularly interesting. So I've created another example called ground. So let's go ahead and look at that. So if we want more interesting behavior, what do we need to do? In a nutshell.
More shapes and make a ground.
Just more shapes and make a ground, exactly. That's a simple way we can get instantly a sense of how powerful Box 2D is. Just introduce more shapes that interact with each other in different ways. So ground is an example that just introduces a ground into our scene so that we can see the box fall down and actually collide with something else. And LÖVE 2D makes this nice and easy. Excuse me, they have a actual edge shape that will allow us to basically form where the ground is. Anything that collides with this, it's effectively a line, but no matter how fast anything moves in our scene, the body will not move past that line. So it's a nice, easy way of getting a ground in our scene without having to implement like a polygon that maybe has like 2 vertices going left to right on the screen. So that's what we do here. We have a ground body, which is a static body, recall, because the ground shouldn't move. We're going to change the box into a dynamic body, but the ground shouldn't move. The ground should be unaffected by anything. It's going to be static in our scene. And it's going to have an edge shape. So notice here we take 0, 0 as the xy, and then a virtual width in 0. So with shapes, when we define them here, they aren't actually, it's not going to draw the shape at 0, 0, at virtual width and 0. This is relative to wherever the body is located. So wherever our body is, this shape will be drawn with these coordinates, this x and y, and this width and height relative to that, and specifically relative to the center point of wherever we place a body. So if this ground is set to 0, 0 at virtual width and 0, where do we need to place the actual body for it to render the ground appropriately?
The middle bottom.
Yeah, so we place it towards the middle bottom. So we actually end up placing the body itself here at virtual height minus 30. And when we affix this edge shape to the body, we'll end up, even though it says 0, 0 virtual width 0, it's relative to wherever the body's xy are. So it's actually going to be 0 virtual height minus 30 virtual width 0 will be sort of where that edge exists. And then lastly, just as we did with our box, we need a ground fixture so that the ground body knows how it should interact with other things. So we're going to affix the edge shape, which is just a line, to our ground body. And then here we do LÖVE.graphics, just as we did up with the LÖVE.graphics.polygon for our box. We're going to do LÖVE.graphics.line for our ground body, and we're going to do the exact same thing, get world points and get points passing the edge shape here. And I'm also setting a line width of 2, just so we can see it a little bit better. And I'm going to color it red. And I colored the box up here green. So let's go ahead and take a look at what this looks like. So I'm going to go into ground. And so notice, and I also added a little bit of restitution to the, as we said before, restitution is a quality that a fixture can have, which gives it bounciness. So rather than just falling flat down onto the ground, it bounces a little bit as well. And we can see the interaction. So I'll play it one more time. It starts in the middle, and then as soon as it hits the ground body that we created before, the edge shape, it bounces a couple times. But it shows that the box is dynamic, but the ground is static. Nothing influences the position of the ground. It gets hard set and will stay there permanently. So that shows a nice sort of easy, simple demonstration of an interaction between a static and a dynamic body. I'm going to go ahead and pull up another example here. So kinematic, recall, what was the sort of difference between a kinematic and a static or dynamic body?
Kinematic can move, but it's not influenced by other shapes.
Correct. So a kinematic body can move. You can ascribe it positional velocity or angular velocity. It's rotation. But when something collides with it, it's not going to be influenced by it. It's going to influence the body that it collides with. It's going to affect it in some way, but nothing colliding with the kinematic body is going to have an effect on its position or its velocity. It's something that exists and does something programmed and will just do that indefinitely, but it will interact with other dynamic bodies as we've programmed. And it will not interact with other kinematic bodies either. They'll almost pretend that each other doesn't exist. If you overlap a static and a kinematic body or a kinematic and a kinematic body, they render on top of each other, but they don't actually influence each other's position or anything like that. So I'm going to go ahead and run the kinematic example. So here we have a few things going on. So we have the box body that we had before, the dynamic box that falls from the middle of the screen. We have the ground on the very bottom to catch it, but we have 3 kinematic boxes in the very center that are spinning that influence the green box when the green box collides with them. So as you can see, it sort of tosses it around, and then the green body falls back to the bottom. And in this example, I've taken away its restitution, so it just, as soon as it hits the ground, it just sort of falls flat, just like that. And so as you can see, these blue bodies, they're moving. They have angular velocity indefinitely, specifically 360 degrees per second. And they will stay in that exact position and rotate in that exact way forever. But as soon as they interact with a dynamic body, they actually cause a collision with that dynamic body, and the collision resolves, and this green body gets tossed around because it's dynamic. It'll basically do whatever it can to interact with the game world, as long as it's interacting with other bodies and resolving its collision that way. And so that's sort of the key example between what the 3 different bodies are fundamentally. And with these 3 body types, you can construct pretty much any scene that you want to. And obviously, the bodies and the fixtures can get insanely complex. I mean, we can look back here at at this first example. Like, these structures are a composition of many different types of dynamic bodies that have been given sort of anchors and joints and all sorts of other things to make them look as if they're like big constructions. But at the end, they're all just a bunch of little bodies that are welded together, fixtures that are welded together. And these fundamental building blocks are sort of how you construct scenes like this. Put a bunch of these blocks together, weld them together with box to these joints in this case. We won't cover joints in the context of this lecture, but if you're wondering how all of these individual things can be collidable while still constructing these massive scenes and having physics applied to them, they're just jointed together using weld joints or other types of joints, pulley joints, depending on what they are. In this case, there's the 2 circle shapes here, circle fixtures that are the wheels on this cart, and then they're welded to the flat sort of constructions here. But that's allowing those to be dynamic allows the wheels to roll and therefore carry the other load with it. Same with this bridge. These are I forget the exact name of the joint, but it's a chain of fixtures together that are welded by a specific kind of joint, and by putting them together in this way, you get a sort of bridge, and all sorts of things that you could think of, including tanks, which is in the notes here. This third link, there's one of them talks about how to implement a tank by having treads going around circles and like a massive body. Like, you could do anything with Box 2D. It's an awesome library. In the context of Angry Birds, really, we just scratched the surface for what is possible here. So I'm going to demo now. Actually, I enjoyed, I think, this demo, this bit of code, more than I enjoyed the Angry Birds implementation. And it's a program that I wrote called Ball Pit. So, oh, by the way, before I get into that, so I'll leave that as a little teaser, I guess. Looking at kinematic really quickly, we're going to look and see that I've created a table for the kinematic bodies, a table for the fixtures, and then one shape, because you only need one shape actually, and you can apply one shape to as many bodies as you want to, as long as they all have the same shape. I just create 3 kinematic bodies here, so spacing them out relative to the center with this math here. They get the string kinematic, and that's really the key difference. And then before finishing, I make sure that I set them to have an angular velocity. So this is how you spin something. If you want to set something to spin indefinitely, just set an angular velocity, in this case 360 times degrees to radians, and that's just a formula written out as a constant, which is just the number. I forget offhand what exactly the formula is, but it's up here. It's degrees to radians 0.0174532.9, etc. But just like pi, it's a number that you can use to multiply a number in degrees, and you'll get a number in radians. And there's the reverse up there as well. We have to do this because Box2D expects, for any types of rotation, it expects it in radians. I prefer thinking in degrees, so I passed in 360 times degrees to radians. And so we render down here, just as we did with the box body, we render the kinematic bodies, polygon fill, kinematic bodies at I, get world points, kinematic shape, get points. Nothing terribly different. The only real key difference is that we've added kinematic as a string to the constructor for the body, and we've added some angular velocity. And recall, this will make it spin indefinitely, but it will never be influenced. Its angular velocity will never be influenced. Its position will never be influenced by anything else in our scene. So now with that out of the way, I'm going to pull up ball pit. So, and maybe I'm just a little bit too excited about this, but I enjoyed this a lot. So what it is this is sort of like a bigger demonstration of putting all these pieces together. We have a bunch of circle shapes. They're all interacting with each other. They all have physics. And then I have a larger shape here, this square, which has a higher density than everything else. And by pressing spacebar, I can just dive into, throw it into the ball pit, and it'll interact. It'll cause an interaction with everything else. And a bug/feature that I discovered about this is that if you press spacebar over and over again, it never resets its velocity. So it just slams down into the ball pit. So it's just kind of fun. And I think there might actually be possibly a game idea in here. But I mean, but what are the pieces here? What's different about this?
They're all dynamic shapes.
Yeah, so they're all dynamic shapes except for the ground at the very bottom. And also hidden from view are actually 2 more static static shapes on the left and right. Because if we didn't have those, all of the balls would sort of fall to the side out of view. But yeah, we have the static sort of delimiters for our scene, but we have a bunch of dynamic bodies. The balls are all dynamic, and then the square is also dynamic. And then, like I said before, the only real difference between them is that obviously the square is a rectangle, but it also just has a higher density. And so by giving it a higher density, it pushes everything else. Oh, what happened there? That was weird. It pushes. I think it went to sleep because we didn't do anything for a while. But we're able to. It's able to fall through everything else because it knows that it's heavier and that it should push and apply a larger force to everything else that's around it. And so by using these fundamental building blocks of what Box2D is, you can sort of construct a lot of really cool simulations and other fun programs and actually get interesting game ideas. I'm inclined to believe that Angry Birds started out as somebody messing around with the Box2D or a physics engine like this, and it was inspired by some other game that I should look into a little bit. But the creators of that game presumably found this physics engine and were like, oh, this is cool. I'm going to put a tower of blocks here and just throw something at it. And then they realized, oh, we could make a game out of this. And so I encourage you, if you're ever curious, to just experiment with things like that. We could probably turn this into a game. I don't know. I like this a lot. It's a good sort of segue from the sort of abstract, for lack of a better word, examples that we used earlier, and sort of merges it more into the realm of how can we make something fun with this. And so that's how we're going to sort of start moving into the distro today. So the main topic of today's lecture was Box2D, and how we use it to make a game. Another thing that we should consider is mouse input. We haven't really used it yet, and I believe I've mentioned it before slightly offhand. But LÖVE2D makes it super easy. It's just like we do with keyboard input. We just have a couple of callbacks that are in main.lua, mouse pressed and mouse released. The difference between these and keyboard or key pressed and key released is that they also get an X and a Y, because usually when you click the mouse or release the mouse, you want to know where it happened, because that's obviously pertinent to what you're doing when you're using a mouse. So these are fired by LÖVE2D every time you click or release a mouse button, and they get the X, the Y, and the key, and you can do whatever you want with those. And just as we've done in prior lectures, so that we can use mouse input in other modules besides main.lua, there's a function called love.mouse.keyPressed and key release that I implemented in main.lua. You can check those out. They're very similar to how we did the input tables for the keyboard before. But they allow us to use this functionality inside of other functions, other modules besides main.lua. So let's go ahead and start looking at. This is where we're going to start sort of looking at the distro for Angry Birds and how we can take all these pieces and form them into an actual game. So the first thing we'll do, we'll take a look at just a couple things, then we'll take a short break, and then we'll get more into the meat of it. But let me go ahead and clear out all of these. And then we're going to pull up. So the distro is in Angry 50. And so main.lua is here. So not a whole lot is different in here. So we have two states in our game. So we had a start and a play state, as we saw before. The start state is like we've done before. The only difference is in this start state, well, for one, it's running a box 2D simulation. And two, we're actually using mouse input. So actually, let's look at main, and so you can see where I've added this, which is different than before. So we have love.keyPressed, as we've seen before, but we also have mouse pressed and mouse released, and then mouse was pressed and mouse was released. So those are the main differences in main.lua this time, as opposed to prior lectures, which we only had keyboard input. And as you can see here, we have input tables for keys pressed and released on the mouse. And so we initialize those to empty on every update frame, just like we've done with the keyboard. And then the input tables get updated in the callback functions, as we've done before. And so that's basically all that's different about main.lua this time, and that's sort of how we've tied together the new mouse functions that we've just looked at into our game. The states that exist in our game are play state and start state. So very simple, very similar to last week where we looked at Zelda. We only basically had a start state and a play state. The start state, we can see here, just to tie together the last bit of our usage of the mouse. Love.mouse.wasPressed 1. Does anybody know what this 1 is? It is left click. So LÖVE2D assigns integer values to all your mouse buttons, and 1 is traditionally the default value for left click. Some frameworks will use 0, but Lua 1 indexed, so start with 1 instead of 0. The thing about the start state here that's kind of cool and interesting, so I'm going to go ahead and play it again. The game. So we start off, and right off the gate, just to make things kind of interesting, rather than just have a static screen that says, Angry 50 click to start, we're actually running a LÖVE2D, a box 2D simulation here. It's a world with a bunch of squares. And so, like, what kind of bodies are all of these? They're all dynamic bodies. And we've encapsulated them all, just as we did before in the ball pit example, with some invisible static bodies on the left, right, and bottom of the screen. Because if we didn't have those static bodies, they would just fall all the way down. And the nice thing is we don't actually have to render anything. So if you want a sort of maybe an invisible barrier for something in your game, or you want to encapsulate something, something physical, you don't have to render anything. You can just have arbitrarily shaped and positioned static bodies, and that will act as a container. So and that's all we're doing there. We have a container set for all of our little square alien guys, And by creating, I think 100 of them and just letting them drop, we have this sort of interesting visual start to our game with very, very minimal effort. So we can take a look at this. So in our start state init, as I said before, we have a world. We obviously need to remember a new world. Anytime we do any Box2D stuff, you have to start by having a love.physics.new world, else you won't be able to run any simulations. We're going to create a ground, walls, and then a bunch of aliens. So this here, we can see that we have a table that we're inserting aliens into, but we have a class called alien. So just anybody want to ballpark what an alien class ultimately encapsulates or ultimately is?
Probably the way it looks, like the skin.
It is, yeah, that's definitely a part of it. So the way it looks, or its skin, so it does have a reference to that. And then more functionally, it also possesses a body and a fixture. So rather than having a bunch of bodies and fixtures that are sort of separated out and maybe like just in tables at the surface level of whatever our level, just like wrap them in a class, and then we just can maintain a reference to each individual alien's body and fixture that way. So it's a little bit more encapsulated. It's a little bit more object-oriented, a little bit cleaner in my opinion. The alien class can take square or round as its, well, it can take anything you want to as its type. So this will ultimately decide how it's rendered and what shape it gets. But if it's square, which is the default, so if you just create an alien with no type, it will get a love.physics.rectangle shape. So as we saw before, that's just a box. And then if not, we just default to circle shape. But you could program it to take in whatever shape you want and then just give it that shape. And you don't really have to do much in terms of coding how it interacts with anything else, in terms of collision at least, because thankfully Box2D will know, okay, it's a circle, it should rotate, it should spin around and interact with things like a circle, or it's a rectangle, so it should interact with things like it's a box. Just nice and convenient. And then we'll just create a fixture here. This set user data function here is important because we'll see in the context of how we actually resolve collisions in a customized way. We'll need user data to be able to differentiate what gets collided in our world. But at the moment, you can just know that this basically allows us to pass in, to set arbitrary data onto a fixture. So we can say fixture set user data alien, the string alien. And what that means is that fixture has some customized metadata about it that says this is an alien. It's whatever we want to do with it. We could give this a table as well. We could just say the user data is a table, and then it has a bunch of information that we can then use at collision time to perform different work on it. But this set user data function is how we are able to resolve collisions between obstacles and aliens differently than, say, players and aliens, or even the alien and the ground, because when we do any Box2D collision, right, the world's taking care of the collisions for us. How do we sort of tell the world, okay, when I hit the ground, I want to play a sound but not do anything. If I hit this box at this velocity, I want it to destroy it. If I hit the alien, I want the alien to disappear, and I want to play a victory. I want to show a victory label. Like, how do we do all these different things? We do that with what are called collision callbacks in the context of Box2D, and we'll see how that works. But suffice to say, user data will be very important coming forward. And then this launched false. Actually, we don't end up using this, so this is irrelevant. But it has a render function here, which just takes in the bodies x and y, and we'll draw it at the angle that it's at. So that's an important thing. Before, what we were doing is drawing things via shapes. So love.graphics.polygon, love.graphics.circle, love.graphics.line. But if we want to draw a sprite instead, we need to draw it at the right position, first of all, right? And then things also rotate in Box2D. So we need to draw it at the right angle. So what we do is we can actually query the body for its x. We can query the body for its y, and we can also query the body for its angle. And then we can draw the texture and the quad that we want to using those x, y, and the angle, and that'll have the effect of drawing a sprite in the world that mirrors what's going on in Box 2D rather than just a simple shape. So that's as simple as it is for drawing a sprite instead of a shape. You can see here the 17.5, 17.5. Does anybody know what that's for? So 17.5, 17.5 at the end is half of the width and half of the height of the alien. So aliens are 35 by 35 in this game. We pass those in. This is the center of origin. So when we rotate something by a center of origin, it basically means where it describes where it's going to, where the rotation is going to take place. So if it's rotated about the top left and we rotate something, it's going to have the effect of the sprite sort of like going around in a circle in sort of an odd way. If we rotate the sprite based on the center of origin of the actual sprite itself, that'll have the effect of rotating the sprite on its center, right? So you can set that origin wherever you want to, and it'll perform a 360-degree rotation about that point. And we're setting that point to to basically the middle of where we're drawing the sprite. And so that'll have the effect of when we give it this angle here, self.body to get angle, the rotation will take place in place. It won't take place, it won't be some sort of weird, about the top left corner rotation, which is not what we want. So when you see center of origin being modified like that, you can sort of assume that it's because we have an offset and we're trying to find the center of wherever we're drawing and rotate about that to do an in-place rotation. But not necessarily. You could also draw something. You could also maybe you want something like some sort of magical ball of energy to rotate about like a rod or something, and so you want it to rotate around a different center, or whatever you want arbitrarily. But typically, at least mostly that I've seen, this is useful for making sure that your rotations, your in-place rotations, are accurately rendered. So, any questions about sort of how the alien class works? All right. So that's the alien class. That's basically the fundamental building block of our game. The other part is the obstacle, right? We have obstacles and we have aliens. The obstacles and aliens are actually very similar. So what's the difference between? I mean, ultimately, how are they similar? They're both dynamic bodies, yeah. Really, the only thing that's different about an obstacle and an alien is what we do with them in our scene and how they're rendered. But they function very similarly. They're just dynamic bodies that we give a shape to, and we render them at that shape, with that shape. In this case, the obstacle constructor, we've sort of decided to design it such that it could take a shape, horizontal or vertical, which is similar to the type that we saw before with the alien, where it could be square or circular. In this case, if we look back at our sprite sheet, back here, we can see there's a ton of different shapes. But the only two shapes that we're going to use in the context of this game, just for this demonstration, are the horizontal, clean wooden shape here, and the vertical one that's right here. And so in order to find those out, I had to open up this sprite in my sprite editor, figure out where the x, y, width, and height were, and then create a quad manually off of that. And then I edited the util.lua, or not util.lua, the dependencies.lua here. Normally we just create G-frames, and then we use generate quads, and you can do that like with the aliens and with the tiles. The tiles being the sprite sheet that this one right here. These are 35 by 35. These are 35 by 35. These are not 35 by 35. These are a bunch of different shapes and sizes. So I went through and G-frames wood is 4 manually created quads here. And then there's 4 because I also added the sort of semi-broken shapes as well, but we don't actually use those. But you could decide to turn these into these on collision, perhaps maybe if the velocity isn't strong enough to break it necessarily, but you want to have some sort of feedback that you collided with it, you can just set maybe the frame to 1 or 2 on collision for that object instead of 2, and render it appropriately. But if you're dealing with a sprite sheet and that sprite sheet has odd sort of distributions of its sprites, sometimes you have to figure out where the offsets are manually and do it that way. The ideal is that you don't have to and that you can do it programmatically, but it really depends on the game, what your domain is, and sort of what objects you're interacting with in the scene. Any questions on sort of the why or how as to that? OK, cool. So back to the obstacle. So they're horizontal or vertical, and what that does is it sets the frame to 2 or 4. And the 2 or 4 being in G-frames at wood, the 4 quads that I sort of had a hand figure out the coordinates for. And really, it's not a whole lot different at that point. If it's a horizontal or a vertical shape, then we need to set its width and height appropriately, because it's going to have a different width and a different height. If it's vertical, obviously the height is higher than the width, and if it's horizontal, the opposite is true. But they're both a rectangle shape, so you can pass in the width and the height after you calculate that and give it the right shape, and then ascribe it a fixture, and then set user data. In this case, we set user data to obstacle. So now that obstacle, the fixture specifically, knows that it's an obstacle, as opposed to being an alien, as opposed to being anything else, as opposed to being the ground. And so when we explore in a few minutes what with the custom collision, world collision callbacks that we can actually define all this interesting collision behavior for, this user data is going to be relevant. And then we render it just like we render the alien as before. So any questions on obstacles and aliens, how they differ, how they're the same? Cool. All right, let's take a 5-minute now. When we get back, we're going to actually look at the play state. We're going to look at what makes a level, and we're going to actually look at how we can customize the world to resolve collisions in ways that are relevant to our game behavior, as in how to make things break when we collide with them, how to make the victory screen pop up when we've destroyed the bird, so on and so forth. All right, welcome back. So before we took a break, we were talking about the aliens and obstacles that are in our game world that interact with each other. They are sort of the backbone of what makes our game / Angry Birds work. You throw aliens into the obstacles break. The bad pigs / aliens die, and then you score up points. But we actually have to model these interactions, and we have to tell our game, our world, what to do when these collisions happen in order for things more interesting than just things bouncing off each other to work. That's the default behavior. Box 2D's goal, by default, is when two things sort of overlap, assuming that they're dynamic, or at least one of them is dynamic, is to push the dynamic bodies sort of away until they no longer overlap via either position or rotation. But that's not the gist or the goal of our game, because what we want to have happen is different things happen, and certain things to disappear and to break, and all sorts of other things to happen when different kinds of objects interact with different kinds of objects at differing speeds. So in order to do this, we need to define collision callbacks for our world. So a callback, recall, is a function that gets called back when something happens. It's just something that will get called at a specific time or later on, and we can define these callbacks for our world such that when two things collide with each other, it will execute this callback and then perform the corresponding logic that we've defined therein. And with every collision in Box 2D, there are 4 callbacks that take place. There's begin contact, so when two things begin to overlap or begin to contact one another. End contact, so once that ends, so once two objects are pushed away from each other. Pre-solve, which happens right before the collision actually gets solved in Box 2D, meaning that the things get pushed away from each other. And then post-solve, meaning right after they get pushed away from each other. And the post-solve in particular is interesting because it gets the information about how the collision needed to resolve. So how much velocity or rotation needed to happen within that interaction. And we will not be using end contact, pre-solve, or post-solve. We will only be using begin contact because really that's all we need in order to model the behavior that we're looking for. Because anything that happens in our game, we can just figure it out as soon as two objects touch each other. And these are things, if you're interested in a tutorial that sort of goes over these in perhaps a little bit more detail, there's a link here in the slides. But I'll show you how to actually implement these callbacks yourself. You do this via a function called world set callbacks, in this case f1, f2, f3, f4. And recall, because Lua is a dynamic language where functions are first-class objects, you can pass in functions as arguments to other functions. And that's what we're doing here. So this is assuming that we have 4 functions we've defined called begin contact, end contact, pre-solve, or post-solve. Their actual names don't matter at all. These are just sort of the de facto names for them. What matters is that you have the logic there and you pass in function objects that perform something. And you can pass in all empty functions, and Box2D will still behave as normal. These are only for when you want more complicated behavior out of your game than just things bouncing off of each other and sort of moving relative to one another. So does that sort of make sense? So we'll see how this actually works. So we're going to go ahead and open up level.lua. So level.lua is a container class that basically has our game level in it, including the world and all the entities, and we sort of update it and are able to model effectively our, like a level from Angry Birds. That's really what it is. It has a world, so the level has its own world with 300 positive Y gravity, as we saw before. It has a table called destroyed bodies, and we'll see that in a second. And then here we have 4 functions. Starting at line 22, we have begin contact, which is a long function, and then we have end contact, pre-solve, and post-solve. These are the 4 callback functions that I alluded to just a few seconds ago. They take in slightly different signatures. The first 3 take A, B, and collision, and then the last one takes in A, B, collision, and then a normal impulse and a tangent impulse, which are the forces that it needed to apply in order to push apart the 2 objects. Like I said, we won't be using these 3 functions, but there might be a situation where you need to use those functions. Maybe you want end contact because in your game, 2 objects attach to one another, right? When they collide, maybe they're magnetic or something, and then once they pull apart, maybe you want like a particle effect or something to show that they've separated or something. And then pre-solve and post-solve. Pre-solve, offhand, I can't think of a use case, but post-solve could be useful for, depending on your game, whether you need to just figure out maybe the amount of force that they needed to separate. Maybe you multiply that by some amount and cause some sort of dramatic effect. Those are ultimately dependent on the domain of your game. The important function that we'll be using today is the first one, begin contact. And notice that we've defined these 4 functions, even if these 3 are just empty, but we pass in, as I said before, the set callbacks function takes in those 4 functions. And notice another interesting thing, because of Lua's dynamic nature, line 11, you can see that we have level init, which is the constructor for our level class. Within the constructor, we are defining more functions. You can define functions as many layers as deep as you want to, and you can even return functions from functions, which are called higher order functions. Really, you do whatever you want to. In this case, we're just defining the collision callbacks here inside of our init, but you could put them most anywhere you want to. You could have them outside of the class. You could have them wherever you want. You could have them be global functions in your main.lua, which I don't know how I feel about that, but you could do whatever you want to. As long as the functions exist and you can reference their symbols, you can pass them into self.world set callbacks, and now whenever a collision happens in the world period, it's going to call all 4 of those functions at each stage of each collision. So you could see that potentially getting a little bit hairy if you were to scale high enough with all of your logic. If you had 1,000,000 lines of code in each of these and it's executing 1,000,000 lines of code per collision, you could run into trouble. But fortunately, we're not going anywhere near that. The gist of begin contact, so it takes in an A and a B and a collision. We don't end up using the collision itself. We just use the A and the B because that's all we need for our game world. The A and the B are what? Do we know what the A and the B are?
Why the 2 objects collide.
The 2 objects. Do you know whether it's a body or a fixture? It'll be the fixture. The fixtures collide with each other, not the bodies. So when you have a body, recall that the fixture attaches the shape to a body. The body is just a position and velocity container for a bunch of fixtures. The body is. Each individual fixture collides with other things, other fixtures in your game world. And so recall that before we had fixture set user data, because that's what we end up needing to have data on when we do the collisions. We check to see, via get user data what something is or what metadata we've given to that fixture, and we can then separate different classes of objects this way. We can say, oh, this object was an alien, or this object was an obstacle, or this object was the ground, and then we can say, oh, did we collide with an alien? It was the collision between an alien and the ground. If it was, okay, let's play like a bounce sound effect. And if it was between an alien and the other alien, the player and the other alien, and the velocity was fast enough, okay, the alien should die, right? We can do arbitrary things. And so the way that I've programmed it here, such that we can see what two things interacted with each other, and this is a very simple use of user data, and all we're doing in this code base is just assigning strings to fixtures, but you could assign tables to fixtures with arbitrary amounts of data and do all sorts of things. In this case, we're only using strings. So I create a table, an empty table, and then I just assign at table, at that string, true. And then I can just query that table. Do I have a key player and a key alien? Do I have a key obstacle and a key obstacle? This is how you can sort of figure out what your two objects were, because A could be a player and B could be an obstacle. A could be an obstacle and B could be the player. So you have to sort of take both of that into consideration. So it allows us to do if types obstacle and types player, so a collision between the player and an obstacle. If it's fast enough, then we can destroy the obstacle. This is what we do here. So I take the absolute value of the velocity on the x and the y. So I do vel x, vel y. It gets the body's linear velocity. So linear velocity is just where it's moving in the world. And it returns two values because the velocity has an x and a y component. And then we sum it here by taking its absolute value of both parts and adding it together. So if it's moving fast on the x-axis but not fast on the y-axis, or if it's not moving fast on either, or if it's moving fast on both, we have a sense, like in general, like what's the average velocity of our object. Like if it's moving fast on any of the axes, we can assume that that's sufficient force to cause an object to get destroyed, right? So we do if the sum velocity is greater than 20, just an arbitrary value that I came up with that seemed appropriate, then we're going to do this. Table.insert self.destroyed bodies, which we saw earlier, and then the obstacle's body. Now, why are we inserting that value here as opposed to maybe just like destroying it inside this function? Do you have a
Destroying the texture?
destroying the body, the fixture, yeah. In this case,
I mean the fixture,
yeah.
sorry. Because you're still referencing it later in the code.
You're still referencing later in the code. Box2D maintains a reference to all of the bodies, all of the fixtures in your world, regardless of whether you've deleted them or not. But if you delete them while it's in the middle of like checking for collision, it'll try to do another collision with that destroyed body, and you'll get a crash or a Stack Overflow error. I experienced both of those. You don't want to ever delete or destroy anything while inside a collision callback for your world. It will cause horrible things to happen. So what we do is we maintain a reference to everything that we're going to destroy by just inserting it. So if we do table.insert the body of whatever we want into destroyed bodies, we can then loop over that after the world updates and then just destroy them one by one outside of the update function. And the reason that we are passing in the body and not the fixture is when we destroy a body, it destroys all of the fixtures associated with that body as well. So we're just destroying the top level container here. In this case, it doesn't matter too much whether we destroy a fixture or a body because it's a one-to-one relationship. But if you had, let's say, a body that has like 5 fixtures on it, And if that entire thing collides with something else and you want to destroy that entire thing, you want to destroy the body, not an individual fixture, because when you destroy the body, it destroys all the fixtures, not just the one fixture. So that's why we're deleting the body, adding the body to destroyed bodies, and then later performing a delete off of that. The function is destroy here. So on line 157, well, 155 to 159, this is where we actually iterate over everything that we wanted to flag, or that we've flagged as destroyed, and we destroy it. So if the body is destroyed, destroy it. And then once we destroy it, we're going to go down here and end up actually removing the obstacle and the alien class from our list of aliens and obstacles. Because that maintains a reference to like what we're drawing, and we want to also delete that. So not only do we want to delete the object from the world, we want to delete the objects that we've created that are sort of a wrapper for the bodies and fixtures, and also the drawing of our alien, so it no longer gets drawn to the scene, basically. So yeah, don't ever delete a body or a fixture inside your callbacks. Always flag them and delete them afterwards. Basically, don't delete in the middle of a world update function call, which we see here. Notice that this takes place 152, we're doing self world update, and then on 155 to 159, we've populated destroyed bodies via the collision callback that we defined up above. So in here, this is where we can actually destroy everything. This is outside of the update function here, the world update function. We don't need to worry about Stack Overflow or a seg fault, which we get by deleting something while it's in the middle of processing its its collisions. So unfortunate bug. If you ever find yourself running into Stack Overflows or seg faults in your collision callbacks, make sure you're not deleting anything. So, but we can see here it's very similar with the behavior we defined between obstacles and the player, between obstacles and aliens, and between the player and alien. Ultimately, it's check to see whether the average of its velocity is greater than a certain number, in this case 20, and if it is, flag it as destroyed. So if the player hits the alien, destroy it. If an obstacle hits the alien, destroy it. And it's sort of similar to how it works in Angry Birds. Like when you throw something at a structure in Angry Birds, and a piece of debris falls off of it and hits the pig, usually kills the pig too. And if your bird hits the pig, that usually kills the pig. But if you're not moving fast enough, or if a piece of debris isn't moving fast enough, it'll just sort of nudge the pig. It won't actually kill the pig. So that's why we're taking all this into consideration. We're not just doing a blind delete off of the bodies in our code. We're actually making sure, is it also moving fast enough, i.e., does it have enough force? And if it does, then perform the code. Then perform the deletion. Flag it as being deleted. And so once again, that's why user data is important, because that's how we're able to, because notice in the callback, we just get an A and a B, and those are always going to be fixtures. Fixtures, in order for it to know what kind of a fixture it is, whether it belongs to a player or an alien, we need to give it some information. So the set user data flags the fixtures as being of a specific type, and then we can fetch it here with get user data, and then actually perform the relevant game logic. Any questions as to how this works?
Are you checking for like two obstacles knocking into each other?
Am I checking with the two obstacles collide with each other? I might not be. In that case, you should. In that case, since we're not, they'll just bump into each other. But yeah, if we wanted two wooden obstacles to like destroy each other if they hit fast enough, you would just do the same thing here. If types obstacle, I guess. But in this case, because they're both the same key, you would have to do if types obstacle. If types, let's see how we're doing it again. So types obstacle is true. Type obstacle is true. You would say if types obstacle and not types alien, not types player, not. There's a cleaner way to do it.
Like a series of else if statements.
Yeah.
Like just a bunch of statements.
Yeah, that's true. Yeah, there's a lot of ways, and if I were to re-engineer this, I would also abstract out this code and make it a function, because it's pretty much the same code between all three of these. But just to illustrate, and just for simplicity, because it's pretty similar interactions, didn't really put too much engineering forethought into it. Definitely, if you expand upon it, I would recommend doing that. But that's the gist of making our world behave beyond just resolving collisions and pushing obstacles away from each other, which is the default behavior. So we set the callbacks. We're good. Now things, when they interact with each other, they'll behave differently. They'll trigger different behavior. We have this thing called a launch marker, an alien launch marker. Anybody know what that might be?
Is that like the little dots that show the trajectory?
Yeah, so it's the dots that show the trajectory. It's one, the alien being rendered on the left side of the screen without any physics applied to it. That's click and draggable. And it also renders a trajectory. And when you release the mouse, it launches an actual Box 2D alien traveling in the direction that that trajectory sort of foretells. If we look at alien launch marker here, it maintains a reference to whether we're aiming or not. So it's got a couple of states. It's got like a launch state and an aiming state. An alien that we'll have a reference to eventually, which will spawn and will give it an impulse. So an impulse is effectively setting its velocity immediately to some value, as opposed to something over time. We can apply force to an object, which would be like you driving your car up against something and then gradually accelerating. That's applying force. And we can also apply an impulse by going full speed with our car and hitting an object, and that will sort of have the effect of applying an impulse at a certain velocity. When we drag our alien and then we release it, we want to apply an impulse in the opposite direction of where we're dragging, based on a certain amount. I scaled it by 10, but you can have it be arbitrary. And then the trajectory sort of models where it's going. And the trajectory is calculated via these lines here. So from line 90 to 104, there's a formula for in that Box 2D set of tutorials that actually shows you how to calculate an estimated trajectory given a starting impulse and a starting position, which is this formula here. It's semi-complicated. The article goes into detail as to how it works, but it effectively calculates 1/60th of a second, assuming that we're running our simulation at 1/60th of a second. It will, over 90 iterations here, 1 to 90, calculate each individual step of that simulation, and then I only render every 5 here. So if mod 5 is 0, then I'll actually end up drawing a circle at trajectory x, trajectory y. Trajectory x and y being here, shifted x, shifted y being the starting location, and then we multiply I by 1/60th of a second, which will give us the scalar for this impulse here. And then with gravity, we have to do this I squared plus I times a half times the gravity on the y-axis times 1/60th squared. The article goes into a little bit more detail as to how it works, but that's it converted into source code. But it's effectively a gravity simulation and a velocity simulation over time. And by rendering it based on 90 iterations, which is 1.5 seconds, at 1/60th of a second, we can forecast where exactly we're going, and then when we apply this impulse, x and y, the ball will actually travel, the alien will actually travel in that direction at that exact trajectory. So that's the complicated part of the launch marker. The other part is that it has a couple of states, like I said before. So when we click and we're not launched, it should go into aiming mode. And so if we're aiming, then we're going to set our rotation to, actually, rotation is not relevant because this was before I ended up using the predictive trajectory method. The shifted x and y, though, those are relevant because that's the sort of starting location for your trajectory. That's wherever your mouse is. And we clamp it so that it doesn't go past a certain limit on the left or the right, so that it stays within like a box area. But this will be whenever you let go of the mouse, that'll be where we spawn the Box 2D alien and apply an impulse in the negative direction relative to where we've moved the mouse. So if we move the mouse to the left and down, it's going to spawn, it's going to negate that with an impulse going up and to the right, if that makes sense. And that's what's shown by the trajectory. And then aside from that, it renders different things depending on whether or not what state we're in. So if we haven't launched, it'll render just the alien. If we're in aiming mode, then it should actually render and calculate the trajectory. Otherwise, it should just render the alien. And so once we release the mouse, so was released 1 and we're aiming, launched is true, spawn an alien, so we create a new alien with self world. It's round. We started at shifted X and shifted Y. And we set its linear velocity to the same values that we calculated before. So it's base X minus shifted X times 10. So the times 10 is a scalar amount. And then it's the base X is the where we've moved it effectively. Or no, base X is where it starts, and shifted X is where we've moved it. And so by subtracting shifted from the base, we get the sort of negative direction that we want to affect the impulse. And then the impulse is set here with linear velocity. And then we also set it to have a restitution of 0.4. Recall restitution is bounciness. So our alien bounces a little bit when it hits the ground. And then anybody know what angular damping might be? Any guesses? Angular damping is when it rotates, basically friction on its rotation. So that when it rotates on the ground, it doesn't roll indefinitely. If we don't set that, it'll just roll forever and ever and ever and ever, which is not what we want. We want it to stop at a certain point, because once it stops, we know, okay, now we can get the next alien ready to launch, right? And that's the gist behind the launch marker, how we render a trajectory. For the math on that, a little bit more in detail, I would explore that URL. It goes into it into pretty good detail. I use that as a reference for creating this bit of code here. But yeah, effectively is it just rendering a bunch of circles with that trajectory and calculating it over 90 ticks, 90 sort of frame iterations. Back to the level. Oh, sorry, any questions overall as to how the launch marker works? Cool. All right, so then we have an aliens table, an obstacles table, edge shape for the ground. And then we just create an alien to destroy, spawn a few obstacles here. So in this case, 2 vertical obstacles and a horizontal one, positioned such that the horizontal one is over the vertical ones and they're spaced apart such that the alien is right in the middle of them. Then the ground here, we give the ground some friction, 0.5, and that's pretty much it for setting up our level. So if we wanted to, after this point, we have the foundation necessary to really spawn arbitrary levels with admittedly simple obstacles at this point, but we could set because all we're doing here is just simple insertions to our aliens and obstacles table, we could create, pretty much any level just by maybe in data specifying, level could be like a table, and then aliens could be another table, and then maybe all it is just a x equals some value, and then y equals some value. And then obstacles is sort of the same thing. And then all we do is we iterate over this level definition, and we just say new alien for every table in here, and then new obstacle for every table in here. And then now your levels are data driven. It's easy just to make levels. You don't have to code really much. And you can put this in a separate file, be like levels.lua, and then just load individual levels at a time. Level 1 equals levels would be the top level container, and then you would have 1 equals all of this, and then 2 equals another one, 3 equals another one, and then you're not really programming as much as you are just sort of laying things out in data. Super nice and concise. That's the nice thing about a language like Lua, is that you can, and it's sort of the same thing in JavaScript, with JSON, you can just define things as data and then write a script to go over it and construct your actual relevant data structures that way, and your code that way. When you have the foundation like we have now, where you can think in terms of obstacles and aliens, you can construct levels like so. And obviously you could go a lot more complicated with this. All we're doing is having very simple sort of almost boring static obstacles. Like they're not static in the technical sense because they're dynamic objects, but all they really do is just stand there and then fall over. But if you wanted like a pulley system or maybe something that's like shaped in like a giant head or something, you can create arbitrarily complex objects that way using joints. And if you're curious, I recommend to look into the documentation for LÖVE2D a little bit more, and especially their weld joints are what you would use to like combine pieces in arbitrary shapes. But you could easily take this to the next level and start to create in that same level definition arbitrarily shaped, welded together obstacles. But that would be, I think, a next step if you're looking to take this beyond just one level. I would say think in terms of how can I get my game world represented in a very simple data-like way, because not only does it make it easier for you to create content, it allows you to shift that burden to somebody else and allow you to give the task of creating levels less to a programmer and maybe more to somebody who has just a design background, who isn't as comfortable writing code, and allow you to create the engine that then constructs the game world based off of this data. Any questions as to how we've set things up here? Okay. So we have the ground, we have a background. A background is just a simple class that renders a static image that you can scroll the image with left or right, but we don't end up using it much. It's relevant in Angry Birds because in Angry Birds they have a camera, and the camera pans left to right depending on how far away the fortress is from your slingshot. So that's in there if you want to experiment with it at all and experiment with it, make a moving camera. Maybe use like timer.tween to tween the camera, or just to have it track the alien if you want larger worlds. But we don't end up using it in the distro as much. Our update function is simple. We update the launch marker, update the world, and then we process all the bodies that we flagged as being destroyed, which we've already seen. We reset destroyed bodies to an empty table because we've processed all of them. We actually remove from our level the obstacle objects so that they're no longer rendered, and we no longer try to reference the bodies that are destroyed. And then notice here too, when we destroy the obstacle, we're playing a sound effect inside this bit of code. So we can just do G sounds, and then I put 5 wooden sound effects in there just for variability. It'll pick a random one, and then using toString at the number, just create break 1, 2, 3, 4, 5 here, and then stop and play it. Same thing here. I have a sound called kill for when we destroy an alien. So when we flag an alien as destroyed and we remove it from the scene, we should also call that sound effect. And then if the alien stops moving in our scene, the player, we get a reference to it here, self.launchmarker.alien, as opposed to like any aliens in our scene. When it stops moving, so we get the average of its velocity if it's less than 1.5, so not perfectly still because it's kind of tedious to wait that long, but almost still. We destroy the alien, and then we create a new launch marker. We destroy the alien so that the world doesn't keep a reference to it, and then we just create a brand new marker which has the effect of instantiating a new alien there when we relaunch. And then here, if there are no more aliens in our scene, if we've destroyed all of the aliens, in this case there's only ever one, but there could easily, with a little more work, be a few more aliens in the scene. If it's set to 0, then go back to the start, which we saw before when we finally kill the alien. And then all we're doing here is deferring rendering to the individual objects that we want to render, the launch marker, the alien, the obstacle. We render ground tiles. So recall from our ground example before, we were just using a line, an edge shape to represent the ground. But if we look at our game, we're not actually, we don't actually have, it's a little hard to see because I'm in 720, but there's actually a ground tile here at the very bottom, a bunch of them. And even though we have all of those tiles, all we're doing to detect collision is just an edge shape. So what we're doing is just beyond having the edge shape in our scene, we draw that tile, which is frame 12 in our sprite sheet, from negative virtual width to virtual width times 2, so 3 screen widths total. And then we just do it in increments of 35 pixels, because that's how wide the tile is. And that'll just create a bunch of the same tile at the very bottom of our screen. So just a graphical thing, not really necessarily functional. We have the edge shape already in our scene, but just to make the ground look a little larger than 1 pixel tall. And then if we haven't launched anything, we should display some instructions here. And then if we're at no aliens left, then we should display the victory screen. And the victory thing will last for just a little bit of time, because even though self.aliens is 0, this bit of code doesn't register until after the velocity of our moving alien slows down sufficiently. So this will get called when we're like just about to finally stop moving, and then we check to see, oh, okay, do we indeed have no aliens left? If not, time to go back to the start. We've completed the level. And then you obviously would just change this to go to be next level if you ended up implementing more levels in your game besides just 1. Beyond that, that's pretty much all of the code that's in this example. It's fairly, I would say, unsophisticated relative to prior examples, but mainly the burden is learning how to use the physics engine, the Box2D physics engine, which itself is quite a few functions. It's some of the longest documentation on LÖVE2D's wiki, I think. But the principles are pretty simple, in my opinion. I think it's actually quite easy to get rolling with a lot of cool features. Like the vast majority of which I don't think we even really covered, at least in terms of what you can do with compound objects and joints and things like that, which really start to go into the world of sort of more sophisticated and interesting physical simulations. Things like I alluded to before, pulleys and tanks and other things like that. Some features that we could look at potentially expanding upon if we wanted to make our game more interesting is more shapes for our objects. So if we look at our sprite sheet here, we can see there are things like roofs and circles and things like that. So more interesting obstacles beyond just square, rectangular shaped obstacles. Go back to, so like I said before, compound obstacles. So bunch of things put together via joints. So pulleys, there's motors, weld joints, which you can use you could affix a roof to a square and then have like 2 pieces that are sort of tied together, and you can make arbitrarily complex and shaped things and just be really interesting. And that big thing, that body with all these fixtures, will collide just as any other thing would, thanks to Box2D. As I alluded to before, instead of having levels to sort of be hard-coded into our level class, maybe define them in a Lua file called like levels.lua, and then just have aliens be a table, obstacles be a table, and then whatever else, however more complicated you want to get with your game, you can add more things, but just have it be represented as simple data structures. So aliens that maybe have different shooting mechanics. So if you've played Angry Birds, you're familiar with the fact that some birds will split off into multiple birds. Some birds will like dive and like go super fast and like break through all the obstacles in their path. Some birds will explode, and then their explosion affects all of the obstacles around them. So there's a lot of different gameplay mechanics you could implement using different types of birds or aliens. And then different obstacle materials is another direction we could go. And it's supported out of the box with the sprite sheet that I provided, because it has sheets for like metal and glass and explosive material. So there's a lot of different interesting things you could do just by changing up what materials you're using in the game. And obviously those will have different densities and behave in different ways. So assignment 5 is a fairly simple assignment. So this is just as I alluded to before. The task here is to split the bird that you shoot by pressing spacebar when it's in the alien. When it's in the air, press spacebar and have it split into 3. So you have your one that you're shooting already, so it should just shoot off 2 more, one that's angled higher, one that's angled lower, and all of those should be interactable with your game world. And that's really it. So if you can do that, then it'll show that you know how to affect the Box2D game world. Next time, next lecture, we'll be talking about, the theme is going to be Pokemon, but we'll be talking about more generally RPGs and turn-based games of that nature. It won't maybe necessarily look quite as pretty as this, but we'll be striving for a similar sort of overworld that we can walk around and then engage in fairly simple like turn-based battles and stuff like that. And also we'll be talking about user interfaces and like things like dialogue and stuff like that. But that was it for Lecture 6, Angry Birds, and I'll see you next time. Thank you. All right, welcome to GD50 Lecture 7. This week we'll be talking about one of my favorite franchises of all time, a core part of my childhood, Pokemon, as shown by the Pokeball on the screen there. So back in 1997, I think it was, the first Pokemon game was released, Red and Blue. I believe it was released a year earlier in Japan, where it was released as Red, Blue, and Green. And the overall goal of the game was fairly straightforward. You were a Pokemon trainer. Your goal was to go out into the world and try and capture any number of 151 different types of these creatures called Pokemon that were, based on a whole bunch of different types of creatures. Shown in this screenshot here, where there's a Weepinbell fighting a Geodude. A Geodude was a rock type. Weepinbell was a grass type. You had different types of Pokemon. When they fought each other, some types were better than other types, like this sort of very large rock, paper, scissors relationship. And it was just a very addicting formula. You'd have a team of these creatures that you had caught and raised and battled, and you'd fight other trainers. And the awesome part of this was you could go and you could actually fight your friends or trade Pokemon with your friends that they had caught. And you would often share stories back and forth about the different rare creatures that you had encountered and all sorts of things. You'd have a customized party that was sort of a part of you. And so this is Pokemon Red. The series has evolved over time. This is a screenshot of Gold and Silver, which was released a couple years afterwards for the Game Boy Color. Again, this was released for the regular Game Boy. Gold and Silver introduced a bunch of new features, including breeding and a day-night cycle and a lot of other things that became part of the core series. Here's Ruby and Sapphire, which was for the Game Boy Advance and got a significant graphical update, but the core formula stayed much the same. Here is Diamond and Pearl, which was for the DS, which was, it made use of two screens, as seen on the top and bottom there. Here's Black and White, which was another step forward in that it introduced three-dimensional graphics for the overworld, so you could actually see sort of 3D for the first time in the franchise. And then more recently, we've seen for the 3DS games like X and Y, which is shown here, and Omega Sapphire, Alpha Ruby, Alpha Sapphire and Omega Ruby, and Moon and Sun. And so this is a great illustration of the RPG genre of video games, role-playing game, even though it's sort of its own unique take on the formula. But it allows us to, we can sort of dissect this and take a look at what makes an RPG and what makes a Pokemon game altogether for a nice, cool demonstration. So today we'll be talking about a few new things. We'll be doing things a lot differently in this lecture example relative to other examples because we're transitioning away from the state machine and talking about a construct called the state stack, which is effectively a more advanced version of the state machine. Whereas before we had, a state machine that was in one state at a time, whereby we could be in the play state or the start state or whatnot. We can now actually have multiple states that exist in parallel that are on a stack data structure, which you've seen in CS50 if you've taken, where we can have, for example, the field state, the play state at the very bottom, which is always there, and then we can push states onto the stack as we need to, for example, a dialogue state, so that we can actually display some dialogue, some text to the screen without getting rid of the play state that we had there before. It allows us to render multiple things at the same time and then also return back to prior states rather than completely create new states every time we want to make a transition. We'll be talking about turn-based systems. So in RPGs, like Pokemon and others, there are often battle systems that are usually turn-based in this particular genre where you're fighting, you have one team or one character fighting against one other team or one other character, and you take turns fighting each other, and you have an indefinite amount of time to make your decision and then form some sort of strategy as to how you want to approach the problem. We'll be taking a look at a very primitive turn-based system, but a fully functional one today. Another huge aspect of this genre is graphical user interfaces, or GUIs, as they're shortened. things like panels and scroll bars and text boxes and menus, all sorts of these things that allow us to get a more visual sort of look at our data and allow us to navigate a much more complex game ecosystem more efficiently. And to tie it all together, RPG mechanics at large will be looking at things like leveling up and experience and how to calculate the damage that one party does to the other party throughout the course of a battle. And so it'll be a fairly complicated set of examples, but fairly illustrative of this genre as a whole. So I'd like to demonstrate sort of the example that I put together. If I could get a volunteer from the audience to come up and take a look. Tani, that'd be awesome. Thank you so much. So this is my simple but fully featured, more or less, demonstration of Pokemon. So if you want to hit enter or return. So this is so here we can see right off the bat we have a text box and a play state like we did before. So this text box is actually a state that's layered above the play state. So you can see here there's some instructions about if you want to press P, you can heal your Pokemon, you can press enter to dismiss. So if you go ahead and press enter, you'll be able to actually move around now. And so something to note is before input was actually halted while the dialogue was on the top of the screen for the play state. You're actually not allowed to access or update this bottom state because the state stack is only allowing input to the top state. And so I've limited the play state here just to this box, but if we walk in the tall grass down here, in Pokemon, in order to actually initiate an encounter with another Pokemon or another wild Pokemon, you walk in the grass. So here we've walked in the grass. There's a random chance for this to happen. Every 1 in 10, there's a 1 in 10 chance basically. So it's saying that a wild Bamboon appeared. So a wild creature appeared. He's level 5, we're level 5, should be a fairly even battle. So you can press enter and it'll say go your name of your Pokemon, which is an Ardart in this case. And it's randomly allocated at the moment. So go ahead and press enter one more time. Now we can see on the bottom right, we have a menu. So we can fight or we can run. So those two choices. So we can go ahead and fight. So if we fight, whichever Pokemon has the higher speed will go first and do damage. We obviously do a lot more damage, but he's a little bit faster, so he's going to go first. So we fight one more time. We should be able to knock him out. So as soon as we do, we get a victory message, we get a victory song. If we press enter, we'll actually get some experience for defeating that enemy. So we got quite a bit of experience. We got 65 XP, and that bottom bar, we can see we have all these GUI elements. We've got a panel here. We have text boxes, we have progress bars, all these pieces are coming together to give us sort of this turn-based system. And so after this, we may level up just to demonstrate leveling, which is part of the RPG mechanics side of this game. So go ahead and press enter one more time. Oh, we did perfectly. So we leveled up, and so now we're level 6. So we can see the 6 changed on our above our progress bars. So now we'll be a little bit stronger every time. And the stats aren't shown here. It's actually part of the assignment is to create a menu that'll actually show you how you leveled up, what stats actually increased. But underneath the hood, behind the scenes, you actually are getting stat increases. And so here we can see that if our HP goes all the way down to 0, we faint. And when we faint, the screen, instead of going fading to white, will actually fade to black to illustrate the difference between the two transitions. And so that we can keep playing indefinitely, the game will restore your Pokemon back to full health. And so this will go on forever. This is effectively what the simulator is. It's just a simple series of infinite battles. There are random Pokemon in the grass. There's 5 total that you can fight. But all the core pieces of what make the game are here. So actually, let's illustrate running too, if you wouldn't mind, just so we can see that there is a difference. So we can actually flee, and then the battle will get cut short there. We won't get any XP, we won't faint, but we still get taken back to the play state. So that's all for the Pokemon demo. Thanks so much, Tani, for coming up to demo it. But there's a lot of pieces involved here. But as we can see, as we will see, once we have a lot of these sort of foundational pieces implemented, it's not too difficult to start layering more and more of these onto the game to make it even more rich. In fact, the assignment is to, and we'll see this at the end, I'll recap this at the end, but the assignment's goal is for you to implement a menu similar to the menu that we saw where fight and run were shown, that allow you to, that will show you what your current stat is for each of your stats. There's attack, defense, speed, and your HP. It'll show you what your stat is before leveling, the amount that it'll increase by, and then the final amount, which is sort of similar to how the actual Pokemon games work. So you can see, rather than just seeing, oh, I increased my level from 5 to 6, 6 to 7, you can see, oh, my strength increased from 12 to 14. I'm a little bit stronger. I'm going to do more damage on the next playthrough. So our goal here, we're going to take a look at the field state, the play state, and the battle state. And there's a common dichotomy in most of these sorts of games, be it Final Fantasy or Dragon Quest or Pokemon, where there is a field where you are walking around, you're a character interacting with a game world with NPCs, going through towns and what have you, and then a battle mode, sort of a battle state, where you're actually fighting against some sort of enemy or a series of enemies, a party or a single creature. And so we've implemented simple versions of both of these to illustrate, and also the transitions between them. Before we start, I want to make another sort of plug for this howtomakeanrpg.com, this book. I actually learned a lot from this and about using Lua in the context of game development, and I pitched this, I think, in one of the earlier lectures. But if you want a deeper dive into a lot of these constructs and to sort of get a sense for how you might do something like cutscenes or more complicated battle layouts and a lot more, like it goes into a lot of detail about a lot of awesome things, definitely check it out. It's not free, but if you're interested in this genre, which I am, it's definitely worthwhile. Here's what the sprite sheets look like that we'll be using for this sort of demonstration. The Pokemon aside, which are individual textures. Here we're using a simple sprite sheet, which just has a bunch of tiles, most of which we did not use. Note that the bush, the tall grass, is not on any sort of background, and therefore we need to layer, basically have two separate tile maps as opposed to one, which we didn't do last time. And we're reusing the sprite sheet that we used in the Zelda lecture. Before we used it for all the enemies, the skeletons, ghosts, and slimes, etc. But now we're actually using it for the NPCs that it contains, specifically just the male NPC here, which is our main character. The foundational class that we're using in this lecture, that sort of everything else revolves around and makes this work, is the state stack. And so before, what we had was a state machine, right, where we're in one state at a time. So you can almost think of it like we have a box here, and it just has one socket. And then we're always looking at this one socket, whether that's the play state or the battle state or a transition of some kind. And now we're transitioning into the idea of, instead of just one state that we can only see at once, we'll make it a stack. And so what we can do with this is, rather than just having one, we can therefore render multiple states at a time, right? So let's say this is the field, right, or the play state. And then maybe this is like a dialogue or something, right? Like we saw before in the field, we had a text box. We can actually layer things on top of each other. And then maybe this is like a fade out, right, or a fade in. So we start with the play state maybe, and we're walking around, and then we interact with an NPC. Rather than transition the play state to a dialogue state, which would, in our previous model, completely eliminate the play state because there's only one state that could be active at a time. Now we just render however many states we have in our stack, we just render them sequentially based on the order that they were popped in. We render this first. We basically render from the bottom up. Render the play state, then the dialogue, then the fade in. And this will have the effect of doing a whole bunch of different things, which we'll see in the distro. But we only really ever need to update one state at a time, right? Because if we have the play state active and the dialogue state active and the fade in state active in this order as a stack, right? We were pushing, the operation for getting something onto the stack is called a push, and getting it off is called a pop, if unfamiliar. If we're pushing all of these states on, then usually we only need to update whatever's on top, right? If there's no fade in, for example, and we only have a dialogue state active, or a dialogue and a play state in that order, top to bottom, then we usually don't want to, update what's going on in the play state. We're only concerned with the dialogue that's taking place. We only want that to take input. And when we press spacebar or enter or whatever button clears that dialogue state, we pop it off, right? And then we're back to the play state. Then we're just updating the play state. And so being able to update just what's on top while being able to render everything that's on bottom. And this doesn't hold true for all game formulas. There's certainly some games where you can have a dialogue and a play state both get updated. And But that's still using a state stack of sorts. You're just then updating things in a top-down way. But this allows us to do all kinds of things like transitions and preserving. Like, for example, the fact that we have a play state and we can pop a battle state on top of that, where we don't see the play state underneath it. We only see the battle state, and that's all updating. But as soon as we pop the battle state off, we're right back where we just were in the play state. It's preserved its state, for lack of a better word, from before. And this is something that this model affords us comfortably. And so that's sort of the foundational class that's implemented in this distro, which will allow us to do all kinds of awesome things. So let's go ahead and take a look at what that looks like. I have state stack open here. So state stack has just a set of states here. And then whenever we want to insert a state, it's going to be at the end of the state stack. So it's going to be whatever the last. So it's if we're looking at it as a series of states in a table, it'll be whatever the last index is in the table. That'll be our the top of our stack. And you can implement this either way. In reverse, if you wanted to, it's just easier because you can just do a simple table.remove to get rid of the table.remove on that table to get rid of the last state. Without having to shift back everything. So if we did it starting at index 1, you'd have to shift everything back. And it'd also be a little bit weird because you would start at 1 and then things would go left. But basically, in order to update whatever our end state is, we just do at number self.states, which will be however large our state stack is. We just call update on that state. And then process AI is here, though we're not using it. But it would, if you had AI, it would be the same thing. It's basically an update for artificial intelligence for your state. Rather than rendering just one state at a time, we iterate through all of our states here using I pairs, which will iterate through them numerically, starting at 1, going to the end. So we call for I state and I pairs of self.states, render it. So that'll render everything back to front, or both bottom to top. And allow us to get this layered look where we have a play state going on underneath, for example, and then a dialogue on top. Or we have a battle state going at the very top, and maybe that battle state itself pushes a dialogue state to this top of the stack, or a bunch of other states, a transition, whatever you would like. To clear it, we just reset the table to an empty table. To push a state, we just do an insert on that state, and then we call enter on that state. As we did before, sort of similarly with state machine, when we changed a state, we would call enter on it and exit. But now we're just calling enter when we push. And then to pop, all we do is call exit on whatever the last state is in our state stack, and then just call table.remove on self.states. And by default, when you call table.remove on a table, just a table with no other arguments, it'll remove whatever the last index is of that table. Does that make sense? Does anybody have any questions as to how the state stack works? All right, awesome. So let's take a look then at the start state. So this is the start state. Fairly simple. We just have a couple of text labels, and then we have just a randomly assigned sprite going left to right. How do we think we're achieving the movement? Yep, timer.tween. And then we're just drawing an ellipse, right? Pretty simple. And then when we press enter, note the transition. Notice that there's a fade to white and then a fade to transparent. And so if we recall from when we looked at match 3, how do we do this? Do we remember?
You had a rectangle across the entire screen and you had tweak transparency.
Exactly. And the rectangle was stored where? Sorry, to repeat for the camera, we had a rectangle that filled the entire screen, and we just tweened the transparency for it, which is true. The rectangle there before, though, was stored in whatever state was active at the time, which was like the start state, or I think begin game state was the name. The actual state that wasn't necessarily relevant to the transition. But using a state stack, we can actually decouple this idea. We can take the concept of a transition, and because imagine if we wanted to make a transition between every single state that existed in our game, right? If we wanted to transition from the battle to the field, or the field to the to the battle, or whatever else we might want, like the start to the field, we would need a rectangle in every single one of those that has an opacity that we're keeping track of, and that's not necessarily germane to the purpose of that state, right? So because we now have a state stack, we can actually abstract out this idea of a transition and turn it into its own state. We can have a transition state. And recall that since we're just layering everything, all these states, and we're rendering them sequentially, having a state that possesses its own, for example, opacity rectangle, we can just layer that, push that onto the stack, and render that, and it'll give us the illusion of having this transition, but we don't need to actually have it be part of the state that we're trying to transition out of and into. Does that make sense? So let's take a look, for example, at the let's take a look at the start state first, just so we can see where that actually gets kicked off. So the start state, we kick off some music. We have a sprite and a sprite X and Y. These are values that are relevant to the sprite that's moving. Actually, we only have one sprite ever. Moving left to right, it just gets teleported to the right edge of the screen as soon as it gets taken to one edge. So we only have one sprite, one X and Y. And then every 3 seconds, as we see here, we have a callback function that will tween the sprite's X to -64 over 0.2 seconds, so really quickly. And then on finish, teleport it to the right, and then do the same exact thing, but tween it to the center over 0.2 seconds. And then as soon as we press enter or return, note this here. We have a G state stack, not a G state machine anymore, and we're pushing onto it a fade-in state, which takes in an RGB, a duration, and a callback function. Now, if we look at main.lua, this is relevant because now we no longer have a state machine, right? We previously had a global state machine, G state machine. We would give it a list of indexes into functions, anonymous functions. Those would return the instantiation of a state. And then when we call change, the state machine will index into its list of states and call that anonymous function, which would have the result of changing the state to some state that we've implemented as a class, right? Now we just create a state stack and we just push a new start state onto the class. And so what this will do is effectively the same thing, only now we can layer things onto this start state, right? Or play state or whatever we want to, and we're not going to ever get rid of it. I mean, we can get rid of it, but we don't have to. For the play state especially, we want that to pretty much never get popped off the stack because that's going to preserve all of our information. We're going to default back to that to store all of our character information, our Pokemon information, whatever else we might want to add onto this shell of a game, an inventory, etc., a world state at large. We want to preserve that and keep that consistent across all of our battle states and so forth. And the battle states will just pull information from that world, from that play state, and construct a battle as needed. Does that make sense? OK, so here we're effectively the only real changes we've made to main are no longer a state machine. Now we have a state stack. We're going to push a start state. That start state has some behavior just like any other state that we've implemented before. And what I was about to get into before was here on line 36 of the start state, we are pushing another state onto the stack. So there's already a start state, and it's from within the start state itself, actually. We're going to take that stack, which is just 1 level deep, and then we're going to make it 2 levels deep now. So now we're going to add a fade-in state. And the fade-in state, as we can see, takes in an RGB. Does anybody have a guess as to what the RGB is relevant for? Yeah.
To decide whether you want to fade in black or white?
To whether you want to fade in black or white, yes. Any color. We could make it a fade to red if we wanted to, or a fade to blue. But we don't have to create 2 separate classes for a fade in white, fade in black, fade out black, fade out white. We can just give it a color. And then, we could even go a level further with this and make it taken in opacity as well, so that we don't need a fade in state or a fade out state. We just need a fade state, right? And the fade state will determine, based on whatever last opacity parameter we give it, the right way to fade in and out. But in this case, the difference between the fade in state and the fade out state is one knows to go to 0, one knows to go to 255. That's really the only key difference. And then this one, the duration, right? We need to tell it how long to fade. And then this last bit here is a function. We're giving it an anonymous function. This is a callback function. Because the fade in state by nature is an asynchronous state. It does its behavior over time. So we need to tell it, okay, when you've finished doing what you're doing, call this bit of code here, so that we can do something not immediately. We can sort of defer its execution till later. And this is something that we'll see common throughout this lecture, because we have this implemented also in like dialog, for example, because we don't know when the user is going to press spacebar on the dialog state and clear the window. But what if we want that window, the clearing of that dialog, to trigger some sort of event, right? For example, if they press enter when they're in the battle, we want it to go to the next action. We don't necessarily know when that's going to happen, so we'll just pass in an anonymous function to that dialog state that will tell that the class will call whenever the close function is called on that dialog state. It says, when closed, execute this anonymous function. And then that anonymous function can do whatever you want it to do. It could pop another several states onto the stack. But this is what allows us to chain asynchronous behavior. That's the key here. So this anonymous function, so we'll take a look now actually at the fade in state, just so we can see what this looks like. So we see here fade in state, right? Takes in the color we saw before. That will be the color we fade to. The time, the length of time that it'll take us to actually perform the transition. And what are we using for the transition, do we think? Timer.tween, right? So most everything that we'll do actually throughout the course of this lecture that has asynchronous behavior, we can implement it with timer, which is nice. It allows us to fairly succinctly and declaratively write out what exactly we want to have happen over time. In this case, we're going to tween over the course of time the opacity of our self to 255. So the fade in is going to fade into the full color of whatever we've given it. So it's going to go from 0, which is shown here by default, to 255. And then, as soon as we finish that tween, that is when we pop the fade in state. We're going to pop ourselves off the stack effectively. And then here we're calling on fade complete, and that's where the anonymous function is. On fade complete is passed in here. So by putting that function into the finish function of the tween operation, we've allowed ourselves to defer that function that we've written up in it was in the start state. We defer the execution of this function until after that tween operation takes place. Does that make sense? Okay, awesome. And that's effectively what it is. And that's a common theme that we'll see if you're looking through the distro. You'll see it in a lot of places. Anonymous functions, or callback functions rather, being passed into things like the dialogues and the fades and a few other places. In the take turn state, for example, there's a function that takes in a callback function as well. And that's effectively how you can chain asynchronous behavior that executes over time rather than it being blocking. Does anybody have any questions so far as to how this works at all? Cool. All right, so when the fade is done, if we're still in the start state here, at this point, the fade is done. We're executing this anonymous function. We're going to pop the start state off of the stack, in this case, and then we're going to we're going to do two pushes here. One is to push a play state, which recall is where we're the NPC walking or the character walking around. And another one is to push a dialogue state. And so what this will have the effect of doing is rather than us immediately going into the play state and being able to walk around, we're actually put right into a world where there's a message waiting for us that we have to press enter on in order to continue. And when we press enter, because we're pushing the play state first and then the dialogue state is at the top of the stack, right? Because things get pushed onto like a stack of plates. You put a play state plate on the bottom and then another plate on top, and that plate is the dialogue state in this case. And you can only interact with the top. We're only updating the top plate at once in this model. We could obviously make a more complicated state stack that allows us to have several layers of states being updated at once, but for simplicity, we only opted to allow the top layer to be updated. The dialogue state is going to be the active state. It's going to be receiving input. All of them are going to be rendered, so we're still going to see, we're going to render things from the bottom up. We're going to render the play state, then we're going to render the dialogue state, but the dialogue state is going to be active. We're only going to be able to press anything on that state. And then lastly, actually, even beyond the dialogue state, we're pushing another state. We're pushing a fade out state. And in this case, it's the opposite of the fade in state. It just takes in an RGB and will go from 255 opacity to 0 opacity in that case. And so what that allows us to do, if we're playing, right, we're here in the start state, pressing enter. That's our fade in state was there. And then we pushed the play state and the dialogue state and the fade out state at once. So it looked at, you would almost think that we'd push the fade in and then the fade out. But we have to lay that foundation before we put the fade out state on top of the stack, right? Because the top layer gets updated. So we have to push the fade out state on top of all of those. That'll get updated, that'll fade out, and then we're back to the two states that we pushed before we pushed the fade out state. Does that make sense? Okay. Does anybody have any questions as to how that sort of flow works? Cool. All right, so that's the gist behind, that's essentially the core of what we're doing today is the state stack, pushing multiple states, and then just figuring out the right order that you need to push them in to get the desired appearance that you want, right? We push the fade out state while we're in the start state, or fade in state rather. That'll take us to white, and then like sort of almost like underneath the, behind the curtain, we're popping everything, and then we're adding the play, dialogue, and then another fade out state. And so you sort of have to balance the order that you put things in order to achieve the desired results. It may not necessarily be exactly as you intuitively think until you think about just how we're updating and rendering things on the stack. And so that's the ultimate hurdle, I think, in really getting comfortable with the distro. But once you've gotten that, everything else sort of falls into place. That and the sort of abundance of asynchronous functions, as we'll see pretty shortly when we look at GUIs and how we've implemented a lot of basic GUI functionality. A lot of that is very, very callback driven, just because of the nature of it being based on user input, right? You don't know when the user is going to do any input, so defer whatever happens with that GUI code, with the triggers involved, when the user presses spacebar or enter, and then call that function that you've passed into that GUI widget. All right, so we've taken a look at the state stack, we've taken a look at the start state, the fade in state. Let's take a look now at the play state. So the play state, a lot of this is actually very similar to what we did back with Zelda, which was which is a very similar type of game, top-down view. The only difference really with that was RPGs of this nature, Final Fantasy, Pokemon, Dragon Quest, they're tile-based to the degree of even your movement is tile-based. And so we've striven to implement that with this lecture. So when we move our player, our character, it doesn't have free motion like we did with Zelda, for example. So I'll demonstrate this. So I'm going to go to the field state here, the play state, sorry. And then when I move, if I press right, he moves in that direction at a perfect grid interval. So if I move up, I'm taking my hand instantly away, He's going to keep moving, and he's going to stick hard set to this grid. And that's just a sort of trend that these games have implemented. It allows you to stay perfectly aligned with the grid and helps you, I guess, certain game. I don't think it's necessarily strictly necessary for probably most of the games that choose to implement this. I think it was a symptom of tile-based games from the NES and Game Boy era being more easier to design and implement because they're very tile-based systems. But I mean, even as an aesthetic choice, I suppose it makes sense because everything aligns very perfectly. So that's the core difference really with the field state in this game. So how can we go about implementing a grid-aligned movement system like this with our player relative to how we did it in Zelda, for example? How do we think? Sure, yeah.
So we don't have X and Y's, we just have the tile positions.
So we don't have X and Y's, we just have the tile positions. Close. It's more, I would say it's more focused on the tile positions, but you still do need an X and a Y because you still need to draw that sprite at that exact position. Right? Yes, Tony?
But when you need to move the sprite, instead of moving it at every update, you tween it between the two tile locations.
Exactly. So rather than moving the sprite discretely, at exact pixel positions per update, you tween the sprite when you receive input to a specific location. And then we actually stop input at that point as well. There's no use for us having any input when we're not exactly at a given tile, so we disable input while he's walking, effectively. And so this is implemented, if we're looking at the distro, in the entity class, there is a, let's believe it's in here. It might be player, hold on. Is it, oh, sorry, no, it's entity walk state, not the entity. Entity is just a container for the information that's relevant. So here in the entity walk state, we have attempt move. And so what attempt move does is essentially looks to make sure that we're within the bounds of the map, right? And then if we are, every entity in this game now has a map Y and X and a regular Y and X. And so the regular Y and X we still need in order to draw our sprite at specific location on the map. We still need to draw it going between 240 something and 230 something, right? But we need a map X and a map Y to basically say, okay, the sprite should be at this position on the map, and then we'll just tween it between that position times 16 and the position plus or minus X or Y times 16, which will give us the exact X and Y value that we need to draw it onto the map. And so that's what we're doing here. So when we're going to call attempt move on inputs. Anytime we do any input, and this is done in the player idle or player idle class, player idle state, we change the animation to the right animation, and then we get its current map X and Y, and then based on whatever direction the player is looking or the entity is looking, we could use this for an NPC class or the like. We just modify our 2x and 2y. So 2x and 2y is going to be the value that we're tweening towards times 16, right? And so if we're trying to go outside the map boundaries, just change us back to idle. Don't let us do that. Otherwise, set our map y and map x to that position immediately, right? Because that's just a minus or plus 1 operation. And then over the course of 0.5 seconds, actually tween to that value. And we can see here we're tweening to the tile size. And actually to the tile size minus self.entity.height divided by 2. Do we know why that is? We do that because if we're looking at the field, you can see here, notice that we're not perfectly lined up with the grass, right? It's kind of like we're halfway above it because it looks just a little bit more natural this way. This is how most sort of games look. And if you're in a game like this and you're like walking up against a wall, for example, this will allow you to sort of look as if you're up against the wall rather than sort of being, at the edge of where the bottom of the wall is, and kind of looks unnatural. Hence why we minus half our height right there. And then when we're finished, we actually test to see whether we're still pressing a key, and if we are, then change our state to walk again, which will just repeat this process depending on which direction we're looking at. And that's effectively it, and that's what allows us to get this grid-based movement. Any questions as to how this works? Cool. So let's take a look then at the play state. Let's go back to it. So we have a level. The level contains our entity, and it can contain all of our entities and whatever objects you want it to contain. In this case, when we're in the play state as well, we're going to check to see if we press P, because that's, recall, where we can heal our Pokemon. Just a little game hack, just to make demoing it a little bit easier. But if we press P, we play the heal sound, we take our, and we'll look at a little bit more detail as to all of this in a little bit, but self.level.player.party.pokemon at index 1 dot current HP equals self.level.player.party.pokemon at 1 dot HP. So the difference is current HP is whatever you currently have. You could have taken damage. HP is whatever your max HP is. And this is, like, in a nutshell, how you get, like, stat changes in games and RPGs and health and MP differences. You got to keep track of a max and a current value for all of those things. And then depending on whether you're buffed or debuffed, or whether you have taken damage or not, or used spells or not, you can have an accurate reflection of where your character is, and then always return back to that state whenever you need to. The interesting thing here, the slightly more complicated thing is, when we press P, we want to show a dialog that says, and I'll demonstrate this, we want to show a dialog, just like this one, that says, press P, your Pokemon has been healed, right? Now I can't move, I'm pressing the arrow keys, I can't move my character at all because this dialog state, we're in a new state, where we've pushed a new state onto the state stack, and that's the dialog state here, which has taken a value, and because it's the top layer of the stack, it can't get updated. Or it's being updated, and we can't update the play state, right? Based on how we've modeled our state stacks operation, or how it works. And then as soon as I press enter, it gets popped off. We've just popped it off. Now the play state's at the top. I can move again. So that's what's going on. So the dialog state then is actually very similar in a sense to the fade in and fade out state, in that notice that it takes an anonymous function. When does this anonymous function get called? Do we know? At the end of what? Yeah, when the user closes the dialog box, correct. So let's take a look at the dialog state then, and we can see it's actually pretty simple. It's pretty small. We have a text that it takes and a callback, right? The text is used here. We instantiate, and this we'll see in detail when we start looking at GUIs and all the widgets that we've implemented here. This text box gets put at a hard-coded position, and it receives this text, and then we set our self.callback to that callback function. If we've closed the text box, meaning we're looking to see self.textbox.isClose, which is a function of the textbox class. If it's closed, then execute self.callback, and then pop this dialog state off of the stack, right? So it's similar in a sense to the fade in and fade out, in that it takes an anonymous function. The only difference is in how it gets executed. With the fade in state, the anonymous function was called at the end of the finish function, which was part of the tween object. In this case, we're executing the callback function explicitly when we've closed the text box. So we're waiting for user input versus waiting for some asynchronous operation to finish. And then, of course, we call textbox render, and then we'll see all of these methods shortly as part of these widgets. But at a glance, this is all that's really happening with the dialog state. Very simple, using the same pattern that we've seen of deferring future behavior to anonymous functions. Any questions as to how this works, or anything so far? Cool. All right, Let's take a look back at the play state. I believe we're getting close to being finished with the play state. Yes, so everything, that's basically what the play state is in this game. And then a lot of what's going on takes place in a level as well. So in this case, in a nutshell, we have two maps, two layers, right? Because the grass in the tile sheet is its own sort of alpha'd out object. It's sort of got transparency around it. We keep a layer of the base, a layer of the grass underneath, and then a separate layer for the tall grass. And then we can just look and to see when we're walking in the player walk state, when we've walked over tall grass, and then what do we need to do to start a random encounter? Yes?
We just push the encounter state on top.
Yes. How do we initiate it, though? What are we looking for? We do push a battle state as soon as we've triggered one, but how do we trigger one? What are we looking for?
Random chance whenever the player is in grass. Although, I don't know if it's on moving to a new grass or if it's time spent in the grass.
So it's, yeah, we do a random chance whenever the player is on grass, and it's whenever they start the walk and they're on grass, in this case. But you could do it either way. You could do it when they're leaving the grass, walking into the grass. In this case, it's whenever you press the button and they happen to be on grass, it'll do a random chance, 1 in 10. And if it's true, if it's equal to 1, 10% chance, it'll trigger an encounter. So that's the gist behind triggering a random encounter. And a lot of these games really, some games do it differently. They'll sometimes make it more likely the more steps you've taken. They'll like sort of keep a counter to say, oh, I've taken 100 steps. It should be a lot more likely now. Some games will just be completely random, 1 in 10, 1 in 5, depending on how the developers decided to implement their game. The former is a bit more robust, but for simplicity, we just chose math.random 10 equals 1. So yeah, we create the tile maps here, pretty straightforward. And then the actual random encountering takes place in the player walk state. So here we have check for encounter. And so what this does is whenever we enter the walk state, which is we press the button to enter or to walk, this enter function gets called because we do the transition to the player walk state in the state machine. All of the entities are still using just a regular state machine, not a state stack. Wasn't necessary for this demonstration, though I'm sure there are some use cases for using a state stack for an entity. In this case, we're just using a regular state machine. So when we change to the walk state, we are calling enter, as we've seen. And then we call self check for encounter. And so self check for encounter will set a flag if we have not started an encounter, basically, and will allow us to move. And if we have checked for an encounter, it will, or if we have triggered an encounter, it will push in check for encounter. It'll actually push a battle state onto the stack. So check for encounter just basically does what we said before. If the grass layer, because we have two layers, right? We have the base layer and the grass layer. So if the layer at yx, where yx is our entities map x and map y, if the ID of that is equal to tall grass, and we have just a global constant table called tile IDs, which has all these IDs. And math.random 10 is equal to 1. OK. Change the entity state to idle, so don't let them keep walking. Pause the field music rather than stopping it, so that way when we come back to the field later and we press play, it'll be at the exact point that it was before. Trigger the battle music. And then we've seen this already. Fade in state, push to the stack, right? So over 1 second, we're going to fade to white. So this will have the effect of the music starting, but we're fading to white right away, which is very sort of similar to how most RPGs do it. And then we have our callback function, which will execute as soon as the fade in state's done, right? In this case, push a battle state. Battle state takes an entity, and the entity has all of our Pokemon information. That's why we're passing that into the battle state. So the battle state can say, oh, what Pokemon do you have? OK, I'll be able to look at your party and say, OK, your first Pokemon is this. Send him out to battle, et cetera, right? And then lastly, push a fade out state, right? Because now we've got the battle state on top of the play state, but we want to fade into it, right? So we're going to fade we're going to put the battle state first, and then, because we're using a stack, we're going to put the fade out state on top of that, and then fade out to that, pop that off the stack, and then we have our battle state that we just pushed, right? And then self.encounter found gets set here. And that's creating an encounter, checking, randomly pushing the right things onto the stack, battle state, fade in, fade out, and then you're set to go. So that's effectively what it's known in RPGs as the field versus the battle or encounter state. Even though we're calling it play state here, we've left the field, we've gone into the battle at this point, and so now we've seen basically everything that the field has to offer us. And we've covered everything that's relevant there. So we're going to take a break now for 5 to 10 minutes, and then when we get back from the break, we'll talk about GUI elements, panels, text boxes, and then we'll dive into the sort of mechanics of the battle state. All right, welcome back to Lecture 7, Pokemon. So before the break, we talked about the play state, we talked about the state stack. More importantly, then we talked about how anonymous functions are sort of the backbone to how we get a lot of this asynchronous and deferred behavior for our game, which is very common in RPGs and a lot of genres, a lot of complicated genres of this sort. Another big key part of games like this are the graphical user interfaces, or GUIs as they're shortened to. Things like panels on the screen, things like labels, text labels that move around, things like lists, text boxes, scroll bars, and you can get a lot crazier with it. In this particular lecture, we'll be talking mostly about panels, labels, text boxes, and scroll bars. Progress bars, rather, not scroll bars. But the sort of the first, I think, the first sort of like keystone GUI widget that we should take into consideration is the panel. So a panel is, I believe this clears. So if we look at this in a game, just pretend this is a panel, I guess. So this is what effectively all a panel is, right? It's just a sort of a rectangle. It allows us to, if you're looking at most user interfaces, like text boxes on your screen, or if you're on Facebook and you're looking at, almost anything like your little message window, a lot of those things at the very core, the very bottom, the foundational part is just a panel. So any guesses as to how in Love 2D we can make a simple panel?
Two rectangles of different colors?
Two rectangles of different colors. That's exactly what we end up doing. So that's effectively how we can make a panel. There's another way of making a panel, which we won't do in this lecture, but it's called, we use a construct called a 9-patch. So a 9-patch is, imagine taking this little image here, and it's of some arbitrary size, but it's very small. And this is very similar to how a lot of games implemented their panels or their graphical user interfaces back, in the 80s and 90s. A lot of games to this day, but back when hardware was fundamentally tile-based, you could take a image like this, split it up into 9 pieces. 9-patch is where the terminology comes from. And sort of similar to how we actually constructed the Zelda dungeon, recall, where you have corner pieces and then a top, bottom, right, and left side. You just layer one of each of these first off, right, of the corner pieces. And then however many you need of these on the sides to sort of create this rectangle, right? So imagine we've created, these are all, if we can visualize these as being a bunch of tiles, right? So just imagine that we've taken these corner pieces. These are the corner pieces. We've taken one of each of those. And then we take these side pieces and we just draw a bunch of them like that. And then we take this center piece And then we can either layer it or tile it a bunch of times or just stretch it. And stretching it has a bunch of nice bonuses associated with it depending on how you've set your filter mode. Love.graphics.set default filter. If you set it to bilinear versus nearest, you can actually get a nice gradient. And if you set it to nearest, you get a nice pixelated look. But you'll see this often, and Unity has nice support for this. Take an image that is maybe more complicated than you could get with just two rectangles, right? Something that actually has a design and maybe a gradient color, and actually layer, create a arbitrarily sized text box to fit your needs. And if these aren't even increments of whatever your tile size is on your 9 patch, you could just scale the top, bottom, left, and right sides as well, just like you would scale the centerpiece. So does that make sense? So this is common. We won't be using that in our lecture, but it's a very, very common piece to a lot of graphical user interface design in a lot of games. You'll see it a lot if you get more into game development, so it's definitely worth talking about. Another piece that we'll be talking about today is the text box. So, what's a guess as to what the text box, how we can implement a text box, and how we will implement a text box. So what foundational piece can we start with? We already have, yeah?
Well, couldn't you just put, use the love print to the screen over one of those boxes?
So use the love print to the screen over one of those boxes, exactly, yep. So maintain a list of text items, right? Text, and then just draw them, inside a panel, and there's a text box. You've taken two ideas and sort of mixed them together. A selection is kind of the same thing. It's the only difference being that with a selection, so a selection is another thing. If we think about, for example, a menu where we have fight and like run, and then maybe in a more fleshed out game we have like an item thing, right? So that's a menu effectively. Which is very similar to what we get with a text box, but it's got a set of ingredients here, fight, item, run, which aren't, they aren't set to wrap. They're not one like contiguous set of text. It's just it's a bunch of items. And then a nice thing about a selection is that you can have a cursor on your selection, right? And then what do we need to associate with, like, for example, if we want this to actually do something, and if we think about what we've been doing so far, how do we go about implementing functionality with a selection like this? Like, what needs to get associated with each of those entries in our selection? Callback function, right? Just as we've done with everything else. If you have a fight item here, each of these, if we think of the selection as being just this part of what we're looking at, right? Because this background part is just a panel. We don't care about that. We care about the selection at the moment. The selection is the items and the arrow, right? And as we'll see in the assignment, your goal will actually be to take selection and get rid of the arrow functionality, because for the assignment, you don't need or want to have a selection active, a cursor active. You just want a list of things. But based on what the cursor is pointing at and where when we press enter or whatnot, we should index into the selection and then execute a callback that's associated with each of these items, and that's how we can get behavior out of the selection rather than it just being a list of things that we render to the screen. If we have fight and we click enter, a callback is set to maybe push a state onto the stack that will trigger an interaction between the two entities on the screen, right? The first one will attack the second one will attack the first one. And that's sort of its own asynchronous set of states that do its own thing. But it's kicked off via an anonymous function that we've associated with each of these things, right? An item pushes another state, which is like an item menu state, where then you open up a brand new set of menus that you can look through all your items, and each of those items has a callback associated with it, right? Your potion has a callback associated with it that says, when I click on this, either by default just restore the HP of my active Pokemon, or let me choose who to restore. So, therefore push another state, which is like a select Pokemon screen with its own set of callbacks associated with each of those. It's just, in order to get all of this sort of complicated behavior that you need to, it's really ultimately just pushing states and adding callback functions to all of these different options that you can select. And then run, push a fade state, and then pop this state, and then push a fade out state. And that's really all we're doing. And so this look at all of these GUI widgets here is just sort of a conceptual look, but we'll take a look very shortly at some actual implementation. The last one that I want to look at is the progress bar. So a progress bar, for example, the HP that we've seen, in the actual battle, where when we take damage, it goes from right to left. Any guesses as to how we've implemented a progress bar? Yes, Tony?
Once again, 2 rectangles.
2 rectangles, yes, exactly. One, and then the nice thing about rectangles in Left2D is you can set the edges on them to be rounded or not via an optional parameter. So without anything more complicated than a rectangle, we can just create these sort of almost elliptoid progress bars, very simple progress bars. One's the red, right? The red, that's the background, and then one's the outline, the black, and one is set to fill with the first parameter, one's set to line with the first parameter. Now, how do we go about animating whether or not, how do we animate the decreasing amount of health when we take damage? Yes?
Between the width.
Tween the width, exactly. And what are we tweening it by? How are we tweening it? How do we calculate how much we need to tween it?
Well, you could just have your width equal your health remaining.
If your width is set to equal your health remaining, then your health is maybe 10, and you want your health bar to be like 100 pixels long. How is that going to work, though?
Well, you could multiply it.
You could multiply it, but if you know the width that you want your progress bar to be, you can just multiply the width by the ratio of the max value of your HP, the ratio of your current HP over your max HP, right? So if you have 50 HP and you're missing 5 HP, your ratio is 45 over 50. And if you multiply that by your width, you get the exact amount of width that you need relative, regardless of how wide you want the bar to be. If you want it to be 1,000 pixels, if you want it to be 50 pixels, as long as you multiply current health over max health times the width, you'll get that ratio no matter what. Does that make sense? Cool. So that's a look at all the GUI widgets that we're looking at, how they sort of relate to what we're doing. We'll take a look at their implementation here. So I'm going to go ahead and open up the panel. And I'm going to move a little bit quickly so we can get into the sort of the meat of the battle here. The panel is, as we've said before, just 2 rectangles, right? It takes in an x, y, width, and a height. And then we just draw 2 rectangles. One is larger than the other. The bottom rectangle is slightly larger than the top rectangle. So the first rectangle gets drawn, and it's white-ish. And then, I'm sorry. Sorry about that. We have x, y, width, and a height. And then we're drawing 2 rectangles to the screen. We have the background rectangle, which is drawn first, which is going to be the full x, y, width, and height of the panel. And then we're going to draw that at a white color, and then draw, in the context of this game, we're drawing everything at the same color, but we can change the color. If we wanted to parameterize it, we could do that. We could set, we could have a color option here in the constructor. We're not doing that. We're just drawing everything the same color. But that's how you'd get like customized menus. Some RPGs let you do that. You could, and then what we're doing here is we're just within a slightly smaller boundary, so just 2 pixels smaller on the x and the y. We're going to draw the second rectangle, which is a kind of dark shade of gray. And that is a panel. That is all a panel is. And then we can just have a function called toggle, which sets it to visible or not visible. And if it's visible, get rid of it. Or if it's visible, draw it. Otherwise, don't draw anything when it gets rendered. So that's a panel in a nutshell. Any questions? Cool. So the next thing that we should look at is the text box. So a text box. So the text box is a little bit more complicated than a panel. A text box in a nutshell needs to take in some arbitrary body of text, and it needs to chop it up based on how wide your text box is. And if it surpasses the height of your text box, right, ideally you should page your text so that you can press spacebar or enter and go through pages of text until you've exhausted all of your text, and you press enter one last time and you get rid of that text box. And so we have a panel here, which is, we have an XY width and a height in our constructor for the text box, and we have our text as well. And then we have a font if we want to explicitly decide what font we want to use. In this case, or at large, we're going to say that we instantiate a panel at XY width and height, nothing too fancy. And then the fancy-ish part, slightly more complicated part, is here on line 20, where we say underscore self.text chunks gets self.font get wrap self.text self.width minus 12. So anybody know what this function does, or want to take a guess? Yes?
Is that the page thing you were talking about?
Exactly. It's the paging of the text. It's the chunking of the text, rather. Not the paging of the text so much as it is the chunking of the text, which we will use to page the text. So we take some arbitrarily large body of text, can be as large as we want it to be, and given this is actually a function of the LÖVE2D font object. So this is given to us from LÖVE2D. Get wrap will return two values, the second of which is all of the pieces of text that the main big body is divided into based on the width. So this self.width of minus 12, that's how wide it's going to divide our text into chunks of, up to. It could be slightly smaller than, because it divides it based on the word. But no piece of text will ever exceed self.width minus 12 width. And this will allow us to then render several lines of text within our text box, and they will never exceed the boundary, right? And so the paging functionality is actually in next chunks. So we call self next here at the end of our init function, and then self next basically checks to see, okay, are we at the end of the text? If we are, then we're not going to display any text, and we're going to close the window. We're going to close the panel. But if we are not at the end of the text, like we still got text left, what we want to do is new table, and then we're going to, up to 3 iterations, we keep track of where we are in our chunks, right? We get self.text chunks equal to all of those chunks, right? And that could be an arbitrary number. It could be only one chunk. There could be like 30 chunks, right? We need a counter to keep track of where we are in terms of based on what page we're on, right? And however many lines we've rendered to the screen thus far. So starting at I, and I gets chunk counter, and chunk counter will get incremented by 3 every time we call next chunks, which is every page. We could have easily just called this next page as well. It's going to insert into that chunks table that we just created self.text chunks at I. And once we've reached the number of chunks total that we returned from getWrap, we're going to flag end of text as being true, and then we're going to return it. And so what this will do is eventually we're going to be equal to the number of chunks that we got from font getWrap, right? And once we are, that will signal with next that it's time to close the text box, because the end of text will have been set to true at the end of that last chunking process. And then we can see here, when we update text box, and that's whenever it's on the top of the stack, remember, we're looking for a space or an enter press, and then we just call self next. And that will have the effect of eventually closing our text box. And then is closed, recall, we looked at that earlier. We checked to see is the text box closed, and that's just a flag that we set here. And then for rendering purposes, we render the panel first, and then for each of our displaying chunks, so we only have up to 3 displaying chunks at one time, which gets set by the next chunks function. We just print that to the screen using I as a multiplier on our Y. And so that will render up to our 3 lines, I plus 1, I plus 2. Any questions as to how the text box works? It's a little more work than the panel for sure, but it's fairly straightforward. We're just keeping a list of a bunch of text things, and then we're just chunking them based on how wide the text box is, the dimensions thereof. And then let's take one look at this selection. So a selection is basically a list of text items with a cursor, right? And as I said before when we were looking at the screen over there, each of those text items has a text value and a callback function. And the callback function is what allows us to assign behavior to this selection object beyond just displaying things, right? Because when you have a menu, when you have a selection, and you select something, you want behavior to happen, right? So each of these items in def.items will expect to have a callback function. And then here, when we update the selection, what we're doing is we're updating whatever our current selection is, which is just a number between 1 and the number of items in that selection, making sure that if we're at 1 and we go -1, that we go back to the bottom, and if we're at the bottom when we press and we go up 1, we go back to the top. And we play sounds, cutesy, things like that. And then for for our selection here, from 1 to number of items, we calculate how much padding that we need, and we draw the cursor at our current selection, and then we draw each item based on I and whatever our gap width is of our panel, which we assign it to. So we divide our panel up and then basically just keep track of where our current Y is and draw the actual selection and the cursor, if that's the current selection, to the screen. Any questions as to how a selection sort of works? And notice here, if we press return, if our selection is being updated, self.items at self.currentSelection .onSelect. So it's expected that that item will have an onSelect function, which is that callback function. OK, and lastly, we'll take a look at the menu. And then we'll finally take a look at the battle, which is where sort of everything kind of comes together with all of this. And that'll be it. And then we'll talk about the assignment. So the menu is a panel and a selection together. That's the gist behind what a menu is in this game. A menu, you can define a menu to be a lot of things, and you can get a lot more complicated with a menu. But in this example, in this implementation, we're just saying a menu is a selection and a panel put together as one item. And we've seen it in the game. If I go ahead and run it. So that's just a text box. I'm going to look for a battle. OK, so here's a battle. That's just an empty panel at the bottom, regular panel, but now it's a text box. We push a text box onto the stack, push another text box onto the stack. And so this is a menu right here. Notice that there's a cursor and there's a selection embedded within a panel. And each of those items, the fight and the run, those have a callback associated with them. Fight, the purpose of the fight callback is to trigger a new state where the two Pokemon asynchronously attack each other and chain behavior one after the other. And then run pushes a dialogue, then pushes a fade state, then pops both of them, and then pushes a fade out state and puts us back to the play state. So that's effectively what's going on, and that's an example of what the menu looked like. And so a menu, just a selection with a panel put together. When we draw the menu, we draw the panel and then the selection. And then when we update the menu, we only update the selection because that's all we care about. And that's basically it. And so the menu itself will get a def. That def should have items. That items will get passed to the selection. That's it for the progress bars as well. We'll look at progress bars when we get to the actual battle state. So now let's take a look at a few of the classes and data structures that are pertinent to the Pokemon themselves. So if you look at party as our first class, very simple class, literally just this. Self.Pokemon is def.Pokemon. It is just a container at this point. You could take this, even in, I think, a fully fleshed game, you wouldn't really need much more than just this. But if you needed to expand upon this idea at all and preserve metadata that exists for the party, this would be a perfect way to do it. The actual Pokemon class itself is not a whole lot more than effectively a bunch of stats. And that's a lot of what an RPG is. Of this genre is, it's mostly just numbers. You're just comparing numbers against numbers and then adding a roll of a dice. And that's effectively, that's what Dungeons and Dragons, a lot of it is. And that's, yes?
Would it make more sense to store just delta per level and your initial one so you could have fewer variables?
Say it one more time?
Wouldn't it make more sense, instead of storing your HP and everything for each level to store your initial stats in each area and how much you would go up per level?
Would it make more sense to store the amount that you go up per level for your Pokemon? Yes, that is what we're doing. Well, so we have a base. So here's how the split works for the stats in this case, right? We have base HP, base attack, base defense, and base speed. A level 1 Pokemon has a level 0 Pokemon has these stats of this species, right? Every Bamboon or whatever Pokemon that we choose will have whatever we've allocated it to be its base HP, base attack, base defense, base speed. And then the thing about Pokemon, and I mean a lot of RPGs will sort of do this thing, but we need some way of leveling up the Pokemon in a necessarily non-deterministic way. Like 2 Pidgeys that level up might not have the same stats, right? One might have slightly higher attack than the other. One might have slightly higher defense than the other. We do this using what's called an IV, and that's what Pokemon itself does. And it's short for individual value. This is sort of like the DNA of your Pokemon, right? So this HP IV is separate from your base attack, base speed, base, etc. And this basically gets compared against a dice roll every time you level up, 3 times. So if you have, this dice roll is, and this is how I've programmed it. It's not necessarily how Pokemon itself does it, but you will roll a die 6 times, or 3 times, 1 through 6, like a normal die, and you'll look to see if that roll is greater than your IV, right? Or it'll check to see whether your IV is less than or equal to that dice roll. And if it is, if it's greater than or equal to that dice roll. And if it is, it will increment that stat by 1 for those 3 dice rolls. So you can get up to 3 more, or you can increase the stat by up to 3 times per level. But you can only have an IV up to 5. So you're rolling against a 6, and you will occasionally not roll a 6. It checks to see whether or not the IV is greater than or equal to the dice roll. And if it's not greater than or equal to the dice roll in the event that it is a 6, or if the IV is up to a 4, for example, which means a 5 or a 6 will go against it, then it will not get a stat increase. And this is a sort of simple way of implementing this DNA-based system. It's randomized, but it's weighted, right? If you have a higher IV, you have a higher likelihood of being greater than or equal to the dice roll. And so that's how we implement stat increases. And then we need a way of keeping track of what our stats are, like our actual stats. So our actual HP, our actual attack, our actual defense, and actual speed that's been calculated level by level. We need a way to keep track of that. We need a level, we need our current XP, and then we need the amount of XP to gain a level, which will get higher and higher per level, as you can see here, because it takes in the self.level times self.level, and then it multiplies that by 5 times 0.75, and then your current HP. So we're really not storing our value level by level. We need the base because we need to know what our base was. I mean, we could effectively globally reference these variables, but it's minor efficiency gains at that point. But we need the IVs, and we need a reference to the IVs. We need a reference to the base HP, and we need to keep track of whatever our actual stats are, and then our current HP always, because our current HP can differ from our actual HP. And in the actual game, you could have your attack, defense, and speed also vary match by match, because you have moves that lower your speed, lower your attack, lower your defense, etc. In this case, we haven't implemented that, so we don't have a current attack, current defense. But in a more complete implementation, you would have that sort of thing. Did that sort of answer your question? Is that in the right vein? Okay. And so here's the level up code. So like I said, 3 dice rolls, 1 to 3. If 6 is less than or equal to our IV, so it could be a 6, in which case it will be greater than what our max IV could possibly be. IVs range from 1 to 5. But if it's less than or equal to that IV, then we're going to consider that a stat increase. It's a weighted odd to determine whether or not we get a stat boost. And it does this for every stat, and then it returns all of the increases. And this is relevant, this line 95, for return HP increase, return attack increase, defense increase. This will be relevant for assignment 7, because your goal is to take these increases and actually display them to this user in the battle state when he gets a victory, or he or she gets a victory and has gained a level. You'll display a menu with a selection that has all of these things, and you'll need this value. So it returns this value, these values here, and you'll be calling this function anyway from your battle state, stats level up. Or we will be calling level up rather, which returns self stats level up. And that's all a Pokemon is, and we use this, it's effectively mostly a data structure, and we use this in our battles to, throw dice effectively back and forth and have a victor and a loser, and then gain XP and gain levels that way. So any questions as to how the Pokemon object class works? Cool. We'll take a quick look at what the actual definitions look like, which you can probably take a guess. It's very simple. Just key names, and then we have the actual name, we have the sprite names, we have the HP, attack, defense, all the things that get put into the actual object, they need a reference to in the definitions. And so Pokemon ultimately are just this. They're just data, right? Which is what we talked about in a prior lecture, data-driven design. The more you can take all of your Pokemon and make them into, or anything, Pokemon or any object, and turn it into an easy-to-write data structure like this, the easier it is for you to add more. We could easily add, it wouldn't take too long to create 150 of these. I mean, they wouldn't be all that interesting because we don't have moves implemented yet, but in an ideal world, we'd find a way to also model moves as data, and therefore you can just link moves to your data structure, to your Pokemon object like this. Yes, Donnie, did you have a question?
Well, I just wanted to mention that the Paradox games are very good about that. I don't know, I just felt that was relevant.
Oh, like Crusader Kings?
Yeah.
Oh, yeah. The comment was Paradox games are very good about data-driven design. I'm assuming you've dug through their files.
To some extent, and also it's just, if you play the games for a while, it's everywhere, like to the extent that sometimes on the wiki they just put the source code up.
Oh, yeah.
It's that readable.
Yeah, no, I mean, it's just good game design, ultimately. If you want to, and their games are large, they have a lot of content. If you want to have a lot of content in your game, you need to find a way to take the burden off the programmer and put it onto the designer, or at least make it easier for the programmer, because making source code and debugging source code all day long, especially very complicated things, is not easy, and it's ultimately not a desired thing to do, right? It's a lot easier for me to whip up a new creature in 10 lines of code here and feel good about it than, hard coding a lot of these sort of things, right? So shifting as much of it to data as you possibly can should be your end goal. So that's what Pokemon defs look like. Before we get into the actual battle, we want to take a look at what a battle sprite is. So a battle sprite is what was rendering onto the screen, right? So we take a look here. That's not a battle sprite, but almost a battle sprite. That was just a texture. So if we get into a battle, slowly but surely, all right? So these are battle sprites, and they don't look much different than a regular sprite, and they're not that much different than a regular sprite, but they have some functionality that's important, mainly that functionality, where one was flashing and then one was being opaque, right? So in order to do both of those things, we need to store some sort of data within our sprite, right? Yes?
Is that what we used in Zelda for the invulnerability flashing?
Yes, exactly. For what we used in Zelda for the invulnerability flashing, for the enemy, or for the, I should say, for whoever's getting attacked, yes, they are getting an opacity flag stored they have an opacity flag stored in their object. That's, we can tween, right? We can tween on and off over the course of time. That's what we did with the entity in Zelda when it took damage. And we said it's invulnerable, and while it was invulnerable, it was flashing on and off. But we can't necessarily do that with the sprite that's blinking white, because there's not really a white flag, right? We can't make something completely white with just a flag. That's something that we actually need to use a shader for. And so a shader, and we're not going to get into too much detail about this. Shaders are pretty complex, a little arcane at first. But what they are is effectively a little program that runs on your graphics card, and that looks at, when you're drawing something, it looks at every pixel, depending on what kind of shader you're doing. But for the sake of this demonstration, we'll look at every pixel that you're drawing to the screen and perform some sort of function on that pixel and produce a new value, right? And this is how you get a lot of really crazy, awesome things to happen, but it can be pretty insane. Shader Toy, I think, is the website that has a ton of really cool. I'm not going to pull it up now just because I don't remember the name. I believe it's Shader Toy. There's a website where people post all the shaders that they've written, and you can see a lot of really crazy stuff. Things that you would never imagine were possible with just code like this, effectively, looking at positions of pixels and positions on the screen and whatnot. But effectively what this does, this is a white shader. The goal of this shader is to just turn a sprite completely white. That's all the goal of this shader is. So it gets a float called white factor, which you've said here. And then white factor effectively is just going to be summed onto whatever the RGB is of that pixel, whatever pixel that we're drawing when the shader is active. What that has the effect of doing is white factor, if it's equal to 1. Here's the thing about shaders and a lot of this stuff. A lot of the data structures within shaders are based on floats that are from 0 to 1. So if we assign the RGB of something to a vec3 that's 1, which is 1, 1, 1, that's going to be 255, 255, 255. Therefore, that pixel's RGB is white, pure white, right? And so what we're doing here is on our battle sprite, self.blinking and 1 or 0. Remember, that's the Lua ternary operation. So we're saying if self.blinking is true, 1, else 0. So send our shader white factor at whatever value self.blinking, based on whatever value self.blinking is. And so that'll have the effect of the shader getting a 1 or a 0 and adding a 1 or a 0 to the RGB of that sprite. And if blinking is set to true, the sprite's going to basically be drawn every pixel at 255, 255, 255. Otherwise, it'll get drawn with whatever that image's pixel value is at that position. Does that make sense? OK. The syntax is a little bit weird, but that's what's happening here in this shader. And there's a link here where I found the shader. But it's a very simple shader. Probably like one of the simplest shaders you could write. But it's a great example of what you can do with a shader, and pretty simply. And it's nice because you can take texture coordinates and do math based on that, or pixel coordinates and do math based on that. You can pass in a sine function, for example, in your file, and have that sine function perform work on an RG or B value of your sprite and do all kinds of cool stuff. It's really neat. The possibilities are limitless with shaders. But that's how we get it to blink, because you can't do that outside of this. I mean, there's probably some weird way you could get it to work as well. But this is how we get this is probably the simplest way we can get our sprites blinking white. And so self.blinking just gets timer dot every 0.02 or 0.1 or whatever. We'll actually see that in the attack state. But that'll flick the self.blinking between true and false. It'll negate itself over and over again. All right, so that's the battle sprite. Last thing we'll look at is another extremely simple class, opponent. All the opponent has a party. That's it. But in a fully fleshed game, your opponent might have a trainer sprite, a message that it says, a full party of Pokemon, a gold value that it'll give you when you defeat it, all kinds of things. But it's here just as a simple illustration. Yeah.
Well, I was just going to say, you could put a method for on defeat if you want to maybe have it, I don't know, collapse the room or something like that. That would be another thing you could do.
Oh, a method. Yeah, we could have a method. We could associate a method with an opponent called on defeat or whatnot that will do arbitrary things, collapse the room or otherwise. Yes, absolutely. Or even push a new state, to teleport us to a new location in the world map. Maybe we cleared the Elite Four and we want to get teleported to the end credits. Exactly. Limitless possibility. So let's go ahead and take a look now. While we have just 20 more minutes or so left, we'll take a look at the battle state, because the battle state and the states therein are probably the more complicated side of how this works. So a battle state, we have a player, we have a bottom panel, the bottom panel for when we start the state, just for that part, but otherwise we're always pushing things onto it. Whether we've started the battle or not, because when we're fading in, because when we initialize this state, we're also popping a, push a fade out state onto it, but we don't want to trigger the tween of the Pokemon sliding from left to right until after that state gets popped. So we have a flag here, which will get set to true on the very first update iteration. And then when that gets set to true, we'll actually tween the Pokemon going left to right and begin and kick off all the other sort of asynchronous processes that exist thereafter. But let's look at the battle one more time just to see what's going on. So I'm going to walk until I get into a battle. Okay, we got a battle. So notice here, the fade in happens as soon as the slide in happens as soon as the fade starts, right? As soon as the fade finishes, I should say. We get a message popped onto the screen, right? It says a wild X appears, right? That's the enemy Pokemon. We hit enter, turn this down a little bit. We hit enter, and then we push another state onto the stack, another battle message, which is very similar to a dialogue state. It says go our Pokemon. And then we push a menu onto the screen, right? We've got a menu that says fight or run, a selection. It's a menu which has a selection. And then now, this is the top of the stack, right? So it's the only thing getting input. Nothing else, everything else is rendering beneath it, but nothing's getting input. So we have the option to either fight or run. Let's say we fight. We fight, we've got a new state now. We're in an attack state. Several things just happen. So what happens as soon as we kick off the attack state? Yeah.
You get a text box saying X attacked Y.
Yep. So first thing we have happen is a text box that says X attacked Y, where it could be either us or the opponent because it's based on whoever has the higher speed. And then what happens next?
Somebody takes damage.
Well, it does. So let's take a look at it right now and tell me what exactly happens as soon as the text box pops up. So what were the pieces that happened there? Okay, so the attacker flashes white, right?
Yeah.
Which is the shader that we looked at. That's the shader blinking on and off. There's some timer that says every 0.1 seconds, blink on or off. And then what happens?
Then the damage is dealt. And then,
Well, damage is dealt, yes, but what happens visually as soon as the white blinks?
the other one blinks?
The other one blinks. What's the other one blinking?
I'm not sure.
So it's opacity, right? So remember, we're doing the exact same thing we just did with the white, with the blinking, but we're tweening every 0.1 seconds the opacity of the defending Pokemon. And then we take damage. Then what happens when we take damage?
The reverse, basically.
Well, what gets animated when the thing takes damage? We've animated the blinking. We've animated the opacity.
The health bar
The,
drops.
the health bar drops, right? So we're chaining several things together. We're chaining first, we're doing the every 0.1 seconds for 6 times, blink white, then blink the other thing, opacity, right? And we're playing sound effects at the same time too. We're playing a sound effect for the attack, sound effect for the hit, and then once that's finished, tween the health bar, right? So we've modified the health of the defending Pokemon. And then what happens after the first one, after that process is finished?
Repeat for the other side.
Exactly. Repeat the exact same thing, but for the other side. And then what are we doing in between each of those? We have to do something.
You're checking if somebody dies.
Checking if somebody dies. Exactly. And if somebody dies, let's say we die, what happens?
You instantly go to the lose screen.
Well, we go back to the play state. We fade out to black, and then we go back to the play state. What happens if we knock out the enemy?
You go to this screen.
Exactly. And what happens on this screen? So what's the first thing that happens? Well, so recall, what happened when the Pokemon died? What happened?
Kind of fell off this platform thing.
Exactly. So that's a tween, probably, right? On his Y value. Then what happens?
You get a nice little text box.
Exactly. We've pushed a battle message state onto the screen. And then what happens when we press enter?
You continue getting stuff.
What just happened right there?
You get a text box that says you earned whatever experience points, then you get your XP bar goes up. And presumably it checks if you leveled up.
Yes, correct.
If you do level up, it has to actually de-level up.
Exactly. So we push a dialog to the screen that says you've earned X experience points. The XP bar tweens, right? We've gone up to however our ratio of current XP to next level XP is. We animate our text bar that way, our progress bar that way. Then we push a fade in state, right, to white. And then we have to pop everything off the stack, and then push a fade in or fade out state to the top of the stack, and then we're back to the play state. But if we do level up, we need to play the right music, play the right sound, and then part of the assignment will be actually in that exact function, you're going to need to add some behavior that will do what?
Display the change, basically, and what the new one will
Yes, and what are we going to need to do? What will we need to do in order to?
be. Displaying, what was it called? The selection box, but without the selection part, basically.
Yes, so once we've leveled up and we're in that victory state of the battle state, right? We need to push a new state, a new menu state, which has all of those stats and the amount that they've increased. And then when we press enter, presumably, we should pop that off and then pop everything else back to the play state and then do the fade in as normal. And that is the battle state in a nutshell. A lot of pieces that sort of are waiting on each other and input and stuff like that, but fairly easy to understand, just because a lot of it is very simple things that are just chained together over and over again to produce this sort of interesting behavior. So here we have sprites. Recall the sprites are what we're going to need to animate those. We have health bars, which are progress bars, which are just two rectangles that are, one's a line, a black line, and one's a fill. The fill's beneath the line, so that it can show. We get a sense of how much is missing, right? We get the width, the height, a color. We can give our progress bar any color we want to, which is how we get the difference between, say, a health bar and an XP bar. We just make one red and one blue, and we draw them in different spots, right? But they're both equally progress bars. And then they get a value. Their value is whatever determines how much of the rectangle is scaled, and the max is how much that should be divided by in order to produce a ratio for the total width, a scalar for the total width, which will allow us to get the sense of an amount missing. And then a player circle X, opponent circle X for the ellipses, just the graphical details, the actual Pokemon, so that we can get their stats, so that we can actually do dice rolls, or not really dice rolls in this case, but so that we can add or subtract HP based on attack and defense. And so here was the update. So trigger slide in. So what trigger slide in does is a 1 second tween, which you talked about, right? The Pokemon going left to right, or left to right, right to left. Their X values, just kind of tweening in over 1 second. As soon as that's finished, we're going to trigger starting dialog. So the starting dialog is push a battle message state onto the stack. The battle message state is just like a dialog state, and that it gets a string here. So a wild something appears. It gets a callback function for once we've pressed enter on that. And the callback function is itself another push of a battle message state that says go and then our Pokemon. So notice that we're referencing the self.opponent.party.pokemon there and self.player.party.pokemon there to get the actual name. And then once we've popped that off, then we push a battle menu state here, right? So let's take a look at the battle menu state. So this is interesting because this is where we actually define the behavior for how our menu works, right? Recall, we need something to tell us what happens when we press fight and what happens when we click run. So when we click fight, notice here items, right? Self.battleMenu gets menu, and menu expects items. This items key, this table, gets fed right back to the, gets fed right into the selection, right? And the selection it expects, remember, a text, because it has to know what to render at that index, and then an onSelect function. And then onSelect function is the callback that gets executed when you press enter at that particular location in the menu. In this case, fight, what that does is it pops this battle menu state. We no longer need the menu, so pop it, and then push a new take turn state. And then take turn state in this game is the Pokemon fighting each other. That's what the take turn state is. And it could have been called fight state, for example, but take turn state is a little more versatile. If we wanted to maybe one Pokemon wants to run, the enemy wants to run, and we want to fight, right? But you can't always run, so they should try to run, and then we can still fight them. Or they can use an item, or we can use an item, right? There's a lot of different things you can do, or we want to throw a Pokeball at them. And if we fail, then they should fight us, right? Take turn is just a general purpose state that we could repurpose for whatever use we want to with any interaction between us and the opponent, whether it's fighting, running away, using items, catching them, any of these combinations of things. But in this case, for the sake of this example, for simplicity, we've only implemented fighting. We and the opponent fight each other during this state, which is one attacks the other, and then we check for deaths in between both of those, and then go to victory or fainting, depending on which of those holds true, if either. Running is slightly different. So if we run, I've programmed it to be 100%, it'll 100% of the time work. In Pokemon, you actually have a chance to run based on what the delta is between you and your enemy. So if they're stronger than you, you actually aren't guaranteed to run away. So what we do here in my implementation is we just pop the battle menu, so it's gone, and then we push "You fled successfully" to the screen, this battle message. But there's a difference here versus the other battle messages that we've shown. I mean, it's not really different, but it's something to keep in mind. So I'm going to get into a battle. And so, first of all, with that message that you just saw on the screen, I had to actually press enter, right? I discarded it explicitly by pressing enter. And that holds true also for these messages. It won't do anything until I press enter. So I press enter, and then I press enter, and then it does its thing. But notice the difference between when I hit run. I'm going to hit run, I fled, and it does it on its own. It's not waiting for input, right? So how have we implemented that? Yeah.
You just use a timer and automatically do it the same way you would afterwards, but instead of waiting for your input, you just wait for the timer to end. Exactly.
So we use a timer, and then when the timer's finished, we pop the battle message just like we would have popped it by pressing enter. This false flag is what allows us to do that. We press false, and false is, can we input or not? And we can't. So actually, if we didn't do any timer thing after this, and we just did that false flag, the battle message would be there forever, and we could never get rid of it, ever. It would get stuck forever. So we got to be responsible and say, okay, we're going to put a timer. We're going to call timer.after 0.5 seconds. Immediately after that, we're going to push a fade in state, and then we're going to do these two pop operations here as soon as that fade in happens. This first pop will pop the message, right? This message here that we didn't pop through input. So this is actually garbage collecting in a sense for us. It's discarding the message that we couldn't discard automatically. And then we're going to pop the battle state, right? So running will push the battle message, trigger a timer tween for our timer.after 5 seconds, push a fade in state, and then after the fade in state's done, then pop both of those states, the message and the battle state, take us back to the play state. And that's where we'll be as soon as that's all done. And that's really what that's all that's in the battle menu state. Any questions as to how the battle menu works and the difference between fight and run and sort of how those operate? Okay. So let's take a look then at the take turn state, which is the last piece and the largest piece, I would say. This is the most relevant to the assignment. So we maintain a reference to which Pokemon is first or second to go, which sprite is first or second to go, and which progress bar is first or second to go up here. And we do that, like I said, based on speed. So whichever Pokemon is faster, and we could have also made this a little bit shorter just by keeping the sprites and the progress bars as members of the Pokemon object or the class, but since they're kind of separated, like we don't necessarily want a Pokemon to have a reference to its progress bar at all times, or I mean, you could. There's nothing preventing you from doing that. It would only serve the purpose of shortening this code here. But we need to keep a reference to this so that we can call attack here, which is this large bit of code, twice without needing to duplicate all of that code twice. Does that make sense? So, Tony, did you have a question?
Well, I was just thinking you could probably put that into a helper function where you just change the order and pass it in.
Sorry? Say it again?
I just kind of feel like, I guess you could take the code and you could avoid duplicating that, I guess. Because it's just reversed. So what you could do is you could, if you passed it into a helper function, which you would just, instead of passing it first Pokemon, player Pokemon, or instead of passing it opponent Pokemon, player Pokemon, you would pass it player Pokemon, opponent Pokemon, and that would probably work, I think.
Well, you also have to take into consideration, so the comment was you could pass in the player Pokemon and the opponent Pokemon into a function, and that would, and then reverse them in that function, I'm assuming, have reference them and reverse them. But the sprites are decoupled from the Pokemon, and the progress bars are also decoupled from the Pokemon. So we could shorten this by making these 4 things here fields of the Pokemon objects, but they're not strictly pertinent to the operation of the Pokemon object, and it sort of kind of makes the Pokemon objects a little too not basically abstract or lightweight enough, and it only serves the purpose at this point of just shortening this bit of code. There's probably a more elegant way to do it, but it's hard to say. If this code were to get larger, maybe. But the gist of this is basically to have a pointer to whatever Pokemon progress bars and sprites should operate first in the attack versus what should operate second. And then the two will trade blows in order based on who's first and who's second. So when we enter the take turn state, we're going to trigger that attack here, this function attack, which will take in first, second, first, second, first, second for the Pokemon sprite and progress bars. And then anonymous function, which gets executed as soon as the attack is finished, right? So this is a code that will pop a message that gets pushed in attack, and then this is where we actually check deaths, right? And then it'll determine whether we go to victory or faint screen or not. If not, and we return if so. If not, we're going to do another attack, but see everything is reversed now. Now it's second, first, second, first, second, first. So we have the same function, self-attack, which just takes in the attacker, and it's effectively attacker, defender, attacker, defender, attacker, defender for the Pokemon sprites and progress bars. And so the attack function here first pushes what does the attack, let's go over it one more time. What do we think the attack function does? In order. What were we covered them just a moment ago, but what was the order that happens when something attacks another thing? Yeah.
So the attacker blinks white.
Attacker blinks white.
And then the defender blinks opacity.
The defender toggles its opacity.
And then the health bar shrinks.
Health bar shrinks. Exactly, and then that's basically it for attack, right? Blink, play a sound. Blink, play a sound. Shrink the bar, and also we're doing damage in that function as well. We actually have to change the stats of the Pokemon. So we do that this is effectively where it starts, right? We place a battle message state onto the stack that says the attacker name attacks the defender name. Notice that it gets false just like the run message did, because we're not accepting input here. But it's up to us in the timer, or it's up to us actually, it gets done up here at line 42 of the enter state. But we're going to, after 0.5 seconds, play the attack animation. So power up sound every 0.1 second. We're going to remember the blinking flag on the sprite. We're going to toggle it by setting it not to itself. So if something is not itself, if it's a truthy value, it becomes falsy. If it's falsy, it becomes truthy. So basically toggling it between true and false. limit of 6, right? Because remember, every will do something every amount of time indefinitely unless you pass in a limit of some value, in this case, limit of 6. So we're saying only execute this code 6 times, only blink 6 times, right? Only toggle 6 times, blink 3 times, right? Because it has to go on and off. And then as soon as those 6 iterations are completed, we call the finish function on that timer object, which takes an anonymous function. As soon as that happens, we do the opacity bit, right? We've blinked the attacker, so now we got to blink the defender. So we play the hit sound. We do the exact same thing that we just did for the blinking, only now, every 0.1 second, we are setting its opacity to either 64 or 255, depending on what the value of its opacity is, right? So we're toggling between 64 and 255. Limit of 6, take a function, calculate damage, which we've just very simply done at attack minus defense, right? Up to 1, though. So if the defense is actually higher than the attack, we should still do at least 1 damage. And then, over 0.5 seconds, we take the defender's bar and we tween the value equal to their current HP minus damage, right? And then that will set in that bar, in the progress bar, it'll set its value. And even though the progress bar is behind state-wise, right? It's on the bottom of the stack because it's on the battle state. And we're in currently the take turn state, but because we're still manipulating the values of that state and we're rendering every state, we're actually still manipulating that state regardless of the fact that it's not on the top of the stack. So that allows us to shrink that Pokemon's progress bar, regardless of it being on the top of the stack or not. Once that's finished, once the tween is finished, actually set the current HP to that amount because we're only tweening the progress bar's value, which is independent from the Pokemon's value. And then that's the end of the attack. The attack is completely finished at that point. So any questions as to how the attack works? Just a chain of tweens, basically. So we do an attack, then check deaths is the next function. And we're almost finished. I'm going to kind of go quickly here. It's at 7:30. Check deaths. Is the player Pokemon current HP less than or equal to 0? Or is the opponent Pokemon current HP less than or equal to 0? If the former is true, we need to feint. And if the latter is true, we need to go to victory. So feint is effectively a battle state, right? Which says you feinted. And then what? Remember what happens when we feint?
It gives you a text box and then it leaves.
It leaves. Do you remember how it leaves as it differs from like running away, for example?
Timer instead of waiting for an input.
Well, beyond that, aesthetically, do you remember how it's different?
It fades differently to black, I think.
It does. It fades to black instead. So that's how we can differentiate, when we're feinting versus when we're running away. And so that's what we're doing here. Notice that the fade in state, RGB is 0, all of those. So it's going to fade in to 0, 0, 0, 255, as opposed to 255, 255, 255, 255. So it's going to be a black fade in versus a white fade in. And then once we've, this is just sort of a thing that I implemented so that we can keep playing indefinitely, but once that's finished, restore the player Pokemon to full health, resume all the field music stuff, and then once we've pushed a fade out state, 0, 0, 0, and then we've gone back to the field, let's push, notice that here it takes a function, right, after the fade out state's done. Once the fade out is finished, so this is right as soon as we're back to the play state, push a dialog state that says your Pokemon has been fully restored, try again, which will take the context and will require you to press enter to get past it. That's feinting. Victory is a little bit more robust. So victory is, do you remember what happens when we get a victory?
Well, it has to check leveling up as well. It says you've defeated your opponent, then your XP bar increases, then if you leveled up, it tells you that you leveled up, and then it leaves.
So it tells you defeated your opponent, XP bar increases, checks for a level up, and then leaves. After displaying the level up message or not, it leaves, it pops everything back to the play state, exactly. So remember the very first thing that happens though, the opponent sprite gets tweened over the course of 0.2 seconds, its Y value to virtual height, which means all the way to the bottom of the screen, right? the typical defeated your opponent from Pokemon sort of animation. Once that's finished, play victory music, push a battle message state that says victory, right? Once that's popped off the stack, calculate the XP, which is, I just chose arbitrarily, sum all the IVs of that Pokemon times its level, and that's the XP you got. Push a state that says you earned X XP, right? It's false, so that means it doesn't take input. So that means it's up to us in order to pop that off the stack. So after 1.5 seconds, we play a sound, and then we tween that XP bar going up, right? So that's what's going on here. Self.battlestate.player XP bar, we're tweening the value of either of the math.min of the XP plus XP or XP to level. Because if we don't, it could go past the edge of the XP bar, because we could go over our XP to level, right? Because we could gain, let's say we have 10 XP till we gain a level, and we could gain 20 XP. It would be 10 XP overboard. So we don't want to tween our XP bar past the edge of the XP bar. It would be a graphical glitch. So we math.min our XP plus XP and our XP to level, which will take the lesser of the two values. Once that's done, it's tweened. We're going to pop the message off, and then we're going to actually add the XP, level up. So this is where we level up if the XP is greater than XP to level. Play a sound, set the XP to the current XP minus our 2-level XP, which will mean that we'll have some carryover, right? And then actually call the level up function. Now, here is where, and also after that, congratulations, you've leveled up. Fade out white, which is just a white fade out here. I used it twice, so I made a function for it. Just pushes a fade in state, play the, stop the victory music, play the field music, pop, push a fade out state. So either way, when we've gotten a victory, we're going to push a fade out white, or we're going to call fade out white, correct? So push a battle message state, and then as soon as we press enter, because we've leveled up, fade out to white. And if we didn't level up, but we still got a victory, we still need to fade out white. And so this is where your assignment is, assignment 7. Assignment 7 is, notice that we have self.player Pokemon level up. The key thing that we're going to need to do here is add a menu that shows us how we leveled up. And if you recall, player Pokemon level up returns all of the stats that you've increased this level. So you can show a menu that just says your HP plus that amount, right? You're going to get all 4 values. It's going to explode to all 4 of those values. And then you're going to create a new battle menu, or not a new battle menu, but a new menu of whatever you want, but probably on the right side of some vertical height. 4 items. The only difference here, the only key thing that you're going to need to take into consideration is, and I'll go back to the slides because we're actually done at this point going over the code, but the selection items, you won't be able to actually select anything. It's just going to be purely visual. So you're going to need to edit selection to not have the option to not have a cursor. And this is detailed in the spec, which was actually released before lecture today. So you can take a look at that. But you'll need to make a change to selection. But all the pieces are there. It should be a fairly easy assignment as long as you understand how the states work, how the menu works, and how to create a menu based on those values, and how to actually get the values from level up. So some missing features that we didn't talk about, which we didn't implement, are, for example, the detailed level up screen, which is your assignment. Monster catching, right? We only had a party of 1 Pokemon throughout this whole entire thing, but one of the arguably main appeals of the game is to be able to catch more. So that'd be something to add, to prioritize, probably adding to the game. A field menu, so you can actually look at all the Pokemon you've caught. That would be nice, so you can actually see how much HP they have. An item inventory, because the regular games have items. You can use potions. You can find gold nuggets that you sell for a ton of money. Different abilities. Currently, we only have basically 1 fight operation, which is like a tackle, and the game itself, the regular game, has like over 100 different moves that have elemental attributes and do different things and cause status effects, buff you or your opponent. So adding those is appealing, and maybe being able to represent them as data is nice too. Trainers that you can encounter in the game that have their own preset or randomized Pokemon for you to fight. Monster evolution, because that's like one of the funnest things, is taking a really weak Pokemon and like raising it to become really strong and evolving it at a certain level. Towns, routes, other levels beyond just our, basic square area. Monster breeding, which is introduced in the second series, so that you can take 2 Pokemon and have a chance to get an egg with a really good stats or a really rare Pokemon from it. And then like a day-night cycle, maybe where different Pokemon come out at different times of the day, so you are incentivized to play at different times of the day for that purpose. But that was it for Pokemon. Next week, we'll actually be diving into Unity. So we're actually done with LÖVE 2D, which is a lot of fun, but now we'll be going into how to make 3D games. So this is a screenshot from the game we'll be making next week, which is a 3D sort of side-scrolling Flappy Bird-esque helicopter game based on a famous web game called Helicopter Game. And it was sort of one of the early ancestors to Flappy Bird. On the Wikipedia page, it actually says that too. I remember playing it. It was back in like 2007 or 6 or something like that. But your goal in this game, this is a modified version of that. Your goal is everything's 3D, but it's a side-scrolling perspective. So this is called 2.5D for that reason. You're controlling a helicopter. You're the purple helicopter, and your goal is to, in an infinitely scrolling world, so we'll revisit infinite scrolling, but in 3D, avoid skyscrapers. So you can see there is a green skyscraper, crudely modeled. Collect coins. So you can see there's a coin there. It's a 3D coin. It will always be spinning. Your coins are up at the top right. You'll see a background that's infinitely scrolling, and then you'll have jets that will randomly fly above you to sort of give you another sort of layer or dimension of obstacles to watch out for. And this will teach us a lot of the basics of how Unity works, so we can start getting into even more interesting things like a first-person like sort of horror exploration game. And then lastly, when we end the semester with Portal, we'll look at a couple of fancy things there. But that was it for Pokemon. Thanks for coming, and I'll see you guys next time. All right, welcome back to GD50. This is lecture 8. Today we're going to be diving into the world of Unity for the first time, which I'm excited about. Going to be kind of a whirlwind tour, but we'll try to cover as much as possible. Transitioning away from 2D and away from Lua and LÖVE 2D into 3D and C# in the context of Unity. So today we'll be talking about Helicopter Game 3D. So a Helicopter Game is a 2D game that was really famous in the 2000s. It was a web game. It was sponsored on a bunch of websites. Addictinggames.com still has it on there, and a few other websites have it. It was a Flash game, but I remember playing it a lot. It was the old precursor to Flappy Bird, which was mentioned on the Wikipedia page. There's a reference to it there. And this is sort of what the gameplay looked like. It was very similar to Flappy Bird, a little bit different in that instead of trying to avoid pipes, you're in a cave and you're trying to avoid the ceiling and the bottom, the ground of the level. And there were these little obstacles that would spawn in the middle as well, so you'd have to navigate that. But it was the same exact mechanic, the sort of like click to go up, and then when you didn't click, your helicopter would just sort of sink down via gravity. Today we'll be talking about a bunch of brand new topics, things like Unity, first and foremost, the sort of ecosystem with which we'll be doing a lot of the things we'll be doing. C# is the primary language we'll be using, so we're going to take a step away from dynamic languages and move towards statically typed languages, languages like C# and Java and the like. Blender is a program we'll look at briefly today just because in the context of 3D development, you're going to want to have a tool that will let you create models, and so the 3D software that I like to advocate for the most, especially for folks that are just starting out, is Blender because it's free and open source and it has much the same feature set as any commercial software like 3D Studio Max and Cinema 4D and the like. We'll talk about what components are, entities and components, how they relate in this model that Unity has adopted for all of its programming. Components are little pieces of behavior that you can then sort of combine to form a whole that will then drive the behavior of whatever object in your scene you want, rather than having to customize its behavior via a long chain of inheritance and instantiation. Colliders and triggers are important in 3D and 2D, but today we'll be talking about colliders and triggers, things like the helicopter colliding with coins and buildings and other planes that are flying. Each of those has to have a collider, and certain things have to be considered triggers in order to trigger certain behavior with other entities. prefabs and spawning. So prefabs is a huge concept in Unity. So prefabs are basically prefabricated objects that you can customize as you want to, lay them out in the editor rather than having to necessarily code all the details. And then you can instantiate them in the actual scene via code programmatically in a way that fits the model you're striving for. Texture scrolling is something we'll look at briefly because it's the way that we accomplish the infinite sort of scrolling aesthetic or behavior. And we'll look at how we can do that in a different way than we've done before using UV coordinates and specifically looking at materials and modifying certain attributes of those materials. And lastly, to tie everything together as we've done before, we'll look at audio, things like audio listeners and audio sources, what the differences between them and how to add them easily to our game project. But first, a demo if there would be anybody willing to come up and take a look and play the 3D helicopter game that I put together. It'd be awesome. Anybody? Steven? Awesome. Thank you so much. Let me go ahead and actually get it. So I've pre-built it. So let me go ahead and... So the nice thing about Unity is it exports to multiple platforms, and right out of the gate you can get just a, I didn't put an icon for it, but you can create just a native application very easily. And so whenever you're ready, go ahead and hit play, and up and down will move your helicopter. So this is the 3D helicopter game, and I don't think we have sound live, but there should be audio. Oh, I might have actually, here we go. There we go, that's my bad. So there's music playing, there's sound effects. So notice that we have a 3D model. This is what's called a 2.5D game. So even though everything is in 3D, the models and so forth, the actual axes upon which we're bound are just two. We're just bound to I believe the X and the Y, it could be the Z and the X, I don't recall offhand. But we're bound to just simply two axes of movement, but all the models, as we can see via the camera, are in 3D, including our helicopter. So we have a few things going on. We have skyscrapers that are scrolling by. We have coins that are also going by at the same speed as the skyscrapers. We have a background that is infinitely scrolling. We have, of course, our helicopter, which has a rotating set of blades. And when we collide with a coin, notice that we get a little, it might be hard to see in-house, but we have a little particle effect that plays. There's airplanes that are flying up top, so we're instantiating those as well to fly past us to provide another layer of obstacle. And if we collide with an airplane, notice that we get despawned, and then we trigger another particle effect to imitate an explosion. And then notice we also have a couple of other elements. We have two GUI elements, a sort of coin total at the top right, and then a game over bit here in the middle of the screen, which only shows up once we have died. And the explosive behavior, if you want to collide with a building, you'll see that it also triggers when you collide with a building. So there's two things looking for these explosions. The airplanes up top and the buildings below. Those are our two obstacles. But when we collide with the coins, we should increment our coin total and then display a different particle effect. And then this goes on ad infinitum. You can press space to restart. So we have keyboard input that's based on what we press, different things happen. And so that's effectively the demo that I put together today. So thanks, Stephen. I appreciate you coming to demo it. So that's the 3D helicopter game. It's got most of the same mechanics as the web version from before. I would say maybe even more features, just to illustrate a few new concepts. But that's effectively what we're going with today. We're just a pretty simple Flappy Bird-esque, differently themed game based on the same principles. Fly forever, avoid obstacles, and in this case, even get little collectibles. And so notice that there are also effectively two states in our game, which are just the playing state and then the game over state. The two are almost effectively the same. The only real difference is that one doesn't have the helicopter present and displays a different GUI element in the middle of the screen. If you haven't downloaded Unity already, there's two links here. So the top link is just the sort of catch-all download link, and then the second link is the beta link. So we're actually using the beta in this course because Unity has started transitioning away from a numerical system for their releases and is now going yearly with their releases. So the last long-term release candidate was 2017's version, but now that we're almost halfway through 2018, the newest beta is the 2018 version. It has a bunch of new features. So go ahead and check that out. And everything's been well tested and runs very well, very smoothly on Windows and Mac with the new beta. So what is Unity. So the difference between what we've done so far and what we're doing today is now we're actually using a full-fledged sort of game engine, this system. It's got a built-in editor and all this awesome, cool functionality that we really didn't get with Love 2D before. What we were doing before was using a framework and just implementing everything purely in code. And as we'll see today, everything that you want to do that's customizable effectively is or can be done via code, but there are a lot of more efficient and more user-friendly ways to accomplish the same thing, which we'll take a look at. So Unity has a tremendous market share right now. I think in 2016 it had like 43% of all games released were done in Unity. I don't know what the current numbers are, I couldn't find them, but there are other engines that are also very well used, Unreal being among them, and Unreal actually may have more market share now because of games like Fortnite and because it's been improved a lot over the last couple of years and really marketed well. But Go.CryEngine, there are a lot of game engines that are similar to this that provide you this all-encompassing sort of way of dealing with your game scene and with all your game data. But Unity is a very easy engine to start getting used to and cranking things out and being productive with without the tremendous learning curve that some of the other engines like Unreal might have. Unreal does have a more user-friendly way of doing things, but if you want to get down into the nitty-gritty with Unreal, you're coding in kind of semi-arcane C++. So for folks who aren't used to it and used to 3D game development, it can be kind of a large board to get onto. The nice thing about Unity, aside from the fact that it's fairly easy to get started with, is that it's free. And you can use it completely with all of its features until you start making over $100,000 in gross revenue using or releasing Unity products. And then there are other tiers. The next tier above that is if you start making $200,000 and you get new features with these other tiers. But if you want to just start up a new company and use Unity and take something to market, completely free to do so. And once you get over $100,000, it's a good problem to have. It's not necessarily too much to ask to start paying Unity to use it as the means of getting onto the market in the first place. And especially in mobile and VR, Unity is sort of like the forefront. It's got even higher percentage. I think it's like 60-something or 70% market share on mobile. And then VR, from the beginning, it's been it's marketed itself very strong towards the use of VR. And we'll actually use VR in the next lecture. And the way at which we will accomplish all of the programmatic aspect of this, getting things actually implemented in code, is via C#, which is very different than what we've used so far, which we've used Lua, which is a dynamic scripting language, very much like JavaScript. We'll actually be using, so C# is very similar to Java, in which things actually have types. And so here's a couple of screenshots of what the Unity editor looks like. So the nice thing about the Unity editor, actually, which we can see right off the gate here, is that it's very customizable. So on the top, that's sort of the default view. You have a bottom panel that shows you all your resources, all your assets, things like scripts and shaders and models and textures and sounds. You have a nice file browser there on the left-hand side, which allows you to easily navigate your project. You don't have to go looking through your Windows or Mac computer, using your Finder or whatnot, or your File Explorer, and actually look through all your files. You get a nice view there so that you stay integrated within the Unity ecosystem right there. On the right-hand side, you can see all the behavior for whatever objects you might have in your scene. You get a nice big scene view, so rather than having to run your game live and look at the behavior that way, you can actually see in advance what your scene looks like and analyze your game objects that way, and their appearances and whatever you want to do with them, and lay them out perfectly rather than have to programmatically figure things out. And on the left-hand side there, you can see a full list of all the game objects. And then on the bottom right screenshot, you can see that the editor is heavily customizable. So you can lay things out however you want to fit your style of development. I often like to have a panel on top, which shows me my scene view, but then have a panel right below that shows me the game view. So if I'm actually running a game and seeing it happen live, I can also see it in the scene and sort of rotate around in sort of this God mode that you can get in a lot of games, and actually analyze and see things that way, and analyze their behavior frame by frame, even if I want to, in a way that's not possible with however I might have coded the camera in the actual game itself. So C#. So has anybody in here used a static language or is familiar with statically typed languages versus dynamically typed languages? Tony, Steven, okay. So what languages have you guys used, just out of curiosity? Steven? Java, C, C++, Tony? C, C++. Okay, so to you guys, this will be it's pretty similar. So C# is very similar to Java. It almost looks identical at first glance. There are some features that are different, but it's sort of Microsoft's initiative to sort of compete with Java. It's a Microsoft language first and foremost, but there are ways to run C# code on other platforms, primarily with the use of what's called Mono. So Mono is an open source implementation of what's called the CLR, the Common Language Runtime, which is how Microsoft allows several of its languages like F# and C# and C++, Visual C++, Visual Basic, they all sort of compile to this intermediary format, like how Java compiles to bytecode. And you can run any of those languages' code, their version of the bytecode, with the CLR. And that what Mono is, and what Unity sort of relies on to allow its use across multiple operating systems, is a CLR that's not just Windows specific. It actually runs on Mac and on Linux machines as well. And you'll actually see evidence of its existence via the nomenclature used for mono behavior. So within Unity, there's this thing called a mono behavior, which we'll take a look at. From the beginning, actually, Unity was developed for Mac platforms exclusively, but in 2012 or 2011, they ended up making it usable across all major desktop operating systems. But C#, suffice to say, very similar to Java. We'll look at its syntax, but it's different from Lua in that with Lua, you could just say, x equals 10, or object equals, and then create a table with whatever you want. C# is a lot less flexible in this sense, in that you have to actually tell it in advance what each data type is that you're trying to make. So you can't just create a table or a integer. You actually have to say int, my int, or x equals, and then 10, and then semicolon. So there's also more syntax to be conscious of. And so really quickly, I can show you just what some C# looks like. We'll take a look at this again going forward. But as you can see here, we have public. So that's another thing about C# and Java. If you're familiar with Java, they're object-oriented programming languages. And as such, there are objects that are public and private, and you have access specifiers for different variables and classes that'll tell other variables and classes whether or not they can communicate effectively. So public class just means effectively anybody can see this class. Other classes can see this. But then you have, let's see if I have one of these that has a private variable. I know there's at least one. Here we go. So private text here, for example. So first of all, notice that these are variable declarations like we've seen before. We're saying this is a variable that I'm going to use. In this case, public game object helicopter. So I'm just defining it. I'm declaring it. I'm not defining it. It doesn't equal anything yet, but I'm saying this is going to exist, right? You can say equals something and then define it on the same line. But in this case, we are just declaring in advance what different variables we're going to need later on when we, like for example here, we see in our start method, and we'll go over what all these methods are and how they're relevant. But we can see here text equals, and then we're calling some function called getComponent. And then we have some funky syntax here, less than, text, greater than, and then function call syntax, 2 parentheses. So we can see that there's a lot more syntax, but all of the same principles still hold true. It's still much the same way to think about programming. It's just there's a little bit more to stay conscious of. And we sort of trade off this dynamism for more performance. So that's ultimately what it comes down to. Static versus dynamic languages, you're trading flexibility for performance in this case. The C# obviously is a lot faster than Lua. We can do a lot more with it. And actually, Unity isn't itself programmed in C#. Unity itself is programmed in C++. But it allows us to program any behavior that we want to with C#. All right, so that's a look at C#. So we can see also, I was alluding to up here, we have our private, public, and we do things with them. And then depending on sort of what we've declared, public or private, these things also transfer into the editor. We'll see how all of that comes together soon. But suffice to say, that's a look at C#, what it looks like, and we'll use it and we'll get comfortable with it. But it's a little bit different than what we've done thus far. Away from programming, we'll take a very brief look at what Blender is. So I have it installed here, and this isn't required for the course. I will provide you with all the models and all the assets that you need to get working. But this is what Blender is. So Blender is it almost looks at first glance very similar to Unity. It's the only difference, well, the big difference is this is meant to create new assets. And technically, Blender does have a built-in game engine, but it's not used for that purpose very much. But the sole purpose that we would be using it in this course would be just to create new 3D models. So as you can see here, I can click on these vertices and move them around. And I'm not a guru by any stretch of the imagination when it comes to Blender, but the helicopter and jet and skyscrapers and those kind of simple models, I made all of those in Blender, and those are bundled with the project if you want to take a look at how those are implemented. And you can download Blender at I forget what the exact link is actually. Let's take a look. Blender.org. And then, if you just go down here, download Blender 2.79, looks like the most recent version. Blender 2.8, I guess it's in development, but there's nothing concrete about that on the front page. But if you want to model 3D assets and you're curious and you want a free piece of really awesome software, can't recommend Blender enough. But like I said, not going to spend too much time on it because that's not it's not something that will actually be required in the course to implement 3D models, to create 3D models, since I'll be providing all of that to you in the project in the GitHub repo. And so here's a screenshot of basically what we just saw. So the fundamental part of Unity. So first of all, let's take a look at the Unity editor. So we can see here much of what we saw in the screenshots, but here I'm live looking at my scene, right? I have a helicopter. I have this background back here. I have a camera that's right here. You can see that it's a camera because it's got the little camera icon, but it's effectively just an invisible game object. It's not actually going to be rendered to the screen ever. And notice that there are no skyscrapers, no coins, no jets, or anything like that. Those are all instantiated dynamically. But this is the beginning of our scene, and it's all laid out in advance. And we can see here with this camera preview, which is kind of hard to see because it's really small. But here's a larger view of what it looks like. And we got a GUI element here. We got coins here. We have our helicopter. But all of this is sort of how it's a marked difference from what we've gotten used to, which is program everything and sort of load it. And oh, did I put this in the right position? No, I didn't. So if I wanted to come over here and just move the helicopter a little bit, which like that. Whoops, I just triggered it. If you click on something, by the way, it will play any particle systems that are associated with it, so you can actually get a preview for those as well. But I can easily just move it here to the right or to the left before the game actually starts. And if I click on the camera, we can see it there. It's a little bit shifted to the left as opposed to what it was before. But if I just press Command-Z a couple times, take it back to normal. So game object is an important concept. So a game object is basically everything in Unity. So the camera is a game object. The helicopter, which is right here, is a game object. Everything, by the way, that you want to see in your scene in Unity is on this left-hand hierarchy right here. So helicopter, game object. There's got to be a light source in a 3D scene in order for you to actually see things. So directional light, that's a game object. Background, skyscraper spawner, we don't see it anywhere, but that's also a game object. It's just an invisible one. A coin spawner, there's something called a canvas, which if we double click that, we can see we have this obscenely large GUI here that paradoxically isn't on top of our scene. Unity does a very interesting thing with all of its GUI elements in that it basically maps the canvas to 1 pixel being equal to 1 Unity unit, which is usually equivalent to a meter. And it draws this in a different draw call than it draws all of the actual 3D stuff, all the stuff that's down here basically in world space. So when you create a canvas and you see it's gigantic, that's just Unity's way of doing GUI. It's strange, but apparently they do it for performance reasons because they don't have to calculate fractional points of where the UI is supposed to be in world space, which can get really small. But the canvas is a game object. Notice that helicopter has children It's got blades, a body, and then a blades collider, which actually could have been part of just the blades object. Canvas itself has two children, coin text and game over, and those are the text on the top right and game over in the center. So those are just two text objects, which are labels that we can just populate with whatever text data we want. The event system is an object that's part of that just gets added to your scene automatically when you add a canvas. Airplane spawner, explosion particles, and explosion sound. So we have all these different objects. They're all part of our scene, and they all do different things, but at the core, they're just game objects. That's the sort of core, like the bottom type. Yes?
So I would imagine you're not actually moving the helicopter or the camera, and you're scoping everything else.
Correct.
So can you actually reset the position of the background, first of all?
So the question was, since we are maintaining a consistent position with the, I'm going to try and scroll in. Here we go. The nice thing about Unity 2 is if you right-click, you can use WASD to move around the scene, which is super easy and convenient. But the helicopter here stays in one spot, and the camera always stays in one spot forever. So do we move the text, or do we move the background image like we do in Flappy Bird, in our LÖVE 2D implementation of Flappy Bird, where we reset its position? And the answer is, I will play it right now in scene view and let you decide that for yourself. So let's go to Window. I'm going to go to Layouts. So I like the 2x3, like I said before, so you can see the scene and the game running live at the same time. I'm going to move my camera in the scene so that I'm looking at this kind of from back here. And then I'm going to play the game. And so here's where I'm just going to hold it still. So what do we think is happening? Does it look like that? Does it look like our thing is moving, or is it staying still? It is staying still. Any guesses as to how we're achieving this? Changing the texture. We are scrolling its texture. So when you take a texture and apply it to a 3D surface, you basically tell it where you map the texture coordinates to the 3D coordinates of the object that you want to render. It's called UV mapping. They call it UV because usually when you're dealing with 3D objects, you have your X, Y, Z, and then you want to think of your texture kind of separately from the 3D object, so you use UV instead of X, Y, since you already have X, Y, Z allocated for your 3D object. And so by shifting the, there's an offset part of the texture, the material that holds the texture. There's an offset field that will sort of reposition the UV mapping of that texture onto the 3D surface. And when you offset it, it will just sort of wrap itself around, if that makes any sense. So what we do is I can actually show you in the code where this is. This was going to be mentioned at the end of the lecture, but we have the scrolling background component here, and there's this thing on each material called a texture offset, which basically shifts the UV mapping of your texture to your 3D object. And so by setting that texture offset to some value offset, which is very similar to what we've done before, notice that offset is just scroll speed times time dot time. In this case, and I don't mean to overwhelm with necessarily all the details here, but the bigger picture is that we're taking time, the amount of time since the beginning of the game has started, and we have some scroll speed that we've predetermined, and we can just scroll the texture offset here. We're just placing it here at the X. So this new vector 2 offset 0, just think of these two as an X and Y. A vector 2, vector 3. Vectors are just combinations of numbers, so 1, 2, 3, 4, however many you want. A vector 2, offset, and 0. So we don't want to scroll on the Y axis. We just want to scroll it left to right. So we're going to apply no texture offset to our Y axis, but we want to apply texture offset to our X axis. So that's what their offset there is. And I included it also here. Notice there's a bump map texture offset. There's no bump map actually on our texture. So a bump map is effectively, I can maybe find a good Google image for it. if you're not familiar with a bump map, I'm going to go in here. I'm going to hope that there's no shady images on Google Images, but a bump map, can we see it well? It's kind of hard to tell. But in a lot of 3D games, you'll see kind of like bumpiness and shininess on surfaces. And that's accomplished the majority of the time using bump mapping, because obviously if you were to model like every single tiny little bump or model in a surface, it would get extremely difficult to render like large objects, because I mean you're looking at thousands of polygons for a surface that was actually this detailed in a game. So what you do is you take what's called a bump map, and the bump map gets, during lighting, it'll effectively skew the surface normals of a 3D mesh. So effectively, it will pretend as if your 3D mesh has a bunch of bumps in it for the lighting, only for the lighting. And so when it gets lit and it gets shaded, it looks as if it's bumpy, but you're still dealing with a completely flat, completely simple cubic mesh in this case, or whatever mesh you want. And so you can, the long story short, here, if you wanted to include a bump map on whatever surface you want to scroll, or if you want to edit the bump map, this is here just because you can also manipulate the bump map texture offset. It's an included field in a material. So any questions as to sort of how this works at large? We still have a lot to cover before we go into like a lot of the specifics, but conceptually, do we understand how this sort of works? Okay, cool. So let's go back to the slides. Right, so we were talking about game objects. So all of those things that we saw before were just game objects. So let's go back to the default layout. And then we can look back at our scene. So this is our scene. All of those things were all of our game objects. Those are ultimately containers. I talked about this in a prior lecture, but this is the beginning of an entity component system, in which case these game objects are our entities. That's sort of the entity class, container class for what drives behavior. And the thing that allows us to actually get interesting behavior out of this sort of abstraction is the use of components. And we'll talk about that. So components are all of the things on the right-hand side by default of the Unity editor. So if we're looking at our camera, for example, and we take a look at all these things on the right, we can see that we have something called a transform. We have something called a camera. A GUI layer deprecated, so that's by default. It was imported from a prior version of Unity, so this you could actually delete this. A flare layer, which we're not using. An audio listener, I believe that comes with all cameras by default, though, in case you do want to use it. An audio listener and an audio source. So all of these different pieces are our components. They're what drive the behavior of this game object. So if we can create just a brand new empty game object. Oh, I created it as a child. We can create a brand new empty game object here, right? It's just a game object in our scene. And it's right where our mouse is. Right, well, it's right here. And it does nothing. It has one component, and that component is the transform. Does anybody guess what a transform is? Yeah.
The position, rotation, scale, etc.
Yes, it is the position, rotation, and scale of a game object. Something that was before, put into 6 fields, or in this case 9 fields potentially, or maybe 3 fields with children, is now an object that we can modify at will. So, well, it's a component that we can modify at will. So if I do this, notice I'm just scrolling the X. It's just moving that transform, which is just the position of that object. And Unity knows to look at that transform component and render our object based upon where its transform lies. Rather than us having to manually set all these things, which we still can do in code, we can just modify them in the Unity editor directly via a graphical interface. It's just an interesting, helpful layer of abstraction. So a transform is a component. A camera, in this case, is just a component. We can attach this to anything we want to, and it becomes a camera. And then we can set it to be either the default camera or not. The camera has a bunch of different things, and I can't claim to know all of the fields of every object in Unity because there's just a tremendous number of things. But clear flags, background, culling mask, all these things that are relevant to sort of how the camera does its job, they're all things that we have complete access to here in the Unity editor. We don't even need to touch code, really, for a lot of things. An interesting, fun thing we can take a look at is if we go to layouts, go back to 2x3, and take a look at our game again. So we have our camera currently looking at the screen here, right? It's just always in one spot. And it has a way of projecting the scene. It's either, it can do one of two things. It can be orthographic projection, or sorry, perspective projection or orthographic projection. Does anybody know what the difference is between the two, or at least visually? So perspective projection, what that does is it models how real cameras, real lenses, the human eye, etc., behave in real life. Things distort a little bit. And so you see things, depending on where you're looking at them, they look wider or skewed and not like completely geometrical like you would if you were just to like draw them at a certain distance. Things have vanishing points, etc. Orthographic, things look a lot different. So notice instantly, so we can see here, perspective doesn't really change a whole lot visually with our helicopter. Things do change a little bit with the background because the view angle is different between the two, the perspective and the orthographic camera. But if we look at, if we make this a little bit larger, so I'm going to increase the size like that, and I play, one thing we'll notice, what's the first thing that folks are noticing? You can actually see the difference between the top and the bottom. Whoop. How, in particular, I'll put your attention towards the buildings. How do the buildings differ? You can't see the side anymore. The lens sort of curves a bit, and so I'm not entirely familiar with all the math involved, but at the end of the day, what it boils down to is with a perspective camera, you can actually gauge things' distance relative to each other a little bit better. With an orthographic camera, everything is completely flat, and no matter how far away from you it is on the axis that's completely perpendicular to you, it's going to look the exact same. So these buildings are always going to look the exact same no matter how far away they are, no matter which position they are, because everything is just looked at completely flat. And everything is, the view matrix is calculated in a different way. And so just with a simple button, you can change sort of how your game looks completely. You've probably seen a lot of games. I believe Crossy Road does everything with a orthographic camera versus a perspective camera. It has a very distinctive look, especially once you sort of skew things a little bit. But that's just one thing that you can change just without having to touch a single line of code, how your game looks via just the camera's implementation. Let's take things back to how it was. And there's a lot of things like the field of view. So if you want to see more of the game world, so things like in Quake and other shooters, you can change this view, usually in your menu settings, just so you can see more around you. And it starts to look, it sort of looks like a fisheye lens a little bit, depending on how you do it. And that's just more distortion of the perspective projection. Yeah, all these things, they all have, I don't know necessarily what every single one of them does, just because it's, there's just a lot involved. And generally, you don't have to mess with it too much. It just ultimately depends on what you're trying to accomplish in your game. And you'll end up finding specific areas of the editor and specific areas of the code base and documentation that you dive deeply into. But this essentially is what a component affords you the ability to do. When you create a component and you attach it to a game object, you can easily not only combine different things to sort of create this emergent new behavior and combination of behaviors for your game objects, but Unity allows you via different ways of programming the components to modify them depending on how customizable you want them to be in the editor itself. So you don't have to touch any of this in code. You can just go into the editor and quickly whip things up because of the way that you've modeled all your components. And so we see other things like the audio listener. An audio listener is something that will literally listen for audio and play it back like a microphone to the game player. And then an audio source is an actual source of audio, and so it'll play that audio at the location of whatever that game object is. So we've combined all these things. So now we have a camera that is it's projecting everything with perspective projection. And it's an audio listener, so it's going to listen for audio in our scene, and it's going to play it. It's also going to play an audio source and listen to itself. And that's just the beginning. We have a whole bunch of other components here, which, I mean, we can take a look just really quickly. So the directional light has a light component, and so a light, you can do all kinds of things. You can make it a spotlight, directional light, point light. All these look a little bit differently. You can make it have a specific color. So if we wanted to, maybe if you wanted like a really dark scene, you could have like a dark light. Or you could even like emulate dawn or dusk with like an orange light. That's sort of how you'd go about doing that. You can bake your lighting, which means that you just pre-compute it so that you don't have to render it in real time when you actually play it on hardware. A lot of different things, a lot of different settings. We don't have time necessarily to go into all of them, but looking through all of these, you can see all these game objects are just combinations of these components, and that combination of those combinations of components are responsible for the behavior that we get in our game. That's the ultimate essence of what Unity is and how it does what it does. And to illustrate the difference, we've talked about this before. This is an inheritance chain where creature inherits from, or monster inherits from creature, which then goes to goblin, goblin chief, elite goblin chief. In Unity, you could create a game object, right, and then give a creature component, a goblin component, a patrol component, right? So maybe you want different things to patrol. You can have it like in Unity it'd be kind of complicated, but you could create basically a pathway and then have your entity follow that pathway at a specific time. And then depending on how you've programmed it, you could specify all these different characteristics in the editor. So you could just say on the editor, okay, I want you to go patrol from this range to this range, and I want you to do it with this length of time, pause for this long, right? And then you can give that to anything in your scene. You could make a camera patrol if you wanted to, and then have that be like demo code for the beginning of your game. The flexibility is just insane. Elite component, right? If you want maybe certain enemies or certain objects, if they're elite, maybe they shine bright, maybe they drop more experience or something. A chief component maybe has better weaponry than like a non-chief component. And then a toxic component maybe is like an enemy that when it dies, it like sprays like toxic gas or toxic liquid all over the place. But the flexibility is there. You can ascribe any component to any object to get any sort of behavior that you want to. It's on you, of course, to implement all of these components, right? You're not going to get all these for free. You're going to get a lot for free. Unity gives you a ton of components, really good components. But you're ultimately going to need to program your game logic, and so you'll have to implement all these things, elite, goblin, what it means to be all these things. But thankfully, it's not terribly painful. The way at which we go about doing all of this, and by the way, are there any questions so far as to how like Unity's model works, the difference between composition versus inheritance, anything we've talked about thus far? All right. The way at which we actually go about making our own components, which is probably what you'll spend the most of your time doing, at least in the beginning when you're bootstrapping your game, is, programming what's called a mono behavior. And so we talked about mono before. So mono is the sort of open source implementation of the CLR. And mono behavior, I imagine, I tried to look this up and see where it derives from. I imagine it's because it was originally a Mac exclusive project, Unity. And so because everything was implemented in mono and because this is the way it's scripted, mono behavior became the name. But a mono behavior is what a component is. They are effectively one and the same. The difference being that a mono behavior is how it's illustrated in code. In C#, if you want to program something to be a component that you can then attach to a game object, it needs to be inherited from mono behavior. Things like, so if we go to like coin spawner here. So the coin spawner has, and you can see the difference between like what's built into Unity and what's your own via, it'll say script here. So in this case, I have a coin spawner object, right? It's just an empty object, at least in terms of what it displays. It's got a transform, which is irrelevant. It could be literally anywhere on our entire scene. The only difference between this and the empty game object that we saw before is that it has a coin spawner. And this coin spawner has a this thing here. All components that you add will have the script field here, just to show you that that's the script that that's getting its code behavior from. But also we have this field here called prefabs, which has a size of 1, because it's actually calculated based on how many elements the list that it's responsible for has. And we have one element, as it says here, and it's got a coin prefab, which is here, this coin prefab. And notice that I clicked on it, it took me right to it in my assets. And so prefabs and all of that, what that means and how to get that all working, we'll talk about that. But a coin spawner script has to exist in our code base before we can actually add it to any game objects, right? So if I go into in my project, usually you have assets, a folder called assets in your Unity project, and then I typically create a resources folder. It's not mandatory that you do so, but just for organization, I'll create a resources. And then I'll have a bunch of folders for all sorts of different things, like we've done before, where in the LÖVE 2D project at the parent level, you have like a fonts, a music or sounds, and then like a source directory. And here, in this case, we have fonts, materials, models, all the different assets that we will need in our game, but also a scripts folder, and all the C# scripts here. All the C# scripts here that we'll use amongst all of our components, all of our game objects. And so you could easily just go to any of these rather than have to go into your operating system, open up a new window, and find your file and navigate through all the files that Unity generates for you, which can be kind of a pain. You can just double click on like a coin script, for example, and it'll open in your default editor. And so one thing that I'll just mention here is if you go to your Unity preferences, on Mac it's Unity and then preferences, you can go to external tools. So by default, starting in 2018, Unity is transitioning away from its prior IDE, which was called Mono Develop, which was a good IDE. They're transitioning away from that, and they're making it focused on Visual Studio as the default IDE. I don't use Visual Studio. I like VS Code. So what I did was, and what you can do, is you can choose your external script editor here, if you prefer a different script editor like Atom or VS Code or Sublime Text, and then just browse for it on your file system, whether you're on a Windows, Linux, or Mac machine. And then you can easily just choose which file you want. In this case, I chose VS Code. And so the effect that has is whenever I double click on a script within Unity, it'll actually open the IDE or text editor that I have assigned to it in Unity's preferences. And so here is the coin component that I have created for this example. And notice that every component, first of all, is a class. And actually, everything effectively in C#, just as in Java, is a class. It's a public class. And notice that I call it coin, and I got this colon and then mono behavior. So this colon, anybody take a guess what the colon means? Connie? Extends, yes. Extends or inherits from mono behavior. So anytime you have a component that you want to create and you want to add it to Unity and allow you to see it in the editor and allow you to actually drive behavior of an object, you need to inherit from mono behavior. Like it says here, my VS Code, since I have the extension for OmniSharp, it'll actually tell me mono behavior is the base class from which every Unity script derives. There's a couple things here. So notice that we have a few methods. So void start, void update, and void on trigger enter. So anybody take a guess as to what, ignoring on trigger enter, does anybody have a guess as to what start and update do? Yeah.
It would be just like init and update in LÖVE.
So say it one more time.
It would be just like init and update were in LÖVE.
Exactly. It'd be just like we did before when we created objects in our LÖVE 2D projects, where we had an init function assigned to every class and an update function assigned to every class, and we would call those ourselves. Every mono behavior can have a start method. In this case, It's empty because every time you create a new script via the Unity editor, it will automatically, first of all, it will automatically create a brand new file for you. So if we want to, let's just say I want to create a new script. So if I'm in the Unity editor and I go to my assets, I right click, create, and then I want to create a new C# script. It'll create it there. I can say maybe I want this to be, I don't know, test component, right? So this should have the effect of when I open it in my VS Code, this test component, this was auto-generated for us. We didn't have to write any of this boilerplate. But every mono behavior, or every script that you create, rather, by default is a mono behavior, which it now strictly does not have to be. You could create a class of your own that maybe you call behind the scenes, or maybe it just represents a data structure or something. But by default, anytime you create a new script in Unity, it'll save you the hassle of typing out all this stuff by hand, and it'll give you an empty start method and an empty update method. And so like Tani said, the start method gets called as soon as the object that it's assigned to gets instantiated. As soon as this component gets instantiated, rather, which usually often is the case that it gets instantiated at the same time as a game object. Not always. You can create game objects or components on the fly. But this start method will get called. Anything that you put in here will get called right away. And then this update method, Unity will every frame go through every component on every live game object and will call the code that's contained within this update function. And you don't have to call this anywhere yourself. Just by assigning this component to something in your scene, assigning the component to a game object in your scene, you get the sort of update and start and all this other functionality given to you for free. And mono behaviors are actually much more complex than just start and update. So if you go to mono behavior, Gesundheit. If you go to mono behavior here, we can see that, by the way, I want to shout out Unity's documentation. Unity has amazing documentation. docs.unity3d.com. You'll go through pretty much everything you possibly could ever want with every object implemented in Unity in quite a good detail with a lot of examples. But here we can see, just in the description, it'll tell us the mono behavior will get start, update, fixed update, late update, on GUI, all these functions called for us, assuming that they're implemented. And you don't have to implement them if you don't want to. If they're not implemented, they just won't happen. If there's no start method, then that means there's no start logic for this component, so it doesn't need to execute. If there's no update, maybe it just needs to start at the very beginning, but never update after that, don't implement update, and update will not be called. All of these are optional. That's just a small chunk of mono behavior, though, because you also have messages. So messages are functions that you override. As you can see, there's a whole lot of them. And all of these messages get called depending on certain things that happen in the game scene. So on trigger enter, for example, if our object is a trigger and we enter it, then the behavior will get called in that function, which will allow us to do things like if our helicopter enters a building, we can call that helicopter's explode method, which is literally what we do in this project, thanks to this function. And all we really need to do is just a couple lines of code. It's very simple. On post-render, on pre-render, all these different things are called at different times. You can look into all of these if you want to, just by clicking on them and looking at their documentation. Late update is called after all update functions have been called. This can be relevant for physics, certain physics calculations, but there's a whole lot of different things you can do. You don't necessarily need to do a lot of things yourself if Unity provides you with the function that gives you the effect that you're looking for. And so if you're curious, mono behavior and then the docs at large, this is just all the documentation, just an insane amount of documentation. And that's just in the classes. There's all these other little side areas as well. And so that's sort of what mono behavior is. It's a component. It gets a lot of these functions called for you. You don't have to implement them, but if you do, you get a lot of functionality for free, basically. Any questions as to what a mono behavior is, how it works, and so forth, or any of the syntax we've seen thus far for creating a mono behavior? All right. And so here in our coin, for example, which we were looking at before, notice that I'm referencing something called a transform. Transform.position.x is less than -25. Destroy game object. If this is the coin, what do we think that this is accomplishing?
It goes off the screen, get rid of it.
Yep. So the transform, recall, was our object our component that encapsulates our rotation, scale, and position. So we can just say, if transform.position.x is less than -25, destroy game object, because we're spawning the coins dynamically when they get off screen, just like we did with the pipes, if you remember. And I had a screenshot actually in that slide that sort of showcased what that looked like. We can see that exact thing alive here. If I go to layouts 2x3 and we play the game again, and then I'll just die at some point, but if we do this, right, we're seeing our scene live. So we're following this. Yep, see how the coin, as soon as the building and the plane and the coins all get to this point, this is -25 in Unity units, not in pixels. Everything in Unity is based on Unity units, which by default 1 is equal to 1 meter, as opposed to, we've been thus far using just pixels, but pixels aren't viable in 3D. But that's effectively what that component does. It's checking in our update function, void update, if transform.position.x less than -25. And notice that we don't actually have to declare transform anywhere, which is interesting. That's because mono behavior by default gives you access to its game object's transform, just by default. That's just something you get for free. And then notice game object, we haven't declared game object anywhere, because by default we have access to game object. It's the game object that this script belongs to, that this component belongs to.
So that'll get this sort of thing.
This would be the actual. So the interesting thing about classes is you don't have to explicitly say this, because if you had like int my number equals 10, and you just say my number, the difference between like Lua and like C# and Java is that my number, it'll already know what my number is. This is my number. It'll know it's this object's. You don't have to do that. Sort of a nice little thing to save you a little bit of time. Yeah, because you could then just say my number plus equals 10. Another nice thing about C#, by the way, which we didn't get in Lua, you can do compound assignment operators. So you can do plus equals, minus equals, times equals. That's one of my pet peeves I have with. Oh, and notice that also the nice thing about the fact that I have OmniSharp, it'll underline, and this is just a trait of most IDEs, honestly. So you get this with a lot of places, but it'll tell you my number is not assigned, and with the underlining and also just by hovering over it. The name my number does not exist in the current context. But I can just say int my number, and then it's gone. A little bit more that we have to worry about, and a little bit less that we have to worry about, a little give and take. But still, I think overall, C# is going to be a lot more syntax heavy. You do have to worry about things like braces and semicolons and, putting everything in kind of like a boilerplate, and then obviously type declaration and return type declaration. It can be a little bit more than we've gotten used to so far, but it's honestly not too bad, just given that you can use IDEs. First of all, the fact that you're statically typing everything, you can detect a lot more errors in advance. If you're trying to do something with some type that you're not supposed to do, like some function accepts some object of some type, but you're passing in some other object, you'll catch that in advance. And so that's a really nice thing. But yeah, it's kind of it is a give and take. And also IDEs will give you, like I said, a lot of the functionality, a lot of the autocomplete that makes a lot of this more sustainable. And that's not to say, of course, that Lua and LÖVE2D don't have their own IDE. Like Zero Brain Studio is popular from what I understand. Haven't used it yet, but particularly when you venture into Java and C# and compiled languages, static languages, having those features, it does save you a lot more time, relatively speaking, than when you're in a dynamic language. So yeah, that's what mono behaviors are. Every component of our game effectively has, like the helicopter has its own script, a heli controller. The coin has its own script. The coin spawner, the skyscraper spawner, the skyscraper, they all have their own scripts that drive their game behavior, but they also have scripts and components that are part of Unity core as well, including colliders and triggers. So if I'm looking in Unity, so I'm going to go to and this will actually be the last thing we look at before we take a break, but if I'm in Unity and I'm going to go back to my default layout, just because it's a little cramped on a 720p, go to my helicopter. Helicopter's got a couple pieces to it, so let's actually go to where I can see it here. So one of the awesome things I love about Unity is it gives you a lot of this editor magic, this editor sort of sugar. It shows you visually where a lot of the things are in your game world. So the green rectangles, anybody know what those are or can guess? Yep, hitboxes, exactly. These are colliders. So the blades doesn't have a collider. That blades collider is actually separate. The box collider here is this collider right here. And so a collider is literally just something that collides with something else. And you can set it to be a trigger or not. If it's a trigger, then it actually won't trigger the on-trigger callback function that we've briefly saw earlier. So the things that you want to activate triggers, you should make those not triggers. And then triggers, all you have to do is just click this little trigger button. So what a trigger is just a region that you've determined or some object that you've determined should cause behavior when it gets triggered. So in this case, I've assigned, actually we could go to, I'll just play it. But the airplane's a trigger, has a trigger, right? Every building has every building, all of these things have colliders, whether they're triggers or not. The helicopter, its blades and its body, there are two colliders, two boxes. The coins all have colliders. The skyscrapers all have colliders, and the airplanes have colliders. The difference is that, oh, and by the way, another cool thing, it's easy to get very sidetracked just because there's so many cool things to talk about. You can pause the game while it's running. So it's paused right now, but it's in the exact state that I left it. So there's 3 coins there. I got my helicopter there. I can freely go about the scene. I can analyze things. I can actually modify this in real time, so I can change its rotation if I want to. Probably don't want to do that, but I could if I want to. I can change its position, right? So I can move it left or right like that. And then notice that I actually have just the body selected so that the blades are kind of separate. I don't even know what kind of crazy stuff would happen if I just like messed with this and just let it run. I haven't tested it that crazily, but you're allowed to step through. Oh, okay, it looks like they both just go. Yeah, oh yeah, because they're parented to the helicopter object, so they're both going to align. They're both going to move at the exact same rate, regardless of how far apart they are, the individual objects. But you can just step through your game's execution frame by frame and get a sense of if you're trying to pinpoint like a bug, maybe that's position-based or something that's kind of tricky and you just haven't been able to find exactly what's going on. You can look through you can look through your whole scene and all of the fields of every object in real time, not in real time, but in step time, just by stepping through this button here, assuming that you're in pause mode, and then just looking at all the components here on the right side. Because those will all still update. All these fields will update anytime you perform any changes in the actual scene. So super helpful for debugging. I know I've used it a bunch. And then if I start again, or if I stop it, the nice thing is any of the changes that you make while it's running to your object, they don't get applied when you actually go back to the game. So notice that I messed with the 2 pieces. I sort of separated them, and then I stopped the game. It ended up going right back to where it was in the very beginning. So all this gets just basically saved like a snapshot. You can do whatever you want during your game, and then come back to it, and it'll all get reverted back to where it was. Yeah?
So I was experimenting with Unity in single player, and I kept making changes while I had it paused, and then losing it, which drove me insane.
Oh, yes. So yeah, it basically echoed what I just said, which was if you make changes in your game while it's running, and you're trying to maybe tweak them such that it's perfect when you're actually done. They don't get saved. So you have to actually make a conscious effort to remember what you've done, how you've changed different fields to fix any bugs if they do exist. But it is, yeah, something that can be disheartening or frustrating if you finally fix something and then you forget what it is you changed and then you have to mess with it a whole bunch. So remember all the changes you make if they're pertinent to your actual game's execution and the debugging of your game. And then there's also a console as well, which is nice. If you want to sort of output things sort of like JavaScript style in the web, you can do console.log. You can do the same thing with a debug call here in Unity. I don't have any of those calls in the actual game, but it is something that we'll look at going forward. And it is something that can be very helpful if you want to measure something or output something that you can't necessarily look at in the inspector. In the case of this game, most of anything that we want to take a look at is visible in the inspector. But if you have an algorithm, maybe you have a generator that's not visual, maybe you're like a level generator and you want to like make sure that the data structure representing your level is generating things properly, you can output everything maybe via hash marks or something in your console and actually see it that way when you're running the code rather than having to run the actual game and look through it that way. Some things just are hard to model in the editor and still need console output. So the console's there to sort of help you. And so debug.log is the function, I believe, that you need to see all that stuff. Right, colliders and triggers. So we had a little bit of a tangent there, but the helicopter is comprised of these three things, but the blades collider should have ultimately been merged with the blades object here. But we can think of it as the blades and the body. The reason they're separated, well, there's two reasons they're separated. One is, one core reason they're separated is they're just different sizes. So the blades are longer than the body, and so we have, for that reason, two separate colliders. So we're looking at the helicopter here. We can see that the collider for the blades extends a little bit farther than the body. We don't want to create a box collider for the entire helicopter because a box collider that's like that goes out here, for example, might not be super fair if we're just coming right over a building and our body kind of maybe the building's right here and we just miss it. We don't want that to be collided with. So sometimes you'll need to combine colliders to accomplish the collision detection behavior you're looking at. The nice thing about box colliders, which we're using here, is that they're not very expensive because they're just boxes. It's easy to compute 3D box collision with other things that are 3D boxes. So, and that's actually sort of a topic in its own, is taking a complicated model or object and then breaking it down, not in terms of what it looks like to be collided with, but how you can simplify the collision detection of something like a character by just modeling its arms, its body, its legs as like cylinders or boxes rather than complicated geometry. You usually don't want to do pure geometry collision for anything because that gets really expensive. You want to try and aim for simple shapes to be your colliders, and Unity gives you a lot of simple shapes by default. If we look at, like for example, in our helicopter, if we wanted to add a component, which by the way you can easily do here, just in the component inspector. If you're looking at the bottom right, there's an add component button, so you can add any of the components that you've written and also all the components that Unity gives you by default. So if we look up like collider, we can see there's a lot of different colliders that Unity gives us for free. Polygon collider, mesh collider, box collider, capsule collider. I try and strive for boxes as much as I can. Spheres aren't bad. Spheres are usually fairly easy to calculate as well, but boxes are the easiest. Capsules are pretty easy too. A lot of players will be sort of capsule colliders because characters usually have rounded heads, so emulating the collision for their head with a capsule sort of makes more sense. And we'll look at that actually next week when we use a first-person component that we can get for free. The default collider for it is a capsule. So, but the blades blades and the body both have their own collider. They're not triggers, but if we look at our prefabs, which we'll take a look at what a prefab is shortly. A skyscraper has a box collider, which is a trigger, as we can see here. And the coin is a trigger, and the airplane is a trigger. So these things all trigger, they all accept other colliders that aren't triggers, and if it detects a collision with a collider that's not a trigger, it will call the onTriggerEnter function, which we saw is something that you can get with mono behavior. Yeah.
Could you have two bodies, like if you want to call a special function and two at the same time have the regular physics collisions? Or is there some easier way to do that?
Can you give me a specific example?
Well, if I want to have a pinball game or something, and I want to call a function when my ball hits something, but at the same time I still want it to bounce off of stuff.
Oh, yeah.
Is there any way to do that? Or?
So the question was, can I implement such that, like, for example, in a pinball game, if I have a ball that collides with something and causes a trigger to occur, but also have it bounce off of something, and you would do that with a rigid body. So you give it a rigid body. In this case, I actually gave a rigid body the helicopter because the original goal of mine was to have it be affected by gravity, but it turned out that I actually liked it a little bit better without gravity. So this rigid body isn't strictly necessary, but it has a gravity component that you can assign to it that will actually then calculate gravity and pull it down wherever you have a global gravity definition that that's in your Unity settings that will affect it that way. And so what you would do is you would give your ball a rigid body, and other things that you want it to bounce off of, those would also have sort of rigid bodies, and they could be static or kinematic or not, basically, which we talked about before. Kinematic can move but not affect but not be affected by other objects. And so the object that's a trigger, you still trigger code that does something. So your pinball machine, when it collides with something and it triggers that thing, it'll still trigger that code. So whether that's increment your score or cause something to flash, a particle to flash, or play a sound, it'll do that in your onTriggerEnter, but your rigid body will also perform its work and bounce off of whatever it, assuming that you don't destroy it with that onTriggerEnter function, it will bounce off of that surface and behave in the way that you are alluding to. Does that make sense? All right. Cool. So So all these things have triggers. The isTrigger flag. That's as easy as we need it to be. So we just give a box collider. And the nice thing about box collider too is if your mesh is a box or square or rectangular, it'll usually just fit it perfectly to whatever you're trying to assign it to. So in this case, I remember adding the box colliders for these skyscrapers. It just, because they're all rectangular or cubical, quadral. I don't know what's the rectangular 3D. I forget the term. What is it?
Rectangular prism.
Rectangular prism. Yes. Since they're all rectangular prisms, the box collider fits them. It'll scale the right way. When you have differently weird shaped objects, it'll just basically be as big as it needs to be to completely encapsulate it. But like I said before, because the helicopter has got some weird geometry, if we were to do that, it would by default just be this entire box here, because this is the farthest it goes out on this particular axis. So we want to combine meshes to produce the collision sort of behavior that we're looking for. And the TriggerEnter bit is relevant because if your game object is a trigger, right, then once we collide with that object, we want, and by default, when you do onTriggerEnter, it'll look for the collider on this object. It's going to take in a collider other, right? And what that is the other collider, the thing that's colliding with this object, with this coin, so the helicopter, because it's the only other object in our scene that has a non-trigger collider. OnTriggerEnter, this is going to be a helicopter. We can just say other.transform.parent, because our helicopter has children which have the actual colliders, and our parent has the helicopter controller component. We're going to get component at the heli controller. So we're going to go through that object that collided with us. We're going to get its transform parent. We're going to do get component, which is a function that will just look through all of its list of components. We specify which component we want using this identifier here, so of class heli controller, and these sort of angle brackets are like the generic, like the sort of generic type specifier syntax, which basically looks for it. You could pass in any type here effectively, and get component will look at whatever type is in here and get the component of that type specifically. So you do have some sort of type flexibility in C#, but you have to go kind of the extra mile and specify it and implement functions that take generic arguments like this, which is similar to Java and C++ and other languages that do it that way. And then once we've gotten that component of type helicontroller with this function call, we execute pickupCoin, which is a function that's part of the helicontroller. Any guesses as to what pickupCoin does? Sorry?
Increments the coin counter and calls the coin to disappear.
Increments the coin counter, calls the coin to disappear. Well, it actually doesn't call the coin to disappear because we do that here.
Oh, okay.
Destroy game object. Game object is going to be this coin that's executing this function. It does one more thing too. Do you remember what happens when we pick up a coin? Particle, exactly, the particle effect. It triggers a particle effect. We can go to the helicontroller class and take a look at that. Pick up coin. Here, coin total plus equals 1. Get component audio source play. So it's a little bit weird. So with audio source, you can have multiple audio files. So get components audio source is what we need to actually get the audio attached to this object. And then at index 0, because there's only going to be one audio source anyway, and then we just call play. So that'll play the coin sound. And then get component, because there's only going to be one particle system associated with this helicopter object. We're going to get the particle system object, and then we're just going to call play on that, which will actually trigger an emission one time of its particles. And so that's sort of in a nutshell what colliders and triggers are. It's a lot of syntax at once, just because Unity's kind of really big, but it's pretty simple. Just make sure that you give the right shapes to your objects, make the right things triggers that you want to cause behavior to happen when like non-trigger things touch them, and then implement on trigger enter with the behavior, the game logic that you need. In the case of the skyscraper, for example, if we look at the skyscraper, so I have a skyscraper component here, and then if I on trigger enter here, it effectively does the same thing that the airplane does, which is just go through the others, transform parent, game object, helicontroller, and then call explode. And so explode kind of is a similar thing to what pickupCoin does, in that it triggers a particle effect, but it also destroys the helicopter, and it tweaks the game over text to turn on at that point. So any questions as to how triggers work? Any of the syntax we've talked about thus far? I know that it's kind of a lot. It's kind of a fast tour, but moving right along. All right. And here's a screenshot I took just to illustrate the green lines, the box, and then the orange is the actual mesh of the helicopter. So we're going to take a break, and then when we get back, we're going to talk about prefabs and spawning them, and dive a little bit deeper into some of the other parts of the project. All right, welcome back to GD50 Lecture 8. This is Helicopter Game 3D. So before the break, we were talking about colliders and triggers, and also just getting our hands used to using mono behaviors and the editor and all sorts of things. But we haven't really taken a look at prefabs, which is a major part of this game. So the coins, the skyscrapers, the airplanes, those are all prefabricated assets that we have sort of gotten ready for spawning into our scene. And we're going to take a look at how that actually works. So here's a list of, in our editor view, all the different prefabs that we have. So we can see airplane, blades and body are prefabs, the coin, all the skyscrapers. There's 3 different kinds of skyscrapers, and then the helicopter. The helicopter itself we're not using as a prefab because I've already created it in the scene and it never gets instantiated dynamically, but we could easily make it so because I have created a prefab with the helicopter. So when we're looking at the scene here, we notice that we have just the helicopter and we have the background, but there's no skyscrapers, there's no coins, and there's no airplanes. What we do have are skyscraper spawner, the coin spawner, and the airplane spawner. And the 3 of those are just empty game objects, but they have associated with them these spawner scripts. And the spawner scripts we've written ourselves. And then once we've written them, we've just simply add component here and then chosen the appropriate spawner. And so what those do if we look in our code, actually, and we go, for example, to the airplane spawner, we have a start method, we have an update method. Notice that the update method doesn't do anything, paradoxically, because, I mean, the airplane spawner is running over time. We are spawning airplanes over time. But the way that we do things over time, sort of asynchronously in Unity, is a little bit different than anything that we've done so far. So this start method here, we see that we're calling this function called start coroutine. And that function takes in a function called spawn airplanes. And so at a high level, a coroutine is effectively a function that yields control every time it's called. So it'll run, and then rather than go through its entire body of code and then end or return some value and have that just be the end of it, it'll actually yield when you use the keyword yield. And depending on what you've done with that yield, it'll pause for some length of time or do something for some length of time rather than end that function call. So this spawn airplanes function here, notice that it has a while true. And so while true is not usually something that you want in a game because that's just going to lock your game forever. But in the case of a coroutine is going to run, but then it's going to yield control back to whatever called it for some length of time, or depending on how we've programmed it. In this case, you can see here, yield return new wait for seconds, random.range 310. Does anybody have an idea of what that does? Yeah.
Well, I mean, it presumably just waits between 3 and 10 seconds and then continues.
It does.
Okay.
It yields for 3 to 10 seconds and then continues its execution. That's exactly right. Did you have a question?
Well, I was just thinking, why do you have 3 different skyscraper setups? Couldn't you just have one skyscraper and assign the skin randomly?
You could do that, yeah. I guess for the sake of demonstrating prefabs, and also it's a little bit more complicated to get into like dynamic material setting and like changing materials in code. But yeah, you could effectively just create 3 separate skyscraper, or one skyscraper with one like base color, and then dynamically change its material, but also to illustrate having multiple different prefabs assigned to an object that you can then choose at random to generate in the game scene. They might not necessarily be skyscrapers that'll have the exact same color. It could be like a goblin or a orc or a troll or something, and they're all different prefabs that we've created, but you can put them in a list and then dynamically choose which one we want at random. So a few different reasons, but yeah, in a situation where everything is just effectively differentiated by a single color and a material change, you could dynamically swap that as needed. So this coroutine that we've started, this function that effectively can pause itself, even though it's being called infinitely, it's being called, this while true is in play. It yields control with this yield keyword, and what it does is it allows us to call something over and over again, but then pause for some length of time, right? We don't have to maintain a counter for spawn time in here, which we could do. We could do like float spawn time equals 0, right? And then float spawn increment equals like 1,000, and then while spawn time is less than spawn increment, or we could say in update if spawn increment, or we would do spawn time plus equals time.delta time first to get the length of time that's passed since the last frame, and then we would say if spawn time is greater than spawn increment, instantiate a new skyscraper or airplane, sorry, and then set spawn increment or spawn time back to 0, and then just rinse and repeat this over and over again. But coroutines take out this need, much like timer did, for having anything that you keep track of with a specific timer. You can do a whole bunch of different things with coroutines. One of them, in this case that we're doing, is just pausing for some length of time to do something. In this case, we want to wait for some time in between each call to or in between each instantiation of an airplane. So we'll just yield control back to our game because we want to break out of this while true, but we don't want to break out of it and completely break out of this function. We want this to keep going over and over again. So we see here this instantiate function is sort of where the actual instantiation happens. And instantiate takes in a prefab, so a game object. So in this case, we have a prefabs list here, game object, public game object array called prefabs. So this can take in any number of prefabs that we want it to. We're going to return a range between 0 and length. And then also, we want it to spawn, we give it a position that we want to spawn in. So instantiate, it takes in an object, it takes in a position, and it takes in a rotation. In this case, we want to give it this position. So it's a vector 3, gets an x, y, and a z. At 26, so off the right edge of the screen, 7 to 10, so kind of like within a range of verticality up towards the top. And then at 11 on the z-axis, which is aligned with our helicopter and the skyscrapers. And then this quaternion.Euler is so 3D rotation is, the math behind it is pretty complex, and I don't know it well at all. But quaternion.Euler allows us to think in degrees and actually perform a 3D rotation on something fairly easily. So if you want to rotate something in 3D, quaternion.Euler, negative 90 degrees on the, I believe it's z, x, y. In this case, the way that the default rotation of the airplane is, we want to set it to negative 90, 0. You could also set up your prefab in a way such that you don't need to pass this in. You could do quaternion.identity in that case. But this is just to illustrate how, if you want to rotate something in code, how you would do it. So quaternion.Euler is the way that you rotate something in 3D. And so instantiate, global function that you can call anywhere you want to, as long as you just give it a actual object or prefab that it knows how to instantiate. And then wait for seconds, another global object, which is a asynchronous object that will allow us to yield for this length of time. We pass in the length of time here. It takes it in seconds, because wait for seconds. And then as soon as this length of time has passed, it's going to come back up here into this while true instruction and then instantiate again. We don't have to keep track of a timer or anything, any weird boilerplate. We just have to call start coroutine here. And notice that we explicitly have to call start coroutine in order to trigger a coroutine function. And to do that, it returns what's called an I enumerator. And so a lot of these details you don't need to necessarily know the low-level details of. I certainly don't know all the low-level details of everything that happens in Unity. But just know if you want asynchronous behavior, your function needs to return an I enumerator, which C# knows is an asynchronous. It's not asynchronous. It's a generator function, which will yield control at predetermined times, and it will manage it for you. And to trigger it, you need to start coroutine, which is a function that Unity has defined for you. So any questions sort of as to how this works at a high level at least?
I'm a little confused, syntax for yield. Is the yield return?
Yeah, so it's a yield takes in something and you get a new, to instantiate a new wait for second, you have to, it's just the way that the syntax is for yielding an object. Yield, it's returning this to the yield instruction, and the yield instruction is then yielding that. So it is a little bit weird though. But you only really have to, this is a common pattern that you'll see, and so you'll just get used to it. So, and honestly, this is probably one of the more syntactically difficult things about Unity. So I mean, as soon as you understand this, pretty much anything else is fairly easy at that point. I would say this is one of the weirder sides of, because I mean, in Lua and LÖVE 2D and those kinds of environments, it's a little bit easier to do that sort of thing with as much syntax. C# being a statically typed environment, to get the same behavior, kind of have to go a little bit further, do things their way. But that's getting asynchronous behavior to work in C# and in Unity. Typically, in order to avoid sort of messy state management, you will use coroutines, which are I enumerators, often with the wait for seconds object, and just make sure to trigger them with start coroutine, and then call that function as if it were an object, just like that. And the behavior for the airplane spawner, the coin spawner, and so forth, they're all fairly similar. So start coroutine, spawn coins, and then while true, so coins, this row is just, it spawns a random number of coins vertically. So you can have one, or you can maybe have a couple. And then for each of those, instantiate them at a random position on the y-axis here, random -10 to 10. In this case, quaternion.identity, because we don't want to rotate them any differently than they already are, which I alluded to before.
What is that?
So quaternion.identity just means no rotation applied to the object. So whatever its base rotation is as a prefab. So it'll be whatever it is when you see it in the editor, and when you create a new one, that's going to be its default rotation. So basically, the equivalent of don't rotate this by anything. And then same as we saw before, yields a new wait for seconds, in this case 1 to 5. So a little bit more frequently than the airplane on average, more coins. As the airplane, I believe, was 1 to 10 or 3 to 10, so every 3 to 10 seconds. And that's basically that. And then we start coroutine just like we did before with the airplane spawner. And then lastly, the skyscraper spawner. In this case, we only have one coin prefab, we only have one airplane prefab, but we have 3 skyscraper prefabs. And so the actual random.range here comes into play because that's how we get, the different color skyscrapers spawning at random. And like I said before, this can be extrapolated to whatever sort of game environment you want, where you have multiple types of objects that are more complicated than just a color swap. And you want to choose them at random. We're doing all the same things that we did before. And also, here we can see that they have a random chance, 1 in 4, so a 25% chance of increasing the speed. So skyscraper spawner actually has, and this is relevant to the assignment, skyscraper spawner has a float called speed here, which is by default 10. And this drives the speed, the scroll speed of the skyscrapers, the coins, and the airplanes. And so when we call it static, do we know what that means? Yeah?
Well, it's the same for all objects.
Yes. So no matter how many skyscraper spawners we create, only one, they're all going to share this field, speed, and it's always going to be equal to the same amount across all instances. So static means that it's part of the class. It belongs to the skyscraper spawner class. It does not belong to a skyscraper spawner object. And so we don't ever really want to change that ourselves in this game. But the airplane, for example, notice that in our update function here, if the transform.position.x is less than -25, we should destroy the airplane. So when it goes off screen, we should destroy it. But if not, then we want to translate this object on the x-axis by negative skyscraper spawner.speed times 2 times time.delta time. So we're translating it on the x-axis, and we're using the skyscraper spawner.speed as our core multiplier. And then if we do this, if we look at coin, same thing. Every coin, and notice that, or I should ask, what is one sort of design consideration if we're looking at this, all these components, and let's say we're trying to get as sort of decoupled as we can and well engineered as we can, what's a consideration that we can noticing that, for example, this exists in coin and this exists in airplane.
What's the question?
So how could we better engineer this? Notice that we have, and taking into consideration this component model in Unity, what could we do with, for example, this?
Would that maybe be better in coin spawner for us?
Well, I'm thinking that because the airplane and the coin, well, first of all, it wouldn't belong in the spawner because the spawner's job is just to spawn coins. But the coins and the airplanes, they have their behavior, right? They have their update behavior. But they're all doing kind of the same thing, which is scrolling to the left and then despawning at -25. So a design consideration here would be maybe we have a scroll component, right? We could set like a scroll and destroy component, or just a scroll component with an optional destroy flag. And then we just put this on anything that we want to automatically scroll to the left screen and despawn, rather than having to code this in every single class. So if you're ever looking through your code and you're seeing, for example, this and this being the exact same, especially in Unity, because of the way how flexible components are, try and think about how you can make it into its own component. So
where would you put the coins?
you make it yourself. So if we went into here, into our scripts thing, and just made a new script, and then we called it like scrollable, and then we double click it, it'll open up in our editor that we've chosen in our preferences. By default, it's going to be Visual Studio with the newer versions. But now we have a new scrollable behavior. And then all we need to do, we would say if dot, oops, not that. If transform dot, once again, I can't type, transform dot position dot x is less than -25, destroy game object, right? And so this is the exact same thing as all that behavior that we saw before. So now we can take all of that out of coin. We can take this out, and we can take this out here, and then just add to the airplane and to the coin prefabs. We just add this new scrollable prefab, and then it'll take care of that for us. Yeah.
How would you add
So if we're going back to Unity, so the question is how would you add the prefab? Or how would you add the component to the prefab? So in our prefabs, note that we have airplane, we have coin, and we have all the skyscrapers. So these are all prefabs. Oh, and I haven't actually detailed how to create a prefab, which I apologize for. So a prefab, all you need to do is create an object in your scene. For example, I did it with this helicopter, so I'm going to delete the helicopter. Because this is just a helicopter prefab, it's not going to actually delete the helicopter from our scene. But if I take this helicopter here, and then I drag it in here, notice that now we have a prefab here. So this is, it's going to be, we could take this helicopter out and just add a new one, like right there. So now I have 2 helicopters. So that's all a prefab is. It's just something that you've made in your scene that you want to replicate or duplicate in the future, ideally through code. And notice it's showing here in our sort of hierarchy view, but obviously you don't want that. But that's how you create a prefab, is you find something that you've sort of configured in your game scene, and then in your code you're allowed to then instantiate that prefab, assuming that you've made that prefab a member of whatever you want, whatever class instantiates it. So in this case, the airplane spawner. So notice that we call instantiate here, like we saw before on line 24. But it's looking at prefabs. This sort of, it's a list, and it's looking at a random range between 0 and the length of the prefabs. You have to declare public game object list prefabs here. And then once we do that, and we go to our airplane spawner here, notice that we have this prefabs list here. So we actually get a editor view of that code, that data structure, and we can just add prefabs that we want to. And if we change the size to 2, then we can add a second prefab. Or if we make the size 10, then we can put 10 different airplanes there. But we only have 1 airplane that I modeled, so I'm just going to make it 1. But this is the same thing. This game object list is that same list, only that's the view we have of it in the editor, and it's the same. It's just like a different way of looking at the data. And that's sort of the nice thing about Unity, is that you can, if you make any of your fields public like this, like public, if I did public int like some number, right? And I save that, and I go back here, my airplane spawner should get some number right here. And then I can just set some number to whatever I want. It doesn't do anything right now because some number doesn't affect the script. But this is a nice way to take the burden from you out of the code, and like you're not experimenting with code. You're not tweaking some variable in your script, some number 10, run it. Okay, some number 12, run it. You can just assign it here in your actual editor view, and then just tweak it as you want. So I just scroll through it. I can start the game, and I can pause the game.
It shows up there if you just if you make it public?
You have to make it public, exactly.
Public, and then it shows up.
Yep. And so I can just do this, and then I should be able to, I can just change this now if I wanted to like 67. And so if that actually had some sort of effect on my game world, if my game relied on that number being meaningful, this would update the scene. And so you can make whatever, you can debug this way, or you can customize your components more this way, but it's just a tremendous amount of flexibility. And so that's how we're instantiating this sort of from this list of prefabs. It's a list of game objects. We've made it explicit to Unity. The editor's going to know, okay, these are game objects, and so prefabs are game objects. So we can just put any of these into this field here, this element 0 field, or however many fields we have, and it'll in the code randomly choose one of those and then instantiate it. So any questions as to how prefabs work or instantiation or anything like that? Okay.
So each prefab has a unique number or not?
Does each prefab have a unique number? Not a unique number. They just are all assets in your folder here. They have some kind of identifier to Unity that's hidden from you. It might be visible from you if you look. They might have some sort of generated ID or something like that, so that it knows underneath the scenes. But it's not something that you worry about in your actual code. You just tell, like, we've created a list here that's just, it'll expect some number. It doesn't know how many. And then in the editor, you can actually tell it how many via the, because every list that you assign to, that you make visible in the editor will have this size field. And that's just part of the editor's abstraction. The editor has abstractions for a lot of different objects. You can create a lot of different objects in your mono behaviors and make them public, and Unity will have a different view for them. Things like color pickers and stuff like that. Like if you actually, I don't know the exact object offhand, but if you make a public color picker in your mono behavior or something like that, you'll actually get a color picker here that you can choose a color for, which is pretty awesome. And there's a lot of different like customized views. Like all of these, like the I think actually the directional light might be an example. See this color here? Like this is somewhere in code. Like there's a public color something. And then in the editor, when you're actually editing it, you can choose the color, and Unity gives you the option to like make it whatever you want. And notice it's actually affecting the background there. So this is like one of the really big strengths of Unity, and a reason to really make your components customizable is this sort of one-to-one mapping between your data, your code, and your editor view of the code, of the data. Take the burden away from you programming it, which you're more prone to make mistakes too. And also waste a lot of time, and then just be able to modify, like how much faster is for me to just say I want this red color rather than like color.r equals something and then color.g equals something, color.b equals something, and then assign it that way. So I mean that's just a simple example to illustrate it, but there's a tremendous amount of potential involved in making your components customizable. And so that's what I did here. Because I wanted the airplane spawner, or the specifically the skyscraper spawner, to spawn one of not just one skyscraper, but several skyscrapers, I created this public prefabs list that I can then populate from Unity here and say, okay, this object, and this object. Put that into the skyscraper spawner here, these slots, and then my code knows to instantiate it, randomly picking one of those.
In your example earlier about, so how would you actually go about making something scrollable now that you made that component? So you just like add a component to the coin.
How would you go about making something scrollable now that you've...
So you declare that scrollable class, right?
Oh, yeah. So I have a scrollable script here. So it's the... do you mean the infinite scrolling background or the scrollable object?
The one where you define it as being destroyed when it's going.
Oh, yeah. So in order to do that, so we've made the scrollable script here. So you would just go to, in this case, since we're instantiating all of the coins and skyscrapers and airplanes as prefabs, you actually edit the prefab itself. So I'd go to this coin prefab, I'd add component here at the bottom, and I would just add scrollable there, which is a script. And you can tell it's yours because it says script there. Just like coin here is a script and rotate script is a script. That's actually an old script that I didn't use anymore because in the coin, I just made it part of the coin itself. But this is another part of what makes the coin class, by the way, is this transform.rotate, x, y, and z in worlds in the different space, either relative to itself or to the world space. In this case, it chose the world space, because I want it to rotate on the world's y-axis. But if you rotate an object, its own x, y, z are like still exist. And so you can have something rotate about its own x, y, and z, regardless of its rotation in the world. And so I want the coin to always rotate. So 5 degrees on the y-axis here. So this is another part that you could take and make it its own script, just a rotatable script, auto-rotate script, and then just make these public fields like public x, public y, public z, and then you could change those in the editor, and then like actually make your different objects, customize your objects without having to go into the code itself.
So you don't have to do any collision detection yourself. You just click a button and then type in the collide function.
Yeah, you don't have to do any of the collision yourself because Unity comes with a 3D physics engine. The actual, I mean, you have to tell it what to do when the collisions happen, but you don't have to actually code, you don't have to do the 3D physics engine yourself, which is a tremendous amount of work. One of the big selling points definitely for doing any 3D things in Unity. I mean, a lot of engines now have 3D engines for free. I mean, there was a time when it was less prevalent.
How would you know what you collided with?
Because there's a collider that it gets. So in the, if we're looking at the, where is it again? It's in like the skyscraper, for example. So every skyscraper, when it collides with something, this on trigger enter gets passed in this collider other, and so that's going to be the object that that you collided with. And so you can get an object, you can assign a name to an object and then get its name as well in code if you needed to do that. And you can also just get, in this case, we wanted to know whether it's the helicopter or not, so we got the heli controller from it. But in our game, it's kind of a special case because there's only one type of object that has a collider that's a non-trigger, and that's the helicopter. So we can assume that this exists when we do get a collision, but otherwise we'd probably want to say get component of heli controller and then test it for equal to null. And if it's equal to null, then we want to like not do something because then that'll cause us to, if we tried to call explode on a null object, that's going to be a null pointer exception, and then you're going to crash your game. So. But in this case, we're guaranteed for that not to happen because, like I said, the only collider that can collide with this that's not a trigger is the helicopter object. So, does that make sense?
Sounds like a physics problem, the explode null.
Oh, yeah. Yeah, that's all too real. In this case, though, all explode is thankfully just destroy game object and then start a particle effect. So. Any more questions as to how like instantiation, prefabs, using the Unity editor, interacting with your mono behaviors, public variables? Yeah.
So the process is you first enter the data in the editor, and then your code, and then it runs the code to load the data, or can you also define the data in the editor?
You cannot define, so the question is, do you first create the data in the editor and then the code, and then tie them together that way? In order to get a new component, you will have to create the class first, the mono behavior that you want, and give it the public fields that it needs for the editor to actually read. So the editor reads your script, looks through all the public fields, and then will create the necessary GUI elements in the editor to interact with the code. But this needs to exist. All this code needs to exist. Anything that has these public variables that you want accessible in the editor needs to exist in code first. And then you have the power to use it in the editor. And then it's customizable at that point. Any more questions? All right. So that's the prefabs. So we looked at texture scrolling before. And we're going to go kind of quickly through this. But all texture scrolling was, if we recall, was I have a scrolling background class here. It's got a scroll speed. So if we wanted to, we could, since it's public, we can edit it in the editor and make it faster or slower. But we maintain a reference to our renderer. Every object has a renderer, a mesh renderer, typically for 3D objects. And the renderer has a material associated with it. Everything in Unity has a material. And so every material, a material doesn't necessarily have a texture, but in this case, our background does have a texture. And it's going to be called main text by default. That's like the main sort of texture if we want to assign a texture to see visually on a material. So material can just be a color. Often, but it can also be a color and also a texture. So in this case, the background is a texture. It does have a texture assigned to it, and notice that if we go to the background, and then here is where we actually create. So this is a material here. It's got a shader. So we're not going to talk too much about what shaders are. We've talked about them briefly. In Unity, they're quite a bit more. You can go quite a bit farther with them. Well, technically speaking, I guess you could go equally far with LÖVE 2D, 2D shaders and 3D shaders, at least in vertex and fragment shaders. But for all intents and purposes, we're not going to go into detail on shaders today, but they're very similar. In this case, every material has a shader in Unity in order for it to render, because anything that renders needs to be shaded in Unity. But notice that here we have a texture. So this is that main texture thing that we saw before, and then this is the bump map here. We don't have a bump map because our texture isn't bumpy. It doesn't have any like contour or like detail or anything like that. But you can just select a texture here. So I could give it that texture if I wanted to, or like I have another couple textures here. This texture here. It doesn't matter which texture you choose, but you can choose a texture, and then that material will then it'll calculate based on the mesh how to draw that texture best to it. And you can set every material's texture offset via its set texture offset function on the x and the y axis, and that'll shift it just like we did, just like effectively accomplishing what a scrolling background needs. It'll draw it, and then it'll basically wrap around to the other side. So that's how we get the infinite scrolling texture. We just set its texture offset. We specifically call set texture offset on the main texture, and then we pass in a vector 2, so just two numbers, offset and 0, because we don't want to touch the y-axis. So 0, and then offset is just some value that increases over time. And then time.time, recall, time since the beginning of the game has started, time.delta time, time since the last frame. And so we can just do a one calculation in here and update every time, and then multiply it times scroll speed to get the scroll amount that we want here. And I've set it to 0.1 just for kind of a semi-slow effect. But in the editor, if we look at our scrolling background, which is here, and then I've made it public, so I could just easily make this like 1. And I don't know how fast that's going to be, but 10 times faster, so probably pretty fast. Yep. So it's hauling. But yeah, all it is just shifting how it maps the texture onto the 3D surface. And this 3D surface, to be clear, is just a plane. So just a plane. And notice that it doesn't get rendered from the back. So anything that's just just a polygon has one side that gets shaded and one side that does not get shaded. So if you see invisibility on one side and not invisibility on one side, that's not a bug. That's a feature. That's the texture scrolling side of things. Anybody have any questions as to how sort of that works? We won't really need it for much going forward. It's not part of the assignment, but it ties in to what we've done before. So that would be interesting to cover. Last thing we'll look at is audio. Audio is pretty easy. All you need in Unity to do audio is an audio source and an audio listener. So a source plays audio. So like if James, if you were an audio source, I'd be an audio listener, and I'm listening for audio and playing it back to the speakers when I hear any sort of source of audio in the game world. So you can have infinite audio sources, but ideally one audio listener, and it's usually whatever main camera that you're drawing with. And then sounds in Unity can be either 2D or 3D. In this case, all the sounds that I've put into this game are 2D, and that's just the spatial blend here. Notice that there's a 2D to 3D sort of slide, and so that'll calculate based on where the sound is, how it sounds in the game space, and based on how far away it is, and like what side of view it is. And so the main camera has the audio source for the music, and so it just starts the music right away. So play on. Notice that we didn't have to code any of this. I just attached an audio source to the camera, and then there's a play on awake checkbox and a loop checkbox. So normally we've done like at the start of our game code, set looping to true, and then play the source. In this case, we'd have to do none of those things. This is just given to us by Unity by default.
So you put the audio on a camera?
Yep.
You could put it on anything?
You can put it on anything you want to.
The sound is relative to that object?
The sound is relative to that object, yeah. And that's audio. It's pretty simple. It's an art form when it comes to how you want to position things in your game world and how you want them to sound and whatnot. And you can get more complicated with it. But that's how you would do basic 2D, in this case, audio. But you could easily also do 3D audio just by making this set to 0 from 0 to 1. And you can make it more or less 3D too. Like if it's not all the way to 1, it'll somewhat be 2D. So you'll hear some of it no matter what, and some of it will be 3D. And then setting it to 1, it'll be purely 3D. So if it gets far enough away, you won't hear it at all. The explosion sound as well gets triggered. And so this happens in the, I forget exactly offhand where it gets triggered. So it's in the, I believe it's in the helicopter explode function. Oh, yes. I created an object with the explosion. I created an object in the scene that has an audio source for the explosion sound. And because I made this public, I can just put it on this object. And so there's a reference to that audio source at all times. And so I trigger explosion sound.play whenever we call this explode method on the heli controller. For the reason that I didn't put it on this object because we destroy this object as soon as we get into a collision. And so I didn't want to put the sort of explosion sound audio source on this object because it would get destroyed and it would not play audio effectively as soon as we destroy it. So we have to have it somewhere else on the scene. I could have also just like made the object invisible, but I didn't. I destroyed it. And so yeah, that's this explosion sound object, which if we look at the helicopter in the heli controller, which is all the way down here, notice that it gets in a explosion particles. It has a reference to an explosion particle system and an explosion sound, and we just have to click and drag the object effectively from here to pair the two of them. And then the script that this is referring to will always have a reference to those, as long as these are set to something. And notice that we also have coin total we made public, so I guess I could experiment with it. And then speed, we made this public so that you could make the helicopter faster if you wanted to or slower. And so you'll find it often useful to make a lot of these fields public just for you to experiment with. And then there's no really harm in doing so because folks aren't going to be able to actually see this in the editor when they download your game. So make as much public as you want for debugging purposes and just have fun with it. But that's audio. Audio sources produce the sound. Audio listeners listen to the sound and actually make it go through your computer speakers or whatever your default audio system is. And here's just a showcase of the two on the camera. And that's audio. So any questions as to like how the audio works at all? All right, couple last things before we close out here. So the asset store is probably one of the biggest things about Unity that kind of sells it. So oftentimes it's a lot easier just to get something, whether it's a library if you're programming or something else, get something that's implemented for you so that you don't have to implement it yourself. In this case, there's an RPG systems for rapid development, something visual scripting system, sort of similar to Unreal. There's a ton of things in the asset store, models, scripts, audio, editor toolkits, a lot of cool things. A lot of it's free if you want to experiment. So like a lot of the assets that I got to mess with in this game here are free, like the coin and some of the other stuff that's bundled with it. There's a lot of really cool things and really cool systems to help you for like 10 or 20 bucks. You can spend a little bit of money and then get like 25% of your game done like right away, and then you can actually get closer to shipping it. So it's I think it's hugely valuable to be looking at the asset store and thinking about how you can save your time that way if you're trying to actually ship a game and get to market. So definitely look through the asset store, see if there's anything that will make your life easier when it comes to developing games, because I know that I've used it several times and I rarely regret doing so. So assignment 8 is going to be pretty simple. So we looked at, for the second part, there's a bug in the game where if you die over and over again, the scroll speed never resets. So it'll just keep being faster and faster and faster and faster forever. But it's a one-line fix, and I want you guys to find where to fix it, given that we know, given what we've seen today. And there's a hint here about static variables. So it'll also be detailed in the spec as well. But this is an easy part. This part's fairly easy too, because all it really is taking the kind of the same stuff we've looked at, the coin generator and coins, and then making gems that spawn instead. Or not instead, but in addition to the coins at a rarer rate. And these gems should be worth 5 coins. And so when you collide with the gems, just add 5 to the coin total. If you collide with a coin, add 1 to the coin total. And that's basically it for assignment 8. So next time, we're going to dive into first-person games in Unity. So we'll look at some of the features that we get for free. We're going to implement kind of a simple maze-like game where you can navigate and it'll be dark and kind of scary, similar to a game called Dread Halls, which is a mobile VR game. And we'll actually test out Unity's VR and try and get a VR headset in here so people can check that out. Cool. Thanks a lot. I'll see you guys next time. All right, welcome to Lecture 9 of GD50. Today's topic is Dread Halls. So last week we ventured into Unity, our first foray into 3D, and not only 3D, but also just getting our hands around, our heads and hands around the Unity game engine, which is, among Unreal and others, sort of the most popular game engines in use for 2D and 3D games. And last week we did sort of a 2.5D style helicopter game whereby everything was in 3D, but we were still aligning things based on just 2 axes, the X and the Y, I believe, possibly the Z and the Y, I don't remember, but 2 axes versus 3 axes. Today we'll actually be diving into using all 3 axes available to us in Unity 3D in the context of a game called Dread Halls. And so what Dread Halls is a it was a VR game, actually the first VR game that I ever played on the Oculus, the Gear VR, Samsung Gear VR. And it pits you in sort of this dark and eerie 3D maze where you don't really know what's going on, and you can go around and get collectibles and encounter creatures and stuff, as you can see in the bottom right screenshot there. Today's example is going to be a little simpler, but it allows us to explore things like procedural maze generation and first-person camera controls. So last week, recall, we were using sort of a third-person camera, whereby we were sort of far back on the scene. Today, we'll actually be using a first-person camera, where the camera is effectively our eyes, as if we were walking around in the maze ourselves. Unfortunately, we won't be using a VR demonstration this week, but next week I hope to put together sort of a VR sampling using this project so we can see how this works in VR and how Unity's toolkit works in VR. So some of the topics we'll be covering today. We'll be talking about texturing. So recall last week, the helicopter and all of the items in our game were just sort of flat colors. They didn't really have any textures associated with them. We'll talk about how to assign textures to materials and how to apply those materials to objects in our scene. We'll talk about materials and lighting. So not only materials, but also the different kinds of lights that Unity supports and a few details about those. We'll talk about, again, 3D maze generation. So we'll have a simple but effective algorithm for creating a 3D data structure to represent our level, as opposed to previously where we had just a tile map that we could generate to give us the appearance of walking around in some sort of 2D world. Now we'll actually perform a similar operation on data, a 2D array, but we'll take that array and we'll actually create 3D blocks and create a maze that we can walk through in 3D space, which is kind of fun and interesting. Last week we only had 1 scene in our game, which was just a play scene, and even though we had sort of like a game over state within that scene, we didn't transition between scenes, we just sort of reloaded the same scene. Today we'll have a title screen and a play scene, which sort of is an evolution of the idea that we had in LÖVE 2D, where we had a state machine that was governing our entire game in terms of the different states that we could be in, whether it was the title, the game over, the play state, and so forth. Unity does the same thing with scene objects, which are effectively a snapshot of a series of game objects aligned in a particular way in the editor. We'll talk about fog and also global lighting and certain other things that allow us to create an atmosphere conducive to the sort of feel that we want to get in our game today, which is sort of creepy and eerie. And lastly, when we talk about how to create UI elements in the game, we'll talk about Unity 2D, its canvas object, and text labels and some other things, and how those all operate, which is sort of 2 sides of the same coin. Unity 3D also comes bundled with Unity 2D, a set of tools used to make not only 2D games, but also 2D interfaces that you can apply to your 3D games.
So first, a demo. Now, I've been sick for the last week, so I'm not going to ask for anybody to come up and demo just because I don't want to get anybody else sick. So I'm going to just go ahead and show just this lecture, the game that I put together for you. So here I have two scenes. Notice here I have a title scene and a play scene. I'm in the Unity editor right now. I'm going to load up the title scene here, which I've done. And then notice that it has sort of a game view and a scene view. I'm going to hit play. I'm going to make sure that it's set to maximize, which it is. And so we have sound here, so we should hear audio. I'm going to hit play. And notice that we have sort of like this ambient, creepy music track playing. We have a we could have easily done this in LÖVE 2D. This is just black screen with two text labels on it. And this is done with Unity's 2D UI toolkit. And so it tells us to press enter. So if I press enter, we instantly get teleported into kind of like this maze, this creepy looking maze. And so I can walk around in this maze, and there are a few things going on. So can anybody tell me some of the things they notice about this scene? What jumps out at them? What are some of the elements, if you were to put this together yourself, where would you start? What are the pieces that we can put together here? Yes. Yep, there has to be a ground that you can stand on, and there is. So we're generating not only walls in our scene, of course, but we need a ground to sit on. And also, if you look up top, it's kind of difficult to tell, but we also have a ceiling. So ground and a ceiling and walls. Some kind of lighting, yes. And so in this case, we're actually using ambient world lighting as opposed to having a light source. So we'll take a look at that. In last week's lecture, we used, or 2 weeks prior's lecture, we used a directional light object. But in this case, we have no lights in the scene. We're actually using Unity's world lighting, which we'll take a look at soon. When we walk around, notice that I can move where my camera's looking with my mouse. So we're actually controlling the camera with a first-person controller, an FPS controller, which is actually a component that Unity provides to you. And then notice, eventually, if we keep exploring the maze, we come across this little thing here, which is a sort of a pickup. And when we pick this up, we get sort of like this piano, weird, creepy piano sound, and then the scene reloads. Does anybody notice anything about what we see in the distance, like how that's affected? Like if I'm looking at this wall right here, for example, it's kind of hard to tell, but as opposed to like down this hallway, what's the difference there?
The light source is further away, I guess?
The light source is further away, kind of. So what we're experiencing here, what we're seeing is it's a graphics sort of concept called fog. And so what fog lets you do is it effectively adds color to the scene based upon how far away the objects are in the scene. It multiplies color onto them, and it gives you the illusion of looking as if you're surrounded by fog, basically. And it's been around for a very long time, back even as far as the N64 days, and we'll talk about that later today. And it's actually incredibly easy to add that into a game with Unity and its world lighting system. Any idea as to how fog, not only in terms of aesthetics, but how it could maybe help with performance? Yeah.
You don't need as much pixel clarity because it's already blurry.
You don't need as much pixel clarity. Kind of. The big thing about fog and the way that it was used a long time ago is that because eventually things are completely opaque beyond a certain point, you don't need far draw distance in your game. So you can actually like dynamically, you can omit rendering things that are a certain distance away because you wouldn't be able to see them anyway. And so this was an optimization technique used a lot back when draw distance was a huge bottleneck on computers and video game consoles back in like the 90s, for example. Like Silent Hill, the game for PS1, was almost exclusively fog, and you could see very little in front of you, and we'll see a screenshot of that later. And they use that to boost their performance and also to provide a certain aesthetic. And then one other thing you might be paying attention to is there's a sound on loop, just sort of this creepy sort of whispering sound, and that's to just add atmosphere, right? Just because without it, we would, little things like that, especially in horror games like this, the atmosphere can be everything. So with very simple ideas, fog, some whispers, first-person controller, sort of tight hallways, you can produce something that's pretty scary. Now, there are a few things missing from this. Namely, there's nothing that's going to come at you and attack you. But it would be not terribly difficult to add, but because we're using procedural generation, you would need what's called a nav mesh, and you would need to generate that procedurally so that things could follow you in 3D space. We might have some time to talk about how to do that a little bit later today, but that's not implemented in this particular lecture. But it would be not too infeasible to accomplish. But those are some of the pieces that we'll take a look at today. This is the title scene. Notice that there's not a whole lot here, actually. So if I zoom back out, we can see, canvases are huge in Unity just because it's more optimized for the engine to render them that way. But we can see, even though it's a 2D sort of UI, it's very visible in 3D space. And if we click this button here, we end up getting, oh no, that just brings us into, sorry, click this button here. That brings us into sort of the 2D, Unity 2D mode. So now we're interacting with things in 2D, and I can actually click on this label and move it around in 2D as if we were using a 2D game engine as opposed to a 3D game engine. So we'll look at that a little bit later. This is just the title scene. So the play scene itself, I'm not going to save that. The play scene itself, I'm going to go from 2D back to 3D here, is pretty much empty. So we have a first-person controller here. This is the FPS controller object. Does anybody tell what basically constitutes an FPS controller just by looking at the scene here? What are some of the pieces that jump out at you?
I thought you just put the camera right where the player is, or right in front of the player.
Exactly. You put the camera right where the player is, effectively where their head should be relative to where their body is. And their body, what's constituting their body here? Can you tell?
It could just be a cube. It looks like a cube in the middle there.
It's actually this capsule right here. I don't know if you can see it. There's this capsule here, this green capsule. It's a little bit more organic feeling than a cube necessarily, but you could use a cube as well. But a capsule is how character controllers in Unity are represented. And character controllers sort of come for free in Unity, which is really nice. They're part of the standard assets. So if you go to import package in Unity, if you're going to assets, import package, there's a lot of packages that come for free that sort of bootstrap you. Notice that there's like 2D packages, cameras, characters. The characters package has 3D characters, or third-person characters, first-person characters, some that are physics-based, some that are not physics-based. This particular controller is not physics-based, meaning that we don't apply forces to it. We move it around. It's kinematic. It is affected by gravity, so in a sense it kind of is physics-based, but it's not strictly physics-based like a rigid body and a rigid body would. And the collisions that occur between this and another rigid body aren't the same as they would be if we were to make this a purely rigid body-based character controller. There is a purely rigid body-based character controller that you can import. I haven't experimented with it a lot, but you could probably figure out a good use for that in terms of a game where maybe you want to move precisely on surfaces that have different materials, like icy surfaces or whatnot, and have it apply it in a very physically realistic way. Another few things that we have here in our play scene, we have a dungeon generator object. So this dungeon generator object is just an empty object with a level generator script here. And then we have a few other objects, a floor parent, a walls parent, and a whisper source. So we'll get into the details of what all of those mean. Our goal today, we'll be talking about a few things. So we'll be talking about, here's a picture of just our maze. So we talked about some of those things at a high level. We'll actually explore how to implement them in Unity today. So making a maze, making the fog effect, walking through it with our character controller. We want to be able to have some kind of gameplay here. So we have collectibles in the form of this red coin. It's actually part of another standard assets pack, the prototype assets pack. It comes with a prototype little coin object that you can throw in. Anybody notice anything about this coin beyond the fact that it's just a sort of red coin? What else do you notice about this scene here? It's emitting a glow. Any ideas as to how it's emitting a glow?
So the light source inside of it?
It's a light source inside of it, exactly. So we'll talk about that. We'll show you how that's implemented. Very easy to do in Unity. And then we'll also talk about, towards the end, our 2D scene, our title scene, and how to construct it, which is actually very easy in Unity as opposed to doing something by code. You very rarely actually for interfaces need to touch code, at least in terms of how to lay them out. In Unity, you can do everything very visually and with the mouse, and it's a pleasure to make interfaces if you're used to just making them in code. So texturing. So last week, or 2 weeks ago, we did nothing with textures. It was, well, that's not true. We had one texture on the background, which was the sort of scrolling background, but we didn't really look at that too much. In today's example, the helicopter and the coin and the buildings and all that stuff, those were all just polygons with flat colors associated with them. Today we'll be talking about how to actually texture things with materials. And so this is very easy to do in Unity. So I'm going to go over to my title scene here, just because it's lit in a fairly normal way as opposed to the play scene, which is not lit in a normal way because we're using environment lighting and we don't have a skybox. The title scene has a fairly normal lighting setup. So if I add a cube here to the scene, so you can see right off the bat, by default, we do get a material here, which has what's called an albedo component. Albedo just means like what's its surface color look like. It has a much more technical definition, and you can look up on Wikipedia what albedo means. It has something to do with the way that light interacts with surfaces. There's a lot of other elements here. You can make something look metallic. You can make it look smooth or rough, and you can also add normal maps, height maps, and a few other things, which gives it more of like a bumpy texture and so forth. And you can also make things emit light this way, which the coin actually not only emits light, but also is a light source, so it does both. And there's a few other things here. For example, let's say you have a very large cube and a small texture. If you put a very small texture on a large cube, what's it going to look like? What's your instinct? If we have a very large cube, but let's say we have a 64 by 64 pixel texture, but our cube is humongous, what effect is that going to have on the cube? It's going to look kind of like an N64 cube, right? It's going to, what basically happens is it's going to interpolate between the texture pixels, the texels, when you apply a texture to your cube. And so when you apply a small texture to a large surface, it's going to look stretched. It's going to look stretched and like it's going to look also filtered, as it like you sort of see in some YouTube videos. If you watch them and they record at a very small resolution, but you blow them up, they look filtered. Or if you've ever stretched a picture in the right software and it looks interpolated and filtered, it's going to have that look. So what you can do is you can apply tiling. So here we can see there's a tiling element, X and Y, so of 1. In the X and Y direction, because it only applies on a flat surface. So the effect of tiling would be such that if you have a 64 by 64 texture, you could just tile that texture several times to get the desired look that you want on whatever surface that you're trying to look at in your game world. Maybe it's a very small object, but maybe it's a very large object that you're looking at as a character, and you want to tile bricks, for example, or stone. So to apply a texture to a 3D object in the scene, I'm going to go into here. So you need a material first. And so these are all Unity material objects. You can tell because they have a circular, they look like as if they've been wrapped around a sphere. These are all Unity materials as opposed to textures. Textures are just 2D textures, 2D images. So this is part of an asset pack that I downloaded for this lecture called Dungeon Modules, Low Poly Dungeon Modules, which is in the asset store. And so what I'm going to do is I'm just going to apply, let's say I want to just apply this rock material to this object, right? And I go over to that. I'm going to first add I think because I went into the material, had a incorrect appearance. So do that. Oh, that's strange. I'm going to create a new scene. And then I'm going to add a cube, and then not pot, but maybe the beam. I wonder why it is not, that's very strange. For some reason, it might be a setting that I have enabled that's not allowing it to correctly render. But the effect of that should be that we apply, normally if you apply a texture to a material, it'll have the effect of creating, it'll instantly texture it. But what I can do is I can go to textures here, and this should work too. I can go to that, and then it'll apply it that way. So normally, if you're in a fresh project and you add a new 3D object and you just click and drag a material onto a 3D object, it will texture it for you. In this case, I think because it's automatically assigning a material to these objects based on some project setting that I'm off the cuff just unable to, I don't know for sure. You can instead just go to the albedo component here. So albedo functions not only as a color, but also as a texture for your object. And so you can apply a texture, just a 2D image, to your albedo component of a material, right? And that'll have the same effect as texturing it immediately. So normally what this is supposed to do is create a albedo, create a new material with that texture as the albedo when you set a material to the 3D object. Now, I wonder if yeah, I'm not sure. I'm not sure exactly why it didn't work as like right off the bat like it's normally supposed to. In a fresh project, it will. I'll try to investigate. But if it ever happens like that, where for some reason I think it has to do with the way the shaders are set on here. Maybe there's a setting I'm just not sure about. But you can just set the albedo component here manually, and it'll have the same effect. So the albedo component of your material, setting that with a texture, textures objects. And so that's effectively how we get from this sort of look of a flat shaded or flat color shaded object to a texture shaded object, just like that. And texture mapping, sort of in itself, is a very wide field and fairly complicated, but ultimately it looks something like this. So can anybody tell me what this looks like here? So we see here, obviously, we have a fully textured model. But if we're looking at this, what does it look like we've done here? So what does it look like? Ignore all the lines, but what does it sort of look like we have on this surface? It's just a texture, right? We can see, we can sort of see the colors here. For example, maybe his belt here, or actually that looks like the top of his head here. This being the top of his head, and then we have like his belt and other things. This right here, we can pretty clearly see that's like sort of his face mask, right? But it's just on a 2D surface. Like this is just a regular texture. And so what we've done here is basically taken all of the polygons that comprise the model and sort of laid them out flat, right? We lay them out flat as if on a table where our texture is, and that's what UV mapping is. And this is usually something that you do in whatever 3D modeling software that you're using. In Unity, when you apply a texture to a material, or a material with a texture to an object, it will use its standard, it has its own built-in like mapping algorithm that'll apply material to a model. And so it does it differently for different objects. We can create like a sphere, for example. Move the sphere over here. And I'm going to try again and just to see if the applying the material works on that. No, it doesn't. So so if you go into this material here, which is for some reason grayed out. New scene again. Create a new 3D sphere, and then oh, this time it looks like it's, oh, I can't tell. No, I don't think that's working. Oh, now it allows us to accept a texture. Okay. So we can apply a texture, we can apply a texture to that. And so now we can see our sphere has been mapped as well. And it looks fairly convincing. It's been wrapped around it in a way that doesn't look too distorted or too weird. And so Unity has its own ways of mapping for its primitive objects, whether it's spheres, cubes, we have a few other ones, capsules, cylinders, planes. And it'll depend obviously on what your texture is. If your texture is fairly ornate, it might end up looking distorted. But for most purposes, for simple primitive objects for most textures, it should work pretty well. Now, if you imported a model that was like a table or a character, and you just applied a texture to it, it's not going to look good. It's going to look messed up. And so your 3D software will export a material with the model, assuming that you've modeled in that software with a texture. It'll actually give you a material that you can then reference that will properly apply a texture to your character, but the same sort of apply a texture, just a regular texture to a complicated model, just isn't going to work because it hasn't been UV mapped in a smart way. Unity's not going to know, I have a table, I want to map the texture to the table in a, in a way that looks convincing. You can see this kind of if we create a cube, and then if we go ahead and, I've been making it apparent for some reason. If we go up here, I'm going to first assign, OK, for some reason that worked instantly. But you can see we've applied a sort of wall texture to it. And then if we scale it down, so this is the scale button up here. So we have, you can move, rotate things. If unfamiliar, the sort of these top buttons up here are transform operators. So you can move things, scale, rotate things, and scale things. So if you scale this along the, this y-axis a bit, and then you zoom in, the texture looks pretty compressed and distorted because it's just doing the same algorithm and assuming it's the same kind of surface without taking into consideration how it's been warped, right? So ideally, you wouldn't have these sort of like flattening thing, this flattening happening. And so in your 3D software, you would unwrap your model and then apply a texture to each separate polygon of your model in a way that looks convincing. And so this isn't anything that you necessarily have to do for the lectures, or for the demonstration, for your project. But if you are creating your own 3D assets, if you're importing 3D assets, and if you want to use textures in a way that we're doing today, you will need to probably become familiar with UV wrapping, UV unwrapping, UV mapping in whatever software that you're using. And if you're just unfamiliar with it in general and have wanted to know sort of what goes on in turning a flat white polygon character into something that has a texture, this is effectively what happens. You unwrap it, make it flat, sort of like stamp the material onto it effectively, and that maps the UVs of the texture, sort of the texture's virtual coordinates, to your 3D model. So any questions as to how this works at all? Or about Unity and applying textures?
What's the general way that you make the textures on the right, where it's kind of like, it's like a world that's been flattened?
How do you make the textures on the right? That's kind of an art form in itself. You do have to do it by hand, and sort of know. There's a good amount of trial and error that'll go into it too, as you're making your model and sort of unwrapping it and noticing, oh, this looks weird as I'm applying this polygon to this surface. I'm going to go ahead and change that texture. But you could use GIMP or Photoshop or any standard texture creation software, and kind of just it's something, I don't do a lot of it, but it's something that I imagine that you just get better at with time, and texture artists and modeling artists probably develop sort of like an attuned sense of what makes a good texture versus what doesn't. Generally, you'll make the model first, and then you'll make the texture. So, OK. So we already talked a little bit about about materials. We'll go back over it really briefly again. There is a resource that I really like and I think does a really wonderful job of teaching far beyond the basics of Unity, and that's catlightcoding.com. And it's totally free. They just have a bunch of free articles on there, which are very in-depth. And this is a screenshot taken from one of the articles where they talk about how to make really interesting materials. So you can see here, this one on the left, it looks it looks like a fireball, like it's made out of magma. and it's got bumps on it. It has contour. You can see that there's sort of like a glow to the fire on it. On the right, you can see that this model has sort of conditional shine on certain parts of it. Like the metal part of it is shiny, but the rest of it isn't. And sort of like, how do we make certain parts of the material shiny? How do we make certain parts of it flat? The article goes into depth on that, and effectively what they do is they use several layers of maps, like a shininess map, which is a texture that tells that you reference in a Unity custom shader that you write, which the article teaches you how to write, which will make certain parts of the texture glossy and certain parts of it not glossy, so matte. And so you can do a lot of really cool, very interesting things, and Unity's shading system is very, sort of the sky is the limit. I mean, because it's effectively a standard shader language, like you would, it's effectively the same thing as HLSL, I believe, which is high-level shading language, which is a, if I'm not misremembering, Microsoft originally came up with it, and it's very similar to GLSL, which is the OpenGL shading language. And so what these are effectively is just little programs that run on your graphics card. We talked about this before, but they tell your scene how to process lighting for the objects that are within it. And everything in Unity has a shader associated with it, even if it's just the standard shader, which by default is just a white color. But you can write your own shaders, and you're capable of virtually unlimited possibility. And this effectively is all a shader, and it's all a shader that's been written in code, but we have a lot of these variables that are exposed to us, and albedo is one of them. And albedo is sort of conditional. If it gets a texture applied to it, it will just render that texture. But if you apply a color to it, it will apply that color to your material. And so that's how you can get, textured things versus non-textured things. Metallic just computes shininess and reflectivity off of surfaces, and that's just something that's written into the shader and produces the lighting responsible to make that happen. And all of these different things are just part of a single shader, and a material is effectively a shader. They're kind of one and the same. A material is a little bit different in that you can also specify how its surface should interact with other things. So for example, if you're in an ice level, a material can not only be like the sort of glossy, icy look of something, but also how slippery is it when I walk over it, and should I slide, and how should other things interact with it that have physics. So like those two sort of hand in hand are sort of what a material is. But likely as you're starting out, the only real things that you'll need to consider, and you're sort of bound only by your curiosity, are albedo and maybe metallic and maybe emission. And then depending on how big your thing is and how small your texture is, maybe tiling. And then recall last week we manipulated offset. So offset is how much the texture is shifted, and recall it loops around back to the other side. And so by manipulating offset on the x-axis, we were able to get a infinitely scrolling texture, right? And so all of these things have their uses, and pretty much everything in Unity has its uses. It's a very vast toolkit to use, but those are probably the important things that you'll see. And this article and many others on this website, which I highly recommend if you're looking to get really deep into Unity, will give you a lot of insight into how things work far beyond just the surface level there. So any questions on materials? All right. So we're going to take a look now at lighting. So materials are one part of the equation. So that sort of defines how things should look when light hits them. But we also need light itself in our scene to illuminate things. And so this is taken from another article on cat-like coding on rendering. And so this is a scene with a lot of lights, a lot of glowing lights, emissive lights. And there's a lot more going on here. But this is another great series of articles on how to understand the lighting model in Unity. And it teaches you a lot. It teaches you almost down to the very bare ingredients of the sort of the software and the rendering if you want to go that deep. I certainly haven't gone through every article because there's just a tremendous amount of content and it's very deep. But if you're looking to really get a sense of how it works, I would encourage you to explore that. So we'll look at a few different types of lighting. Beyond the more complicated things that this article talks about, we'll look at the different styles of lights, which you'll probably use more often as you're starting out. So point lights. Anybody have an idea as to what a point light might be based on this picture? It's not pointing in a very specific direction. That's actually a spotlight. So a point light is a source of light that actually shoots out in all directions around it. So it emits light in all directions, but within a confined area at a specific intensity. A spotlight shines light in a specific direction, so only one direction. And what's interesting about spotlights is you can actually apply what's called a cookie to them. And what a cookie does, very similar to what the Batman light does, it allows you to apply a texture to a light and therefore cast shadows, specific shadows on the light. So if you wanted to make like something like the bat signal, you could put the Batman icon cookie on your spotlight, and that'll shine the light, but the Batman logo will be in the middle of it. It's effectively the same thing as taking a literal spotlight and putting a object onto it. It produces a shadow, a manual shadow. It's called a cookie. Yep. A directional light. So anybody know what a directional light is? So despite its name, it's actually not the same thing as a spotlight. So directional light, we used a directional light last week actually, last lecture. Directional light casts light in a single direction, but throughout the entire scene, as if it's the sun. So this allows us to illuminate globally the entire scene, but all light gets cast from one direction. So if you want to produce the appearance of daylight in your scene, just a single directional light will illuminate everything. And then the last thing, which is used less, is called an area light. So does anybody know, can anybody guess what an area light is based on this picture here? Yes?
So it's light that's only on the surface?
Light that's only on the surface. Kind of, yes. So it's light that will emit from the surface of a specifically designated rectangle, effectively, in one direction. So you can define a large area, for example, maybe you want like a wall strip in your game or something along the wall to emit light specifically to the left or something like that. That's what an area light is capable of. Now, area lights are computationally expensive, and so you can only use them when you bake your lighting. Does anybody remember what baking means when referring to lighting? So baked lighting just means that instead of real-time lighting, calculating things dynamically, the light gets calculated one time and saved and almost like freezed onto all of the objects in the scene. And so there are pros and cons to this. What's a pro to baked lighting, do we think?
It's less computationally intensive.
Less computationally intensive. What's a downside to baked lighting?
Can't be dynamically affected.
Can be dynamically affected. So if you're walking through a baked lighting scene and you're expecting to cast a shadow on something or for something to cast a shadow onto you, it's not going to happen because the environment's already been, the lighting for that scene's been pre-baked. It's almost as if we've just recolored the world in a specific way, but we're not actually doing any lighting calculations. But this is how lighting worked in like the N64 era, and it's how it still works now for certain situations. If you know nothing's going to cast a shadow on something, you can make really nice looking lighting for a scene without needing to do it in real time. You can just bake it, right? So those are the different types of lights. So we can see that in Unity. So if we go here, I'm going to, so right now we have a directional light. So this directional light is this object here. By default, and you can zoom in as much as you want, but it's sort of like, oh, there we go. This directional light is only shining in one direction. So I can move it here. So currently I'm in, it's a little bit weird to navigate just because it's been rotated a little bit. Given that it's a directional light, its rotation. So notice how it changes. So if I shine it upwards, notice that everything becomes black because the lighting is just shining upwards, right? It's as if it's coming from below. And if I shine it towards there, notice that the lighting on the sphere and the little cube there sort of change a bit, right? Because they're getting affected by the direction of the light a little bit. But they both get affected the exact same because the directional light is omnipresent. It's throughout the entire scene. It's a global object. Now, if I delete the directional light, Notice we have no light now, so these things just look kind of like statically shaded. You can add a new light through, if you right-click in your sort of game object view, and then you go over here, you can see we have all the different lights we talked about. There's also things called reflection probes and light probe groups, and those are a little bit more complicated, but those allow you to effectively get pseudo real-time lighting and reflection with baked lighting and reflection. We won't talk about those in today's lecture, but here's a point light, for example. So let's see, where is it? Oh, it's right over here. So I'm going to move it over here. So you can see it's not global like the directional light was, right? It's just affecting this very limited, and I'm going to zoom in a little bit so you can see a little bit better. But it's affecting just sort of these two objects relative to where its position is, right? And so this works perfectly for things like lamps in your scene, if you want to have a street light, or whether you want to have maybe like a fire going on in a house, or if you want the, like the power up that we had in the, or the pickup that we had in the Unity scene, right? We have just it's just emitting a purple light that is within a very small radius. Notice here, we can change the color of the light. So if I make it like that, for some reason, oh, here we go. So we'll do that. So notice now it's emitting a purple light. So you can color a light however you want to produce whatever effects you want. So fire is not going to emit white light. It's probably going to emit like an orange-red light. Street lights are probably going to emit kind of like a yellow, orangey light. So depending on what your scene looks like and what you're trying to emulate, you can accomplish pretty much anything with just the, these very simple objects. So I'm going to get rid of the point light, and then I'm going to create a spotlight. I'm not going to create a area light just because we need to actually bake the lighting into the scene, but I will create a spotlight just so we can see what it looks like. Get it in the right position. Sometimes it can be a little tough to figure out exactly where you are. Okay, getting close. There we go. Perfect. So there's the little spotlight right here is being produced by our object. So we can see we can move it around, and then we can apply a cookie to it if we want to as well. It's right here. So if you're in a spotlight and you want to apply a texture to it, just this little cookie, and it just expects a texture. So whatever image you want. And if you're creating a cookie texture, white means full light, and black means full shadow. And so you can make it a grayscale image. You can make it anywhere in between white and black, which will allow you to produce some interesting effects. For example, the manual in, it's not here. I didn't include the picture here, but the manual shows like there are some kind of like the lights that you put on a stand, and they have a bunch of LEDs, right? And they're sort of in a grid, and they shoot out a spotlight. You can create a cookie that's kind of a grayscale with those gridded lines, and it'll shoot light onto the scene as if it's being broadcast from a sort of grid of LEDs. So there's a lot you can do with just some very simple ideas. Those are the kinds of lighting that we can use, and in today's lecture we only really use the point light, and in last lecture we used the directional light. And spotlights, you could, for example, programmatically change, for example, the rotation of a spotlight. If you want to have like a swinging spotlight in your scene to illuminate some wall or some surface, there's a lot of cool things you could do with it. So those are the core types of lights in Unity. Does anybody have any questions as to how they're used or how they work?
For the directional light, does it matter where it's placed or only the direction it's facing?
It does not matter. So for the directional light, it does not matter where it's placed. You could place it anywhere in your scene, 0, 0, or some far distance away. It'll have the exact same effect on the entire scene. Yeah. Any more questions? OK. Cool, cool. So those are lights. Bump mapping, talk about very briefly. So bump mapping is, we actually do use this in the game. A bump map effectively is, so what you see here on the left is an actual 3D scene. These are actual models being shaded in real time. Not in real time, but they're actually real models being illuminated. In the middle, we can see what's called a bump map. And on the right, we can see just a flat, like a flat plane with a bump map, with that same bump map applied to it and then illuminated. So what a bump map allows us to do is to take a flat wall or flat surface or whatever you want and then simulate like an actual three-dimensional contour, three-dimensional bumps or whatever you want on that surface without needing to create the actual geometry to make it possible. And so there are different tools that will allow you to create bump mapping objects, or bump mapping textures. Often 3D packages will have these, so you can create them, or other software. But they are effectively just the encoding of what are called surface normals. So just a vector going from outside of the polygon at that given point, and they tell the lighting system in Unity, pretend as if there's actually geometry pointed in that direction when you calculate it. And so even though it doesn't distort the geometry in a way that's like this is still completely flat, the lighting thinks that the geometry is kind of, you know, contoured. And so it allows us to create, this is kind of a toy example, but it's actually relevant in the case of walls that have, and we covered this last week, just not in as much detail, but walls that you want to be flat and you don't want to have a lot of polygons for, you can create a bump map for and apply that bump map, and then when you're rendering it, when you walk past a wall, it's going to look as if the wall actually has cracks and bumps in it for a realistic effect. And this is used in the game to a slight degree, and you can crank it up if you want to. I didn't on my computer because my settings or my specs aren't sufficient, but every texture in today's example has a bump map associated with it, so you can actually see what the you can actually see the effect of bump mapping at various degrees of use. The materials here, so I'm going to load up the scene that has the actual stuff. And I'm going to, actually, I don't need to load up the scene. All I need to do is go to the materials and the floor, for example. Where's the floor? Right here. So notice that before we talked about albedo, and then I also mentioned normal map. So right here, all you really need to do in order to get Unity to detect normal maps, and this is just part of the standard shader. Normal maps and bump maps, by the way, are effectively synonymous. You can just drag your normal map texture into this field here, this little square, and then give it a degree at which to apply that normal map. And so if you look at this here, I might be able to see, I don't recall, yeah, we can sort of see how it changes the texture, right? So at 0, there's no normal mapping taking place at all. That texture is just completely flat, as if we had done just the regular apply a texture to a sphere. But the degree at which we apply normal mapping, so notice at degree 1, it kind of looks pretty realistic, as if we've got kind of a stony texture. And the more we go, right, the more exaggerated it starts to look, right? And you can just keep doing that, and it'll eventually just look really distorted. But that allows you, and depending on how strong your computer is, you can go higher or lower to affect just how bumpy, just how strong the bump map, the normal map, affects the lighting rendering. So it's that easy to get just a fairly sort of extra sense of realism in your scene. So you'll notice if you're walking through the scene, if you turn off lighting, it's even easier to see all of the surfaces, the floors, the ceilings, and the walls have a bump map as well as a texture map. So that's, in case you're wondering what these weird colored textures are, RGB are XYZ for the surface normals and their permutations thereof. And that's how it gets encoded into this. And so often you can see, if you're looking at a bump map and a texture map, you can kind of see together like, oh, okay, this makes sense. The parts that I would expect to be bumpier do have a correlation to how they look on the actual bump map texture. You can see it here. Everything that is bumpy or contoured is very visible in the bump map. That's just by nature of the way the data is encoded. So any questions as to how bump maps work or what they are or how to use them in Unity? All right, cool. So now we're going to start getting into a little bit more into how this all comes together in our maze, on our game, and we'll talk about maze generation. So I'm going to just start up the game, the scene here. So I'm in the actual play scene. So in scenes, I loaded up play as before. I'm going to hit play. I'm going to turn off my sound just because the creepy sound is a little disorienting after a while. And then I'm going to, I'm going to go to a 2x3 view and then hit play. So we have the regular game view down here below, and then also, if I zoom out, you can see that our scene was empty before, but now we've got a maze. And currently, it's not very visible at all because, one, we're applying fog, right? And recall, fog allows us to effectively add color to objects that are farther away from us. And two, there's a ceiling on top of our, a roof on top of our maze, so it's actually blocking out the actual what the maze looks like. So we can fairly easily make a couple of changes here in order to see our maze a little bit better. So I'm going to go to Window, I'm going to go to Lighting, Settings. And so if you go to Window, Lighting, Settings, those are your sort of global Unity lighting settings, right? You can set your skybox, you can set environment lighting, you can set things like fog, you can choose how things are baked. There's a lot of things here. We won't cover nearly all of them. We will cover a few of them. Environment lighting is a big one. That's actually how we're lighting the scene in this game. So all of the lighting that's not, all of the lighting is environment lighting. That's how we're doing it. We're doing it with color. So notice that you can choose skybox, gradient, and color. So if you choose skybox environment lighting, it's going to have sort of like, it's going to look kind of like this skybox that we have here, right? This sort of in the far distance looks blue, kind of looks a little bit more natural. But when it's applied to our scene, it doesn't look quite the way we want it to look. So what we went with instead was just color, and I chose this sort of murky, greenish, brownish color, and that gave the result that I was looking for. But you can make this any color you want to. We could make this some sort of bright yellow color. I have no idea what this is going to look like. This is probably going to look horrible, but yep. I mean, actually, this in a weird way, this kind of looks interesting. This actually looks closer to the original Dreadhall's game than what I did, but it's not very scary. Kind of looks like we're in a pyramid. That is, am I able to go back? No. Okay. Well, I screwed up the color. Let me try and find kind of what color I had before. It's kind of like a nasty green. Kind of like, nah, that's probably good enough. Okay, something like that. And so we play it again, we could see, we're back to the nasty dark color. But that's environment lighting. So it applies a lighting uniform, just ambience, kind of like a directional light, but it doesn't have a direction. It just applies to everything in your scene at a given intensity. And that is how we are lighting our scene. It's that easy, just environment lighting in our scene on our lighting scene window. Now, the other important thing here is the fog. So fog is almost as easy as just clicking this button here that says fog, and then choosing a color for it, probably. You can choose the density. So obviously, if it's a higher density fog, it's going to look as if you're in a foggier place. Like it's going to sum the color to things that are closer to you faster than it would if you had a lower density fog. And there's some other features here, some of which I'm not terribly familiar with, but for the sake of today's example, just make sure fog is selected, and then click make sure you have the right color for your fog. So if you have like a ridiculous red color for your fog, it's probably going to look weird. Yep. But you can see how you could do all kinds of weird effects just by adding these things together. Like if you want to have the effect of being in some sort of like, I don't know, noxious foreign world, maybe you want like a purple fog instead of like a dark green fog or whatever. That's, super easy. You produce a lot of very basic but effective effects that way. I think it was just kind of the same nasty green color.
Bring this screen up again, the one that says lighting.
So to bring up this lighting screen, all you need to do is, if you're on a Mac, I think in Windows is the same thing. There's a window option in the top menu. Window, and then lighting here, and then settings. And so this will bring you to all of the settings that are pertinent to at least today's example. And so we're not using any lights in our scene that we talked about before, at least for the lighting of the scene itself. Now, there are point lights being used for the pickups, and I'll show you that in a second. But what I wanted to illustrate was how you can sort of look at our maze after it's been generated. And so what we need to do first, notice that before we were kind of, we couldn't really see our maze at a distance because it was just purely dark green because of the fog. It was adding green to that geometry because it was so far away. So I'm going to disable fog for now. It'll actually remember your settings, which is kind of nice. So just going to disable fog. And I'm going to actually add a directional light to the scene. So I'm going to go here, add a directional light. And then I'm going to hit play again. So now our scene is lit. And you know, it looks a lot different, a lot less scary. And we can see our maze a lot better. We can actually see that it is a collection of blocks. It's tiled blocks. Now, we can't see into the maze because the maze has a roof. So what I did was I just made generate roof an option in the script. And so if you unselect that and then we try again, now we can see our maze. So this is what our mazes look like. And so the cool thing about Unity, which I really love, is just this ability to look through your scene independent of the actual game, just to like help debug. Like, it's hard to know if you're generating your maze correctly when you're creating it in 3D. You know, in 2D you can easily just look at it, but in 3D, especially in a first-person game, you can't really see it. So being able to split your view like this, the scene and the game, and actually see, oh, my algorithm's working or it's not working. It's super helpful. So we can see that it is carving a maze for us. It looks a little bit weird. It's not a traditional maze in the sense that it has the classic maze shape to it, but it effectively functions as a maze, and it works very well for its intended purpose. And the algorithm is incredibly simple, and we'll talk about that. So that's our maze. I'm going to go ahead and revert all of the, I think if I just reload the scene, it should just revert it. Don't save. Yep. OK, so everything's been reverted, all the lighting, everything. I'm just going to do a sanity check and make sure. Yep, everything works perfectly well. So anybody have any ideas as to where to get started if we were to implement a 3D maze?
The way I did it once before is you put a bunch of X's where you want something to be drawn in an array, and then you loop through the array and instantiate the walls.
Yes, so create an array, populate it with X's where you want, data wherever you want something to be instantiated, then loop over it and instantiate everything. It's exactly how it works. Now, in terms of actually creating the maze, do you have any ideas as to how would you go about implementing a simple maze generator? And there are obviously very complicated maze generation algorithms, so like nothing terribly fancy, but just a simple, how would you make a maze?
So it's random? Or
it's random.
Oh, so it's random.
So starting with the idea that we have an array, right? It's got to be a 2D array because we have two axes upon which we're generating things here. Even though we're in a 3D environment, we don't need a 3D array. We just need a 2D array. Because if there is a positive value for wherever we want to generate a block in our 3D array or our 3D maze, we just generate a column of blocks. We don't need to worry about a third dimension, right? Our maze isn't like taking into consideration like multiple levels, at which point we would need to maybe consider 3 dimensions. I mean, even still, you can still divide those into separate 2D arrays of mazes. We just have an X and a Y. So how would we get started? What would we start populating the array? Let's say we have an array, it's just a bunch of zeros, right? What are we populating with the array after we've initialized it?
Maybe you would kind of start off with just full of walls and then add like corridors, maybe?
So start with a bunch of walls and then add corridors. That's exactly what we do. The algorithm is actually pretty simple. So I'll try and maybe draw a little bit just to see if I can illustrate how this works.
Make sure that you can get from one side to the other and there's no wall in between?
By making sure that every thing that you change is orthogonal. Every block, every step that you move is orthogonal. That will ensure that you start at one point, end another point, and those points will always be accessible to one another, just by virtue of how simple the algorithm is and the orthogonality of it. So if we start with walls, so 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. These are all, in the distro, these are all Booleans because we only need zeros and ones, so we're just going to use true and false. We don't need to use integers for that. So this is our starting maze here. And actually, I'm going to add another dimension because, or not another dimension, but another size, just because the walls always need to be there. These are basically untouchable. I'm going to try and draw that as best I can. Right? So we effectively have this as our working area for creating a maze, right? Because we want this to be, we want walls no matter what, because we don't want our person to be able to walk outside the maze or see the outside world ever. We want them to be locked in. So we have all of these ones here, these trues effectively. And so all we need to do is start like at some random position, let's say this value, at 3, 2, or well, it's actually technically it's 2, 3, because we index at y and then x in a 2D array. So we go 2, 3, we go here, and then we basically can move either left, or we can move either left or right, or up or down. Well, we can't move both at the same time. And why can't we move both at the same time? Let's say first of all, let's say we're going to carve our way through the maze, right? So we're going to turn these ones into zeros, but we can only move orthogonally, meaning left or right, up or down. We can't move diagonally. So we can only, let's say we have an x move, right, and a y move. And those can be set to, but by default, there's 0. So we're basically saying, where on this step of the generation are we going to move? And actually, technically, it's direction, because the way that we do it is via directions. Yeah.
So if you're moving down, then what's in front of you will have no wall. And there'll be walls on either side of you except for where you came from.
Yes, so if you're here and they move down, this is going to be 0, this is going to be 0, and so those points are linked.
Right.
And then from there, we're going to move in a given direction. And so all of those, let's say we move here, all of those are going to be linked. And so if we move here, all of those are going to be linked. Just by virtue of the fact that we're moving orthogonally, we can't create a maze that's unreachable, because the way that, just by virtue of the fact that we're moving now orthogonally. Now if we move diagonally, if I were to move here, right, there's walls right here, and then 2 spaces there. That's not going to work, because we can't access that. We're going to see a cube here and a cube here, and we're going to see we won't be able to move diagonally through walls, right? So that's why we need to ensure that we only move either in the x or y direction, not both at once. And so what the algorithm does is it randomly chooses, should I move x or should I move y? And should I move positive or negative? So it'll do math.random equal, 2 equals 1. Effectively, in the code, it's random.value less than 0.5, because random.value in Unity gives you 0 to 1 as a float. So you say, if random.value less than 0.5, which is a random chance between true and false, effectively 50%, move in x or move in y. And then, same thing, but should I move in the negative or positive direction, right? So if I'm here, I'm thinking, okay, let's say x move or y move. It's going to be an x move, so I'm going to move either left or right. Okay, so am I going to move either -1 or 1 step, 1 to the right or to the left, right? So if it's -1, then that's going to move to the left, right? And if it's +1, it's going to move to the right. So, I mean, that's the essence of the algorithm, just looped over a bunch of times. Whenever I move to another tile, turn that into a 0. So actually, this becomes a 0, change the color. So this will become a 0, right? So that's now an empty space. And in the code, that instantly teleports the character to that space too. So we know that our character is always going to be in an empty space because he gets placed in the first open space that gets generated in the maze. And so let's say x move is equal to -1 on this iteration. So let's say we're looping until we've cleared x blocks. So I want to clear, let's say I want to clear 5 blocks. So to clear equals 5, right? That's how many blocks. When we've cleared that many blocks, we're done with the maze generator, right? So cleared 1. So our current counter is 1. So x, we get flip a coin. We're moving to the x direction by -1. So we move to here, and then we turn this into a 0. Now, this implementation of the algorithm moves one step at a time. And so because of its randomness, what this ends up doing is it produces very large chunks of deformed space just because the crawler is just constantly moving around kind of like haphazardly. So what's a refinement that we can make to this algorithm to make it look a little bit more like corridors or like hallways?
Just keep going until you hit the outer wall in the same direction.
You could do that, yeah, keep going until you hit the other wall. The result of that, you mean hit the side of the maze?
That's what I mean,
Yeah, because, well, if you did that, it would effectively just be like, it would kind of be, it might work in some cases, but it will be very long hallways and not a lot of like turns or anything like that. So the result, what we actually want to do is when we flip a coin and we say X move or Y move, we want to also say times to move. We want to create a new variable called number of times to move, effectively, right? To move. And then we just set that to a random number between 1, so we're going to move 1 tile, or the size of the maze minus 2, right? Taking into consideration both walls, right? So let's say we get the, let's say we did X move minus 1, and we only got to move equal to 1, right? So we only move here. We move once in this direction, so we've got 2 spaces. And then let's say we flip a coin again, and then we got Y move, right? Positive 1. And then to move, we got 2, right? So we're going to move 2 directions in the Y axis by 1. So what this is a result of us going down here. So we go 0 and then 0, right? And so the effect of this is that we move, we can move in more than just 1 block at a time and avoid the sort of random, like haphazard, weird, organic, large room aesthetic that we want. If we want like a hallway, grid-like, dungeon-looking like room generator, right? Now there's a caveat to this, and that is if we start here, for example, and then we want to, let's say we flip a coin, it's X move, but it's positive, like positive 4, right? We can't obviously move 4 tiles to the right because 1, it'll go into our walls on the outside, and 2, it's actually beyond the bounds of our array. So we need to clamp that value down. When we add 1 to our value, to wherever our X, we have to basically keep pointers, right? We keep pointer to whichever tile we're currently at. We need to keep, when we actually go to the next tile in our step, we need to clamp that value within the range of our walls. So we need to clamp between 1, so because we don't want to be at 0, we want to clamp it between 1 and maze size minus 2, actually, because we want to make sure that we don't go any farther than this one here. Does that make sense? This is how, that is effectively how our generator works. It's a step beyond just the move 1 block at a time, just because the mazes look way too empty and weird. With this approach, where you're moving in a direction and for a random number of tiles as opposed to just 1 tile at a time, you actually get pretty nice looking, simple mazes. This isn't how like actual maze generation works for mazes that you would see in like an actual maze that you do on like a crossword puzzle book or a maze book or something. Those are more complicated. But this solution works well. It's very fast and very cheap, and actually pretty simple to understand. So any questions as to how the maze generator, the algorithm, at least as applied to our 2D array, works? All right, cool. That's basically the gist of it. So we're going to take a break here for about 5 minutes, and then as soon as we get back, we'll dive a little bit more into sort of how the character controller works and the pickup and a few other aspects of the game. All right, welcome back to lecture 9. So before the break, we were talking about the way that we implemented procedural maze generation. So a fairly simple algorithm that creates this sort of hallway look where we can easily get lost, but they aren't technically mazes in the traditional sense like you might have seen growing up in puzzle books and such. Another pitch for Cat-like coding, because his articles are amazing. He has another one on how he did a maze generator, and in this one, beyond just regular blocks, oh, I'm sorry, I didn't have the slide there on the thing. So this is a screenshot of another article from Cat-like coding, where he talks about how to make his own maze generator. And the cool thing about his is that he has a bunch of different geometry involved in the scene. It's not just blocks. He has doors and windows and other things. And his algorithm is a little bit different than mine and produces some pretty interesting looking things. And you can see here also it has a view of the scene sort of superimposed on the actual scene, which he does with a trick using 2 cameras. So, also, here's another maze/dungeon generator article that I really like, where he creates sort of like Dungeons and Dragons style generators, and this is sort of pertinent to my interests as a developer because I really love roguelikes and dungeon generators and RPGs. But he goes into extensive detail on how to make a really nice and efficient 2D maze/dungeon generator that produces really nice looking dungeons. So as you can see here, it's got a very variable layout, lots of corridors and rooms and stuff like that. So implementing something like this in Unity would be really cool. And there's a plethora of generators and assets like this that'll do the same kind of thing in Unity, available on the asset store. So you don't have to make this yourself most of the time. You can just go find either free or paid assets that will do all this for you and save you a tremendous amount of time. And much of them are also very customizable too, so that you can tailor the generator to fit the domain of your game. So we saw how the lighting works in our game. We've seen the maze, sort of how it's generated, what it looks like. We have not taken a look yet at the character controller. So we'll briefly just take a look at that. It's actually incredibly easy to do in Unity, at least to get something fairly basic up and running. The way that we get a FPS controller in the case of our game is Unity has, which I alluded to before, a set of custom or built-in standard asset packs that allow people getting used to the game engine or just trying to bootstrap their game up and running with some very basic components, very basic things that are super helpful for just sort of getting your game running. So actually, we use the prototyping standard assets pack for our pickup. We use the characters one for the character controller, the FPS controller. So if you're in a fresh project and you just go to import package and you import this characters thing here, it'll import it into your game so that you can immediately use the prefabs that it gives you to create a character object. So it'll by default just put it in your assets folder underneath standard assets and then characters, and then there's a first person folder. And within the first person folder, there's a prefabs folder which has the FPS controller game object. And so all you need to do is just drag it into the scene, and then that becomes your default camera. So, sorry.
That comes with Unity? It's just
it comes with Unity, correct. That's just a standard asset.
It's always in the prefabs folder?
It's always in the FPS controller will always be in the, so you have to import it first. You have to import the asset package, the characters package. Once you've imported the characters package, you'll go into standard assets. In your assets folder, there will be a new folder called standard assets. Within standard assets, you'll go to characters, then first person, and then prefabs, and then that's where you'll find the FPS controller. Yes, no problem. So the FPS controller, if we take a look at it, we talked about it before briefly, but effectively, it's just a capsule collider, which is sort of defying physics because it's kinematic with gravity applied to it. And it has a camera sort of on towards the top of it where the head is to simulate the perspective of somebody from first-person view. And there's some programming involved that allows you to control it with the keys and the mouse, to control the camera's rotation with the mouse and the position of the collider with the WASD keys. And if you want, you can dig into the actual script for it too. They're all included with the standard assets pack. When you import that into your project, it comes with all the scripts that make all that possible. I haven't dug through all of them in too much detail, but it's all there for you if curious as to how it works. And so if you want to get just a simple FPS controller in your game, a character in your game to walk around and play a first-person game, it takes about a minute to get up and running. Now there's a lot of customization that you can apply to your character controller to make it not just the standard basic character, right? So you can set a walk speed, you can set a run speed, you can set jump speed, you can you can set the sensitivity of the mouse look on the game, on the FPS controller. You can apply what's called FOV kick, which means when you're sprinting, which it allows you to sprint with pressing shift, which multiplies your speed. It'll actually, I think it'll expand your depth of field a little bit to make it look as if you're kind of like claustrophobic, right? Like things kind of like go out, and so it looks more narrow, and it kind of gives you that look as if you're like sprinting down a path. And you can set just how much it increases by. You can set the curve of how that is applied here. So this is one of the components that Unity allows you to do is there's a curve object, and you can use this curve to influence various things in your game. I actually haven't used it much myself, but if you're looking for something to apply a curve to, Unity has an interface for making that visible within your inspector. Head bob, which means when I walk, should the camera kind of like go up and down. When you do have a head bob, like what's the curve look like? So here's another curve. This is the sort of what the head bob looks like, kind of a sine wave, but a little bit distorted. And a few other things. So for example, footstep sounds. Maybe you don't like the sounds that come by default with the controller, so you give it your own footstep sounds. Super easy to do. Just drag new sounds here. Jump sound and a landing sound, 2 more sounds that you can add to it. And that'll allow you to customize most of the feel of how your character moves around in terms of just a basic FPS controller. And so just by applying those very basic things, customizing them a little bit, we got lucky with this maze. This means that the maze went all the way around and then looped right back to where we were and ended there. So that's that maze. Okay. But I'm going to go ahead and turn up the sound. You can hear the footsteps, right? Along with the creepy whispering. But the footsteps are just provided to us by the FPS controller. And again, you can customize those to be whatever you want. And so this gives you the ability to walk around in your scene from a first-person view. It doesn't really give you much more than that. In order to do like an FPS where you have like maybe a gun or a weapon or something, you need to program some more things, and it's a lot more complicated. But for just basic navigation of a 3D scene, that's a great foundation, a great way to get started. So, any questions as to how the FPS controller works? There are other controllers too. There are third-person controllers. So if you want to use those, they don't come with a camera. Based on my experimentation, they don't actually come with a camera by default. So I think you have to parent a camera to them in the way that you want for your game. Like for example, some games have the camera super high above your character while you're walking around, and some of them have like a like behind the shoulder look, almost like Fortnite or Gears of War, like really close to the character. And then some kind of have, like in Banjo-Kazooie, you could be walking up a mountain, and then so the camera's kind of like perpendicular to where you are and sort of like follows you around. So camera programming for 3D characters is a little bit more complicated than it is for first-person games. And so that's why I imagine it doesn't come with a camera by default. So it can be a little bit more complicated. But I do believe there are a lot of assets on the asset store that can help bootstrap you for getting a programmatic camera setup going for your character in a 3D, third-person view. Yeah.
I noticed, like when you're walking around your maze, like occasionally you're like clipping a wall and kind of seeing like what's behind it.
Yep. That I believe that's a result of the collider being a little bit too big. So what he said was that walking through the maze, you can kind of clip through the wall a little bit. See if we can actually experience. Yeah, like right there. Yeah, and that's I believe that's just the camera or the collider being a little bit too large, and so we could probably like get rid of that altogether just by shrinking the collider a little bit. Just a detail that I didn't iron out, but you'll see that in a lot of games actually. A lot of games have like clipping that you can get that you can observe depending on how they've programmed the game. But yeah, any other questions as to how character controllers work and like how the import process works and how to get it in your scene? Okay, cool. Yeah, it's super easy. Again, here's what the FPS controller looks like. Capsule collider with a camera. And then the third-person controller, by default, they give you a pretty nice-looking model on the left side there so that you can experiment with it. And they apparently give you an AI one as well, so you can test AI in your scene with it. But I haven't experimented too much with that to vouch for how well it works. So an important aspect of today's example is that we've gone from having just one scene to having two scenes. So I want to illustrate how we sort of move between the scenes a little bit. And also I realized we didn't really cover the dungeon generator in code detail, but notice that I have exposed a lot of things here: floor prefab, wall prefab, ceiling prefab. These are just the cubes that are textured to be our floor, walls, and ceiling. We can just click and drag them from the inspector into our scene onto the components there. We have a character controller reference here so that we can place the character controller in our scene when we've generated the first block. We can basically take the transform and set its position to whatever that XZ is. And then a floor parent and a walls parent. So the reason that we have parent objects, actually, which we didn't look at before, whoops, I've lost track of where there it is. The reason that we have parent objects here is because when we instantiate all of the cubes in our scene, just sort of just instantiate them without really thinking about it, it ends up, basically, I'll show you here. Well, first of all, I don't know what this is. Oh, I think that's interesting. Oh, because I clicked on the floor parent, right? Okay. So you click on the walls parent. Actually, I didn't do that yet, but it'll actually show you where all the objects that are parented or that are dependent on that parent. So the floor parent here, see how many floor blocks there are? There's quite a lot. Excuse me. There's a lot of floor blocks here, and in the walls parent, there's even more. There's a lot of walls and ceiling blocks. And if we just generate those without assigning them a parent, it'll just fill up our hierarchy there very messily, and it makes navigating our scene during debugging very difficult, right? We don't need to see that we have a million clones of the floor or the ceiling blocks or the wall blocks. And so what we do is we just take all of the clone blocks and we just parent them to an object. And when you parent something to an object, you get that little drop down. Like, for example, this first person character, this FPS controller is the parent of this first person character. And so those are two separate objects that both comprise the FPS controller effectively. A parent is top level, and its children are therefore within it, within this little arrow here, and it's collapsible. All of the things within the play scene, for example, the play scene is the parent to all of these. It's sort of like a folder hierarchy type of thing. And so if you want to clean up your scene, if you're instantiating a ton of things, just effectively containerize them by putting them into a parent object. And so we do that in our game with a function called createChildPrefab. And so what createChildPrefab does is it does an instantiation as normal, right? Creates a prefab, instantiates it, gives it a position XYZ, quaternion.identity because we don't want to apply any rotation to it, but my prefab.transform.parent equals parent.transform. It's effectively linking we're assigning the parent field of that prefab's transform to the parent's transform. And that has the effect of basically linking them together in a parent-child relationship. And that will allow us to collapse and expand a list. When one parent has a bunch of children, we can expand it and contract it in the hierarchy view and save us a bit of a headache in terms of navigating our scene when we instantiate a lot of things, which is fairly normal. So the actual maze, I'll go over this fairly quickly. It's a fairly simple algorithm, and I talked about it on the screen, and we don't have a ton of time, but basically we go z to x. The reason that we go z to x is because in Unity, z and x are sort of like the ground axes, and y is sort of like the up and down axis. And so we don't want to instantiate, we're not really worried about navigating the y-axis during our maze generator, because all we're going to do is instantiate 4 blocks along the y-axis during that phase, right? So we're basically taking our 2D array, and we're iterating over it x, y, and then we're mapping that to Unity's zx, or xz, if that makes sense. Because notice like this is our ground, right? So where this transform is, you can see the ground, how this is x, the blue is a z, and y is this axis here. We're effectively only concerned about generating on the ground, and then when we generate a wall, we just generate it 4 blocks high on the y. We don't think about the y. So that's why x and y for our 2D array, but x and z for applying that array to Unity's 3D coordinate system. Does that make sense? Okay. So we're iterating over z and x, and then we're indexing into our map data, z and x, which is effectively the same thing as y and x. And then we are creating a child prefab if map data zx. So recall that our map data is a 2D array of booleans, right? And so if we have map data zx equal to true, that means there's a wall there. It means that there's a true in our array, so we should instantiate a wall at that location. So we create 3 wall prefabs, assign them to the wall's parent so that they get containerized within there, so they don't clog up our hierarchy view. And then, let me see here. And so if we don't, so if we've gone through our maze, right, if we're generating our maze, and we get to our first tile that's actually not a wall, so it's an empty space. So basically the else here, so if map data zx is not true, it's going to be false. So if that's the case, and if not character placed, so character placed is just a Boolean. It's a private Boolean. We don't want this to be visible in our inspector. There's no purpose for it to be visible in our inspector. This is just a Boolean for us to use in our script. So we set that to false by default because we haven't placed our character yet. But when we generate our maze, we have to make sure we put our character in a spot that there isn't a wall, because we obviously don't want him trapped in a wall or clipping through the maze, right? So if not character placed, we're going to set the character controller's transform. We're going to set its position and rotation, which is a function. We're going to set it to x and then y1 and then z, and then no rotation, so quaternion.identity. And then set that to true. So therefore, this will never be called again. So this only gets called in the very first empty space that we go through our maze. And that's it for that. No matter what we do, whether there's a wall in our maze or not, we're going to want to generate a floor and a ceiling at that space. So that's, of course, assuming that generate roof is true, which recall we made a public Boolean in our inspector so that I could debug and show you guys what the maze looks like from up above. So if generate roof, create a child prefab for ceiling prefab at x4z, so a bit higher up. And then no matter what, always want a floor, so create a floor prefab at x0z, so down below. And our character controller gets placed at, recall, x1z, so just above the floor. The assignment is actually, part of the assignment is generate a hole in the floor. And if there's a hole in the floor and the character falls through the floor or the hole, you should get a game over, right? So you're going to need to create a game over scene. We're going to need to transition to that scene. And then we're going to need to check to see whether the character's transform has gone below a certain amount, right? That's all fairly easy stuff to do. But you'll look to do some of that in here. And then the actual maze data function is here. I won't go over it in detail, but it's the algorithm that we talked about before, where we choose direction to move randomly, and we choose a random number of steps to move, clamp that value within the constraints of the maze, and then set every tile that we explore to false. And that has the effect of creating the maze. And then we just return that data back to our function. It's just a 2D array. Notice that in in C#, to create a 2D array, it's a little bit different than in a lot of other languages. It has its own set of syntax for that. You have the array syntax that you're probably familiar with, but then you also have this comma. And that comma is to designate that there are 2 arguments to that index syntax here. Just means an x should go here, and a y should go there, basically, or a yx. And that's 2D array. And you can make it as many degrees as you want to. Just add more commas to it. And notice that to actually allocate the memory that we want for that 2D array, new bool, maze size, maze size. So our maze is always square shaped. Same. And you could easily make this maze x, maze y if you wanted to make it like rectangular. So you just need to have 2 public variables instead of 1. And all of this is fairly visible through the inspector too. In our dungeon generator, you can see I made a tiles to remove 350. So that means that our maze is going to cut out 350 tiles. And as soon as it cuts out 350 tiles, it's done. And then our maze size is 30 by 30. So that means there's going to be 900 tiles in our maze. So you can tailor this to whatever you want in order to produce sparse or denser mazes to your liking. So any questions as to how the code for that works, more or less? So now we'll actually get to the scenes part of it. And so transitioning between, oh yeah. Yeah.
I'm thinking like, for like a smaller game like that works great. But like for a larger game, wouldn't you want to model the walls as like 2D kind of objects and like the ceiling instead of like a whole cube?
Oh yeah. So for a small game, is it more ideal for the walls to be rendered as like one discrete object as opposed to like several cubes? Yeah, absolutely. That's 100% true. And actually, Minecraft is an example of this sort of idea that you think would work, but they actually consolidate all their geometry after they've generated it in this way and produce like models that are more optimized. Like that you think that you're interacting with this world that's a bunch of these little blocks all separate, but it's actually one big piece of geometry, and then it dynamically figures out what you're hitting and removes and adds blocks as needed. And there's some cool videos on YouTube as to how to do this in Unity too, which I looked at a long time ago, and it kind of shows you can actually dynamically create meshes and vertices and stuff in Unity and then create objects that way, which is really cool. But that's a little bit more on the advanced side. But yeah, absolutely. For an actual implementation of this, a simple but more efficient way to do it would just be to have one solid large wall object that's like as tall as you need it to be and maybe as wide as you need it to be for one character, and have that work. But for simplicity's sake and to illustrate the algorithm, we are just using the cubes. Yeah, exactly. But yeah, good point. That's 100% true. All right, multiple scenes. So the way that we do this, so I'm going to go into my text editor. Whoops. So the grab pickups script. So grab pickups is a component that's attached to the character controller because he's going to be picking up pickups. And what the grab pickup script effectively does is the character controller built-in has this function that you can define for it called onController collider hit, where anything that collides with the controller's collider will trigger this callback function. And you can grab the information about the object that you collided with and then perform some sort of logic on that. And so it's actually calling this function every single time we collide with any of the tiles or the blocks in our scene as well. There's just no logic to account for them, so it's just effectively an empty function call. But if it's the case that the game object has a tag of pickup, which we've set in our Unity editor, and I'll show you how to do that, then we should play a sound from our pickup sound source, and then we should, we actually used this in the last lecture, but only within the same scene. We're going to call scenemanager.loadScene play. And you need Unity engine.scene management using Unity engine.scene management at the top of your script in order to use this. And load scene effectively just will literally just load a scene by its name. And we're doing that in a couple places. So we're actually doing it there, but remember we had the title scene, which had the same sort of thing. You press enter and you load the play scene, right? So this load scene on input component that I created is attached to a text field in the title scene. And all we're doing here is in the update, we're just saying, hey, if input.getAccess submit is equal to 1, then scene_manager.loadScenePlay. Almost the same code, only in this case we're querying Unity's input. It has a global input manager. GetAccess, so it has several axes is how it defines it, different methods of input. And then it defines them by keywords. So in this case, submit is a keyword, and you map those keys, or you map those keywords to specific keys and input sources on whatever platform you're targeting. In this case, submit is synonymous with either enter or return, depending on which platform we're using. And it could have other meanings if we're exporting this to Xbox, or if we're exporting it to the web, or if we're exporting it to a mobile phone. There's a lot of different ways it changes. And so the way that it checks is it'll be 0 or 1 specifically. So we can say if input.getAccessSubmit equals 1, scene_manager.loadScenePlay. And it won't let you do if input.getAccessSubmit because it's explicitly expecting an integer, and it'll throw an error if you're trying to use it like a Boolean. So we need to use this equals 1 to test for equivalence. And that's all we're effectively doing there. Now, the interesting thing is when we reload the scene for the pickup, right, for the maze, there's a soundtrack playing in the background, and we want this soundtrack to constantly be playing the same thing and to loop, right? The sound effect. We don't want it to start up immediately again and start up like from the very beginning again. We kind of want this seamless sort of feel to it. And so how do we think we can solve this problem?
So it doesn't take any when
you reload the scene?
Sorry?
You don't want it to start over when you reload the scene?
Correct. So any ideas as to how we would do this?
for level 1 only in the beginning or something? Is that what you're saying?
Well, so whenever we collide with the pickup, we reload the scene completely from scratch. And so when you reload a scene, it destroys every game object in the scene, including all the objects that have audio sources attached to them. And so when it reloads the scene, it reinstantiates all the game objects in the scene, including those with audio sources, and re-triggers their playing. So what we want to do is prevent this from happening.
So just have a counter, and when you get the first pickup, then it goes to 1, and then you say if less than 1, play the sound.
That will have the effect of, so you're saying have a counter, and when...
Or true false would be, Boolean would be better at this.
So have a counter or true false. When you load the scene, it starts the music. But what happens when we reload the scene from scratch and the audio that was playing gets deleted?
Can you transport certain objects between scenes?
Can you transport certain objects between scenes? Effectively, you can. There's a function called don't destroy on load, actually. So with that, it's a Unity function, which allows you to preserve an object as it is between scenes. So if you don't want your scene with the music to, or your object with the music to destroy itself and then reinstantiate on load, well, technically just don't destroy itself. Just do don't destroy on load at the game object. And so this don't destroy, we apply this to our audio source, our whisper source it's called, in the scene. The only problem with this is if we reinstantiate, or if we don't destroy on load this object, it's going to persevere. But when we reload the scene, it's going to instantiate a new one. So what's the effect of this going to be? Going to have 2 audio sources playing at the same time. What happens when we do another one? You're going to have 3 audio sources playing at the same time. So for every time you go to a next level, you're going to add the same audio track to the scene. It's going to be very annoying very quickly. The way that we avoid this happening is by making what's called a singleton. And so what a singleton is a class that can only effectively be instantiated one time, right? And we do this by creating a static variable here called don't destroy. No, we called instance, which is of type don't destroy. So it's this component here, right? And so the don't destroy class as a whole has this static variable called instance. And we set it to null by default when we haven't instantiated a don't destroy component yet. And what this ensures in our scene, by the logic we have in the awake function, awake is almost the same thing as start. It just means whenever you can pause an object and it'll awake from its pause state, but awake also gets called when an object gets instantiated. So if the instance is set to null on awake, instance equals this, so this don't destroy. So whatever this is being called from, this don't destroy will be the instance. Whatever the first don't destroy component is in our scene, the very first maze that we generate. The sound source instance will be this. And then we set don't destroy on load for the game object that is holding that don't destroy component, right? That audio source. But if the instance is not equal to this, so if we've awoken, and this is level 2, for example, instance is going to be set to the don't destroy component on the don't destroy on load object that we created in the first maze, right? Because we did this logic here. And so it's going to try and instantiate a second don't destroy component. It's going to another sound source. But instance is not going to be null. Instance is going to be equal to that first object. So we say if instance is not equal to this, destroy game object. So this is going to be from the standpoint of the second don't destroy that got created.
So the singleton basically persists.
The singleton will persist indefinitely upon its first instantiation. And there will only ever be one singleton. This is a very basic, very common pattern in software engineering for ensuring that you only have one object of a given type present throughout your entire project. But this is how we prevent multiple sound sources from being instantiated. We always ensure that only one object of that with that component gets instantiated at once, and any future instantiations of that object get destroyed immediately, assuming that they aren't that first object. If they are that first object, instance will equal this, and so it'll still skip this part, and so it'll stay alive. So any questions as to how the persevering through multiple scenes works for their sound source? Okay. That's how we get multiple scenes. So fog. We looked at fog already, but I have a few screenshots here to kind of help illustrate what fog has looked like over the years. So fog looks pretty unconvincing in this screenshot. This is Turok for the N64. It's just kind of looks as if, sort of at a certain distance, a very dense sheet of fog has appeared. And you can actually make this happen in Unity by setting the, there's a curve, a fog curve that I believe you can manipulate that will effectively, the algorithm that determines how the color gets summed to things far away is very fast as opposed to gradual or linear. So you can make it just like exponential effectively and make it look as if the fog is incredibly dense and starts almost at a very fixed spot and have the rest of this area sort of in front of you look normal. Here's another example, Star Wars Shadows of the Empire, one of my favorite N64 games, which has sort of the same look. And so in this area, you can see fog is very distinguishable, very artificial looking because it's very tinted. In this case, it looks very blue. In this case, it looks very like pale blue. This is Silent Hill, and Silent Hill looks realer, more realistic, but kind of the same thing at play here. You have a very pale gray metallic blue color, and the density in this case is very high. The density is much higher, well, maybe close to as high as it is in our game that we're showing today. But it's effectively the same thing, just with a different color. And they used it to great effect in here, not only for sort of this aesthetic to make you look as if you're in some sort of desolate town, but also to dynamically load objects or to prevent rendering objects that are a certain distance away and to optimize performance on the hardware that was severely limited at the time, which was PlayStation 1, which was a fairly weak console. And then here is Shadow of the Colossus for PS4, which just came out not too long ago, and we can see fog is still being used, but it looks photorealistic. and there's probably a lot more that they're doing. They probably have several layers of fog. They probably have textures and transparent objects that are simulating fog and a lot of more complicated things like that. Fog that only hangs at a certain distance, so it looks like fog going over the lake. There's a lot of things here, but it's the same idea, and they probably have the same sort of foundational base fog present throughout the scene. And then here's our game just to show how it looks like. You can barely even see it, but it does give you this sort of like lost in a really dangerous maze feeling, which and it's super easy to do, and it can save you performance, and it can add a lot of aesthetic to your game. And so the last big thing we'll talk about today is Unity 2D, actually. So I'm going to go back into questions about fog. I know that was a pretty high-level overview, and we've already looked at fog. We looked at how it applies in the settings. Any questions as to how it works or how to get it to work in Unity? OK. So we're going to go ahead and look at our title scene. And so we looked at this earlier briefly, but I'm going to go ahead and show you the components. So I'm going to take a look at our canvas. If you double-click on something, you'll zoom out. And so it'll automatically detect sort of what your resolution is and scale the canvas accordingly in your scene view. There's a 2D button here. I'm going to go ahead and go to my default layout. I'm going to click on the canvas. Notice that it shifted things a little bit because now I have a larger window that's going to be rendered to. I'm going to click on the canvas, and then I'm going to go into 2D mode. And then notice when you click on 2D and 3D mode, you go like instantly into like seeing it as if you're manipulating it in a 2D engine versus a 3D engine. And then going back to 3D, now it's a three-dimensional plane that you're actually looking at. So in 2D mode, you can easily sort of navigate it, right-click, and drag it around. I'm going to go here like this. And these are very simple components that you can just interact with as a GUI. Now, the main thing that you need to get any of this to work is the canvas, which is here. So if you right-click and then go to UI, you can go to Canvas if you want to, or you can just add any of these things that you want, and it'll automatically add a canvas for you, because a canvas is necessary for all of the Unity UI rendering stuff. So if I were to just add a text on an empty scene, it'll just create a brand new canvas and an event system. The event system is just how Unity talks to the canvas and all the UI elements of your canvas, given mouse and keyboard input and stuff like that. It's nothing that you necessarily have to worry about or use. But the canvas is the sort of overall container for all GUI stuff that you do. Now, if I click on the title text or the enter text, notice that they are children of the canvas. So they are within the canvas. The canvas is their parent. The title text, I can move it around. Notice that it snaps, right? It's got some nice snapping functionality. I can set it up there. It'll snap to the top. It's pretty handy. You can scale the bounding box. It doesn't scale the actual text, but notice that I do have like right justification, centering, left justification, those sorts of helping the sort of features. Right? I can increase the font size via a slider, right? So I can immediately see, without having to edit some code and then reload the project, what changing some of these values will look like. I can easily change the color in real time, so I can get a sense of how that looks. If you wanted some sort of slimy Dread 50 look, I guess. And you can also assign materials to it as well, which is kind of cool, which I haven't explored too much in detail, but you have that option if you want to give it a material instead of a color, materialed font. Because ultimately, all this stuff is still 3D, but Unity presents it in a way that makes it look as if you're interacting with it in 2D. It's pretty nice.
So you put it in 2D form, and when you hit play, it's going to open up to that?
Yep.
And then how do you transition to the rest of the game?
So the transition to the rest of the game is in the load scene on input here. So this script that we looked at earlier, so this is assigned to one of those text labels. So I just gave it to I think it's the enter text. So I gave it this load scene on input just because it's the enter text. It seemed appropriate. Could put it on anything in the scene. It doesn't matter. As long as it has this update function, which then has this if input.getAccessSubmit equals 1, and then recall go into the project settings, input. All these axes here are defined for you automatically. And then you can choose what they map to, but submit, as you can see, positive button is return. So if submit is equal to 1, when we press return, it'll be equal to 1 effectively. And it gets mapped to other buttons depending on what input sources you have on your device. But you can check what it is on your computer just by going to axes in your input manager. So it's, once again, edit, project settings, input, and then you can see all the axes here.
So that the 2D scene, that's just a scene in itself.
It's a scene in itself, completely. It has a camera, so we are, the camera renders, the thing about Canvas is it's kind of separate from the camera, so it gets rendered onto whatever the camera is rendering separately. But the camera in this case, what I've done, because if by default we just render the camera and the UI, it's going to look just like this. It's going to look like the sky with Dread 50 and press enter. That's not the aesthetic that we want. So I take the camera, and then you can give it a background. So by default, the background is that sky, is the skybox. And so it's set clear flags. Clear flags are same thing as background. So whatever there's no geometry or anything, this clear color, clear flag, this gets drawn to before any geometry in the scene, basically. Excuse me. So clear flags, solid color in this case, and then just black using a color picker. So super easy, super nice. And then this UI, this canvas, will get drawn on top of this camera. So that's what produces the sort of combined effect of having the UI text and then the black background. And then that enter text having that component that checks for the submit input, because that's what enter and return map to. That is what lets us transition from the current scene to the play scene. And so there are a lot of other cool features that these like labels and such have. For example, being able to set its anchor position. So depending on what device you're shipping to, you might want, you know you're going to have multiple screen sizes and screen resolutions. So you can say, I want this label to always be at the very top middle of my scene. And I can do this by clicking this little box here, which is the anchor point selector, and then just clicking that. And so that'll always anchor Dread 50's text at the top middle, no matter what our resolution is. It'll always be there. And there's a lot that you can do on top of that. And you can do that with any UI component, just relative positioning depending on the resolution. And the nice thing about Unity 2, if you go to game, you can actually choose, in the second menu, you can choose a lot of aspect ratios. So 5:4 doesn't look that great. 4:3 doesn't look that great. 16:10, 16:9, and then standalone. So standalone is the default export size of your platform. But you can choose, you can have it, you can test different resolutions, and you can also add more too. You can add a fixed resolution if you want, or an aspect ratio, and do a lot of cool things that way. So you don't have to necessarily test it physically on different devices, although it's very good too, so you can make sure that you're not blowing up your hardware, but you have that option. So any questions as to how Unity 2D works and how the canvas works, or how we've gotten this simple UI to work? Part of the assignment will be, and we'll take a look at that now actually. So assignment 9, we talked about this already, about the gaps in the floor, but this will be part of the maze generator, right? Because it's where we generate ultimately, or the maze instantiator, the actual part of the maze generator that creates the physical maze. But create gaps in the floor. And then when the player falls through, approximately 2 blocks below, which so you can check the transform is the Y positions less than a certain amount, right? Which should be less than 0. I think it's based on the top part of it. Then you should transition to a new screen that says game over. So create a new scene, very similar to the first scene that we looked at, which was just the title screen. And you can probably copy most of that. But that scene should say game over. And then pressing enter there should load the title scene, right? And then lastly, add a text object to the play scene that just keeps track of how many levels you've navigated through. And you can probably do this with some kind of static variable. But any solution that accomplishes it is welcome. But altogether, all pretty easy pieces to put together. That was this week, which was Dread Halls and our first foray into first-person games. Next week, we'll look at Portal. It won't look necessarily this good, but it'll look similar to this. This is a screenshot from Portal itself. But we'll look at how we can render to textures, how we can cast rays from our character, our first-person controller, how we can actually make it look as if we have a weapon or a gun or a portal gun, which is, you know, not too difficult. You just have to parent basically a model to your first-person controller. And then when we walk through a portal, how do we transition from from one portal to the other portal? So just teleport your transform to another position. But that was that. Next week is Portal, and I will see you all next time. All right, welcome to GD50. This is lecture 10. Today we'll be talking about Portal. So Portal is a very iconic game. I think most of us have probably seen it before. The gist is you have a portal gun, a gun that shoots just these elliptical portals. If you look through one, you can effectively see what's sort of coming out the other one, which is pretty cool, and vice versa. And then if you walk in between the portals, you'll actually be teleported to the other side. And so they achieve a lot of really interesting effects with some pretty cool tricks and stuff. And actually, Valve themselves will be coming to give a talk on a lot of the technology that they used on the second, so we can get a glimpse into their version of Portal. My version of Portal is a bit simpler. But we'll look at a lot of the same sort of principles and see how I accomplished a lot of the same things. So this is also the last lecture of the semester, and we've covered a lot of ground. I have a few screenshots here to show some of the games that we've talked about. You know, the very first game was Pong, and we've come sort of a long way. We've gone through very simple sort of arcadey, Atari-like games like this, and have gone and created worlds effectively, and now we're in 3D. We're doing all kinds of awesome stuff. But this was where we started the course. And it's kind of fun to look back and see where we've come. So, here we talked about scoring and just effectively drawing shapes onto the screen. Then we transitioned to Flappy Bird, or 50 Bird, and we had sprites and characters, and we talked about scrolling and infinite level procedural generation type algorithms, and that was fun. We took things a step higher than that with Breakout, where we had the same sort of procedural ideas in the context of a very famous arcade game. We talked about particle systems and some arcade-style physics and high scores. Then we went into puzzle games. We talked about Match 3 and how to actually calculate what goes on to determine whether we've gotten a match, and how to clear blocks, and how to tween things, do operations over time, so this asynchronicity. Then we went into probably what is my favorite lecture, which was Super Mario Brothers, and we talked about how to create procedural worlds that all look very different with some very simple algorithms. And then we had triggers and events sort of happening. Then Legend of Zelda came, and we had this infinite dungeon algorithm, and we had enemies walking around that we could use a sword on, so it felt more like an actual action game, action RPG. Then we took a brief look at physics in the context of Box 2D with Angry Birds, and I still remember the ball pit example was probably my favorite part of that. And then probably the most complicated example of the semester was Pokemon, where we actually had a semi-full turn-based battle system, and random encounters, and like a little world where there's actually two main stages to our world, where there was the field and the battle scene, which is a very common thing to have in RPGs. Following Pokemon, which was the most complicated code base, we went into Unity, which was our first foray into 3D. And even though we were just exploring 2.5D, we still got a chance to look at, how does the Unity engine work, and how do we get actual 3D models onto the screen. And we put together a very simple Flappy Bird-esque game so that we could sort of recycle prior ideas. Last week, we looked at Dread 50, which was sort of a Dread Halls horror-inspired game where we got to look at lighting and how to actually transition between scenes and use some basic UI in Unity. And today we'll be talking about how to create a game similar to this, although much simpler. Today is mostly just a tech demo more than anything else. But this is a screenshot of the actual game Portal. And as you can see, they do a lot of really cool fancy things. They have a portal on sort of a slope. They have another portal coming out of the front wall or back there, different colors, so you can differentiate between left and right, orange and blue.
they have sort of this object here on the side, and I believe that's to shoot cubes out, which this here is a cube, which you can then grab with your gun and then shoot it through portals and see it come in and out of portals, which is pretty cool. And we'll talk today about how to create sort of a simple version of this, primarily just the aspect of how do I create a portal that looks out of another scene and see it updating in real time, and how do I teleport and get back and forth between the portals and carry a weapon and then shoot a ray that'll actually place a portal where I want to in the game world. So today some of the topics we'll talk about. So one, holding a weapon. So we've used a first-person controller, and this is a very easy and simple thing to do, but it helps illustrate what parenting is, and so we'll talk about that. Ray casting is the actual shooting out a ray from your object's Z direction forward. So you have an X and a Y, which are sort of the angle at which you're moving around, but then you have Z, which is always, if you're using the forward vector from your character, it's going to be forward in the Z axis wherever you're looking effectively. And so that allows us to, we can cast a ray in that sense, which just means, shoot a straight line, an invisible straight line from that point, and wherever that point intersects with an object, we can get some information about that and then do whatever work we need to do. In this case, take a portal prefab and just like affix it to the wall, basically. Rotate it from its default position and then just like put it flat up against a wall. Texture masking is sort of how we're going to achieve this portal effect, right? Because when we create what's called a render texture in Unity, which here's the third bullet, a render texture just means a texture that we are rendering to with a camera. So rather than have a texture be an asset in your game, in your hierarchy, with something that you've made in Photoshop, you can actually dynamically create it at runtime with what the camera is seeing. And Unity gives this to you for free very easily with what's called a render texture, which is just another asset type. And then texture masking is effectively sort of kind of the same thing as stenciling, where we can choose certain pixels of an object to delete. In this case, we create a texture that's white in the center and then black around the edges in a sort of elliptical shape. And what that allows us to do is tell it with a simple shader, don't render these pixels when you actually render the render texture, just render the ones in the middle. And so that's how we achieve an ellipse, just by effectively discarding the pixels on the outer rim. Decals is an idea in 3D games where a decal is just something that you affix a texture or some object that you affix to a surface. In this case, we'll be using decals to act as our portal. So our portals are actually just going to be decals. They're just meshes with a render texture affixed to them. And then all we need to do is just sort of slap them onto a wall whenever we shoot it, and we get a ray that intersects with the wall. And that'll have the effect of actually making it look like we're putting a portal on a wall, when in reality we're just taking a mesh and we're just kind of like slapping it onto a wall. Some other examples of decals that you've probably seen in other games are, for example, bullet holes, which use the same principle. Teleporting is very easy, although the FPS controller sort of complicates things a little bit. So we'll talk about how I went about sort of solving the problem of teleporting in a way that makes sense. It's usually just as simple as a change on the, setting something's transforms position to another transforms position, setting the rotation to the transforms rotation. But the FPS controller caches its rotation data. So in order to do that teleport cleanly, you sort of have to override some default behavior. And lastly, we'll take a look at some new tools that Unity has introduced with 2018.1, Pro Builder and Pro Grids, which allow you to actually model geometry in the scene. And this is what the assignment is going to be focused on. Because going forward, I foresee it being a major part of sort of modern Unity development and or prototyping. The ability to model your scene in Unity without needing a third-party program heavily optimizes the actual creation process and allows you to do easy what's called gray boxing, meaning create a level create a level in your game engine and then prototype it, test it, make sure that it's actually game playable right off the bat. That's called gray boxing. But first, let's get a demo. So does anybody want to come up here and play my implementation of Portal?
I'm landlocked.
That's true, James is landlocked. All right, James, you're not landlocked. Let's go. All right, so I'm going to go ahead and set that up. And so disclaimer, there's actually a bug in this as well, so I'm curious to see if you can spot what the bug is. Okay. Go ahead and hit play as soon as you're ready. And then the mouse on the right will be your sort of angle of your portal. So we see here I have a character with a portal gun created. So if, James, if you shoot a wall with the left mouse, that'll create a portal, and then if you use the right mouse, so that's one other bug. So let's go ahead and restart the program, actually. So that's one bug. And so if we avoid stepping into a portal that's there, and this could be fixed in a couple of ways. So now you have two portals basically created. Do you see what's wrong with the portal as it is here? Both of these portals, actually?
Characters invisible?
Oh, actually, no, I'm sorry. These portals are actually completely right. But walk through them, and I will show you. Okay, so you can see it works pretty well, right? You can not only see your character rendering completely or moving in real time when the other texture, but you can jump through them or walk through them. You can jump with spacebar if you want. And that'll teleport you out the other end so you see from the perspective of the other portal. But if we try shooting one of the other walls, for instance, like one of these white walls, you can see something weird happens with this particular wall. Anything strike you as odd about that portal? Anybody? It's upside down. And so if you walk through it, though, it works perfectly fine. Now, the reason that it's upside down, I spent probably like 10, 15 hours trying to debug why this is. It's in a state of what's called gimbal lock. So this prefab right here, there's 3 axes of rotation in 3D space. And if you perform a rotation in some odd way, there are these things called Euler angles, which are your angles of rotation about the x, y, and z axis. And you can sort of think of them as sort of being able to rotate interdependently. But there is a situation in which you can, for some reason, Unity's internal representation of a rotation can get messed up by manipulating these angles. And so you can actually lock 2 axes together such that rotating, like for example, in this case, it's z and y, they both rotate each other. And so you're unable to get, in this particular case, the portal to rotate about the axis that lets it look like it's right side up based on the wall's surface normal. And so had I maybe another week, it probably could have debugged it, but I had to leave it in. Unfortunately, I ran out of time. But if you don't, the interesting thing is if you do shoot that same wall, so try and shoot that wall, the other wall with, put one portal on the buggy wall, so the right wall. It's only that wall, by the way, for some reason. So that wall is a bit, so notice that now it's right side up. So if you shoot both portals on the same wall, that buggy wall, they do get right side up. And I, for the life of me, couldn't ascertain exactly as to why. I know it's gimbal lock. Unfortunately, I was unable to debug it quite in time. But every other wall, including the ceiling and the floor, will work if you shoot a portal up on them. So you can create one up there, and then you can jump through it, see how it's looking down, and it'll sort of put you at the top. And altogether, minus the weird single wall that gimbal locks the portal, we have a pretty functional implementation of a very basic portal game, right? We have this model here is parented to the camera, so it's always going to look in the exact same direction as the camera. We shoot a ray from the tip of the gun, and then whenever that ray intersects with a plane, in this case any of these walls, we get the information about the intersection, and we flip the decal, the portal decal, such that it's the same angle as the wall rotation. And then what happens when we actually collide with one of the portals, just in code, if we were to think about how to implement like the behavior that goes on here?
It's transporting the player?
It's transporting the player, and it's doing effectively setting the player's transform position to the same transform position as the portal. Now, if we do the same thing on the rotation, the player ends up getting the FPS controller's rotation gets a bit skewed if you mess with its X and Z rotation, the default controller. So all we do for now is we keep those values, the X and Y rotation, but we just change the Y rotation. Y rotation is his position in space like this, effectively. So that allows us to get, when we jump out of the wall, we notice that he's sort of like flat from it, but if we jump through any of the wall portals, so if you like create a portal on the wall here, and then jump through it, you'll notice that you sort of get you're sort of angled at the right, and the reason that it's skewed is because this one's upside down. And so it's flipping the camera that's rendering the texture, and it's looking a little bit weird. But when you jump through, it basically keeps your X and Z, but rotates your Y position, such that you come out looking as if you went straight through the portal, rather than
by default, it has you look back at the portal that you came out of, which is a bit weird, or whatever direction you were walking through it when you went through the portal.
How are you getting the mirror sort of thing so you can see yourself?
That's just default, because it's rendering it's a render texture. So there's a camera actually behind each of these portals. So the prefab is a mesh with a render texture, and then behind it there's a camera. And so the camera is rendering in real time what's in front of the portal, basically, from behind it. And so it's seeing your model from both of these portals. Both cameras are seeing your model, and so it shows up in the render texture on the other portal. So it's effectively like looking at two video cameras instead of a portal. It's a sort of a trick. And this is a very crude implementation of Portal. The actual game uses a much more sophisticated algorithm for, and it also tracks your position with the camera, so that, like, based on your angle of rotation, you'll actually see something different on the texture there. But it's a lot more complicated to put something like that together. I have some resources that I've included in the lecture and the assignment that'll show you actually how to do that. But it would take many, many more hours than I had to put this demo together.
Right now it's just fixed.
Yeah, it's fixed. So if you actually look at it from the side, you'll notice that it's like just a flat texture. There's no perspective. Ultimately, it's perspective. And there's an awesome video that I'm going to show later in the slides by a YouTuber named Brackies, where he actually implements a perspective correct shader that allows you to see, and with camera tracking of the player, like both cameras will track the position of the player as well as render a texture. And the result of that is, because the cameras are changing their position, it's sort of like changing the angle at which the scene is being rendered onto the portal mesh. But also the way that it's being drawn is a little bit different. And so he has a really cool shader that does that. And then Valve, when they present, they'll actually show how they went about doing it, which is even more complex, but looks really good and is a lot more, technically interesting. But yeah, that's my sort of implementation, bare bones implementation of what makes Portal work. So, and it's somewhat fun to like walk through these, walk through these portals and just sort of play around with it. Now, the reason that if you just walk into a blue portal, it doesn't work is because the portals are actually stored off screen until you use them. And so a way in which, so I'll open up the scene here. Oh, by the way, thanks, James, for coming up to demo. I appreciate it. So the portals are over here, right? Both of them are right here. And so what that does is when you only shoot one of them, the other one is still out here. So when you walk through it, you end up just teleporting outside the level. And in order to not have that happen, what you really need to do is have a flag on both of them that just says, don't teleport unless they've been shot once, right? And that'll prevent that sort of behavior from happening. Simple fix, but an entertaining one to take a look at. And that is my crude implementation of Portal. It's far from being anywhere near as polished as the actual game. And there is the slight weird wall that gimbal locks the portal, which I would like to figure out why exactly that is. But everything else is sort of in here. Now, it doesn't include something like shooting blocks through it, but the same sort of principles would apply, because all we're effectively doing on the portal is saying, it's basically a trigger, right? It's got a box collider on it, and it says, if I collide with something, and in this case the player, I want to teleport that collider to the other portal, which means that the portals sort of have to link to each other, right? One portal has to have a reference to the other portal so that it can say, teleport to the linked portal, and vice versa. The linked portal should have a reference to the other portals that can say, teleport back if you collide with this. And so if we have another object, like say we shoot a cube into the portal, it would also get teleported to the other portal, right? And now the other consideration for that is, like, if it's a rigid body and it has physics applied to it, for example, let's say it's going like 10 on the X and it teleports to a portal that's like perpendicular to it, and it's still going 10 to the X, then as soon as it shoots out of the portal, it's going to go straight left, which isn't the behavior we want. We want it to go forward. So it's like linear velocity needs to be calibrated to go in a different direction. Didn't have enough time to put a full demo of that together, but if you were curious, in a nutshell, that's sort of like what you would need to do in order to implement like some basic physics with Portal. So holding a weapon, based on the screenshot, can anybody tell me how they think I went from just a plain FPS controller to an FPS controller holding a gun?
You just stick a gun, like one one unit in front of the camera.
Yeah, there's not really a notion necessarily of pixels in 3D space because that changes depending on your resolution. But yes, Unity units, so it's effectively equivalent to a meter, and you can change what it represents in Unity settings. But yeah, I mean, it doesn't necessarily have to be one unit, it can be an arbitrary amount. And what it really was me going into here with this model. By the way, got this model on the asset store for free. So the asset store is an awesome place if you're looking to just quickly prototype your game. They didn't have any like obvious portal gun lookalikes that looked really good. So I was just like, oh, this gun's got like the same kind of color. I'll just choose this. It's like a sci-fi kind of gun. But as you can see, there's a hierarchy here. Now, how are we keeping the gun like affixed to where the camera is looking? Do we know?
You do the same thing as you do with the first person shooter code. Is you have the camera follow the gun or vice versa.
You have the camera follow the gun. Do you have any guesses as to how we're doing that? It's actually a really, really simple thing.
I know I'm doing it, but I've never verbalized it.
So all we're doing, oh, Steven, did you?
I was gonna say, do you set the cameras like transform like as like you relate this is transform kind of to the guns transform like with an offset in like same direction but like just position offset?
Yeah, kind of. So set the guns transform to the cameras transform, but just with an offset. I mean, that is effectively what we're doing. And in order to accomplish that, it's really as simple as just making it a child of that thing. So this is the first-person character controller. It's got a camera attached to it. Anything that you parent to something, or you make a child of something else, it's going to have the same transform like changes applied to it, including rotation. So by making the gun just a child of the first-person character, which is where the camera is here. First-person character, by the way, is just a subcomponent of the FPS controller, which I've renamed to Portal Gun FPS controller here. The portal gun, anytime this first-person character is rotated, which is the camera, so anytime the camera is rotated, it applies that rotation to the portal gun here, this gun mesh. And so that gives you the effect. So what you do is you start it off by, you figure out, okay, you start off in 3D space like this, you're looking at your game scene and you have your character, and then you move your gun object around. In this case, let's go to layouts 2x3. So we can see it in real time. See, this is the game view. This is what it's going to look like on startup. I'm going to go over to my editor view here. And I'm just going to grab the actual gun component here, the gun object, I should say. Go in and position it, and I can just move it, right? And so this is how you can like change where your gun is relative to the camera. And this is going to affect sort of how it feels, right? Like I could put it here and it's kind of a little lower. I could put it here. It feels a little weird, obviously, because it doesn't have a hand on it. So it's kind of almost looks like a VR game. And that's kind of like what VR games do is they take your hand positions and then they like, the gun transform is locked to basically where your hand controllers are. In this case, all I did was I just positioned it. I said, I like how it looks right here. So I'm just going to do that. And as soon as I make it a child of the first person character, which is the camera, it's just going to get all the rotations applied to it. So anytime we make any rotations to the camera, which I'm doing here, it stays exactly aligned with the camera. This applies to any operation that you do in Unity. When you make any sort of transform, position, scale changes, they all get propagated down the chain. All the objects that are children of an object that get transform operations applied to them will have the same transform operations applied to them, sort of like this recursive kind of effect. Yeah.
So if you import the first-person controller, right, that automatically has jump and move left and right, and then you just move your asset, your gun, to be underneath that controller, it'll just follow?
Correct. So if you just import the vanilla FPS controller and then just make the gun, specifically the gun needs to be a child of this, the first-person character bit, because that has the camera, and recall the camera is what's driving our rotation, right? Because we're moving the camera's rotation with our mouse. That is ultimately going to determine how the transform gets applied to the gun. But yes. And so just whenever you're doing anything in Unity, and you'll do a lot of things where like one thing's movement or scale or rotation should apply to another thing, just remember that it's usually just as easy as making it a child of something else.
So any other questions as to how we've gone about implementing the weapon? All right. So ray casting. So ray casting is a nice feature that Unity gives you for free. It's part of the physics sort of namespace in Unity, part of the scripting API. And what it allows you to do is effectively look at from whatever transform you're operating at or whatever transform you give it as the source, so whatever point you give it as the source, you can tell a direction, give it a vector as a direction. In this case, what we're doing is we're saying transform.forward, and transform.forward just means basically wherever we're looking x and y and then straight in the z direction. So if you're doing it on a camera, it's always going to be exactly what you're looking at. It's always going to be exactly forward on the, like transform.forward on a camera is always going to be like center of the screen wherever you're looking at. And so if we cast a ray from the point of our character, or actually we're doing it from the point of our gun, to the transform.forward, like a line going from our player to transform its the forward vector of its character, the forward vector of our camera, it's going to have the effect of we can shoot something, right? We can create a ray cast and then just like affix something wherever that ray intersects, and it'll be at the exact center of our camera view. Does that make sense? So shoot a line from your z axis, which is your forward vector, and then based on how you've rotated the camera, x and y are the x and y part of that, and z is always forward, that'll let you shoot things or cast rays directly in front of you. And you can cast rays between any object and from any source point with any sort of direction you want, but it's particularly pertinent in the context of how we've shot it from our gun. And so here's a screenshot actually of what that looks like. And so the nice thing about Unity actually is it has a function called debug ray, or debug.drawRay, which I'll show you here. I implemented it in a function called a component rather called debug ray, so that you can actually see where a ray is being cast in your scene and eliminate any ambiguity there. So you can see draw ray, transform.position, and then we just say transform.transform direction, vector3.forward, and then times 1,000 just means 1,000 units, from that point, and then color.red. And so what that'll do is only in the editor view. So this doesn't apply in the actual game. This is just a debug call, debug.drawRay. And so it'll render in this scene up here, just not down here. So if we hit play, I actually have all the portals rendering a debug ray from their forward transform and from my gun. So you can see it there. I'm just doing a debug.drawRay with just transform.forward and using my transform.position as the source point. And forward is always going to be, notice that the Z arrow, it's always following the same direction, right? X and Y are sort of changing, the back plane, sort of like how that's rotated, but Z is always forward, right? And so that's the ray coming from our gun. And if we shoot a portal there and there, I have those also set to, here, let me pause it so I can rotate the view a little bit. I have those also set to draw a ray from their forward position. So those are also drawing a ray from what's their vector3 dot, or their transform dot forward, their directional vector. But yeah, ray casting, it's pretty easy just to get some pretty simple collision tests this way with guns, with a lot of different things. But primarily you'll see this used for like calculating whether something is blocking something else. Like if a car is moving and it detects, maybe if it detects another car, like if you're in Grand Theft Auto, for example, and your car is driving down the center of the road or something, and it wants to know whether there's a car 2 units in front of it or something, it just casts a ray and see if there's any geometry there from its forward vector, right? Transform.position, car.position, and then get its forward vector, which will be its Z direction. And then it depends on whether maybe your game's top down, maybe it's not your forward vector, maybe it's your Y vector in that case. But that'll effectively give you not only that you've got a collision, but also tell you where the collision is too, which is nice. And we do that in the portal gun script, where we call physics.raycast. So this is the function, by the way, to actually do the raycast. The interesting thing about raycasting in Unity is that it returns a struct object, and so you need to declare this hit object, which will tell you all the information about the hit, sort of like where it was,
whether there was a hit to begin with, and what the normal was on the surface that it collided with, so the angle at which that sort of plane was projecting out. And then you call physics.raycast with a position and a transform direction, and then you pass in out hit. So out is interesting because out is sort of C#'s way of allowing you to return multiple values to something. So out is going to be an object, in this case it's going to be our raycast hit that we declared up here, right? Which is a struct, which recall is just a collection of variables like in C or C++. And out hit just means that normally we pass in these values to the function, they don't get manipulated, right? But we pass in this variable as out, which will allow this function to actually change the data inside this hit variable. And so the result of that is hit from this point forward contains all of the information about the raycast that we just triggered. And when we call mathf.infinity, that just means raycast to infinity, which is until forever and ever. And Unity obviously doesn't check infinitely whether something's collided with something. It optimizes the right way, but you can use that just if you don't want to necessarily specify, I want to check 2 units or 5 units or 1,000 units in front of me. I want to just check forever and see if it collides with something in your scene, right? And then as you can see here, once we have detected a collision, we play a portal sound, we get the right portal, and then we set the portal's transform and rotation based upon the hit's point and rotation. And that's pretty much all that's involved in shooting the gun. And you can take a look through here if you want to get a sense of how it works, and maybe explore also the raycast, the physics.raycast section of the API, just to understand what exactly it returns and what you can do with it. But in this case, this is how we're using it to detect whether we've intersected with a wall. So it'll intersect with any sort of mesh, and then when it does, it'll tell you exactly how it did. So that is what raycasting is. Raycasting has another name for like old school games like Wolfenstein. The method of rendering was called raycasting, where you would generate one sort of, you would generate a ray from every pixel of the screen effectively, although it was mostly just every line of the screen. And you would just look up and down for everywhere it intersected in the scene, and then just draw like a texture there. And so that would generate a world that looked 3D, but you couldn't move up and down because it was always generating all arrays completely forward, and so you were locked onto 2 axes. But raycasting is different in Unity. Raycasting is just literally casting a ray in 3D space versus the sort of 2D space that it was casting in games like Wolfenstein. Here's another screenshot of normals from our portals casting out rays. And I want to look up and see if I can just find a picture of what Wolfenstein looked like. I'm pretty sure most folks are probably familiar with, not the new one. Yeah, Wolfenstein 3D. So this is Wolfenstein. So old school, but this sort of ray casting was different. It would it would basically shoot rays from every single line of the screen up and down, and it would detect based on the level geometry, which was very simple level geometry. It was just basically whether there was a wall there or not, true or false, kind of like a 2D image. And it would draw, based on how far away it was, that particular point of the geometry, it would just draw like pixels from a texture, a specific texture, at a specific point. And they had to interpolate where on the texture it was, so it was a little more complicated. But in case you see in case you see ray casting used in those 2 different senses, in the case of old school game engines, and in the case of modern Unity sort of ray casting, that is what is involved in that. So any questions as to how, sort of in a nutshell, the ray casting works in the context of our game here?
We're going to be using the glasses.
So unfortunately, no. The Oculus does not work on Mac. They do not have Mac support. And so we were unable to get a sort of version of it working. We don't have the means to necessarily transport given how much time we had. Now, getting VR working in Unity is actually very easy. If I recall correctly, I have to just remember the exact menu. I had sort of anticipated talking about this before.
I think it's player, XR settings. Yeah, that's what it is. So in order to get, so it's incredibly easy. If you want to do a game in VR in Unity and you have a PC, out of the box, it's very easy just to get it working. All you need to do is go to Edit, Project Settings, and then go to Player, and then in the XR settings, so Unity has like deemed all of its VR, AR stuff as XR, and you click Virtual Reality Supported here, and you have your Oculus Rift or Vive or whatever plugged in. It'll just work with the camera, like right out the gate. So it's pretty easy. You may have to install drivers on your computer such that your computer knows that you have an Oculus plugged in, but assuming that's all set up, your project is as easy as just clicking this checkbox.
Which headsets was this for?
HoloLens, Oculus Rift, and I'm pretty sure the Vive, like 90% sure the Vive. I'm not 100%. We can Google it though. Let's see. Unity
Special
5.
developer versions of those headsets, or is it?
More importantly, student version.
It looks like it does. It looks like it definitely does. Yeah, and of course, VR ready Windows PC is very. I apologize. I totally thought going into the course that that Oculus worked on a Mac, but as of even October, they were like, it's not going to work on any MacBook ever released, so only on a PC, unfortunately. That said, if you do have a PC, super easy to get working, and it looks like this is actually a pretty cool tutorial. I haven't looked at this, but I tend to like Ray. I don't know if his name is Wenderlich or Wenderlich, but he makes really good game programming tutorials in general. So just, because we're coincidentally here, if you guys are curious, I really like this website for basic tutorial stuff.
Are there other headsets that you work on the Mac? You have Vive?
We have Vive, and Vive, as far as Vive, the thing about Vive is you need to install like ceiling-mounted cameras in order for it to work. So that's kind of out of the equation. We have the Gear VR, but we would need to export it to mobile and test it, and it just didn't have. I didn't anticipate it not working for Mac, and so it kind of came up a bit late, and so it's on me. I apologize, but if you are doing a PC game in Oculus and you want some assistance, I'm happy to help out. It looks like it's very easy just to get working with the default FPS controller camera. So definitely reach out if you're developing Oculus and need some assistance. Maybe for the next iteration of our next Unity course, we can have a big sort of VR day where we bring in all the guns. But yeah, back to sort of ray casting and what we were just talking about. Shooting a ray on your z-axis based on your rotation, get information from it, and then sort of what we do is we flip the portal based on the hit dot rotation of the surface that we collided with, and that's effectively all the ray casting that we need to worry about for Portal. But the actual making a portal is probably the most interesting part of this whole project, and so let's go ahead and go back into present mode. So a render texture is a basic. It's not a basic means. It is the fundamental way at which we go about doing it, and there are various ways to accomplish doing it. Some that are more technically challenging and look a lot nicer than others. I did a sort of simple version of it, just to get a sort of proof of concept out of the gate. But Unity makes it really easy just to get a simple render texture up and running. So a render texture is, recall, just a texture in Unity. So it's an asset. It's a Unity asset that you can create. The difference between a render texture and a texture that you might have imported from like Photoshop or GIMP is that a render texture can be rendered to. And typically this is used for things like cameras being rendered to it. Although, from what I understand, you can render anything to it, so you can create procedural textures this way as well. But in this example here, we're essentially creating a screen into which we're looking at the viewpoint of our other portal, right? From its forward direction. So we can see what it will look like once we walk out of the portal and go into the next area. And so a render texture, so I have some in the slides. If you want to download the slides, they're here. You can see exactly how to create a render texture. So literally just create and then render texture. That creates a render texture. These are the settings that I used for the actual render texture. So what'll happen, do we think, if we use like a low-res render texture? Just logically. And let's say, what if my render texture was like 200 pixels by 200 pixels? And our resolution of our game is like 1080p.
Will it just like be like blown up?
It won't be blown up because what we're doing is we're taking a mesh and we're affixing the texture to it, so it'll just scale to fill the mesh. But what'll it look like when it's rendered? Because it's rendering a 200 pixel texture. It'll look pixelated. It'll look really like nasty. And so in order to fix that problem, typically what you'll do, a smart way to do it would be to dynamically figure out at runtime what's the resolution of your game, right? If it's going to be rendered in various resolutions, up to 4K, maybe down to 720p, and then create a render texture that is the size of your game. And then by doing that, it'll ensure that no matter what your resolution is, it'll always be 1-to-1 pixel ratio, even if you're right up close to it, right? It'll fill up your whole screen. In this case, we went for a simpler method so we didn't have to do any dynamic instantiation of the render texture, which you can absolutely do, and it is the more robust way to do it. But in this case, I just chose 1024 by 1024, figuring that that was going to be good enough for demonstration purposes. And most of these other settings, I believe actually all of these other settings are completely default render texture settings. The only ones that changed were this is 256 by 256 by default, and it just looks really pixelated and nasty, especially when you're right up close to it. And then all we need to do, so once we've created a render texture, right, in our scene, in our assets, so here I'm going to go to textures. This is where I'm storing all my textures, whether they're render textures or not. I have these two render textures here. And so these are, by default, they're not going to be mapped to anything because they're just empty render textures. We effectively allocated them and said something will be rendering to these later, but for now, they're just empty. They're just placeholders, right? They're like blank screens, but the TV hasn't been turned on yet. In order to actually render to them, we go into our first-person character, or sorry, not our first-person character. We go into whatever camera we want to render to the render texture, because we're effectively taking these render textures and we're rendering a camera view onto them, right? Each of the portals has a camera behind it looking out from it, and so we want to take that camera's view and we want to render that onto the other portal's face, the other portal's render texture, the texture that we're going to put onto it. And so all we need to do is say, here's my orange portal, I have my camera here. Every camera has a target texture just right out the gate. So you can just say, okay, I'm going to take my orange portal texture, my render texture that I've instantiated, so it knows that it's going to be able to receive an input source, and I'm going to just click and drag it there. And it's that simple. Now, whenever you run the game, you'll notice that your render texture updates. I'm not sure if it updates in real time in the inspector, but it renders if you're showing it onto a, yeah, it doesn't render in the inspector, but it will update if you've affixed it to any other surface. And so what we're doing is we're affixing it to the meshes that are associated with each portal. James, did you have a question?
Yeah, how did you make the just blank texture that you...
Oh, sure, the render texture. So I just right click, and then I go to create, and then a render texture right here. And that'll give you most of the settings that you need to get up and running with it, and you can assign it to a camera. But the important thing is do consider your resolution for your render texture. Make sure that it's high enough such that your game won't look pixelated when you're looking at it like pretty close up.
So it's as easy as that, you just make the texture and then drag the camera.
Yep. And so that'll do is create a link between the two such that anything the camera sees, it's no longer going to be rendering to the scene or anything like that. It's just going to render to the texture. And actually, I think you can render to the scene and the texture, but these aren't rendering to the scene at all. The only one rendering to the scene is the first-person character because it's the default camera, main camera.
What happens if you set the resolution too high on the render texture? Like it's 4K resolution on the render texture, you're playing at 720p.
If it's too high of a resolution, it's just going to like compress to fit the mesh, whatever it's affixed to, and you'll probably run into performance problems, but it's not going to break. Yeah, because you're not affixing it to any, because your resolution, it doesn't really have an effect necessarily on whatever's in your game world, and like that doesn't cause any issues. It gets interpolated, like Unity will just like calculate how to render it to the screen, right? Yeah. Like game textures generally are very high resolution, like 4,000 by 2, like 4K textures are often used even if you're running your game in 1080p. And our game engine will probably optimize it and like downsample the texture so that it is like actually a 1080p texture, and you don't like, you're not trying to calculate more, draw more than you need to. But Unity will figure that out for you. You don't have to worry about that. But yeah, that's what a render texture is. And that's how we are creating this illusion. Remember, everything in the game is an illusion. In this case, we're not actually, and it's obvious in this example because we're not actually, because the textures are flat and there's no perspective correction, you can see that it's a texture, even if it is slightly convincing from far away. Like from far away, it actually kind of looks, I mean, I don't know if it necessarily looks real. I mean, it kind of does, right? Like from here, it's hard to tell. And from here, it kind of looks like we're going into another room, right? If I go like that, that's the broken wall. If I go like that, right? There's a portal there, and it kind of looks like it's a real room that we're walking into. It's just a resolution, but all we're doing is we're just drawing a camera's view onto that texture in real time. And if you notice, you can see our gun. It's kind of hard to see, actually. See if I can do it from there, maybe. Yeah, there I see a little bit better there. When we move, we can see the gun, so we can see that it's rendering in real time. And that's the power of a render texture. And this will allow you to do all kinds of things. You can have like, TV screens in your game that are rendering another part of your scene. Obviously, an example like this where you have a portal looking into another area. Now, if you apply a perspective correction to this, whereby your camera actually tracks where your player's position is relative to the portal, you can accomplish a much more believable look. And you can actually make it seem as if you're looking into another area because the camera is literally moving with your player. So the camera's, like the stuff that it's capturing is going to be changing in real time, not only just your character's model, right? The actual angle is going to change and therefore be perspective correct. And there's a awesome tutorial that I'm going to link to in the slides that'll show you how to go about doing that. And it's really awesome. And so this is what it ends up looking like. This is actually before I changed. One of the portals had a slightly offset camera angle. So you can see here, this is like a little bit higher than this one is, even though this should be exactly the same, but it's fixed now. So texture masking. Oh, also, any questions about any of that process before we talk about texture masking? Okay. So texture masking is basically the process. So if we just take a plane and we put a render texture onto it, that's what it looks like. It just looks like just a square. And this could work fine if you want sort of a square portal look. You don't have to do any extra work. But if you want a circle, right, you can't really create like a circle-shaped plane object. That doesn't really exist. And even it did, it wouldn't be efficient, especially if you want a very smooth plane, because everything is triangles and polygons, right? So if you have a circle, it's going to be a bunch of these sort of fanned out polygons, especially a very high-res circle like one of these. That's a very high-res circle. Making a polygon that looks like that is not an optimal way to go about solving that problem, right? A much more optimal way to go about solving that problem would be to designate certain pixels of some texture as being pixels that we want to read, and then certain other pixels as being not pixels that we want to read, and therefore produce the final image that gets put onto a geometry, right? And so what we end up doing is creating an image first. So it's this image, which is kind of hard to see, but it's just a simple sort of, can you guys see it from the, yeah, you can. So it's just a simple oval, right? It's the exact shape that we want our portal to look like. And the pixels that are white are the pixels that we're going to render. And the pixels that are black are the pixels that we don't want to render. We want to consider those as like pure 0 alpha, effectively. And using a awesome shader that you can get for free just easily on the Unity webpage. This is just a masking shader. And I'm not great at writing shaders. But what this does is it turns lighting off, first of all. What happens if we have lighting applied to our portals? Going to look a little weird, right? You're going to get like shadows cast onto your portals, and that doesn't make sense, right? Because we're effectively supposed to be looking into another place, another area. So if we have shadows that are being cast onto our thing, we're effectively like almost seeing like a glass door on our portal, right? It sort of breaks the illusion. So lighting should be off. A lot of these things I'm not 100% on because I'm not great at writing shaders, but it's a very simple, easy shader that you can grab off of the Unity webpage, and I think I clipped the URL here at the very bottom. But I grabbed that off of the Unity web page, and all it does is it adds onto your material this second image here. And it gets blown up a little bit because Unity makes any texture that you apply to, basically any texture you put into like an image selector will get made into a square shape, and our image is not square shaped. But what this does is when you pass in this image, which is called a culling mask, it will basically combine the two images and then cancel out any of the pixels that are black on this. It'll effectively add the black and white to the alpha of the texture pixels, right? So you can actually make some of these gray, and then that'll have the effect of sort of making it half transparent. But in this case, I only went with full transparent and full hard 255 alpha. So we get sort of a crisp outline for our portals. And that's how you end up putting together a basic sort of oval shape on something that is just a flat mesh. And you can do this with anything. Anytime you need to sort of take away detail that would make making a mesh extremely difficult or doing really cool effects, it's often just a lot easier to create a mask for it and then use the right shader that's meant to have that mask, and then just manipulate that however you need to. And again, the link here for the shader is here, and then you can use this for pretty much anything you want. End result of that is we go from having a square portal to a elliptical portal. So pretty nice. I didn't have to use a plane, but it doesn't really make sense to use anything else. Because using a cube, it would create depth. We don't want the portal to have any depth really, right? It's just be a flat surface. And then when we go through it, it's just teleport us to the other surface to make it look sort of seamless. I don't think there's another choice of geometry that makes sense for this use case.
You wouldn't just make a cylinder flat and have no depth and then project on it?
No, I probably wouldn't. Make a cylinder flat and project it and have no depth on it. You would be able to still see the rings on it, and also texturing that is a little bit more complicated because then you'd have to UV map your both your sort of mask and your regular texture onto that, because by default it's going to wrap it weird just because this is just a plane, so whatever you texture map onto it is just going to be completely flat. But a cylinder is going to wrap it around all sides, and it's going to look a little bit funky. I suppose in theory you could use a cylinder for it, but I think it would be a tremendous amount of work. I don't think it would be anywhere near as easy as getting it to work with just a flat plane or a mesh. Interesting idea though. I guess you could theoretically create a cylinder that has, if you wanted to, like a bridge between two worlds and have one end be one portal and one end be another portal, and then be able to walk between them. That's a cool idea. Maybe you can make that work. But I think for this, the plane is the right way to go. Any more questions as to sort of how that works? All right. So we'll talk about teleporting now. So teleporting is pretty easy. All we really need to do, right, is just create a mesh collider on the portal mesh, the orange portal and the blue portal. And then when that mesh collider, if that mesh collider is a trigger, right, and it detects a collision with something else, we can just define on trigger enter. And then with that, we can teleport the collider other to the other portal's location. So every portal, this is the portal component. It has a linked portal, right? Because we need to know where to teleport the player to the other portal. So we need to have a reference to its transform. Whether it's active, right? Because if we allow ourselves to teleport to another portal and another portal, like back and forth, just without any restraints, what do you think is going to happen? Infinite loop. We just get an infinite sort of weird flickering effect. So you need to effectively have like a toggle switch on both portals and say, as soon as I enter a portal, I should not be able to teleport back into it, right? And as soon as I teleport to another portal, I should not be able to teleport into it either.
but once you exit a portal, you should be able to teleport back into it. And so what that effectively does is we enter a portal. It gets flagged as not teleportable, right? We get teleported to the other portal. As soon as that happens, this portal can now be teleported into. This portal that we're standing in is now flagged as not teleportable. And then we walk out of it, and we're allowed to teleport back into that one and the other one. So it's effectively an on-off operation that you have to balance appropriately. The actual portal game is a little more complicated because they allow you to walk in between portals. This does not go into that level of detail, and it's a more complicated problem to solve. This example just assumes that you walk into a portal, you get teleported out the other end, and there's no sort of in-between state. And actually, if you're in between two portals, there's a replication of geometry, which Valve will talk about in their talk as well, which I think will be very interesting, because if you look into another portal while you're in the middle of a portal, right, you want to be able to see yourself, in that portal, right, halfway in and out of that portal. So there's a lot of interesting considerations for getting very believable portal systems, but ours is a very simple illustration. And so this toggle function is all that I have to toggle the function's on and off capability, and all it is just portal active is not portal active, and that just flips that flag. Super easy. On trigger enter, we effectively cache our position on the X and Z axis, so we don't rotate it, because when we rotate our X and Z on the first person controller by default, it causes some really weird buggy behavior based on the way that the FPS controller works. So all I do is I cache those positions and then make a rotation on the Y axis. And that'll save us that weird sort of going topsy-turvy effect that you'll get. If you use the FPS controller by default and you do perform rotations on it, you'll notice this. So I haven't had the time to dig in depth as to how to fix it, but this is the way that I was able to fix it for this example, at least, is only allow yourself to rotate on the Y direction, which is where you're looking in sort of like the ground, relative to the ground plane. And that'll allow us to rotate based on where we're exiting the portal, at least on the sort of walls that are going up and down, and then have that sort of believable effect. It doesn't allow us to like jump down into a portal from up above and see us coming down from the other portal, which is a cool effect, unfortunately, but it does allow us, sort of to get most of the way there. And so we set our position to the other portal's position and our rotation, but only the Y. We get the Y, and then we set it here using Euler angles on our player's transform. And then there's a function that I created called mouse reset, which effectively just calls init again on the FPS controller's rotation on the camera and the player. And then that's sort of like the hack that you need in order to... The reason that a lot of the weirdness exists is because the player controller caches its rotation information. And so if you perform a rotation on your FPS controller by hand, as opposed to allowing it to happen with the mouse, it will immediately reset it back to its prior position and rotation, which has the effect of when we teleport from one portal to another, even though we set our direction of rotation to be like outside, going in the direction of where the portal's facing, we end up having the same position, the rotation that we did entering the portal. So we end up coming out of portals often just backwards. And so that's just a limitation of the first-person controller, but you can fix that by calling mouse reset, which is a function that essentially just calls init again, init is part of the FPS controller's mouse look object. I won't go too much into detail about it just because it's a little bit arcane, and the source code's in there if you want to take a look and dabble with it. But effectively preventing it from caching its rotation information and just hard setting it, and then recalling the mouse look init function, which does the actual setting of the rotation on the camera and the player. A little bit weird, but that's Unity's FPS controller, and that's how other people are saying to fix it. So you could roll your own, you could create your own FPS controller and probably prevent this from happening. But if you want to use the regular FPS controller, that's sort of the limitation there. But it's mostly working, and it looks pretty good. Some more time on it, and we could probably make it look even better. But for now, I think it's good. So that's teleporting. Set your position, and then set your Y rotation. Override the FPS controller's default rotation caching. And
we can walk in this portal and then instantly walk out this portal, and that's what we see. So any questions as to how sort of this works in a nutshell? Or maybe any of the code here in our portal? All right. So a much better version of the portal, at least from the rendering side, is this video here. So it's Bracky's. So he's a very good, he explains things very well. He's got very high quality to his videos. He creates a bunch of Unity tutorials, and in this case he created a portal that used a sort of shader, an interesting shader that'll only render everything but geometry, and also onto a plane, in which case this plane, and does the camera interpolation of the player that I alluded to before, which allows us to actually have so these are two separate worlds in tandem right now. So there's this red world here, and then this camera is looking at a completely different green world that's completely like set off in the distance. That's the exact same geometry, but completely colored green as opposed to red. And if you look through here, it's just completely seamless, and the walkthrough is completely seamless. And he goes into detail as to how he accomplished all of this if you're curious, and he provides you the shader that you can use for free. So definitely check that out if that's of interest. There's a link there in the video, and here's a link to his YouTube series if you want to. I put some of these in the Slack because somebody requested some AI videos, and he has a bunch of different AI videos and a bunch of other really cool series, so you can take a look at that if curious. And the best version sort of Portal obviously is Portal itself, and Dave Kirscher and Tajiv Kohli are employees at Valve who worked on Portal, and they'll be here on May 2nd to give a talk as to all of the technical sort of things that went behind the scenes and related to rendering and physics, and just getting a believable and good feeling experience with Portal for the actual polished final game that we're talking about. So definitely come to that talk if you're curious. We're going to take a break, and then as soon as we come back, we're going to talk a little bit about some new tools that Unity has released called Pro Builder and Pro Grids, and we'll talk about the assignment. And that'll be it for GD50. All right, welcome back. This is lecture 10. So we talked about Portal before the break. We talked about ray casting. We talked about render textures, sort of what those are, how easy it is to make those in Unity. We talked about how to give our first-person controller a gun so that we could actually look around and look as if we're holding a weapon. We talked about the portals themselves, how we're masking out the texture, the render texture as applied to a plane, and how each of those has a camera behind it so that it can render what is going out from the portal in the direction that it's facing. We're going to deviate from Portal now and talk about Pro Builder and Pro Grids, which are two tools that are part of the new Unity 2018.1, which will allow us to actually model geometry per the screenshot. This is actually a level that I created and that is in the distro. It'll allow us to create geometry in the actual scene view without needing to go into a third-party program like Blender or Maya and have to sort of alternate between the two and import and export, incessantly. Not only that, but as soon as you model something like this in Unity in the scene view, you can immediately test it for gameplay and make sure that it actually fits what you want, and you don't have to worry about scale issues when you're importing and sort of making it work and figuring out ultimately that, oh, I don't like the way this level is, let me go and tweak it and redo it. It just allows you a ton of ease and flexibility. And I previously mentioned Bracky's before, but he's got a couple of awesome tutorials here on Pro Builder and Pro Grids to supplement sort of what we'll talk about today in lecture. But if you want sort of more of a showcase of all the features of both, then you can look at these videos here and get a sense of how they work. So we're going to go ahead and just mess around with Pro Builder a little bit here in the scene view so that we can see what it looks like. I'm going to open up my other scene. So I have the Portal scene. If you're in the distro, this is where all the stuff that we've been looking at exists, just the Portal game. There's a Pro Builder scene as well, which I'm going to not save that. And so this Pro Builder scene is the level geometry that I created earlier. Now, it looks pretty horrendous because I didn't spend a terrible amount of time on it, and I'm not a particularly talented visual designer by any stretch. Let me go ahead and make it a little bit larger so that we can see it a little better. But it showcases some of the interesting features. So we see, we have obviously sort of polygonal, square-shaped, rectangular geometry. We can see that some faces are textured and some aren't. So we can see this face here, for example, is just white material. the default material, we can see that all of these sort of have this brick texture, which I got off a procedural generator website that allows you to choose a template for your texture and then specify colors and stuff like that. I did the same thing for this texture. This is another procedural texture, which is kind of like a blue marbly type texture. The cool thing about it is, at least for texturing, you can just choose arbitrary faces that you want to texture rather than have to texture the whole thing. Like you would do if you were to just give a mesh a default material, it'll apply it to the whole mesh. In this case, it's just applying it to whatever faces we select in ProBuilder. Another interesting thing which I really like is ProBuilder gives you a lot of tools for creating special kinds of geometry very quickly and efficiently. In this case, this is a staircase, which all I had to do was, with ProBuilder, select Build Staircase, and then you can choose a lot of different parameters. We'll take a look at how to do that in a second. I did the same thing here. So notice this staircase has kind of a spiral to it, and then this staircase is really tall but has no spiral. And then we have another staircase here which is kind of shorter and doesn't have a spiral, and then it ends up coming up here to this point. And then if this were the assignment, maybe this spot here would be where you put your collider that says, oh, this is the finished, this is the level's conclusion, you've beaten the level. So the assignment is, with ProBuilder, so to make a level, it doesn't have to be anything terribly fancy, like I'm not a great designer, but it should have at least one section where you're required to jump, so some sort of jump puzzle, just so that you can, think about the design of your level a little bit. And it should be, meaningfully large, not like, it doesn't have to be gargantuan, and it shouldn't be small. It shouldn't be like 10 meters or, maybe not 10 meters, but it shouldn't be like, 5 meters large. Obviously, that's very small. It should be something that you would consider, a somewhat sizable level. Using something of this size is a fair metric. So ProBuilder. If you've installed ProBuilder, so by default, ProBuilder is not installed in your project. You have to go to the asset store. I don't know, asset store has been a little bit slow last couple of days. We'll see if it works quickly. Looks like it is. So if we go to the asset store, open this connecting again, being slow. Okay, so if you search for assets and you just type ProBuilder, it'll pop up here. And notice that it says Unity Technologies. Anything basically that says Unity Technologies will be a free sort of supplement to Unity that you can easily just import from the asset store. Now it's a little bit cramped, the window here, and because I'm in a 720p monitor, but you just have to click download and then import in order to import it into your project. The distro for Portal for Assignment 10 already has ProBuilder and ProGrids installed. ProGrids would be the exact same process, just ProGrids right here. And when you import both of those into your project, you'll immediately have the ability to go up to Tools, and you'll see ProBuilder and ProGrids here. And all you need to do is click on the ProBuilder and then ProBuilder window, and you can see here this nice little widget-filled window pops up, and you can also dock it here if you want to. I actually did that on accident, but Unity makes it pretty nice so you can dock your stuff wherever you want it to. And there's a few different things. So you can do new shape and a new poly shape. The new shape actually gives you like shape templates. So here I've chosen just cube by default, and it allows you to do stairs, prisms, cylinder. So I can just do a stair, for example, and then we immediately see this like stair mesh here, right? I can generate the number of steps that I want just by changing the slider. I can change the curvature if I want so that it's a rotating staircase. And then I can also change how wide and how tall the stairs are. And also this inner radius is like how deep the steps are, if that makes sense. And then all of these together, once you finish, you just hit Build Stair, and it's done. Now you have a stair mesh that you can just put anywhere in your level, and it's that easy to make stairs. Before I get into more of the sort of what makes ProBuilder work, I'm going to go ahead and enable ProGrids. So ProGrids is a cool feature. It's a cool, add-on, which will actually lock everything in your scene to a specific grid, which you can designate based on how fine or coarse you want the grid to be. And what that'll allow us to do is when I move, notice that it's moving on the grid, right? It's not moving in continuous, like sort of a continuous motion. It's actually discrete steps. And the advantage of doing things this way is that when you're modeling your level or whatnot, let's say you have maybe a sort of a diagram or a drawing that you've created, you slap it on a texture, a flat mesh in your scene, and then you just sort of draw your level on top of it. everything will sort of just like map up nice and cleanly when you're creating all your geometry, and you can snap things together and align all on the same axes. And it makes creating levels like this just a lot easier. You don't have to worry about things being slightly off and then like missing vertices and everything sort of be looking a little bit unclean. This ensures that everything is very clean. So again, just notice the discrete steps that it's moving. These are all locked to the grid here. And so you can change all the settings here as to like how large it is. If I create a cube, so I'm going to go ahead and create a new cube. I'm going to build it. Notice up here, these 4 buttons are sort of like the modes with which we can interact with our cube. And this is very similar to what you get in 3D software like Blender or Maya or whatnot. You choose vertices with the left mouse, and then you can hit Shift to select multiple, and then you can just move it. And since I'm using ProGrids, it's snapping it to the grid, right? So if I turn off ProGrids, it should just be continuous like that. And so you can get whatever sort of angles you want, depending on what your use case is. So I'm going to go ahead and hit Command-Z. If I click on the face mode and I click this face and I shift click, it'll actually extrude it and make a new face. And I can keep doing this sort of over and over again. I'm going to zoom out a little bit so I can see a little bit better. And I extrude that, and then I extrude that, right? Starting to build something, right? It's not beautiful, but it's something. I can extrude that again, right? I believe I can scale as well. So you can build it out like that. And I haven't spent a ton of time mastering how to use the tool and all the ins and outs of it, but it is very, I think, useful if you're looking to get into sort of level design and you want to avoid the overhead of dealing with third-party software like Blender or Maya and having model files that you're sort of importing and exporting. It can be kind of a pain. However, if you want to export models, you can definitely do that. So there is a method here. Forget which one it is offhand. I think it's this one. No, it's one of these allows you to save the model. I don't remember exactly which one it is. Is it this one? The menu is a little bit cramped here, so I'm going to actually blow it up. Yeah, offhand, I can't recall which of these allows you to actually export. I don't have the icons memorized yet because it's a fairly new tool. But one of these will allow you to actually export the object as FBX or OBJ, whatever your software is that you end up wanting to. So you can just also go up here to the export menu, which is a lot easier to see everything by name, and you can choose how you want it to export. You can also export assets too for your game, so you can have objects in your scene that ProBuilder will generate for you, so you can create prefabs that way. But then here's like OBJ, so that you can export it to your 3D renderer, 3D software of choice. This is relevant for situations where, for example, you want to like rig and model and animate a mesh. You can't do any sort of rigging in ProBuilder, but you can do that in other 3D software, so it makes sense to export it that way. You can also create the model here, export it, rig it, and then re-import it if you want to, and that's relevant.
But that's a usable scene as it is right now.
This is a usable scene as is right now. The lighting gets a little bit messed up. Notice here when you mess with stuff, but that gets fixed. There's a little sort of meter here where it does some calculating, and by default it'll actually bake lighting on all of your objects. But as is, this will perfectly collide with any characters that you have. So I have an FPS character. I'm going to bring this guy up. Let's go ahead and set the transform up here. Just put him in the right position. And ProGrids is like attaching that, like sort of making that grid visible next to where I am, and you can set the access for that. Currently I have it actually disabled, so if I enable it, now this will actually move in increments, see? And it'll snap it to the grid perfectly. But now this, as soon as I hit play, I'm actually going to close this. I should just be on this mesh up here. Yep. And so this is just part of the scene now. Like as if you had made it in Blender or Maya or whatever. I actually jump down to my actual level and then explore it a little bit. This is all just haphazardly created whoops, stairs and other meshes and stuff. And so, make it all the way to the top. Whoop, I fell down. I'm also horrible at playing games. But this is the beauty of it is you can just play it instantly, right? Right out the gate. Now, another cool thing that I'd like to showcase is what we talked about gray boxing earlier. For making interior levels, gray boxing is the purpose of making levels and testing them for playability. The cool thing about Pro Builder is that it has an invert normals feature, which I think is just generally accessible in 3D software. I don't know offhand which menu it's in. Actions, geometry. Do I have the right thing selected? All right, I'm going to open up the Pro Builder window. And then one of these is invert selection. Sorry, wait. Flip normals. There we go. And so what this does is now this is an interior level. So all we did before was we made a sort of like polygonal creation of arbitrary size and shape. If you invert the normals, so recall every 3D polygon, 3D surface has a normal in whatever direction that's facing. Going the opposite way, going towards that normal is what gets rendered. But behind it, if you're going in the opposite direction of the surface normal, it's invisible. And so the effect of that is if we flip all the normals of something that is convex, we get an interior scene. And if we're looking at it from the outside, it looks a little bit weird, right? Like we can see into it, right? And this is something that you might see like in Minecraft, for example, when you're looking in part of the geometry that you shouldn't be able to see. You can clip through the world and see all the other interior parts of the world because you've basically gone beyond the surface normal of that polygon, and you're only seeing from that perspective all the surface normals of polygons that are facing in your direction in that way. But often you'll allow you to look straight through all of the other sort of cubes that are along the way because you're looking at all the rear of their, the inverse of their surface normal. You're looking in that direction. And so again, only one direction can a polygon be lit at once. And even if we look at it from the top, you can see that as well. We're looking at it from the top, flip the normals. It becomes a sort of concave or a convex 3D object, flip them, now it's an interior level, right? So I'm actually going to go into this, and I'm going to flip the normals again. I'm going to click on this. I have to click on a lot of these actually because it split up the mesh, but it's going to be easy enough. I'm clicking all the top surfaces of this, making sure I didn't get any on the other side on accident. I did not. I'm going to extrude this. And then I'm going to flip all the normals. And then I'm going to take my FPS controller, which is here. And actually, I think it's already inside, which it is. I'm going to hit play. The lighting, I'm not sure if it'll be messed up. It is messed up because it's in the middle of calculating a bunch of stuff. But now I've created an interior level, right, with the weird mesh that I had before. And so if you sort of make the building of your level sort of, this concave thing, and then you flip all the normals, you can create an interior scene very easily with ceiling and everything else. Normally, otherwise, it would be kind of a pain in the butt, but it makes it super easy to do with Pro Builder. And there's a lot of other features. A material editor for one. So with the material editor, you can actually designate specific materials. So in this case, I've created a couple of materials, a brick texture here and a marble texture, which is just I took some textures, created a material, made the albedo component of those materials that texture. And what that allows me to do is I can select an arbitrary face. So in this case, I'm going to choose these faces. And I can just click on this brick texture. And now these are textured as that brick, right? It's not applying it to the entire mesh. It's just applying it to whatever specific face that we want to. And there's a UV editor, which will allow you to actually take the mesh of your model. In this case, this is our entire mesh here. Just remember, as we talked about it last week, everything gets cut out and made flat. So you can sort of see, if you remember the shape of what we're dealing with, all the polygons that we were, that comprised our sort of weird large object. They're all now splayed out for us. So we can just very easily take a texture and just put it wherever we want. on here. Now, I don't have a ton of experience using this, so I'm not 100% confident in my ability to UV map something right now in front of you, but the documentation on the ProBuilder website goes into detail as to how to use this. So if you wanted, say, a specific texture to be like in part of the mesh, and then maybe another texture to be on another part of it in a specific like welded way that's not like just splat onto it, the UV editor will help you with that. For example, a face on a character model or something else. But yeah, or maybe like a sign on a door somewhere or something like that. You can do that all here. Just click and drag all the faces. The faces are actually dependent from one another, so that you can lay them out in a way that fits the texture that you are trying to map everything to. That is ProBuilder in a nutshell. There's a lot of features. We don't have time to cover all of them, and I mean, frankly, I just don't know all of them super well yet, just because the technology is so new. But I think this is going to be a huge part of like Unity's future, and like making it accessible for people that would otherwise have maybe been turned off by the idea of modeling their level geometry or their object geometry. I mean, certainly for me now, this just makes me want to make a game in Unity like right now, just because I know I can instantly just like start creating my levels, right? Like it's just nice and easy and convenient. And ProGrids, you should definitely use ProGrids in tandem with ProBuilder, so that you can optimally rearrange things in a way such that they're all like evenly lined up with each other. Otherwise, you're going to end up with issues in like manipulating their position in a very specific way, and like coming up here and setting their values manually, and that's just kind of a pain. So much easier just to snap everything to the grid, the ProGrids, and deal with it that way. And so the assignment is, largely just going to be take ProBuilder and ProGrids and just like make a level with it, and then just like take the principles that we've learned, create a controller, create a collider, and just make a very simple scene, and otherwise probably spend your time focused on your final project. So any questions as to ProBuilder, how it works, how to get it set up? Yeah.
So what would it look like? Can the character actually stand on top of an object that has normals inverse?
No, it should flip through it. Let me go ahead and put this up here. It actually it might not. I think it does still trigger collision, but you'll just be able to walk. You'll just be able to see through the It's just visual, like the. Yeah, it's just a visual. It's just a visual bug. It's a lighting bug. The physics should still apply. I'm going to go ahead and set the model up here. Okay, hit play. No, actually it looked like it went through it. So I think it also inverts the collision box. Yeah. I've seen some games where you can clip through something and still collide with it. So I think it depends on ultimately the engine or the implementation that you're using. But in this case, when you flip the surface normals here of this mesh, it also flips the box collider, the mesh collider's normals. Yeah.
The obvious thing to do would be to copy it, size it up a little bit, and then not invert it, and then you would have a kind of inner and outer layer, which would let you have both. Precisely,
yeah. If you wanted, you could make a copy of the interior. You'd have to make it. You make it the same size, I suppose, and then not flip its normals, such that you have a shell and an interior. Yeah, absolutely. Generally, I don't think you'd. It depends. If a lot of interior levels, you'll never ever be outside of their boundaries, and so you don't often see that happening. But it's very much the case that you could have that happening. And if you have like a house model, for example, then yeah, you'll actually see house models are modeled with walls that are two planes. So there's a bit of thickness. It's actually a rectangular shape, so it allows you to have a collision on one side and another side. Because there's two planes of the collider, rather than just the single plane, which is the direction of the surface normal. Any further questions on ProBuilder? Yeah.
So how come you can fall through the ceiling but not through the floor? Like, is the bottom and the top?
Because the bottom surface normal is pointed upwards. So this right here is pointed upwards. But notice that here, the surface normal is actually pointed down. So you can only collide with the direction of the surface normal that's facing you, if that makes sense. You can walk towards the direction of the surface normal, but not like against the surface normal, if that makes sense. That's the way that Unity calculates its mesh renderer component.
What about the left and the right? So the left is, can you go through from the left to the right?
You could go through from this direction, but you could not go through this direction. Because this direction, the surface normal is pointed this way, right? So if we try to walk against it, we'll be walking against the normal, and so we won't be able to, we will trigger a collision. But if you're walking through it in such that you're going the same direction as the surface normal, so if you're coming from this direction, then it won't detect a collision. Does that make sense?
Yeah.
Yeah. What Tani suggested, which was to make a shell around it, would solve that problem. So if we created this exact mesh, duplicated it, and then inverted it, then we would have two of the same object, but with normals going one direction and normals going the other direction, such that the mesh renderers account for both potential movement directions. Cool. All right. Any further questions on Pro Builder? Again, not meant to be a comprehensive tutorial. There's videos and documentation that I've linked to in the slides, but more just to illustrate how awesome this tool is really, and that this is probably going to save some people doing Unity projects some time if you're doing any Unity, like if you're doing any asset modeling, I should say, or level modeling. Another thing that I didn't make a slide for, but which I talked about in class was shader graph. And so what shader graph is another 2018.1 feature, which allows, rather than having to write shaders in Shader Lab, which is Unity's shader language, which can be quite an experience, quite intimidating, you can actually create them now with this node-based programming language. Not really programming language, but this node-based programming environment, I should say, which will allow you to choose all these preset nodes that influence the shader's behavior. And there's a lot of different kinds. And have the result of that be, you can see your shader every step of the way. So the shader is just a series of transformations going from left to right in one direction. All of these sort of transformations, you can see how they end up accumulating to produce this final effect, in which case here, if it may be kind of hard to discern, is a sort of marine guy with these blue holes that are actually like masking his mesh. And we talked about masking earlier. This shader itself looks like it's applying a mask with this noise that it's generating, and it comes with noise generation functions, generation nodes, which will allow you to feed those into sort of like the mask component of your shader and then produce some very interesting, cool effects. Otherwise, this would be kind of, unless you're like a shader expert, which I am not, it would be pretty complicated and non-trivial to implement something like this with just code, but this generates code for you such that you don't have to actually write any code at all, but you can still see the produced shader that gets created for you from Shader Lab or Shader Graph. I believe that it's just a asset now. I'm not 100% sure. I didn't test this going in. Hopefully I'm not just missing it. Supposedly you should be able to just import it. I'm not 100%. Let's see how you actually, is it this article maybe uses it? Via the package manager. Package manager. I think this is a new window package manager. So we go to window and then package manager. And then all. And then shader graph. Yep, so right here. So window and then package manager and then shader graph, and that will allow you to import the means to which, by which to create these sort of graph layouts if you're using 2018.1, which the course is using. But if you're at home and you're using 2017.4, then update to 2018.1 and you should see this in your package manager. And then once you do that, you can actually create a new shader graph object, and then you'll see it as a new window that pops up in your scene, and then you can start adding nodes. I don't have any material prepared for it, and I didn't anticipate talking about it necessarily, but it's something that seems to be very game-changing, and it's something that Unreal has had for a long time that sort of differentiated it from Unity, in my opinion. And it's, I think, a very valuable thing that they've added that shows a lot of awesome progress for 2018. So, again, a link to Brackeys if you want details on how to use not only Pro Builders and Pro Builder and Pro Grids, but a lot of other awesome features of Unity and to do a lot of cool stuff. He makes some really cool videos. Assignment 10. So assignment 10 is going to be creating a level with Pro Builder, just to get your hands wet with it. The level should be pretty complex. So not, like I said earlier, not like a finished game level. Like I'm not expecting you to do awesome, amazing, incredible things, but a level that has maybe, a few pieces of interesting geometry, maybe generate some stairs, it has some pipes you can generate and some other things. Have a jumping puzzle in there. So this says there should be one jumping puzzle for the player. The assignment doesn't officially say it yet, but I'm going to make the change to make it say that there should be a jumping puzzle. You can interpret this however you want. Just a couple platforms is fine, but honestly, whatever you would like. And have two different textures or materials. So you can create just an easy, just import whatever texture you want, or you can go to a website that allows you to procedurally create a texture, and you can assign it to a material, put it in the material editor of Pro Builder, and then use that to assign it to a face or to the whole object if you want to. But it should be at least two, not the default. So to make it a little interesting, you can use many more if you want to, but only two are required. So this should be kind of like a complete scene. So make a new scene, separate from the Pro Builder scene, separate from the Portal scene. Include an FPS controller so that we can move around the scene immediately after creating the mesh, right? But that's it. You can just use the default controller. You don't need to do anything fancy. And then at the very end, you should have a trigger on a collider somewhere, which it can be invisible. It doesn't have to be invisible. You can make this whatever you want. You can make like an arch, or I don't know. Your imagination is, you're free to use your imagination as much as you want, but there needs to be some collider, whether it's invisible or not, at the very end, and a trigger. It needs to be a trigger, and then when you collide with it, it should say level complete on the screen. So just take a text object from Unity 2D, part of the canvas, just drag it. If you just add a UI text in the scene, it'll automatically add a canvas and an event system for you. Create the label and then just set it to on or off depending on whether or not you've collided with the trigger. There's code for this in the helicopter game in the game over text script. You can see exactly how this is done. All it effectively is setting the color of the text to 0000 versus 0001 or whatever color you want to, effectively just a change on the alpha component of the text color. And then once that's done, then you have a complete assignment, and then you can spend more energy. Hopefully this should only take maybe an hour, maybe less. You can spend more energy on your final project, which will be due on the 11th. But altogether, it's been an awesome pleasure teaching this course, and I hope that a lot of you were able to learn a lot of interesting things, and hopefully were inspired to create some of your own projects, and will continue to create some of your own projects in the future. I certainly enjoyed making a lot of the stuff, and especially Super Mario Brothers. I think that was my favorite. But this was GD50, so thank you so much. All right, good afternoon, everybody. Thank you so much for coming to today's talk. My name is Colton Ogden. I'm the course instructor for GD50, which is CS50's new Introduction to Game Development course. We started this last spring, and we've been having lectures every week so far for this last semester. Last week, we took a look at Portal, which is a famous game by Valve, whereby you get a gun that can essentially shoot these portals that defy the laws of space onto different surfaces in the game, walk in and out of them, and teleport through them and see through them. And there are a host of interesting challenges associated with implementing a game like this. Now, last week we looked at a simple version of it in Unity, but today we are joined by Dave Kircher and Tajiv Kohli of Valve Software, who who actually were on the Portal team and implemented all of the interesting sort of design and technical decisions that went about making it work and making it fun and believable. So without any further ado, this is the Portal Problems. Thank you.
Hi. So we're just going to run through. So both me and Dave were actually students when we were hired by Valve, and we were hired to recreate like the work we did as our student projects for Valve, for Portal 1 and for Portal 2. And today we just wanted to talk to you about some of the issues we had trying to create the mechanic for portals, and then also some of the design, like both the technical and some of the design issues that we had to tackle and work on to make the mechanic work properly. So Dave's going to start off, and then I'll jump in later.
Hey folks, as he mentioned, my name is Dave Kircher. I was hired on specifically to work for Portal. So I'm going to go ahead and preface, we're jumping through a lot of topics today, jumping very quickly, so this is a very video-heavy presentation so that we can jump quickly in and out. And I'm sorry if I go a little too fast. I'm kind of optimizing for the stream. So hopefully if I've gone too quickly over something, you can review the stream and see it the second time. So without further ado, let's start off just quickly. I'm assuming that most of the people here have played Portal, or at least are familiar with it in some sense. That's just an assumption, and that for at least the technical portions, that you are at least somewhat familiarized with 3D rendering. If you're not, you may need to study up a little bit and then come back. But let's start off with just what is a portal. A portal is a discontinuity in 3D space. It's a 2D discontinuity where we basically define a 2D rectangle somewhere in space such that the back face of the 2D rectangle is defined as the front face of another 2D rectangle. So I've got my simple little example here of this blue portal and this orange portal. We're defining them to be back to back, which gets us this result over here. So from the perspective of this little portal guy, it should look like there's another room attached with a cube in it. But we're not actually moving 3D space at all, because otherwise, if we're trying to make sure that this perspective is true for both this guy and the cube, then you'd have this weird overlapping space that doesn't make any sense to anybody. So we do a lot of hacks to make it seem like space is folding in these interesting ways without actually moving space. Another way to think of it is that it's a door. If you look closely at this doorway, it's a very standard door. It's door-like. You walk through it, different stuff happens. But what I'm not telling you initially is that this actually isn't a door. For technical reasons, this level required a portal here because we needed this room to move. So even though it looks like a doorway, it's completely fake, and that it's a doorway that actually takes you about a half mile across the level. But it looks like a door, and so my job on the Portal series was to make sure that when we're creating portals, that they feel to the player like a doorway. And if you think of them in terms of a doorway, all the interesting stuff for a portal happens on the inside of the doorway, and nothing interesting happens on the outside. And it's my job to make sure that all the interesting things that are happening outside the door don't happen, because that's all stuff that doesn't make any sense. So as you can see, I just flew across the level, and that's the other side of that door that we just looked at, and I'm walking through it, and it's a doorway. So it's a door that doesn't take you a couple inches, it takes you about a half mile across the level. Now we're into our rendering section, which is basically one of my main expertises in the Portal area. So we're going to be talking about quite a few things, and we're going to be jumping quickly, so hopefully I don't spew it out too quickly. That's kind of my problem. So there are primarily two ways to render a portal view. There might be more, but these are the two that I'm primarily familiar with. The preliminary way that we did it with Narbacular Drop, which was the predecessor to Portal, was with rendered texture. And then when we got to working on the Portal franchise, we switched to a method where you draw it all in a single pass using what's known as a stencil buffer. And I'll be talking more about that in a bit. But there are trade-offs to each method. So with a texture, you have to have separate textures per portal view, and if you have support for recursion, you have to have many, many textures pre-allocated to do this, so your memory growth gets big very fast. You have to use the painter's algorithm or something like it to render your portals. You basically have to figure out the deepest portal you can see into and render that one first, and then any outward ones from that, you're going to render them because they're going to contain a view of that first portal. So you have to render it in that order. I don't know if it's true anymore. It definitely was when I originally was working on the first portal, that you couldn't effectively use anti-aliasing. So you get small visual artifacts as you get close to a portal, because it would be rendered as a texture that doesn't quite render the same way as the rest of the back buffer. But it is the simplest to implement, especially if you don't support recursion at all. It is super simple to do because you can ignore the painter's algorithm and just render all of them before you do your main view. By contrast, when we render with stencils, it renders the entire frame to the back buffer, so you don't have any extra texture memory requirements. You're doing it all in a single pass. You starting from your main view and working your way in, you actually have to nest it a little bit, so it's interesting. You're guaranteed to get homogeneous visual quality because it's a single pass the way you're rendering the rest of your frame. But it has a lot of extra complexity of when you render them and how you render them. This rendering portion is going to require quite a bit of spatial thinking. So I'm going to show you this video. Basically, this is a layout I'm going to use a couple times. Is this playing? Hopefully it's playing. Yes, okay. This is a room layout that I'm going to use a couple times, where I've got an orange portal and a blue portal, and behind each one is a thin wall with some stuff behind it. But hopefully to help illustrate what's in front of the blue portal, you can see there's a whole bunch of blue stuff over there. And let's see here. So yes, that is the example layout I want you to just kind of keep in your head, because spatial thinking is important to actually have reference. Let this finish one more time. Okay. Now, this is something that pertains to both rendering with textures and stencils, and I'm going to let this play once because I've been advised that if I front load this too much it sounds confusing. So while I'm playing this, I want you to look at the fact that when the orange portal is on screen and when it's not, everything inside where the orange oval is looks exactly the same from when it is and when it is not there. And so what I'm doing here is, as I'm toggling between the views, is I'm teleporting to where the virtual camera is that's rendering out of the orange portal. Whoops, come on, go back. Oh God. Okay, I'm toggling back and forth. I'm looking into the orange portal, but I'm toggling to where the virtual camera is behind the blue portal. So if you remember back to when I said that we're defining the back face of one rectangle to be the front face of another rectangle, that means that they should be coplanar at all times. And so if you think of my, my player model in terms of locking it to the orange portal, when I'm rendering my exit view, I should end up behind the blue portal as I'm rendering out of it. So it's important to remember that all the angles carry over from that, and most importantly, that whether you're rendering to textures or rendering to stencil, that nothing inside ever moves, because it should be the exact same view angles, the pixels should be in the exact same place. If they're not in the same place, your math is wrong. And this is especially important when rendering with textures, because one of the first mistakes I've seen several people do is that they render the entire screen to a texture, and then they map the entire texture to this little quad right here, and it looks all weird depending on how close or far away you are. But as long as you project the, sorry. Trying to work with videos is not the easiest. Okay, so as long as you project where the vertices of your mesh are in screen space, you can reuse those coordinates as your texture coordinates, and then it'll line up perfectly. So that's the point of why it's rendering as one-to-one, is you just want to make sure that you're rendering the same parts to the same part of the screen. Now, I said I'd be using that previous layout a bunch, and I swear I'm going to get back to there. But this is a much better layout for rendering with stencils, and so now you need to learn a new layout just for a minute. It's only used in stencils. But I've got these two portals looking at each other. They're kind of one stacked on top of the other, and they've got these light bridges that are just serving to show you that transparencies are kind of a special case. So I'm going to play it one more time. So you just got two portals facing each other, and they, even though they're tiny, it does make an infinite recursion down into the portals. Okay, so rendering with stencils. I'm kind of assuming that for this part of the talk that you have some idea what a depth buffer is. You may need to read up on that if you don't. The stencil buffer is very similar to the depth buffer in that it defines rules and operations for when we can wholesale just not draw a pixel, or when we do want to draw it. And then also, while we are drawing pixels, you can define several operations of how to modify the depth buffer. But for all intents and purposes, it's invisible to the user except for the end result. So stencil buffer, a lot like a depth buffer, but you're controlling the values in code instead of by vertex depth. So before we render any scene using stencils, what we're going to do is we're going to clear our stencil buffer at the same time as we clear our depth buffer. We're going to clear it to all 0 values. And the stencil buffer we were working with Portal 1, I believe it only had 2 bits. I could be wrong. It might be up to 8 bits, but it's not a lot of bits. So we need to be very conservative with what values we get put in there. So we're going to clear it to 0, so everything in it is 0. And then we're going to render all of the opaque objects in our scene, and that's where we get to the visual I'm showing you here. So you'll notice that none of the light bridges are here, none of the cool fancy window stuff is here. So all we've done is drawn all the opaque objects. And then we take a special detour to render a portal. At this point, we've rendered this oval here, and while we're rendering the oval, we tell the rendering system to increment the stencil buffer wherever we render a pixel. So while we're rendering, all of these pixels here go from 0 to 1, and that's an important bit. So we're going to be able to use that to tell the depth, to tell draw operations where to draw from then on. And then as soon as we've drawn the incrementing of the stencil buffer, we tell all draw operations from then on to only draw where the stencil value is 1. And we tell it to not modify anything. We're only drawing where there's a 1. And then we can basically just forget all about stencil buffers for a little bit and keep drawing. But at this point, if you've been following along with the depth buffer, we've already drawn this nice little wall behind the portal. So the depth is the same as this little quad here. And so the first thing we do is we render a full screen quad with depth at maximum value, which does really effectively make this a hole at this point. And if we were to continue drawing opaque objects and things like that, they would just show up in this hole. So then we start, after we've punched our hole in depth and we've required that all draw operations have this matching stencil value of 1, then what we do is we just start over in our main scene again and just draw it again. But this time we move our virtual camera. Just the same operation as I showed you in the rendering is 1-to-1. We just have to do a matrix transform such that we're behind the blue portal. And we draw it again. And so, let's see here, I think I have a magnifying glass. Boop. So you may notice that we're in, oops. Okay, I can't apparently zoom and use a laser pointer. So you may notice that the player model is there, and then the exact same setup as I had shown you before. It's the same set of quads and the oval again. And we do the exact same thing again. We tell it to increment. So all the values in this tiny little oval here are now 2. And then at that point we tell, okay, only render to pixels with a stencil value of 2. And then we can just ignore stencil buffers again. We punch the hole again. And then we recurse again. And we go into a value of 3. At this point, I'm going to get more into detail on it later, but we stop recursively rendering to stencil buffers because otherwise we'd draw a whole bunch of scenes that we're not going to actually see. We pull a little trick that I'm going to get into, but so as we've drawn all of our opaques, we would theoretically do our detour, we don't, and then we finish by drawing all of our translucent objects, and I know it's very tiny to see in there, but it'll become more apparent later. I think that's actually our rendering trick. And there, now we've actually drawn the translucence in that view. And I know this is very small, but it'll make more sense at recursion level 1. So as we draw our translucent objects, we're still all confined to drawing where stencil value is 2. And then once we are done drawing all of our translucent objects, we render the portal oval. Oops, sorry. I'm going to pretend that we're drawing to the big oval here because it's easier to see. We would draw another quad at this level, sort of like a window, telling it to decrement the stencil value back to 1. Oh, sorry, need to take a step back. We need to replace depth so that there's no longer a hole there. So we draw the full screen quad with depth equal to the portal plane while still restricting to the nested view, and then we decrement, sorry. So by the time we've done decrementing, that means all of these pixels inside this first recursion are now 1 again. Every single one of them is a 1 on the stencil value. So we can continue rendering the translucence from the first recursion, just like we did when we were doing the opaques. We can say, just restrict your drawing to all stencil value 1. And then we finish our translucence there. We do the exact same thing again while we're going back to the main view. We fix up our depth, and then we decrement the stencil values again. And then we just finish out our main scene. And now you have portals drawn using stencils. They required no extra texture memory whatsoever. So bouncing back to the scene that we had shown before this, one of the things that we had to solve pretty quickly is when you have some object in the middle of a portal, you have to be able to see it in two places at once. And the way that we do this is we literally just look up every piece of rendering geometry it uses, every texture, and replicate it and teleport it every single frame to wherever the original is. And while we're replicating, this object over here, you can see that it's slightly more in front of the orange portal. So basically the rules are defined such that whichever side of the object has its origin in front of the portal is the master, and the origin for this cube is right in its middle. And origin is just a term that we use to define like the one point in space that defines where this object is. So usually it's in the center of an object, not always, but so that means this is the real one and this is our complete and utter fake one that we have to do for every single object that is penetrating the portal. Now, when we duplicate geometry, and whether we duplicate or not, we have another problem to solve. I'm going to let this video play. I'm going to be toggling a broken part on and off. So when the cube is not behind the wall, that's the fixed version. And when you can see it behind the wall, that's the broken version. So if you think about replicating geometry, we have replicated the entire model to this orange portal, which means all the stuff that is supposed to be in front of the blue portal is also sticking behind this wall, because once again, we have defined the two faces to be coplanar. So what we have to do is we have to use what's known as a clip plane to tell the rendering system, you know what, just don't draw any pixels if the mesh is on this side, this half of this half space. And we define the half space to be the portal plane. And we can turn this clip plane on and off as we're drawing objects inside the portal plane, and that's what makes it work. Otherwise it would clip the whole world. I'm going to play the video again. It happens. So yeah, we're just telling it, hey, you need to just ignore every single pixel that's on that half of all of space. Don't draw them. And that makes it so it doesn't seem like it's sticking out the back in weird ways that people don't understand. Okay. Now, this is a very similar concept, something that we coined the term banana juice for, even back in Narbacular Drop, because it's just confusing. And I know you're asking yourself, what in the heck is banana juice? That doesn't make any sense. We decided to use a completely insane term for it because even our technical shorthand for describing the problem didn't accurately describe what it was. So we decided to use a term that it was obvious that explanation was needed. What we've got here is I've got my orange camera and I'm looking into the orange portal here. And that means I've got my blue camera, virtual camera here, looking out of the blue portal. And if you remember back to my example, we've got this geometry that's behind the blue portal, and it's between the blue virtual camera and the portal. And if we render that, it's going to look completely broken. So banana juice is a term to define this broken stuff that you would see if you were looking behind a thin wall. And I have a video of it here. I believe I'm toggling back and forth between views, just like when I showed you renderings 1-to-1. And that's me turning off the clip plane. This is what it would look like if we were in the virtual space and the clip planes were not enabled. And then I go back to our main view, and you'll see as I move around in a second that it looks completely broken, and it kind of breaks your brain if you don't understand what's going on. So that is banana juice. And you fix it exactly the same way as with the entity clipping. You have clip models, but what we do is, I'm going to replay the video here, is if you're watching, this entire part of the level is now clipped. So what we do is while we're rendering a virtual camera, we just clip the entire world behind the portal plane. All of it, everything that's back there. Yeah, so that's how you fix banana juice too. It's not super difficult once you understand it, but I can tell you it took me about 2 days to figure out exactly what was going on when I originally saw it. It just didn't make any sense. So moving on again, I know we're jumping a lot, and I'm sorry, we're just going to keep moving on at a quick pace. So infinite recursion is something that people kind of expected to see when they were playing Portal. If you ever played the original Narbacular Drop, we didn't support any form of recursion, and it was kind of a letdown. So I'm going to go into how this works. So in this view, you can see that we have this blue portal. That's our first recursion right here, and it's taking up most of the screen. And then we've got this blue portal that you can see the entirety of it. That's our second recursion. And this one in here is completely and totally fake. So that one, there is no portal there whatsoever. What we're doing is we're taking whatever we see of this portal, the second recursion, we're taking that exact view from the previous frame. We're taking those pixels, and then we're basically just doing a fix-up in case you moved your camera around. and we're applying the texture coordinates from the second portal to where the third portal would be. And by completely fake, I mean, we didn't even render this blue oval. That's just a copy of this oval right here. So it's the exact same thing as if you point a video camera at a video monitor that's showing what it's recording. You know, you get that feedback loop. But we have access to a little bit of extra special math that means that we don't get that weird snaking effect if you move it back and forth. We can fix it up quickly. But this video is actually going to show you about how this quickly breaks down, because if you're thinking ahead, you might be wondering what happens if you can't see all of the second portal. And the answer is that we stretch it. So as you watch the third one, it just kind of stretches off in weird ways, which is a problem that, you know, if we spent a bunch of time, we probably could have fixed. But in game development, sometimes you just call it good enough and move on, because I bet anybody that played the original Portal never noticed this whatsoever. So another breakdown of it, which I find personally annoying and interesting at the same time, I'm just going to show the video of it first, is as I'm walking, you'll notice at the third recursion where it's completely fake, you're going to see a pop. You're going to see every single time I walk through a portal, it pops around. And so this is actually fairly easy to explain once you understand, really understand how the hack works. So if you look at my visualization here, this is what the actual recursion would look like if we actually did it. So we've got a couple of portals here at these blue lines. And so inside our first portal that we're fairly close to, our field of view is really wide. And then as we get to our second portal, it gets really narrow really fast. But then as we get to the third, it narrows even more. And then the fourth, it narrows even more. But since we're cutting and pasting the second recursion, if you look down here on this visualization, this is the hack. So we take this one, the second visualization, and copy and paste it onto the third, onto the fourth. And you can notice that this doesn't converge at all. It doesn't narrow. So we're seeing the same amount of wall around each of the recursions, no matter how narrow this magenta cone is. So as we walk through a portal, the magenta cone, we're picking a portal that's further off, because now that's the second recursion after we walk through a portal. So it starts off narrow, which is closer to what it should look like at infinity. It should narrow, you know, to basically where you're seeing a blue tube. But then as we walk closer and closer to our main portal, then it's going to widen and widen and widen. And so there's just a pop where it snaps into place. So hopefully that made sense. And once again, completely changing topics because we got so many things to cover. So when we're rendering portals, we have to have a mix of rendering first person and third person. So in this case, you can see I've got my third person model over here through this portal, another third person model over here, and then we don't see it in the main view because I'm about to turn it on. It would look really weird if you saw the third person view in the main view. Yeah. I mean, some games do try to fix this with very special representations. You know, they'll try to draw just the legs or something like that. But yeah, so we have to kind of have a complicated system to figure out when to draw third person and when to draw first person. And if you were to guess, I bet you would say, well, just render third person every time you look through a portal. And it turns out it's slightly more complicated than that. I'm not actually going to get into the complicated version, but I'm going to show you how it's broken if you use that simple rule, because why would life be easy and we would just be able to render just when we're on the other side of a portal? So in this case, let me look up. So you'll notice in this case, I'm on a tilted angle, and this is a case where my feet are on one side of a portal and my eyes are on the other side of a portal. So it kind of breaks the original system that would say, oh, just render if you're on the other side of a portal. And so, yeah, it's a little more complicated. Not terribly. It should actually look way more broken than this, but we actually had the fix in several places, and this is a special build where I had to go back and break things, and I only broke it in one place. Yeah. Okay, and then the last on our rendering portion. So earlier I had talked about how we need to duplicate geometry that is mid portal, but there's also another thing that we need to duplicate, which is there are screen space effects where we can query draw operations and things like that. And so one way that we use these draw operations that are in screen space is to determine how much light glare to use around these lights. And so how these work are we draw a quad while we're drawing the light, and then we say, okay, in a couple frames, I want you to tell me how many pixels actually drew. And we're not allowed to actually query this immediately because of pipeline reasons. We don't have the results for several frames. So we have to cache off that handle that says how many pixels did you draw, and we'll get the result at some point later. Sometimes you're lucky and it's just 1 frame, but usually 2 or 3 frames. So you have to save it for a while. But you may notice that even though we're not replicating the geometry of the light, we're drawing 2 of them, because they're in screen space. So that means that this query system had to be smart about it. And I'm going to show how we have 2 separate results. Now, if we had used the engine as it was originally written, there would be just 1 query for 1 light. But then that would mean that these lights would dim in unison. So we need to have separate buckets for each view of portals. And every view query any view query that is issued while in that recursion, we have to keep it in a totally separate bucket and then call it back later. And then as we walk through portals, we have to transfer those buckets. So like if I were to walk into the blue portal at this point, all of those handles we have to transfer to the main view, and then all the ones that are from the main view we transfer into what was now orange, because we would be walking out of this orange one if we walked into the blue. So yeah, that is the quick set of rendering things I wanted to cover. So now I'm going to hand it off to my colleague Tajiv to talk a bit about design, give your spatial thinking a bit of a rest. Yeah.
Yeah, so that was a lot of technical stuff about rendering of portals, and you can see it's more complex than it seems at first. The naive solution seems like it'll get you most of the way there, but then as you start putting in more things in the game and more ways the player can interact with the game, you see there's a bunch of different complexities that you have to account for, and a lot of those complexities are not just in a technical sense, but also from a design sense. So I just want to talk through some of the issues that we came up with as we were making Portal 1 and 2, and some of the ways we tried to solve them. One of the first things I wanted to mention was when first coming up with the idea for portals, before figuring out if we should spend a bunch of time making this idea, like this new game mechanic that most people haven't seen before, what we did was Dave and his team made a prototype of Portal in a 2D game engine that is used in DigiPen while they were students, and it was made in the in-house DigiPen 2D engine. And you can see here that it's a 2D version of Portal, but it's still got all the basic game mechanics that are used in Portal, and it's like the main goal of doing something like this is to vet out the mechanics and to see if they're still fun at their core. And part of what you do here is you playtest, right? You make this simple prototype and you get other people to try it out and play it and see, hey, is this fun? Is this something that we should spend our next year working on as a proper 3D game? And the prototype, you can see, had most of the basic functionality there, and kind of vetted out the idea of the mechanic to take it forward. And as we take the mechanic forward, one of the first things that you realize is this is a brand new mechanic that people don't really understand, and you have to train them with how the mechanic works, and also train them with sufficient knowledge so they can use that mechanic to solve puzzles, which is the core of the game. And one of the things that we did is you have to have certain sections of the game where you can be sure that the player has the knowledge that they need to progress. So a lot of this is about making sure that the levels you're designing are done in such a way that when the player finishes that level, they have that knowledge that you want them to have. And one of the ways we kind of ensure that is through doing a lot of playtesting. And playtesting is something I'll talk about a little more as the talk goes on. But the basic idea of playtesting is just getting someone else to play the game. And that someone else could be your coworker who sits next to you, your friend, anyone else really, like anyone that someone you get specially to come play the game from outside the company. But usually it's just your coworkers, people that sit next to you, people that see you work on the game but don't know exactly what you're doing. And you just kind of observe them and see what they're doing, get some feedback from them, and then use that data and iterate on the mechanic. And you can see here, so this was This was a level in Portal 1. It was pretty early on this level, and you can see the portals here. The blue portal here is moving on a timer. It moves from one to the next to the next. And the idea of this level was, by the time players solve this, they understand that I go in one portal and I come out the other. Right? That's the basic idea here. And in Portal 1, this level did a pretty good job of teaching players that. For Portal 2, we have a very similar puzzle. I'm going to just have it play here. It's a pretty similar puzzle, right? The idea is the same thing. You have the 3 sections where the portals can go. The one change we made here was we moved the portal away from a timer and moved it to buttons. So this way the player has more control of where the portals are opening. There's a few reasons for this. The main one here is like the level in Portal 2 has a lot more visual noise. There's a lot more like, it's an old level, a lot of foliage, a lot of destroyed stuff. So it's not as clean as Portal 1. And also, there's a case of, in Portal 2, there's a lot of people that have already played Portal 1 and are probably already familiar with the mechanic. So we don't want them to have to go through the timers and wait for all the things to happen, even though they know how it works. So this way, they can just go in and show us that they know how the portals work without having to wait through all the timers. And the basic goal is the same thing, that by the end of this level, we're confident that the players understand how portals work. One of the other things that you learn through playtesting is you learn what you need to teach the player. There's sometimes when you'll be making the game, and there's certain things that you as a designer or as a creator won't think are challenging concepts or are things that need to be taught to players explicitly. One of those things that we noticed early on is this concept here, where a lot of players kind of thought portals were one way, that you go in one and you come out the other, and that's it. But they had to be taught that you can actually go in both ways. You can go in the blue one and come out the orange, or you can go in the orange one and come out the blue one. And so this puzzle specifically does that, where the blue one is the only one that you're moving. So the orange one stays stationary. First you go in the blue one, you come out the orange one, replace the blue one, and then you go in the orange one and come out the blue one. So the idea with this, again, is you have to figure, like through playtesting is how you figure out the different things, the different discrete small things that you need to teach the player, and then also try to figure out how to teach them in a way where they're figuring it out instead of you telling it to them. So for the most part, in Portal 1 and 2, there's certain things that we tell the player, but for the most part, we want them to figure it out and have that epiphany themselves, because then they really learn it. If you just tell it to them, they might not take in the exact knowledge. Another thing here is, this was a level in Portal 2, but we noticed through one of our playtests, it was through a few of our playtests, that players were super hesitant to place portals on the floor, even though this level is probably the 5th or 6th one in the game, and you've done that a few times in the game before this, but usually you're doing it way down there and like doing a fling. It's a fling mechanic where you like fly through the portal and come out. So players have placed portals on the floor before, but they haven't done it right at their feet. So we had to design a scenario here where the only way forward, like this, you're trapped in this black room with nothing else, and the only thing you can do is place a portal on the floor there. And that's one of the things that you realize as you keep testing, and is you'll come across players of different skill levels and different knowledge of video games and different knowledge of how controls work. And typically you want to make sure that you're not only catering to the low end or the high end. You want to make sure that both of them can have a good time with your game. So you want to design puzzle gates in a way that aren't super intrusive. If a player that sees this gate here already knows that I can place portals on floor and go by, this doesn't seem like anything that's stopping them. This just seems like part of the level. But to a new player that comes in here and is like, I don't know how to proceed, it takes them a while to figure it out. And then when they have that aha moment, they feel pretty smart about it. So you want to make sure that you're designing stuff in a way that isn't frustrating players that already understand the mechanics, but also isn't making players that don't understand the mechanics have to have to be super frustrated as well. Another thing that we had to do, so Portal 1 and 2 both have this mechanic where you go into a portal on the floor and come out one on the wall, and it like keeps your momentum and your velocity and flings you forward. One of the things we noticed while we were working on this mechanic is that there's a lot of times when players don't exactly quite line up as they're falling through the portal, which means that when they fall in, they're not going to fall out. They're not going to come out the portal on the wall in the correct way. And a lot of times, players won't know that they had the right solution. They just kind of messed up the execution a little bit. And we want to try and help the players in these cases. But again, try to be not intrusive about it. Because you want to make sure that the players, as they're solving puzzles, they're not thinking that they had a right solution, but it didn't work the first time I tried it, so now I have to rethink the whole solution, even though the solution was correct the first time. So one of the things we used a few different things to help the players out in this way. And again, with the idea of them being mostly invisible to the player. They're not always completely invisible, and in some cases we have ways to opt out of them. But this is one of the things that we used. So if you notice here, the player is going to drop through the orange portal. But as you notice, as I walk forward here, I'm purposely not going to fall exactly straight. And one of the mechanics we had in the game was, it was pretty subtle there, but I'm going to do it again. You'll see I'm walking to the side, and the game kind of funnels you into the portal. So we had this special thing we used in portals, for portals that are on the floor, facing mostly up. Imagine there's like a cone coming out of the portal, and if you're falling from some height, and if you're within that cone, and the cone it's not super wide, it's pretty narrow. If you're within that cone, then we kind of funnel you into the center of the portal, so that when you're coming out of it, you're going to be lined up perfectly with it. And as you can see, the third time I did it there, it didn't happen, because the way this works is that it only works if you're looking at the portal. So it works the second time, but the third time I'm going to go mostly in the same direction, and it's not going to work. So that's our way of kind of trying to make these things be non-intrusive, to where if players don't expect to go in that portal, it's not going to work. But if the player's looking at a portal and they expect to go in it, we kind of nudge them along a little bit. And you can see it here and this is a second case of the same thing, where there's a portal on the floor and the ceiling. And you can see as the funnel is working, the player's perfectly in the center of it. But I'm going to look forward a little bit and disable the funnel, and you can see the player's going to go off axis, because the funnel got disabled and the player slowly went out of it. So now the funnel is disabled now. And again, the idea of this is to reduce a bunch of the player frustration and to reduce a bunch of the false negatives that players get. You want to make sure that players that think they got the solution, and if it was the correct solution, you want to kind of help them out a little bit. You don't want to solve the puzzle for them. You don't want to give them, like, here's the answer. But you do want to try and help them out a little bit, and because that helps, that makes the game a little bit more fun and reduces the frustration. So that was a helper we had for when you're entering portals. We also have the opposite, and that was there in Portal 1. And in Portal 2, we introduced something that was the opposite of a helper, which we use when you're coming out of portals. So Portal 2 had this mechanic called aerial fate plates, which is pretty straightforward. You step on this fate plate, and it propels you through the air. And the level designers can place the fate plate on the level and can kind of control the trajectory of the arc of where the player is going to fly. And this arc is not really visible to the player, but it's pretty apparent based on the level design. So you can see in this one, I'm going to play the video as I'm talking and then maybe play it a couple times. So the tech that was developed for these aerial fate plates is something that we reused for like a fling helper. So you can see here, there's all these fate plates. I'm going to turn on some debug draw, and you can see right here. So this green arc here is the arc that's on the fate plates, but you can see there's some stuff coming out of the walls there as well. So this is a part of the level where the player is going to fling out of. He's going to fling a box out of that, actually. because we want this to work for objects as well as the player. So you can see as the box goes through here and then here, these are just faith plates. And then when the box comes out of that, we kind of have the box follow the arc that's kind of predetermined. Because that's I think what the player is expecting at that point. They expected to have solved the solution, solved the puzzle. But the funnel, the trigger here, just kind of corrects the arc to make sure that it's always going to go in the place the player expects. And we also have a case of the same things working for the player. So you can see here there's two different arcs that are coming out because we've kind of doubled up the triggers over here. The way these triggers worked in the game is they won't always enable when the player touches them. They require a minimum velocity threshold. So the player has to be doing most of the work, right? So the player has to have figured out a way in the level through the puzzle design to get that velocity. But we know that there's some differences in physics and differences in the exact mechanism you might use. So we're just saying if you got the minimum velocity that we require, we're going to take you all the way there. So in this one, you can see we have the two different cases. So if I just fall out of the portal, it's not going to activate any of them. If I somehow manage to get some velocity, it's going to activate the fail case one and take me there. And the reason we have the fail case one is because we want to make sure that if players somehow get most of the velocity, but like bonk on the wall, they don't keep thinking that that's the correct way to do it. So we want to make it obvious that you failed. So it's again the same way. We have to help. We are like helping the players out, but not by giving them the solution, just by making it obvious that the thing you did was correct or wrong. And then if you do the correct way in this level, which is to get velocity doing that, and then you make a portal there, you're going to do the correct thing and fling out of it. And again, the main idea here is to get rid of those false negatives. Is like, especially here, because there's a few different spots on the wall that you can put the portal. And we don't really want to restrict a lot of that and just put the one square on the wall that is the solution square. Because again, if you put the portal down here or put the portal up here, the arc is going to be slightly different. So this mechanism we had just kind of corrects those arcs and makes sure that it goes in the one or two ways that we want. Another thing we added this was added in Portal 2 was a highlight for your portals. So you can see where your portals are placed through walls. And this is something that's super useful in levels where you have to keep track of which portal you placed over there, so you know which one to place over here. Because sometimes it's like, okay, I just got out of the blue one, and the orange one's over there, so if I place the blue one again, oh, I got to do the whole puzzle again now because I placed the wrong one. So this helps a lot in just making sure that you know where your portals are, so you can be like, I want to come out of that one, so I'm going to place the other one. And this is something we added in Portal 2, and it was pretty helpful. And it's also helpful in the co-op version of the game, because in the co-op one, you want to see where both the players' portals are at all times, and this mechanic helps in that. Another thing we added to kind of help the player a little bit is a thing we call the placement helper. And this was not used a whole lot in the game, but there's a few sections in the game where we want to encourage the players to come out of a portal in a particular direction. So we have these things that we placed in the level with a certain radius. And if you place a portal within that radius, we just kind of snap it to the direction, to the center of it. But they're on a timer. So if you place one portal and you're like, oh, I actually want to place it over here, you can always opt out of it. And that's, again, what I was talking earlier. You want to add some, excuse me. You want to add these helpers in a way that for players, that they're mostly invisible to most of the players, but the players that want to opt out of them have a way of opting out of them. So, excuse me. So you can see the first portal that's placed does get snapped, but the second one that's placed goes exactly what the player wanted. And we use these in a few spots in the game, but they weren't used a whole lot because for the most part, you want to make sure the player feels like they're in control. And one of the other things that was a lot of fun while making Portal, and Dave will talk a lot about this. Excuse me. we'll talk a lot about this later, is the physics of portals, or physics of objects interacting with portals. And for the most part, we're trying to be super accurate with it, right? We're trying to make stuff work the way players expect in real life, because that's kind of what we're trying to simulate here. But one of the things that we thought, that we added here that we thought was more fun than accurate. So you can see when the sorry, I'm a little bit sick. You can see here that when the box starts off, it's just resting on the floor. So it's got no initial velocity whatsoever. So when you place the blue portal down, the expectation is probably that it keeps resting there, or maybe it goes in the center of the portal and just stays there. But that's not a super fun game mechanic. So here we just have it be so that objects coming out of portals have some minimum velocity. So they always have some minimum velocity. And this works also for other parts of the game, like the paint. And you can see here that there is some air resistance that takes place, and the paint does slowly come down. But once it comes down to its minimum velocity, it just stays there. And this is completely fabricated fiction. There's no real physics for this. It's just kind of this is more fun than trying to simulate real physics. So you can see here, it's air resistance is making it go down. They're slowing down, but once they get to the minimum velocity, they just stay there. Yeah, this is about it. So once it gets here, it's just going to stay here. It's not going to go below that. And speaking of gels, the gels actually came up, were an idea that we had for a student game that we made while we were in DigiPen. It was called Tag: The Power of Paint. And in Tag, you had a paint gun that you used to shoot the different colors. And the Portal 2 mechanic was adapted from this, and it's pretty similar. But one of the things we did get rid of for Portal 2 was the idea of having the paint gun. Because one of the core ideas we had while working on Portal 2 was that any mechanics we add to the game should really work with portals and should really interact really at a core level with portals. So we thought instead of using the gun to move the paint around, it would make much more sense to use the portals to move the paint around. And that was kind of core, not just with the gels, but with any new mechanic we added to the game, was that portals is the core idea of the game. So everything we do should kind of center around how portals work. And this is just showing you the different colors we had in Tag. One of the colors that we added in Portal that wasn't there in Tag was the Portal gel. And this is, again, going with the idea of how do we make the gels and portals interact better. So this one just lets you spread around like white paint, so you can put portals anywhere that the paint can go. And this is a pretty cool mechanic in that it allows for a lot more open-ended level design and a lot more player freedom, because you can place portals essentially anywhere now. Because for a lot of the game, we're restricting where the players can put portals, on the black surface or the white surface. And this just allows, you can just put white anywhere and put portals anywhere. We didn't use this a whole lot because it is pretty open-ended and does break a lot of puzzle design. But there are a few cases where we use it and in a pretty open-ended way and have the player just kind of have fun, spend some time painting the whole level and figuring out what to do. And these kind of levels usually have a couple different solutions because we don't know where the player is going to paint, so we just put a bunch of different ways to get to the exit, and players, some players figure all of them out, some players find the first one and just go there, and it helps to break up the pacing a little bit from the conventional puzzle design with the specific spots where here's some white spots, here's some black spots. So it helps break that up a little bit. One of the things that didn't make it through from our student game was the sticky gel that you saw in the student version. So this is going to look a little bit broken because this is from a really old version of Portal 2, because the sticky gel got cut pretty early on. And you're going to see some stuff here that doesn't really make sense, but just go with it. So you can see we use purple instead of blue here. So you can walk on walls and stuff, which is pretty cool. So here you can see there's blue paint coming out of there, but you can't see the actual paint blobs because they're invisible for some reason. I couldn't figure it out. But you can see the actual paint on the walls, on the floor. So this is just an idea of the kind of puzzles we were trying to come up with using the sticky paint. There's an extra portal gun for some reason. Just ignore it. This is a really old version of the game. So this is the kind of puzzles we were trying to come up with of combining the different paint colors and portals together. But we did end up cutting this feature though. And there were a few different reasons. One of them was obviously it is quite disorienting. You can see like going up a wall and like trying to figure out where the ceiling is, where the floor is, especially in a lot of these levels where they're mostly just black and white. It gets pretty disorienting, and we had more than a few playtesters complain about that. But the other big reason that we cut it is because it didn't really interact well with portals. You don't really want to walk into a level and have the pots already placed for you, and like there's no real good way to make a pot on the entire wall without having to place the portal like 50 times. And also it didn't really interact well with the portal player physics and portal physics, and Dave will talk some more about the player physics through portals. And this is one of the things that you can see. So we had a paint gun for a little bit, but we ended up cutting it. So you can see I'm painting the wall over here, and I'm going to walk on the wall. But as I enter the blue portal, you can see like, oh, it's just not letting me go through. But if I go to this way, it works. And that's just one of the things that's like, well, we got to solve this. We can't ship like this. We got to solve the problems. And we spent some time trying to work on these issues. But at some point, you realize that you're not guaranteed to solve these problems no matter how long you spend on them. So at some point, you got to just be like, okay, I don't want to spend an extra month or two trying to fix these problems, not knowing if you'll get there. And plus, there's other reasons why the mechanic isn't working out. So let's just stop working on this and work on other stuff instead. Another thing we ended up cutting this was from Portal 1 that was present in the Numerical Drop, was the ability to place portals through portals. And it's a pretty confusing thing. And that was the main reason we cut it, because most players just thought it was way too confusing. Because you're placing the blue portal by looking through the orange portal here. So the blue portal is, like, he's pointing through the orange portal here and placing the blue portal over here, because the other blue portal is behind him. And it's just like, it's too confusing. And also, there's not a lot of puzzle design that you lose by disabling this feature. The thing you do gain is like players aren't getting super confused, and also you're not necessarily cutting a bunch of puzzles that you can't make now. So this feature got cut as well. And this is something that we didn't really cut, but we stopped using in Portal 2. That was used a little bit in Portal 1, was the idea of a double fling. And I'm going to show it here. So double fling is basically placing a portal while you're falling out of a portal. And it's one of those things that like it works pretty well. And it's a pretty cool mechanic. And it was used in a few spots in Portal 1. A couple puzzles required, like this puzzle here, requires you to do this double fling. But one of the things we noticed was a lot of players have difficulty in executing a lot of these super high precision movements, even though they know what the solution of the puzzle is. So players will walk in this room and figure out like, okay, I got to do this, I got to do that, and it's going to work. But then a lot of players have trouble like walking out of a portal, making a portal quickly, and like it adds a lot of stress. And we wanted to move away from a lot of the Twitch movement-based stuff and towards more of a kind of, aha, I got it, that kind of stuff. And once you get it, we don't want you to spend a bunch of time in like making sure you get the precise movements right. So this feature, we didn't really cut it. It's still a mechanic that works in Portal 2, but none of the puzzles in Portal 2 require it anymore. And once we added the level editor, a lot of the puzzles people are making do require it, and a lot of players like it. But it's not something that we thought we wanted to make sure, make everyone have to do. And another thing that we changed from Portal 1 to Portal 2 was these energy balls. These energy balls at the time, I mean, part of the reason we used them in Portal 1 was because they were there in Half-Life, and it was an already created mechanic that we had that we could just crib from them. But the basic mechanic is these things fire this ball that bounces around, and it needs to go in this receptacle here. It's under my gun right now. It needs to go in this receptacle here, and once it goes there, it finishes the puzzle. There's a few issues with this mechanic, though, in that there's a bunch of timing element involved here, because the ball takes time to travel, and also if you get hit by it, you die. Which, I mean, it's fine. It's a game mechanic. But for Portal 2, we just thought, can we improve on this idea? And the thing we came up with was using lasers instead of the energy ball.
Sorry about the mess. I've really let
Lower the
place
volume a
go
little bit.
since you killed me. By the way, thanks for that.
So here you can see it's the same level from Portal 1, and you can even see the energy ball dispenser going away and being replaced by a laser, because we wanted to make sure players no, GLaDOS is improving these mechanics now, and got better versions of it. So the laser effectively is very similar to the energy ball, right? Like it goes in one, and you want it, it goes in over here, and you want it to go to the receptacle over there. The big advantage here is that the reaction is instant. So if the player got the solution or not, it's instantaneous. You don't have to have situations where you place the exit portal, and now you have to wait for the ball to go all the way across the level and see if it lines up or not. This way, it just instantly does it. Plus, it also opens up a bunch of different gameplay opportunities, because now you can use multiple relays on the same level. You can have the cube that redirects the laser. So overall, it felt like an improvement over the energy ball. And talking about lasers, so far we've been talking about a bunch of these smaller decisions we made to solve these smaller problems as they kept coming up, like entering, exiting portals, making sure things are lined up or not, improving on the specific game mechanics. But one of the things that you need to do when you're trying to make a whole game is to see how these mechanics come together, and how you can combine them together to make a whole game, to make a few puzzles that increase in difficulty, complexity, and go towards some crescendo. And one of the ways we did that is by kind of using this kind of process that I'm going to go through. And we used it a couple times, both in Portal 1 and in Portal 2. And there's a few different mechanics that we use this cycle over and over for. And that's kind of how the entire game track is designed. So it starts off with an introduction. And the introduction is the puzzle we just showed you. That's the intro puzzle for lasers. And it's really straightforward. It just shows you the mechanic. It goes in one portal, comes out the other, goes in the receptacle. It's really straightforward, introduces a mechanic. Most people won't get tripped up on this. From there, we then try to saturate the player with that same mechanic. We introduce different twists on that same, without introducing the whole new mechanics, we just introduce different kind of versions, different tweaks on that same idea. So this room still only has lasers, but now we've introduced relays and cubes. And you can experiment, figure out how to connect the three relays together, figure out how to move the cube, figure out how to move the laser through the portals. But still, it's only lasers, nothing super complex yet. Then we give you more of that. We give you more of just the same mechanic. Here, there's two things firing lasers and two things you got to connect. And so it's the same idea. It's like just using lasers, but not super complex, just like building on the complexity by little, followed by a puzzle that's like, okay, this is the puzzle that's going to teach you all about lasers. By now, you've seen lasers in a few different ways. This one, once you get this, you understand how lasers work. You know everything there is to know about how lasers work. So this puzzle here, there's two cubes and three things firing lasers, and on the other side of the puzzle, there's three things you got to connect them. And this puzzle is fairly difficult, but by this point, you've been slowly introduced to the different ideas of how lasers work, and this one kind of taking them all together. And then once we've done that, then we start combining them. Then we start taking, okay, now you've got a laser and a different cube and a bridge. And by this point, you've seen like a whole separate, we've done the whole introduction, saturation, graduation track with bridges as well. So by this point, you go in there and, okay, I know how bridges work, I know how lasers work, how do they work together? Like, how do I combine them together? And then we just start escalating from there. And then you go into this puzzle that has a bridge, has a laser, has a turret, has some cubes coming out, has a catapult, has a bunch of this stuff. But by the time the player gets here, they're not really overwhelmed by it, because they've been introduced to all these mechanics separately, and also smaller combinations of them, so that when they get to this point where there's a bunch of different mechanics, they know how they all work individually. And that's kind of the process that we use of like slowly ramping up the difficulty, first with a single mechanic, then by combining them, And then that's kind of how we take the individual smaller design elements and combine them together and turn them into the whole game. And now I think Dave's going to come back and talk some more about physics.
Okay. And after I cover these last 4 bits of physics, we're going to open up for questions. I know we have a whole miscellaneous section that we've outlined here, but that's more just buffer material. So hoping you're going to put your spatial thinking caps back on. How we handle portal transitions is there's 2 distinct methods. One is that we've got volumes here, which we call touch volumes or trigger volumes, and those are centered around the portal. So I've got my blue portal here, I've got this green volume here, and you'll notice it's entirely in front of the portal. That's important. And then I've got this yellow volume here. So the yellow volume is just, its whole job is to tell us which objects in the world are just kind of close to a portal. And I'll come back to why that's important in a minute. But it separates us from having to think about objects that are way out in the world, you know, all over in the white space around here. Just, we don't have to think about them. And we also know they're not objects behind the portal because we're only interested in stuff that happens in front of the portal. And this green volume here is where most of the magic happens. This volume says the objects in it are so close to a portal, we need to think very hard about what they can do, what they can't do. We're going to let those objects start passing through the portal. And so we keep these objects in 2 separate lists. Objects that are in this green volume no longer intersect with any objects out in the white space out here. They don't have to think about them. They're kept in a completely separate list, and they don't collide with them at all. They also don't collide with world geometry. I'll get to that in a bit. And then objects in this yellow volume are the only ones that the objects in the green volume have to worry about. So these are objects that are just kind of close to a portal. And so another important interaction with portals is raycasting. So we're only interested in rays that pass through the portal quad. So if a ray happens to just pass the portal plane but not intersect the quad, we don't do anything with it. It's not special. We just treat it like any other ray in the world and let it do its merry thing. But we got this magenta guy. It intersects with the portal. So now we have to recast a new ray out the other orange portal, which essentially gives us 2 ray segments. And if you think about that, if you were to write any piece of code that just did the ray casting and hand back 2 ray segments where somebody was expecting 1, you're probably going to get weird results. So this means, the fact that this is happening means that we have to go through every single system in the game that possibly casts a ray through a portal and fix every single one to understand that if we give you back multiple segments, different things happen. Instead of, you know, assuming that like this starting point goes directly to this end point, and which doesn't even go in the direction it wanted to in the first place. And so at its core, remember how I told you how every object had a origin, a single point that defines where it is in space. We use the ray casting to determine if an object that's in this green volume and just kind of moving around, we use a ray cast from one point where it was one frame to one point where it was another frame to see if it either passed through the portal or outside the portal, because if it went over this way, we do nothing at all. If it went this way, we need to teleport it. So that's the basics of our handling. Now, so how do we let objects pass through walls? This is one of the things I spent a whole lot of time on because we wanted our portal transitions to be very seamless. Remember one of my first slides I showed you, it should be like a door. People expect to walk halfway through a door and just stand there. And how we do this is, I'm going to talk about it a bit first, is we take, whenever you place a portal, we take a snapshot of all the world geometry around you and create a very small representation of that and carve a hole in it. And we don't do this for the entire world because that takes way too long. And by way too long, I mean a quarter of a second. And in game terms, that's just way too long. Well, I don't know if it was a quarter of a second. I remember originally that we had a problem where I think carving the mini version took a quarter of a second, so it'd probably take several seconds. So I'm going to show you a scenario here where I've got a portal and it's going along this this corridor gateway gangplank thing, and it's going to go into this little classroom area. And as I go back around the wall, I'm going to show you a debug mesh of our collision representation. Now, so in this debug representation, we've got these green lines, and then also these cyan lines, or I'm probably mispronouncing that. I called them bluish, but my colleague has told me I need to call them cyan. So I'm going to call them bluish now. These green lines and the blue lines are in local space, so they're with the blue portal that we placed locally. And I know it's super hard to see, but there are a bunch of red lines over here and some magenta ones. Those are from the other portal that's in the classroom that are flipped and glued to the back of our local portal. So it's all in this local space around this blue portal. We put some new stuff behind it and some new stuff in front of it. And so you may be asking yourself what the colors actually mean. Green here is representing brush geometry, which most level editors, you can create walls and various shapes directly in the level editor. And at least in our terminology, we refer to these as brushes. So they're usually very simple convex shapes and super easy to deal with. And this bluish geometry is from what's known as a static prop, which is a model that somebody modeled in a model editor, so it can be arbitrarily complex, but it has to be made up of convex shapes. We take a small snapshot of that and then carve it. Oh, sorry, I forgot to mention. We call it a static prop because we are guaranteed it does not move. And that's very important because it's really easy to simulate things that don't move. They don't move. And the same is true of the red and magenta here. The red is the brush geometry on the paired portal side, and the magenta is static props on the other side, which is namely the desks. And as I'm looking through here, you can see just a small snapshot, and then also you can see this magenta outline here of the desk mesh on the other side. It's important to know that that's not me looking at the mesh through the portal. That's the local space version, and it just happens to line up the desk because we have to make sure everything lines up. Otherwise, your physical interactions will seem weird if something is halfway in a portal and it's kind of not colliding with something or it's colliding with it wrong. And as I walk through, you'll notice all the colors change because we switch spaces when I walk through in just a second. So now all the colors are local space for this side. That is how we carve a hole. It's a very, very small area of the level that we carve a hole in. And so we're getting back to the volumes I showed you 2 slides ago. If we carve a small representation of the world, we have to know when the player is colliding with that versus the regular world, because if they're colliding with the regular world, they're going to collide with the wall that's behind the portal, and they're not going to go through it. So we have to use exclusively that carved version when they're close to a portal. And we do that using the same volumes I was talking about earlier. This is the 3D representation of them. And you'll notice that they have a large amount of space above and below the portal. That's important because it's 3D space instead of a 2D space. So as I enter the yellow space, I still collide with the world. I still collide with all the desks and things because I'm still, while I'm exclusively in the yellow volume, I'm still colliding with the world. I'm going to show you. It's a bad example, but it's the video I've got. I'm going to hit this chair behind this desk because it's still in the real world. And then as I transition into the green volume, I am exclusively colliding with our carved version of it, which, that wasn't a bad frame to cut. If I'm happen to look back in the portal, which side is scrubbing? Okay. Sorry. So if you happen to look inside the portal, you might be able to see it. I know it's super hard to see, I'm sorry, but we did carve a hole. There's no geometry right here to stop us going in, and since we're exclusively using this new mesh, we're allowed to just go through that space. So more importantly than static geometry, which doesn't move and is super easy to physically simulate, we have dynamic props and things that move, specifically, in this case, boxes. So the way we model this is very similar to how we did with geometry. We're going to be duplicating everything, and I'm going to show you by walking near the portal. So this blue box that just appeared is my player physics object that's replicated from this orange portal to the backside of the blue portal. And this is using a system known as a physics shadow. At least that's what our system is. I'm not really a physicist. That's just what we call our representation of it. So I haven't dealt with many physics systems when I talk about that. So what a physics shadow does that's different than our rendering geometry is we're not allowed to actually teleport it from one frame to the next, because if you teleport a physics object, then all sorts of interactions that intersect, they have no previous basis to go from of how to solve that. They can't rewind time. because they've suddenly teleported into an interpenetrating space. So all of our physics objects, we give them a target of where they need to go. Sorry, not all of our physics objects, our physics shadows. So just like the player volume and just the examples I'm about to give you, we tell them where we want them to go, and they try their best to apply forces and rotations to go there. But if it doesn't work, we're kind of SOL, and they do their best. So I'm replicating that for the player over there, and we're also going to replicate it for the cubes in a second once I get around to placing them. And so it's important to note that we're not really solving the discontinuity in space because that would be way too hard, at least for a person of my skill level. What we're doing is we're saying each side has this cube over here is the master of its physics, and this cube over here is the master of its own physics, and this cube over here is just trying to replicate whatever this guy is doing. So they don't quite line up, but they work well enough, and in game development, good enough usually goes a long way. So as I'm using it, you might notice they don't quite work super well, but you can see that I've got this representation over here. I'm pushing it in my virtual version, and it's all lining up kind of. And yeah, that's how we do it in Portal. So I'm going to go ahead and tell you that I'm really glad that we didn't have levels with more than 2 cubes, because if you try to do this with a train of cubes, 3 or 4, it breaks down horribly. And this last little bit is me just showing you that we're not intersecting with anything in the back of it, because we're not inside the green volume or the yellow volume, because we're behind the portal. It's really important to manage your lists of what can interact with what when we're faking holes in space and overlapping space. I spent a whole lot of time on this. And I think that is the end of our physics material. So we had some more miscellaneous filler material, but it looks like we ran over a little bit of our initial time. So we're going to open up for Q&A now. We might get to our miscellaneous material later, but yeah, if anybody's got questions, now would be a good time.
Yeah, sure. Go ahead.
Could you talk a little bit about how lights interact with portals for just lighting up objects, and like would you get shadows in the portal?
So originally I had a slide on that, and
the question was about lights.
oh, sorry. Yes, sorry. The question was how lights interact with portals and shadows and things. So I'm going to preface with saying that most of this stuff I did a decade ago. So if I say something that's not true, I'm not trying to lie. I just don't remember it. So basically, there was a time during Portal 1 where we tried very hard to make lights work through portals, and we kind of settled on a cheap solution where we would define a point barely in front of one portal, see what lights were projecting what amount of color on that, and just kind of make an emissive sphere on the other side that would kind of do that. So the downside is that you only noticed it in cases that were very high contrast, which was also the cases where it was the most broken. So we just don't do it.
On Portal 2, we tried for a while to have the portals themselves project light on things, and that was also kind of broken for a while, and then we just took it out.
Yeah, so we just punted on that one too hard.
Any other questions? Yeah, sure.
Draw on that stencil buffer multiple times?
So the question was, what were the performance implications of having to draw multiple scenes with the stencil buffer? So it's very analogous to having to just draw a more complex scene. You know, you're just drawing more quads and things. One of the slides in our miscellaneous section, you know what, why don't I just go ahead and jump to it. So it's very important. When we're rendering things in a 3D space, we have what's known as a frustum. It's kind of a pyramid which comes out from your camera, and you can use it as a very quick test to see if you should even bother rendering something at all. So I've got the, you know, I'm just going to use my sides. The sides are defined by the screen itself. So you know, the screen that you're drawing has a top, it has a bottom, so those project into space. So we take our one side and we can say, okay, if an object is completely on the other side of this plane, we don't even need to bother trying to draw it. We can just skip it. And so one of the optimizations we have in Portal is that every time you look through a portal, we confine the frustum to a smaller space. I took the easy route in that I kept it as an object that still had 4 distinct sides. So sometimes it's a little bit broken, but in this case you can see I'm looking through the blue portal at this little button here, and I've got this. It's probably impossible to see, but I've got this this mesh coming out. This is the updated frustum of everything we should try to draw. So you can see it mostly just encapsulates a little bit of level and the button itself, and that helps us not even attempt to draw the complete scene over and over again. But I don't think I ever did a performance analysis, so I couldn't give you concrete numbers, but it was, it was better than trying to draw the entire scene over and over again, because since we still had the depth buffer on our side, we had already drawn most of the screen, and then we also had the stencil buffer telling us not to even attempt to draw most of the pixels. It was not nearly as bad as trying to render the entire scene. But we did find that for the graphics cards of the day, which not even all of them supported stencil buffers, some people that played Portal 1, they got textures. We found it was best to just limit to 2 recursions, because we could do our depth, or we could do our recursion fake, and it worked pretty well, and I don't think it was terribly expensive even for the cards of the day.
Yeah. I know there were cases during Portal 2 when we were trying to make it work on consoles. There was a lot of perf tests that were for cases, especially in co-op, when you're playing in split screen with 4 portals on screen at the same time, all looking at each other. There's like 16 views being rendered of the entire world at the same time. And there was these like weird edge cases where like, if you do that, you get like 2 frames a second. Just don't do that. So there was a few things in levels we had to change where like the corner case was the worst, where if you have a wall like that and you can put a portal right next to each other on both sides of the corner. So we had a couple cases where we had to actually change the levels to not have those cases. So you can't play, so like we just moved the corners apart like 16 units or whatever. So you can't always see both portals through both the views. So there was stuff like that we had to work through, especially for consoles. Back in the day, like we were working on PS3 and 360s. I'm sure now it's better, but it's been a long time since we've done that.
If I remember correctly, using stenciling was strictly less expensive than using textures, because you're still going to draw the same amount of geometry, but you have no texture cost whatsoever. Yeah. Hopefully that answers most of that.
Yeah, go ahead.
How did you cover all of your bases for each level so that a player could never get stuck? So in the sense that if you fell off a cliff, or maybe you accidentally erased a portal, you could always find a way to go back or to keep progressing forward.
Yeah, so the question was about how we covered our bases to make sure the players can't get stuck in levels if they do something bad. Mostly through playtesting, and then later on through bug testing. It's a lot of just trying to make sure that you can see parts of the level from different parts. Towards the later process of when we're getting closer to shipping, we do something called like the greasy pig pass for the levels, where we make sure the players can't literally get stuck on walls and stuff as they're walking through them. So we'll have a bunch of invisible geometry there that like smooth the collisions along stairs and along, because especially in Portal 2, there's a bunch of these broken pieces and a bunch of this like foliage and broken parts of the levels that are tilted at weird angles and stuff. And it's like, for the most part, we left them as is, but a lot of cases we had to go in and put invisible stuff everywhere to make sure that like the wall might look like it's broken up into like 15 different pieces, but the player's just colliding with the flat plane. It's to like make sure that like those things don't happen, where the players don't get stuck in spots. And there's also a bunch of level design work that goes around in making sure, because we have to take care of the opposite as well, right? You have to take care of like, well, we got to make sure the player can't see the exit portal from the start of the level, so they can't just portal and get to the end. And so like doing that process helps with what you're asking as well, because if you can make sure that the exploits aren't there, that you're also getting rid of cases where the player can get themselves in a bad spot. And so it kind of works itself out through the course of development. You don't go in starting to make a puzzle or making a level with that in mind a whole lot, but as you start refining it, things get tweaked and things get tuned. Some things might be have to tweak for like perf reasons, like, hey, this doesn't work on PS3. So you gotta be like, okay, I gotta fix this, and like tweak the puzzle a little bit. But then once you tweak the puzzle, now you gotta do the whole testing all over again, because like, all right, now I can't just put a portal place over there, because now you can solve the puzzle without doing any of it. So there's a bunch of work that has to go in from that end.
And it's important to note that as we get closer to shipping a product, more and more of our dev team switches to playtesting. And we have some very smart and mischievous people that specific question of like, how do you make sure you don't get stuck, is on the checklist. It was on my checklist, at least, of like, I am going to make sure I can't get stuck. I'm going to sit in this level for about half an hour and think long and hard about how to get myself stuck. And if I can't do it, then pass. Yeah.
Anyone? Yeah.
Was there anything that you would have liked to have pursued but didn't due to either time constraints on shipping or like the limitations of graphics cards of the day that you thought about but for whatever reason couldn't do?
The question was there anything that we didn't pursue for various reasons before shipping? I can't think of anything. I think I was pretty happy with what we produced. Most of the things I focus on were bugs that we shipped because, once again, getting back into shipping mode, as you get closer to shipping something, you want to touch the code less and less and less. Even if you know that the fix is going to work 100%, it'll definitely work. It might break something new. So I certainly have a small list of things that I wished I had fixed, but nothing that I wish I'd. I couldn't think of any features that I'm.
There's stuff that we worked on that obviously didn't end up shipping. Some of them we touched on over here. I don't know if sticky paint was something that we should have worked more on though, because I feel like we spent a lot of time trying to get it to work. And the reasons for cutting it then are still valid now. So like I'm saying, like if we were to go back, I don't think we would try to solve that problem. We would probably come up with new problems to try to solve. We did have like another thing we tried was I think we tried it after the game shipped for like a DLC expansion was reflection paint. So it was paint that would reflect the different elements of the game, so like reflect lasers or reflect light bridges. And we didn't get too far with it. Again, like it leads to a bunch of like weird levels because you have to have all levels have angles. Because if you think about Portal, most of the levels are like 90-degree walls and stuff, and 90-degree reflections don't go anywhere. So like we had to have like make these super contrived looking levels with these weird 45-degree angles everywhere, and they can reflect things. And then there's other problems like, well, how often, like how many bounces do we allow on things, like, and like also like stuff just looked weird, like tractor beams reflecting off of walls just looked weird. There's probably other ideas that I can't remember right now, but there's a lot of them get cut short pretty quick because the flaws are really apparent pretty quickly. Like you might sit down and think, oh, this is a great idea, I'm going to go out and work on it. And then as you start working through it and testing it out with others, you start seeing all the problems. And those problems get apparent pretty quickly. And at that point, you make the call of just being like, this is not worth pursuing anymore. We had some more game modes we were trying to work on. I think we had like a competitive mode for a little bit we worked on.
Yeah, we actually had a slide about that for a little bit. It didn't get fleshed out, but after Portal shipped, we immediately said to ourselves, what does multiplayer look like? And so the first thing we tried was deathmatch. Turns out that's a horrible idea. Everybody wants to just put portals under other people's feet. So you spend most of your time just completely disoriented and confused. And then I think we made a collect the coins kind of like, oh, do flings and things. But once again, everybody wanted to put their portals under other people's feet. So now we have co-op.
Yeah, and the co-op was very successful, I think. And there's a bunch of other challenges that come with co-op that we had to work through. I think we tried some more different competitive modes. We tried like a time trial kind of mode, but they're doing it together. But that's effectively just playing 2 single-player games at the same time. So there's not much interact. Because anytime you let players interact in a competitive way in Portal, they just want to put portals on their feet. Like that's really all they want to do. And it's fun for a bit, but like not as the receiving end, right? Like it's not fun. Or they just want to keep bumping each other's portals. Like when they want to put their portal exactly where the other guy's portal is. So like they walk in and they go in there instead of where they were supposed to go. It's fun for a bit. I'm not saying there's no merit there.
By a bit, I think he means about 5 minutes.
Yeah, like by a bit, isn't that like that's the thing you look at it, you're like, oh, that's funny. But then like you realize like there's no real, at least in the mechanics we tried, there wasn't much depth to it. It's not something you could flesh out for a game mode. It's more of something you could do as like a level, as a gimmick once. But then there's not much reason to do that. Like, and the cost to doing that is really high. So you have to figure out like, do you want to spend a bunch of dev effort in making this gimmick that's going to get really old and half the people are going to get annoyed and frustrated. So you just don't do that. In the back there.
You mentioned you could cache some stuff in the pipeline for some of the lighting flaws earlier. I'm wondering if there were any other kind of hardware hacks that you do in order to keep kind of performance targets that you wanted for the portal behavior.
So the question references how there were some pipeline restraints on the pixel queries, and if there were any hacks that we had to do to meet performance. I believe you asked.
Any other stuff we did?
Yeah. Once again, I'm going to have to say that I did most of this about 10 years ago. I can't think of anything off the top of my head. There wasn't a whole lot.
We did stuff for the paint. I don't know if we did a bunch of hacks, but I mean, one of the big hacks on the paint that we did was the paint that you're seeing is not the paint that's doing the painting. So I mean, that's like nobody can tell. It's pretty good. But especially on multiplayer, the paint that the client is seeing is not the paint that the server is seeing. Because we couldn't transmit all that data, so they're both generating their own paint data, but then the server is the only one doing the actual painting. So all the blobs that the client is hitting in the world do nothing, and the server blobs do the painting and then tell the client, paint over there, paint over there. So that's the kind of thing, because the network bandwidth is pretty limited, and there's a lot of paint flying through the world. So we couldn't just transmit all the paint all the time. So they all generate their own paint blobs that are through the world, and then the painting itself happens on the server, and then that gets transmitted. But the paint flying through the air is different on everyone. But it's random enough that you can't really tell.
Is Half-Life 3 gonna have portals?
No comment.
Probably not.
In all seriousness, so after the initial Portal came out, one of the other experiments was not only what does multiplayer look like, but well, how fun is this in a Half-Life environment? And it turns out that the way that Half-Life is made, there are a whole lot of slightly scripted sequences to make things work. And so the way those levels are designed are fundamentally different than Portal levels, and they basically just break down. So if there were portals in Half-Life, Half-Life would seem a lot more like Portal.
Yeah. Well, if you think about a Portal level, it's pretty constrained. The sightlines are pretty constrained. The level takes place in a box. You can't see really far, and there's a lot of kinks in the wall, so you can't like see all the way to the end. Half-Life levels aren't designed like that at all. So you would just go in a level and like portal all the way to the exit, and then skip all the gameplay. Which I mean, there's probably mods that allow you to do that, but like I think the games themselves and the mechanics are fundamentally different enough that I don't think they interact really well, unless both of them change or one of them changes a lot, so it's no longer what the game you want is. Yeah, I think you were up first. Yeah.
You mentioned that you had done like a student game project before you got hired by Valve. What was the story there? How did that work out?
Yeah. So the question was asking about our student game projects. So Dave worked. We both went to a school in Redmond called Digipen. Dave went there before I did.
I graduated in 2005, so I worked on a game called Narbacular Drop, which if you Google it for it, it will be the only result because the name was chosen, so that would be the only result on Google. If you can spell it, good luck. And so that was our senior project at Digipen, my team at the time. And so we ended up, through a very convoluted long story, showing that at Valve, and they hired us on the spot to basically recreate those mechanics for them. And that was actually, there wasn't a whole lot of confidence at the time that would actually ship, but it became Portal, so it seems like a good thing.
Yeah, and I was part of a team that made Tag, The Power of Paint, the video I showed with the paint gun. And that was our team's junior project at Digipen. And yeah, same thing, I think Valve saw it a couple times and hired the entire team to come work on that mechanic at Valve. And then once we got there, it became obvious to try to integrate it into Portal 2. And that's how we started working on Portal 2, and that's how the Portal 2 gels came about. Yeah.
So the paints and gels, which were introduced as a mechanic in Portal 2, ended up being part of the story as well. Can you talk about how some mechanics end up affecting the story, how story elements end up affecting the mechanics?
So the question was about how the story and the game mechanics interact and how one affects the other. So the way, at least in Portal 2, and I think Portal 1 was very similar, the way it kind of works at Valve is we don't really have an overarching design for like a design doc for the game before we start. It's a lot of smaller things that we try to then combine using similar techniques like what we discussed today. And the story kind of builds out of that using the same techniques. Because the way we kind of vet out most of our design decisions is by playtesting. And the story follows a very similar path. But you don't really want either one to override the other, because if you see the game, like if we have a team that made a bunch of puzzles for the game that haven't been very play tested, and then like the writer comes in and does a bunch of writing for it, and then you realize 3 weeks later that half these levels aren't shipping anymore because they didn't test well, then you made a bunch of dependencies that don't really work. Portal was lucky in that the puzzles themselves are compartmentalized, as like you enter the elevator, or you exit the elevator, you do a puzzle, enter the elevator. So they're all pretty compartmentalized. And a lot of the writing that was done for it was essentially just jokes. So a lot of those jokes do fit in to most of the puzzles. So the puzzle can change and the joke can just be inserted into it. But for the overarching story of the game, I think that required a lot more collaboration. So the writers were on site, like they were Valve employees, and they were sitting in the same room as us, watching the playtests, bouncing back and forth ideas. And we had GLaDOS for most of the game, and the voice artist was local, so we had her come in many times and record a bunch of lines. We also used some like fake online robot voice for a while, but those are hard to judge because the playtesters almost never laugh at those jokes because the robot voice doesn't really know how to speak them. But it sounds like a robot, so it's better than nothing. It's better than just putting text on the screen, which we also did for a while. So like with the writing, there's two things you're trying to test, right? You're trying to test out the individual jokes, and a lot of them can be transponded to any level, so they're not super dependent on the levels. But then once the story starts coming together and starts taking shape, at that point you're making changes to the levels to accommodate the story. And from that point on, you have to have a pretty good amount of confidence that these particular levels are going to ship in the game. And so that starts happening, I think, fairly late into our dev cycle at least. There's always an overarching goal. There's always a goal of like you're trying to capture Wheatley or you're trying to go kill GLaDOS. But the exact mechanics of how that happens doesn't come together until fairly late. Because you don't want to spend a bunch of time integrating your story and your levels without having a bunch of confidence that these levels are actually good enough to ship. Which we do have for a bunch of the game, but as new levels and new mechanics are being introduced, it all kind of goes haywire. So it's just mostly just a pretty strong collaborative process between the writers and the designers, and it all goes back to the playtesting. Yeah, sure.
Graphics, but could you talk a little bit about how sound interacted with portals, like in 3D positioning of audio sources?
So the question was how sound interacts with Portal, and my memory is a little fuzzy. I'm pretty sure we tried to replicate a little bit using just basically the exact same solution as with our lighting, where it's like we have a sample point in front of a portal and we have an emitter on the other side. I can't remember if we shipped that way.
I think we did.
Yeah.
I think there's a microphone or in-game microphone and an in-game speaker on the portals. So on both sides. So if you're on this side of the portal, you'll hear what's happening on the other side. I'm pretty sure that's how we shipped.
Yeah, but I don't think we made any special concessions to make it seem like it was going through a tunnel or anything like that. We just wanted to make sure you could hear what was going on.
No, not through the portal specifically. I know there's a bunch of stuff we did for like the tractor beam. Like when you enter the tractor beam, it kind of fuzzles like everything else around you and like muddles the sound a little bit. But going through the portals themselves, I don't think there's anything specific we did there. Or at least not that I can. It's been a long time.
It's been a long time.
Sure.
What were examples of puzzle games that inspired you when you were making your prototype games?
Portal. The question was what puzzle games inspired us when we were making our game.
I can't think of a strong inspiration. I'm mostly a code guy, so I didn't do a whole lot of the actual like puzzle design. But when I'm thinking back, we didn't have a whole lot of sources to draw on because it was a fairly new concept in general. Yeah, I can't think of any sources I drew on. I mean, yeah, nothing.
Yeah, I wasn't kidding when I said Portal. When we were making Tag, I think Portal had come out a year or two earlier before that and was really good and like a big success. And we were trying to learn from how they were teaching the players different things. And that's one of the biggest things we took away in our student game was like, how do you teach players different mechanics? And I think Portal did a really good job of that by like teaching by doing instead of by showing. So you like the players doing all the stuff and then figuring it out instead of someone showing a video or just telling the player, hey, here's what you do next, and then going doing that. So we tried to like take that at heart, and as we were doing in our game, introducing new paints and new mechanics, doing it the same way where we introduce them in a way that the usage is obvious enough that the player will try it out, and when they try it out and it works, they feel really good about it because they feel like they figured it out instead of us doing all the work and showing them what to do. So it's like a lot of that that was the specific thing that we took from Portal in trying to do it in our game. Yeah.
How many people did it take to create these two games, Portal and Portal 2, like across the different, I guess, like functional units between like development and like writers and everything else?
So the question was about how many people it took to make Portal and Portal 1, Portal and Portal 2. Portal 1 was a pretty small team for the most part.
Yeah, so Portal 2 started as the 7 people that worked on the
Portal
student
1.
game. Yeah. Sorry. Portal 1 started with the 7 people that worked on Narbacular Drop directly transplanted, and then we started working fairly early with 2 writers. And we were leveraging other people at Valve to answer questions and help us hit the ground running as far as how to use the engine. But it was mostly just those 9 people working day to day. And then Portal 2 ballooned quite a bit.
Portal 2 was a much bigger team. By the time I joined Valve in 2009, I think there was already a pretty big Portal 2 team. They'd already had a few of the mechanics figured out. The game was pretty different from what we see now. But at that point, it was already maybe 10, 12 people. And then like it slowly increased. Like we were 4 of us that got hired for our paint game. So we joined that team, and then I think by the end of it, there were probably close to 40, 50 people working on it. That was towards the very end because we had to ship on 2 consoles and PC, and we had a whole co-op mechanic, and there was a whole co-op campaign being worked on separately, as well as single-player one. So it was a pretty big team by the end of it, much bigger than Portal 1. And the game itself, I think, is much bigger than Portal 1 as well. I think the single-player campaign itself is probably more than twice as long.
Yeah, I remember.
And then the campaign, the co-op one is probably also that big.
I remember in Portal 1, we would have to do frequent integration testing, and I think I got my playtime on Portal 1 down to like 45 minutes, and Portal 2 was several hours.
Yeah. So it's a much bigger game, so it took a lot more people. Yeah.
How does the game engine that you used compare to like Unity? Is it more like straight up C programming, from scratch, or is it a lot of the drag and drop stuff?
So the question was, how does our game engine compare to something like Unity? For both Portal and Portal 2, we used Source, which is our in-house game engine, and it's very different from how Unity works. So the way Unity works is mostly kind of like a WYSIWYG editor. Like what you're seeing in the editor is the game, essentially. Like all the entities and stuff are loaded. Obviously, more stuff gets loaded at runtime. But what you're seeing is what you're getting. Whereas the way Source works is it's got a bunch of these discrete tools that make stuff. So there's a level editor, which is where you make your level. And then you import that into the game and you run the game separately. And what you're seeing in the level editor is not what you're seeing in the game, because a lot of the entities and stuff don't translate to the editor. A lot of the lighting and stuff has to be pre-baked. Unity has some pre-baked lighting as well, but in the way it worked in Source is, I think, it's a combination of a bunch of like discrete tools for each different aspect of the game. So like there's a separate particles editor, a separate model editor, a separate editor for like VO and the face poser, and the separate level editor. And then there's a game engine that like takes the compiled versions of all, like compiled outputs of all those things, and then puts them in the game engine and combines them together. And then all the code is pretty much exclusively C++. I don't think there's really anything else. There might be a couple, like handful of things that are not, but all the tools are C++, all the game engine, all the runtime code, it's all C++. Source 2 is a little bit different, but still going forward on that front. Is like I'm not trying to do what Unity is doing, because Unity is more of you're running scripts, C# scripts, and then you're just compiling them while the editor is going, and like rapid iteration and stuff. Source doesn't really have that same model of working, but the advantage is that like we control all of it, and then the ceiling for what we can produce is theoretically quite a bit higher. So there's trade-offs to it, and also we make all our tools and all our engine stuff in-house. So and we're the primary customer for it, like our games. So we're not trying to do what Unity is doing and trying to service to anyone out there who wants to make anything. And Unity has like thousands of people working on their engine, and we have quite a few orders of magnitude less. But like I think we're aware of all the trade-offs we're making. We're not like trying not to do what they're doing. We're just seeing, and we're learning from them too. And Source 2, we've taken a few cues from stuff like Unity and stuff like Unreal, trying to be more user-friendly, even to our own customers, like internal employees. But it's not like the way of working is very different between Source and Unity. Anyone else? I think we're good. All right. Well, yeah. Thanks again for having us.
Thank you all so much for coming. So there's some extra pizza outside, but that was Portal Problems. So thank you very much.